Transformer Paper Explanation and Implementation from Scratch. Transformer paper is also known as Attention is All You Need, and in this paper they would have explained an architecture known as transformer, and we are gonna dive in deep into the architecture, and finally we'll be training a text classification model by using transformer architecture from scratch. So in this video we are gonna see about why transformers was required at the time of introduction of this architecture, as well as we'll also see a brief introduction to the architecture of transformers. So let's jump into the video right now by starting with the first question: why transformers over RNN? So before diving deep into the question of why transformers over RNN, let's have a brief idea of how an RNN works. Okay, so let's consider three cell states, okay, at timestamp t-1, t and t+1. okay, so in every place there goes an input and output comes. Alright, so similarly it will be for other timestamp as well. Alright, so this is how usually an RNN works, where at a given timestamp we'll send an input and the output will be provided to the next timestamp as well. Okay, so this is how an RNN architecture works. But what is the problem here? Let me give an example for you all. I like eating, let me take another color, apple, but I like using mobile phones from the Apple company more. Okay, so the main problem with RN was it wasn't able to understand the context very well. Okay, to understand a given context, like let's say in this example, you need to see what is the sentence or what is the word, what are the words before a given word and what are the words after the given word. Okay, that is how you understand the context generally. And even if you see, I like eating apple but I like using mobile phones from the Apple company more. Here the first apple means a fruit and second apple means a company. How do we say that? Even if this company was not there, okay, alright, but I like Apple products more, something like that. Okay, you will identify the fact that it is denoting an organization known as Apple. It's not the eating apple. Okay, so that is why I gave different colors for both of those. One is denoting a fruit and the other one, which is the red color, is denoting the organization. So to understand what this apple means and what this one, which is the fruit and organization, you need to have context aware vectors, because at the end of the day we are working with embeddings, which is nothing but vectors. Okay, but these are just embeddings. Let me give a short note on how an embedding is. Okay, let's say apple is there, it will always be some number, let's say 111. okay, the dictionary is not going to change. Let's say this dictionary is there, this will be a mapping. Okay, I think probably this can be even written better. Just give me a minute. Oh, sorry. Okay, so how will an embedding dictionary look like? It will be token to embedding, but let's say word to embedding now. Okay, it will be apple is to some dimension. Let's say your dimension is 128. It will be 128 numbers. Orange is to some 128 numbers. So here, be it the Apple company or be it the apple fruit which you eat, it is going to be the same vector. So that is why RNN fails with lot of scenarios which currently we are using LLMs with. Okay, transformers are the base for whatever LLM we are working with currently right now, and transformer came into the picture because of this main disadvantage. Let me highlight it here as disadvantages. The core disadvantage of RNN is that no context awareness. People might think, Vasanth, we have bidirectional RNN which will see front and back. Again, it will be t plus 1 knowing giving information to t, and t minus 1 giving information to t. How about a timestamp t plus 3 which has some dependency on t? Okay, in that time again bidirectional RNN will fail. Okay, so there is no context awareness in case of RNN. So the second one is RNN, as you can see, is a sequential network. It will go token by token, and when you have a larger number of tokens, it will fail again. So that is another problem. Okay, sequential processing. And long context failure. Actually, you can see that these two are separate. Okay, we can also have these as separate ones, where I'll say why sequential processing is a problem. Okay, when you have GPUs, to have the maximum computation out of your GPU, you need to do parallel processing. That's why we do batch processing and all. Alright, so these are some of the problems which was there with RNNs. Okay, and then transformers came into the picture, where all of these disadvantages became advantages. Alright, so the first one was, it was able to generate context rich vectors by using attention. Okay, there is a concept known as attention, which is the core invention in this transformer architecture. That is the most important component present in this transformer architecture, and we'll be seeing about that component separately in a video in the series again. Okay, then we'll have parallel processing being enabled in transformers. Okay, and then it can also handle long context. Okay, so that is why we needed transformers over RNN. Okay, now let's have a brief introduction to transformers. Alright, so transformers is an architecture provided from the paper Attention Is All You Need from Google themselves, Google team. Alright, this was released in 2017. In transformers itself, there are three types of architecture, where there is encoder, decoder, and encoder decoder architecture. This paper has encoder and decoder architecture. Don't worry about these words, encoder, decoder. These we'll be seeing in detail about in the architecture deep dive video. Okay, so that is about the contents I wanted to say as a start to the series. I hope you'll all be interested to know how this architecture works and create a transformer from scratch by yourself by using PyTorch. So let me give a brief idea or kind of a roadmap of what this series will have. First, we'll start with introduction, which we have done now. Next, we'll move on to architecture deep dive, where I'll explain about the architecture in depth. Then we'll go again, like we are starting from shallow level and we are going in deep. in this architecture itself there are lots of components, and we'll go component by component, where we'll be going through positional encoding, then we'll move on to attention, we'll see about layer normalization, we'll have a brief idea about feed forward of how it works in here, and then we'll wrap all of these components into encoder, how it works, decoder, and then how it works. And whenever I say each component, it will be both implementation as well as the explanation. Okay, let's say if I'm having the third video, positional encoding, I'll be explaining about positional encoding as in the paper, and then I'll also implement that from scratch. Okay, both will happen hand in hand. Then we'll combine all of these into a single transformer, and then we'll build our data set. Next we'll create our own tokenizer, and then finally we'll do our training and inference. And I'll also show you how tokens are processed during training and inference. Okay, as a bonus, finally we'll see a visualization to the attention, followed by at inference what are the decoding strategies there. Okay, as you can see, this is a very long series which I have planned. I hope you'll all be interested and will be keen to know what is there about transformers and what are all there to know. We are going to dive in deep into the transformers architecture. In the previous video, we saw why do we need transformers over RNN and what is transformer all about. We saw an introduction to it, and in that we gave a small introduction that transformer consists of two parts, which is encoder and decoder, right? Now we are going to blow up these two architectures separately. Okay, these two are components itself, and inside these there are some components also. Okay, so now I'm going to show you a brief idea on what is encoder and what is decoder, and I'm going to dive in deep to the architecture itself. All right, so basically encoder is kind of used when you want to learn a lot. Okay, learn representations. Whenever a task needs you to understand the context very well, let's say if it is QA or classification, text classification, token classification, something like these and all, then you will need encoder. Okay, and for decoder, whenever you need generation, whatever it is, then it will require decoder. Okay, encoder decoder combines the best of these both worlds. Okay, and here encoder is BERT family, decoder is GPT family, and encoder decoder, it contains of models like BART, T5, T5s, uses the same architecture almost as specified in the attention is all you need paper. All right, so basically the idea is that encoder will, in encoder decoder architecture which is there in the paper, encoder will try to understand the context and will provide the information to decoder. Okay, and decoder will try to generate accordingly, will try to rather complete the task, if you may. Okay, if you see, encoder is not autoregressive, but decoder is autoregressive, and that's what makes it suitable for generation. Okay, so in these encoder and decoder there are some components. Okay, they are positional encoding, and guys, we'll be seeing rather separate videos in this series on each of these components. Okay, positional encoding, attention, in which there is self, cross, in self itself there is multi-head and masked multi-head. Okay, masked multi-head is only for decoder. All right, And then we have layer normalization, which will use residual connections. Okay, the people who know about ResNet might have an idea about residual connection and it might help. And if you don't have an idea, don't worry, I'll explain that as simple as possible in the layer normalization video. And then we'll also have a video on FN block. Okay, so these are the components which are present in the architecture. Now that we have an idea about the architecture on how it might look, let's go on to the architecture itself. Okay, as you can see here, this is the paper, Attention Is All You Need. Okay, it is from Google, and here they have provided their architecture. All right, so as you can see here, once you provide the input in here, the input embedding is computed along with the positional encoding, which becomes your input embedding. Okay, so positional encoding and token embedding, that is how I call it usually. You can also call it as input embedding, however you want to. If we add this together, that will result in input embedding. Okay, not this input embedding, here one. Okay, and then it is passed on to multi-head attention. And guys, this is your encoder. Okay, just give me a minute, let me take my pen. All right, so this is your encoder and this is decoder. Okay, now for the paths. All right, this is number 1, and then you have multi-head attention, which is number 2. Add and norm is nothing but your layer norm being connected as residual connections, which is number 3, and then finally you pass on to feed forward, which is number 4. Okay, and then this output is passed on to the decoder. Okay, before going on to that, we'll start from here. The output start token will be computed, and then the positional encoding is computed and it's passed to masked multi-head attention, which becomes your number 5. And then it is passed on to layer norm, and here I can see there is this connection which is passing the outputs from encoder as an input to the decoder, right? This is cross attention. Okay, and don't worry, as you can see, there is 3 here to the multi-head attention, there is 3 here to the masked multi-head attention, there is also 3 here, but here there is only 1 passed from this side, which is decoder side itself, but 2 is passed from encoder. Why is that? I'll say in depth about it in decoder video, but what are those and why it is there, I'll say now itself when I'm explaining the architecture in depth. Okay, then it is passed on to feed forward, and then it is passed on to linear layer, which is projection. Okay, I didn't add that here, let me add that also here, projection. Okay, now finally you will have your softmax. Okay, so this is how the architecture is there, and don't worry about each of the component and what is going on behind each of the component. I have made or I'm going to make separate videos on each of the component in the series, so don't confuse about the videos. Okay, here let's go on to this. Okay, so here you can see I've made a detailed architecture. Okay, let's go on to this flow. Okay, so given an input, okay, given an input, let's say it is start token, and then you have some series of tokens and then end token. Okay, it is computed as token embedding. Okay, and for this sequence of token there is positional encoding calculated. Okay, this token embedding is nothing but a vector representation for each of this token, and positional encoding is nothing but a vector representation for the position of each token. Okay, I hope that makes sense. And then now we'll add both of these, which will result in your position embedding or input embedding or token embedding, however you want to call it. It will result in your position embedding. And then we have our query, key and value, which is nothing but the position embedding being copied thrice, and we'll split that according to the number of heads in attention, because this attention will have multiple heads. Okay, if this is attention, in that there is multiple heads. Okay, for each head we'll split this. Let's say if it is 512, it will be 512 by 8 if it is like something like 64. Okay, this is how it will be. Now it will become 64 from 512. Okay, now we'll pass the query key value and all from here to here. Okay, okay, now we are passing the query key value onto the multi-head attention. As you can see here, we are passing query key value into the multi-head attention, where inside that what happens is we'll multiply this query vector. All of these are vectors, all right? So we'll multiply this query vector with the key vector, and then we'll add it with some padding mask. Okay, so what is this padding mask, what it does, we'll see that in the attention video. Okay, but what happens is we'll add that and the shape will remain the same. Okay, it will be qk transpose again, and then we'll do a softmax on it, and then we'll multiply that by this value vector. All right, finally will result in something called attention values in each head. Okay, so here as you can see I have some 3, right? This is nothing but your head. Okay, num heads. If your heads increase, this kind of line will increase. All right, so the attention value of each head output is concatenated together, which will become your attention tensors. Okay, the attention output is then again added with this positional embedding. Okay, this is your residual connection. Okay, so you are adding that positional embedding again with this attention computed positional embedding, and then you are doing a layer normalization, which becomes your add and layer norm 1 output. Okay, so that is your residual connection 1, and out of that again what you're doing now, you have computed multi-head attention, you are adding that with your input embedding itself, or rather positional embedding, and then we are sending that to feed forward neural network, right? So what it will do is, in feed forward neural network, the block will have 2 layers. Okay, 2 linear layers. One will expand it and then the other will contract it to the same dimension. Sorry. Usually in feed forward, this dimension will be 512, and then this will be, or 5, not generally 512, let's put it as D model, and then this will be DFF is equal to D model cross 4, because you have learned something in attention, but to learn everything to be there in that attention, it requires a lot of learning, and for that we will be expanding the dimension from a given dimension to 4 times this dimension, and then we'll project all those information into the same dimension itself by projecting it from DFF to D model itself. Okay, now we have our feed forward output, and now what we are doing, yeah, you guessed it right, we are adding that with this add and layer norm 1 out. As you can see here, it is added here, and that becomes your encoder output. Okay, as you can see in this encoder output, what I'm doing is, just give me a minute, this won't be needed actually. So this encoder output will be again copy pasted twice to become the input for your decoder. Like I said, some input will be provided to the decoder, right? That will be there, but your encoder is completed. Now when you come on to this decoder, as you can see here, you will have some token which is computed to its embedding, and then the positional encoding of that sequence is also computed. Okay, which will become your position embedding, and then the query key value again same, it goes here, but the difference is here you will not have just padding mask, you will also have look ahead mask. How that look ahead mask will look like, I'm just giving you an introduction, but I'm not going to explain how it works, because that is there for a separate video known as attention. Okay, normal padding mask will be something like, if the token is length 10 and you have 3 here, okay, 1, 8, 6, we'll what we'll do is we'll pad it to 10 with all zeros here, 0 or some value for pad. Okay, for this, to indicate that padding, we'll do something called masking, and here it will become like 1 1 1, indicating that these tokens are there, but don't focus on these tokens. Okay, 0 0 0, something like that. But in look ahead, to make the decoder model alone being generative, what we'll do is, for let's say the output will have 8 tokens in it, we'll have that padding mask that is there, but in look ahead mask it will look something like this, array of arrays, where it will become 1 0 0, let's say it is 5, okay, not 8, it is 5, so it will be like this, okay, 1 1 0 0 0, and then 1 1 1, and then 1 1 4 times 1. Okay, so what it will do is it will only know what are the tokens before it and not after it, making it forced to generate some token. Okay, but in case of encoder, it will know what is there before and after. That is why encoder can be used to understand the representation, but decoder should be used for generation. Okay, so other than that, the process will remain the same. And then what we'll do is, here the attention tensors, we'll just consider that to be our query. Okay, here we had query key value, right? That query key value, instead of that, what we'll do is we'll add this with position embedding, we'll normalize it, and that will become our query, new query. And then again it will go to another thing called multi-head cross attention. So now the question of what token is to be generated next is there in this query, and then the answer is somewhere in this key and value, and that focus happens in this multi-head cross attention. Then you'll have your output there with added with the query tensor, which will become normalized, taking you to the add and layer norm 2. As you can see here, mass multi-head attention is there. Query is passed from here. Key and value are the 2 lines. Like I said, I'll say what are those. Key and value is passed from here, and those are added and they're passed to feed forward neural network. Like I said, it will be expanded, and then finally you will have your projection layer and then output. Okay, so this is how the architecture is there. It is a very big architecture, but as you can see, it completely involves matrices, and that is why it allows parallelization. Okay, parallelization is enabled in transformers because of this matrix multiplications. And as you can see, I have lot of components here to be saying. We'll have token embedding and position encoding as a separate video, which is 1, attention completely as another video, 2, flare normalization as 3, feed forward neural network and projection as 4, and then also we'll have separate videos on encoder, decoder, decoding strategies, how token will be passed when it is input, and how token will be passed when it is like during training and inference and all. Okay, so yeah guys, there is lots of things there in this playlist coming up. So that's it for this video. I hope you like this video where I dived somewhat deeper in this architecture. We know what are the components which are there in this architecture now. Now it's time for us to understand each of these components separately. So we are going to start with the first component, which is positional encoding, in which I'll cover about embeddings in detail. Because the positional encoding is a part of the input embedding, where the input embedding is computed as follows. As we saw in the paper, input embedding is a combination of both token embedding and positional encoding. Alright, though it is a positional encoding video, I'm gonna give you a small idea of what is token embedding, and then I'll explain in detail about token embedding. Sorry, positional encoding. Now coming on to token embedding. When we come on to token embedding, we'll see about tokenizers. Alright, usually we train tokenizer to split the sentence into tokens. Let's say we are doing a white space tokenizer, and the sentence is as follows: the apple is tasty. Alright, here now let's consider the batch size to be 1, sequence length will be 4 in this case, and then we'll consider our embedding dimension, which is D model, to be 512. Okay, so now what happens is, now these 4 will be separately, or rather separated by using the tokenizer, where it will become the apple is tasty. Alright, and we'll have a dictionary. Okay, there will be a dictionary where first these will be mapped as numbers. Let's say it is 1, this is 10, this is 8, and this is 7. Okay, and this dictionary will be something like 1 is to a 512 dimension number or array representing this number. Okay, a 512 dimension array which will represent this number, and those are known as vectors or embeddings. Alright, I hope now it makes sense. So now what will happen is, this the apple is tasty sentence would become something like an array of 4 arrays, and each array inside will have a dimension of 512, and this will be your token embedding. Alright, I hope now it makes sense. Now, why do we need this positional encoding? Okay, I had 2 apples, one orange apple and another let's say red apple. Okay, and there is no thing called orange apple, but I'm saying orange apple. Alright, another red apple, where the second one was slightly tastier. Alright, here when you do the normal token embedding, this apple and this apple will have the same embedding. Okay, but here it differs, right, based on this orange and red. Okay, then there is, let's say it is coming will complete as it comes from Apple company, Apple Inc. Okay, Apple Inc. Now these 3 are there, right? So all these 3 are at different positions but will have the same value, right? But you need some attention to go for based on the position of the token. Okay, here the second will denote this apple and not this one. Okay, alright, so this will happen only because you will have a position token. Let's say it will be 0, 1, 2, 3, 4, 5, 6, 7, and something like 8, 9, 10, 11, 12, 13, 14. And since it is saying second, and there is an apple at the 6th position, and there is an apple at 11th position, now this second will focus on this 11th apple, which is a red apple. Okay, and then again this apple will be focused based on, okay, this red apple is coming from Apple Incorporation. Alright, so that is why we need positional encoding, because each token will have its own representation in 512 dimension across all other features. Okay, and we'll see a mathematical calculation for it soon. Alright, so now let's see why do we need sinusoidal positional embedding. Okay, because we would have used sinusoidal positional embedding, or rather the authors would have used sinusoidal positional embedding in the paper. Okay, sinusoidal. Now the problem was, when you have 0, 1, 2, 3, something like that, it is not scalable, because if you train a model to have till 512, then it will always have 512 dimension to be its restricted size. Okay, and it can't learn any other feature rather than this. Okay, this is in the number 1, this is in the number 2. It is not learning respect to other features. Okay, when we do sinusoidal, this apple will learn respect to this apple will learn respect to it comes, something like that. Okay, it is not relative to other positions. Okay, but sinusoidal does that, where it will encode each positions in a unique different position in a sinusoidal wave. How a sinusoidal will look like? It will be something like this. Okay, in this wave, something like it will be here, 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 here. And again, you might think, Vasanth, this is as similar as encoding it to something like a direct number, right? So what happens is, first thing, the good part is sinusoidal wave has a range of -1 to 1, since we have cosine, sine and cosine. Okay, sine and cosine will be used, and the range is -1 to 1. Always it will be -1 to 1, so it is always scaled in nature. Okay, that is one good part. And then the next one is, like I said, encodes relative position to the words. One word, how it's positioned to other word, will be encoding that as well. And the formula goes as follows. Okay, position of a given position, let's say this is P, positional encoding of a given position. Let's consider probably its position, or let's consider it as, yeah, we'll consider as position, comma 2i. Okay, so here we'll be using sine of some value for even positions and cos of some value for odd positions. And why is that? I'll say in some time. Okay, so the formula goes as follows. It will be sine of position by 10,000 part 2i by t model. Okay, so this is how it goes, and here 10,000 will be your frequency. All right, so let's consider this to be n. Why I'm giving some notation for this, I'll be showing you, and I'll be giving you an exercise about calculation of position embedding manually by yourself. Okay, for that I'll give you some exercise, and if you're interested you can try to do that when it is odd number. Okay, for given 2i plus 1, let's say it is I is equal to 0. Okay, then it will be 0 here and 1 here, right? So yeah, so always when you add 1, it is going to be an odd number, right? So now it will be cos of position by 10,000 part 2i plus 1 by d model. Okay, so this is how the formula is. All right, let me give a box for it. And guys, don't worry, I'll provide this notes in the comment section. I'll upload this somewhere, and then I'll put in the comment section so that you can refer it whenever you want it to. All right, so from what we have seen, let me say like a title, why sinusoidal. The first point is unique, let's give another color here, probably blue, unique encoding of position of words, right? That is the first point, like we said. And then we'll encode it relative to other position of words. Other position, like I said, the first one, let's say it is in 0th token, it will be encoded with relative to all other position, something like that. Okay, and then we'll have the next one is the range. Like I said, range is normalized. Okay, it is -1 to 1. Okay, so this is why we need sinusoidal. Now, like I said, in that itself we have a problem where, like I said, we'll not use just sine, we'll also use cosine. Why sine and cosine? Okay, why both are needed? This is a question. Okay, when you plot it like this, okay, when you plot it with I, which is your position, I with respect to your position, I is your embedding position. Let's say if it is 512, right? 512 is your embedding dimension, and I is, if I is 0, it is your 0th embedding dimension. Okay, something like that, if it helps for you. Okay, when you put the plot of P0 to P6, how it will come is, let's say it is 0, 1, 2, 3, 4, 5 and 6. Okay, what happens is P0 and P6 will have same value. Okay, P5 will be here somewhere. Okay, P5 will be here, and then P6 will have the same value here, and let's say if it is P1, it will be here. Okay, so this is how the plot will happen, and to avoid this issue, we'll have both sine and cosine. Okay, if we do that, it will not give any problem, because sine and cosine will operate in a slightly different frequency. Okay, so as you see, the wave structure also will be different. Okay, let me show you how sine and cosine wave will look like. Sine wave will be something like, if I consider this to be like that, it will be like this. Okay, but cosine will be something like here to here. Okay, because sine 0 is 0, but cos 0 is 1, right? So this is how it will start the curve. Okay, and that is why we are using both sine and cosine for encoding even and odd terms. Okay, now for an important concept, which is dimensional dependency. Okay, which is an embedding dimension which you consider. All right, so for dimensional dependency, let's say your embedding dimension is 0. In that, it will look something like this. 0, let's say it's 2 here, 4, 6, 8, 10, and then 12, and it goes on. Okay, so it will be something like this. Okay, let me have the same plotted here as well. Be 2 here, 4, 6, 8, 10, 12, dot dot dot, 0, sorry, 2, 4, 6, 8, 10, 12. If it is I is equal to 1, I is equal to 2. Okay, it will go till 5, 12, or whatever dimension you give. Okay, 2, 4, 6, 8, 12, 2, 4, 6, 8, 10, 12. Okay, now if you plot it, right, now what happens is it will be like, let's now consider the dimension to be something like probably 20. Okay, the embedding dimension is 20. Okay, in this case it will be like I is equal to 20, sorry, I will be something like 20 at the end. Okay, and I'm just gonna plot it for 2 Okay, now the graph will go something like this, right? From 3 it will go to 6, it will go to 9. Okay, it will go something like this, and then it will go through 12, something like this. Okay, and then when I'm going on to odd position, like I said, it will start as cosine, so it will go from 1, and then it will go to 4, it will go to 7, it will go to 9, and then it will go to 12. Okay, and when it is 2, it will start from here, it will go from 8, and then it will go so on. Okay, it will go to 16, 14, and 16. Okay, so this is how it will go. When you go to 512, it is going to differ a lot. Okay, now let's consider the positions. All right, let's say it is 1 here, sorry, 1, here it is going to be another 1, and here it is going to be another 1. Okay, so here if I draw a line, right, as you can see, in each wave, the place at which it coincides in the wave, at the 0th dimension it is here, though the place will be similar, the characteristics of the wave is different, right? That is why we say that with more embedding dimensions it will be better. Okay, here it represents 1 with respect to all other dimension. Okay, let's say you are having a sequence length of 4. The first token will have different characters encoded in 512 dimensions. Okay, but we are just seeing 2 here. Okay, so that is the key difference. Let's say if it is 3. Okay, if it is 3, something like here, if I plot it down, right, as you can see, here it is at top, here it is bottom, and here it is somewhere like at middle. Here the value is going to be different, here the value is going to be different, and here the value is going to be something different. Okay, so that is why we use sinusoidal. All right, it encodes each position relative to other position of the words in given number of dimensions. Now let's consider the value formula. Okay, let me write the formula first again. Formula. And guys, I know this is a long video, but we are almost going to end the theoretical part. Okay, position encoding of let's say here, let's go for the another page. Let's do it here. Okay, formula, position encoding of position comma 2i, it is going to be something like sine of position by 10,000 part 2i by d model. Okay, d model is your d here. Okay, d which I have written here, right? Let's say I said, right, let's consider d to be 20, but here it is 2, right? It is going to be something like 512 here. All right, so when you have odd position, it is going to be 2i plus 1, and it is going to be cos of same but 2i plus 1, but you get the sense, right? Same formula. Now let me say this example. Okay, the water is tasty. This is going to be the sentence I consider, in which my position will be of range 0 to 3, and I'm considering the d to be of 4. Okay, and then we'll have the frequency, like which is the n term, to be 100. Okay, I hope now you get the sense. All right, so let me do a table now. The water is tasty. At the ith position, like I said, it is going to be 0 at sine, 0 at cos, 1 at sine, 1 at cos. Okay, now the d is at 4. Now it's completed. All right, sine of 0, let's put this in the formula. Position is at 0, right? So 0 by 100 power 2i, I is 0 here, 100 power 0 by 4, because I said d model, right? Let's consider d to be d model itself. Okay, d model. Okay, so 0 power 4 it is going to be something like 0 of sine of anything power 0, 0 divided by anything 0, and anything power 0 is 1, so it will be 0 by 1, which will be sine of 0. Answer is 0. Okay, I'm gonna erase this. This is the calculation. Okay, I'll have a separate calculation at the bottom. For two values, I'll give it, and then we'll have some exercise. Okay, sine of 0 is 0, cos of 0 is 1, sine of 0 again will be 0, cos of 0 is 1. Why? Okay, now let's consider this. Here it is position 0, 1, 2, 3. Okay, now position is 0 and I is 1. Okay, now let's consider for these two. Okay, now we are considering for those two. Position of 0, I for 1 without sign. For now, let's consider these two, this formula alone. Okay, 0 by anything is going to be 0. Okay, that is why it is like this, but it is gonna change, right? Now we'll calculate for position equal to 1, I is equal to 0. We'll compute that, and then I'm gonna stop there, and you're gonna fill the table for position 2 and 3. Okay, now let's do this. Position equal to 0 and I is equal to 0 first. Then we'll do position equal to 1, I is equal to 1. Now we are doing position equal to 1, I is equal to 0. Okay, so the calculation will be going something like this. Sine of 1 by 100, right? Now I said this would be our frequency term, and now it is 100 here. Okay, 100 power 2i, 2 into I, what is the value here? 1, right? 1 by 4. Okay, it is going to be sine of 1 by 100 power 1 by 2, right? 2 by 4 is going to be 1 by 2. So it will be sine of 1 by 10. Alright, and the value for sine of 1 by 10 is, if you put in internet, it will come, it will be 0.84. Okay, now I'll do a similar thing for cos. Okay, cos of 1 by 100 par, right, yeah, 2 into 1 by 4 plus 1. Okay, it will be something like this, and then it will go to cos of 1 by 1. Okay, because it will be like, just give me a minute. Yeah, I was just verifying, and as you can see here, I substituted 1, which means we are doing calculation for I is equal to 1 and not I is equal to 0. So it will be again cos of 1 by 10, and it will give a value of approximately 1.0. Okay, and if I do I is equal to 0 and position equal to 1, it will be sine of 1 by 1 and then cos of 1 by 1. Okay, so the table finishing will be something like, it will be 1 here. Okay, cos of 1 by 1, which will be 0.4, and then we'll have sine of 1 by 10, which will be 0.10, and then cos of 1 by 10, which is approximately equal to 1.0. Okay, so you can try to fill this table by substituting this formula and let me know how the exercise was, and if you find any confusion in the theoretical part, let me know. So once you compute this for 512, again this will be of dimension, sequence length, comma, embedding dimension, right, like we saw now, and the previous token embedding will also be the same. So what happens is, input embedding will be token embedding plus positional encoding. Alright, so this is how the embeddings shape up. Alright, now that we have a clear understanding of the theory, let's go for a practical code implementation. So now we have the code. As you can see, I've almost coded this architecture and I'm working on the training part now. Alright, but that is irrelevant. Let's cut all of these tabs. So first we'll compute the embedding, token embedding, and like I said, it is just a mapping of kind of dictionary, and that is done by using the embedding layer from Torch. Okay, in torch.nn, which is neural network, it has a layer known as embedding, which we will use. Okay, for now let's see the class. Okay, as you can see, I've written some docstring here so that even at the future for reference it will be easy for you to understand of what is going on in token embeddings. Okay, in init function I have dmodel and then vocab size. Dmodel is your embedding dimension and vocab size is the number of tokens in your dictionary. Okay, the dictionary which I said, it will be something like vocab size comma dmodel. That will be a shape, which means 30,522 comma 512, as you can see here, right? 30,522 by embedding dimension. 30,522 I'm saying because it is one of the common vocab size used, but we would have used some different vocab size. Okay, let me say what it is. It is 10,000 actually. Okay, we'll be having it as 10,000 comma 512. All right, so how you need to calculate embedding for a given token? What will happen is, if you give a tensor of tokens, let's say it is 1 comma 4 of the dimension, if it is something like that, batch size is 4 and you have some tokens of number to be 4. Yeah, let me type it here. If you give input to be bs comma seq length is nothing but your sequence length. Okay, the output will be of shape bs comma seq comma d model. Okay, I hope you understand that, because in sequence length each token will be mapped up to 512 dimension of embeddings. Okay, That is your vector or input representation, whatever you want to call it. Okay. And then vocab size, like I said, is your vocabulary size, which is the dictionary. Next we'll compute the positional encoding, for which we'll need D model sequence length, and then we'll need a dropout. If you want, you can use a dropout, or else even if you don't want, you can just not use it. But as the paper uses dropout, we'll also use dropout. Okay. And here you can see I create a layer called as dropout, which will have the dropout probability. Dropout is nothing but, let's say if you have 10 neurons in a layer. Okay. If I give the dropout probability to be 0.2, it will drop 2 neurons, or rather it will freeze 2 neurons for a given step. Okay. This will reduce overfitting, and it will help to increase the performance. Alright. For position encodings, we'll first create an empty tensor, okay, which will have 0 of the dimension sequence length comma D model. Okay, we'll have like that. And what is the number of positions we need? It will be 0 to the sequence length, and we'll have the batch size to be 1. Okay, we'll have it as sequence length comma 1 because we need to pass it as 1 token. Okay, next for the even odd I. Okay, here we written, right, this is your PE and this is your pos. Okay, we wrote PE is equal to sine of pos of sine of position by 10,000 par 2i by D model, right, and 2i plus 1 for cos. Usually if you compute 2i or 2i plus 1, always the value will be same. I have experimented it. So we are calculating the 2i, and why written as even odd I is because it will be 2i and 2i plus 1. Since it is the same for both sine and cosine, which is in even and odd position, I wrote it as even odd I. So it is starts.arange of 0 comma D model comma 2. So what will happen is it will try to have the values from 0 till 512, but it will be in 2 dimension. It will skip 2. Okay, so that is how it will work. And then we have division of frequencies terms, and here you can see we have 10,000 par even odd I by D model, which is your 10,000 par 2i by D model, right? It is usually like that, right? Position by 10,000 par 2i by D model, and here till now we have computed 10,000 par 2i by D model. And then next, now what we need to do, we need to compute position, and we need to compute sorry, yeah, it will be positions by division frequency terms. Okay, so we are dividing the positions by division frequency terms, and based on if it is even position or odd position. As you can see, we are going from 0, then we'll go to 2, we'll go to 4, then go to 6, and we'll go to 512, which means there will be 256 positions, and that is what is there in even odd I. Okay, and then again from 1 they will go to 3, then we'll go to 5. Okay, so always it is going to be D model by 2 even odd I. All right, and that is why we had the same value, and it is going to be cos of position by div frequency terms. And then now the position encodings value is position encodings dot unsqueeze of 0, because we need it to be a batch, right? It will be sequence length comma D model, then we are adding 1 because we are saying that this is one sentence. Okay, next important step is to register this as a buffer, because this is not a parameter, okay, but this should be a part of the module. Okay, this is a part of the module, but this should not be updated while backward propagation and all. So that is why we are registering this as buffer. Okay, and what happens in forward is, given an input tensor, which will be input embeddings, in which we'll call the token embedding, and that input will be provided to proportional encoding, that will be added to this positional encoding computed value, and then it will be added. Okay, so given a token, its positional encoding is calculated here, and it is added with the input embedding. So that is how it happens in the transformers, and we have replicated this here. Okay, now I'm just giving you a walkthrough, but if you guys need a live coding, this series is obviously going to be a walkthrough, but if you guys need a live coding, just let me know in the comment section. I'll try to have a big live, and then we'll implement the whole of the transformers from scratch by coding from scratch and all. Okay, or even we can do subsequent, because I have plans to implement Mistral and other architectures from scratch also. So at that time probably we can try to implement it from scratch. Okay, I mean live coding rather than walkthrough. And as you can see here, we have computed the positional encodings, we have computed the token embeddings, and here we are doing nothing but adding those. Okay, as you can see, it is added here. We are just passing it, and then your input embedding for your model is ready. And guys, before ending the video, a huge shout out to Umar Jamil, who has been a very good inspiration for me. A lot of content I have inspired from him, and there is another channel called Code Emporium. Shout out to him as well. I have inspired some bits from him as well, so a good shout out to both of these. We are going to see about the attention mechanism explained in the paper. So in the last video we saw about positional encoding, which will help a lot for attention, and now we are going to see about attention, which makes transformer very unique and solves a lot of problem which was there in RNN. The problems in RNN were discussed in the first video of the series, so if you haven't checked out, please check it out. But let me give a gist of what was the problem. It was generation of context rich vectors. Alright, it didn't know the meaning for the vector. Alright, it didn't have any context, rather it didn't understand the real meaning, if you might. Alright, so to solve that, there was this mechanism which was created by the author, which is attention, which also solved the other problem of parallelization. There were no parallelization in RNN where everything were processed sequentially, but attention happens in a parallel manner because it handles in matrices for handling the vectors. Alright, so let me give an example of how the attention might look like. Right, so let's consider an example of my name is Vasanth. Alright, so let me write it here. It is my name is Vasanth here, and my name is Vasanth in here also. Alright, whenever you compute attention for a token against another token. So before going on to that, let me say a gist of how a token will attention will happen. Alright, for each token it will try to do dot product against all of the other tokens in the sequence. Okay, that is just a gist of how attention works, and this type of attention is known as scaled dot product attention. Alright, so that is the attention which is used in the paper, but there are some other mechanisms of attention as well. So when you multiply my with my, it will be strong. So with the number of lines increased, it means the number of attention is also going to be increased. Okay, let's consider it in that way. So always it is going to be high when one token is multiplied with other token. And let's say if my is there and name is there, usually it will have a kind of a stronger relationship, right? So let's give 3, and with the is, it is going to be slightly lesser, so let's give 1. And then my for Vasanth, it might be stronger or weaker, so let's give 2, something like that. Okay, and then for name with my, it will be like this, and then for name to is, it will be something like again like this, because usually stop words are of no use. Okay, so again this is also something like we can't use anything, but name and Vasanth will have a very strong relationship because usually name follows by the name, right? So we'll give a strong relationship there. is with my won't have a lot of relationship, but name and is might have. So let's give a plus here. Okay, 2. Okay, and since this is followed by Vasanth, let's give a 3 here. All right, and then for my and Vasanth, it will have a strong relationship, not the strongest, but yeah, strong. With name again, it is going to be strong, and is it will be very less, right? So like this you can have a see like now you know which token are you supposed to focus for a given token. When I am at my, I need to give the most importance to my, followed by name, and then Vasanth, and then is. Now you can see, right, is there in between, but there is very less focus to is. All right, the most focus is on name and Vasanth and my. With increase in the sequence, this will be more useful. Okay, increase in seq length. Okay, so usefulness also will increase. By this again, now you can see you are getting some awareness of the context. So you are generating context rich vectors. You are understanding the context, right? For simpler purposes, I have taken a simple sequence, but you can also work up with some complex sequence as well. And don't worry, at the end of the series probably I will make a video, like I said, on attention visualization. At the time we can give sequences like this and see which token has impact on which token. Alright, so what happens is usually this context rich vectors will be generated at the encoder side and will be passed to the decoder, which will usually generate the sequence. Okay, so when you generate a sequence of token, you are understanding the context and then you are generating it, which was lagged by RNN, but it is very important. Okay, now for the example purposes, we have seen how this works. Now let's see in architectural manner on how this attention will work. Okay, so in attention, when you are going into attention, there are 3 main components you need to understand. If you see the transformer architecture as in the paper, you can see, right, it will be embeddings in here and it will go into 3 main split, and then it will go here, which is residual connection, which we'll see in the subsequent video. But these 3 are very important now, which is query, key and value. Okay, these 3 are very important. Now let's see in depth about what is query, what is key and what is value. Let's have it as 3 colors because it will be very easy for me to explain you all. Query. So query is, as the name suggests, will represent what you want. Okay, key will represent the location of the answer, or probably like where you want the answer, like the location of the answer. Okay, you for a given query, where is the answer, the location will be provided by key. And value, as you will all would have might guess now, it is the answer. Okay, so this is how it works. Let's say an example of in encoder you have seen, let's have a question answering example. Okay, context is there, context example. Context is Vasanth is a YouTuber who has good handwriting, not good handwriting, bad handwriting, let's put it like that. Okay, who has bad handwriting, and in question we'll have it as who has a bad handwriting. Okay, so in decode, usually let's say these are the input for your encoder. Okay, these are all passed to the encoder. Usually that's how it happens. These are all passed to the encoder with decoder. And don't worry guys, for the working of encoder and decoder, I'll be explaining it separately, like how the tokens will go into it. I'll be explaining it in this separate video of encoder architecture and decoder architecture, but just have a starting idea so that it will be easy for me to explain you all how this attention works, especially this query key value. Usually it will start with some start token decoder, and then now it understands the fact that I need to answer who has a bad handwriting. So this will be starting with your query. Okay, let's even consider now that this question is on the right side. Okay, you have provided it. Question is to who has a bad handwriting. Okay, now currently till this there will be a representation which will become your query. Okay, key and value is from your context, or yeah, okay. So currently let's consider question is here. Okay, in decoder, question is who has a bad handwriting. Now it should complete the sequence, right, with some answer, because decoder will act as an auto regressor. It will try to generate the next token as we saw in the architecture in-depth video. Okay, architecture in-depth deep dive video. Now it is the query here. Okay, now for this there will be a query token, and this query represents who has a bad handwriting. Now the context which has been passed in the encoder, this is the context which has been passed to the encoder. Now it will try to say like who has a bad handwriting. Now it will go through this. Let's say here for this there is a representation, for this, in each of the token there is a representation. Okay, for every token there will be a value and there will be a key. Okay, oh sorry, value, and then there will be key. Now when you start with this one as your query, all right, till now it knows that I need to see about who. Okay, who has been influenced in this question. So what happens is this q will be multiplied with the k of all of these tokens. Okay, now how it will happen is this q will multiply with q star the k of, sorry, yeah, k of Vasanth, and it will happen with q star k of is, and so on till handwriting. Okay, till that it will happen q star k of, and then for each, since it is a dot product, it will give a score, and since it is who, it will as you can see this question represents a person. All right, the maximum score would be on Vasanth. So let's say it is 0.8, and then it is 0.01, 0.05, something like that, and it will add up to 1, because in probability everything adds up to 1 to the max. Okay, so since it is representing 0.8, now we'll take the value of this one. All right, how that happens? Because the formula will go as follows. Okay, for attention the formula is q k transpose by root of d model softmax. You'll apply softmax in this so that the probability goes to 0 to 1, and then you'll multiply it to v. So when you have this, you'll be dividing all of these with the embedding dimension, which is 512, which all will result in a sum value, and then you will do a softmax. Obviously the maximum one, which is Vasanth, will always be the maximum one. Okay, and then you will multiply that with this value. Okay, in each of the value you will multiply it, which finally will return Vasanth. All right, so finally the answer would become something like Vasanth. It will try to generate. So this is how attention works. Okay, it will try to map the query and it will give the value. Okay, if we see it on a general purpose, it will look something like this. Okay, for a given query, let's say the sequence length is like this, 1 2 3, 4, 5. Okay, for a given query which is here, it will try to multiply with all of these keys. Okay, in all of these keys there are some values. Okay, here it will be q.k, which is transpose. Let's not consider that right now. q.k, and q.k. Okay, this value will again be soft maxed root D model, and then it will be soft maxed, and then it will be multiplied to the value. Okay, so finally whichever value is the maximum one, it will try to give more attention. Let's say it is 0.9 here, 0.01, 0.05, 0.02. when we add 0.07, 0.08, and then it should be 0.02, and then it will know that okay, I need to focus on this first token because the answer is in the first token. Okay, something like that. This is for one head. Now we are coming on to the next concept. This is for one head. Alright, I hope you all understand what is query, what is key, what is value, and what is this formula. As you can see, there is query, we are multiplying it with key transpose, we are dividing it with root of D model, and then we are multiplying it with softmax. We are softmaxing the value, and then we are multiplying it with the value vector. Okay, all of these are vector: query, key, value, all are weight vectors of query key values. Okay, and what are the query key values? Like I said, query represents what you want, key represents the location of the answer you want, and value is your answer. Alright, so these all happen in one head. Now actually the paper uses something called multi-head attention. Okay, so what happens is, whatever happens in this one head, it will also happen simultaneously in n heads. Let's say n is equal to 4 here. So this will have some values, this will have some values, this will all these all will have some values. Okay, these all will be concatenated to a single value. Okay, a single vector which will say let's say this one will focus on, the first head will focus on Vasanth, the second one will focus on YouTuber, the third one will focus on something like who, okay, something like that, and then the fourth one will focus on Vasanth, and then it will know okay, 2 heads is focusing on Vasanth, then my answer will be Vasanth. Okay, so this is how a multi-head attention used to work. Okay, now there is another concept before I'm going to show about the working, how the shape changes in multi-head attention. I want to say about one concept which is specific to decoders, and then there is another small concept where I want to say why we divide with root of D model. Okay, so when you do dot product, right, of q.k transpose, the variance has been found to be very high. Okay, the variance between one value and the other value has been so high, so to reduce the variance we have been dividing it with D model. Okay, so that is one point I wanted to say. The next point is a unique component which like I said in the first video, or rather the second video, architecture deep dive video, is masked multi-head attention, which is unique to decoders. And why it is unique to decoders? That is what makes decoder auto-regressive. Auto-regressive is nothing but it will try to generate the next token without knowing what token comes up next. Alright, see what happens is, let's say you are having the answer to be here rather than Vasanth. Vasanth has bad handwriting, let's say that is the answer. Okay, what it will try to do is, the answer is Vasanth has bad handwriting. Alright, this is the answer. So now what happens is, here the sequence length is 4, right? We'll generate a mask vector where it will be 1 0 0 0. If it is 0, it will not see that token. Okay, decoder generally does that. Instead of 0, we'll then replace it with -inf, because when you do softmax of -inf, it will become 0. Okay, that is how it becomes 0. So next, at the next step, it has seen Vasanth. Next step, it should see Vasanth and has, and then the other two will be 0. And then in the third step, it will be Vasanth, has, bad, and then it will be 0 again. And then the fourth step, which is the final step, it will see all the token. Why we'll send this kind of token is that it will be autoregressive. And you might now think, Vasanth, if I'm gonna generate the first token, how it will just generate like Vasanth always or something like that, right? It might generate how many ever tokens it want, and let's say it might generate some other tokens. It will happen based on something called teacher forcing, where the ground truth will force the first token to be Vasanth and second token to be has. Okay, so that is how decoder works. And when you don't know what is coming up next, you will try to generate the next token. If the wrong token is wrong, your loss will be propagated via back propagation, and then you will update via your optimizer. So that is how the attention will work in the decoder, where in masked multi-head attention alone, wherein if there is mask, it won't see. Usually what we do is, this is look ahead mask. This token or this mask which we saw for decoder alone is known as look ahead mask, where it is not allowing the model to look ahead of the token, current token. But there is another mask also known as padding mask. Okay, because at all times you won't have the same sequence length. You'll have a sequence in a batch. Let's say you are having a batch of 10 sequences, and each might have like 1, 8, 9, 17, 170, something like that. So what we'll do is, usually we'll take the max length of the batch, and then we'll try to pad everything with the pad token. Okay, so everything will become 170, 170, something like that. But we should not focus on those pad tokens, and that's why we'll mask it. Alright, so there are two types of tokens, and there is something called cross attention as well. Self attention is what we have seen till now. Okay, be it masked multi-head or normal multi-head. Normal multi-head happens in both encoder and decoder, and masked multi-head happens only in decoder. But both of these are self attention. In cross attention, there is a small difference. Okay, and that we'll see in decoder architecture video. Okay, I have hinted this in the current video itself while I'm saying that example, but I'm going to explain that in detail in the decoder architecture video. Alright, now let me show how a token or the given input will be processed in attention. Alright, let's draw some diagrams. Alright, let's give an input. Sorry, not here. Let's put it here. Input. This is of dimension sequence length, comma, D model. Alright, when you go like this, obviously you will split it as 3, like I said. Okay, it will be again sequence length, comma, D model, which is your query, key, and value. Guys, it is nothing but when you are computing the embeddings, right? When in the architecture you would have seen something like this, right? It is 3. It will be splitted, right? The same vectors will be there. The query, key, values all will be same at the first part. At this part, query, key, values all will be same because same vector has been copied thrice input. Okay, but you will multiply this with something called weight q, weight k, and weight v. These are all random weight vectors which will be initialized and then will be updated upon back propagation to learn about the query key values. Alright, this will be of dimension D model, comma, D model, all. Okay, Now you will result with some vectors known as q dash, k dash and b dash. Okay, how the q dash will look like. Okay, let's say that if it is something like this will be your sequence length, number of tokens, and this will be your D model. And guys, I hope you can resonate with this kind of table, because this kind of table is what we did in positional encoding. And guys, if you haven't seen that positional encoding video, please do watch it. It is something in which I have covered a lot of things about positional encoding. Alright, this one, let's say it is like this. Okay, it will be easy. This is how it is. Like, let's say the sequence is 4 and D model is 4. Now it will become something like this: 1 2 3 1 2 3 4 1 2 3 4 1 2 3 4 and 1 2 3 4. How we are splitting it? D model is equal to number of heads by number of heads star head dimension, or you can do vice versa as well. Okay, head underscore dimension, which you can also frame it as head dimension is equal to number of heads by D model by now head dimension. Okay, it is interchangeable. And here this is 1 2 3 4, which is your num heads, and here you have it as dh, which is your head dimension. Okay, now this will be of something like sequence length, each will be of sequence length comma head dimension. Okay, and if you consider all of this, it will be sequence length comma D model. Okay, like I said, this will happen for all of these three. Okay, all of these three will be separated like this, and then you will do that q, k transpose and all, which will have you with an output of things like this. Okay, 1 2 3 and 4. Okay, now this will be of dimension sequence length comma dh, right? Now what you will do is you will concatenate this upon all the heads. Okay, as you can see, for one head, not just one head, the attention will happen on each head across each k and each values. Okay, what it will go to become as is, it will try to give a value which is, let's say, the multi-head attention out. It will be of dimension sequence length comma D model again. Okay, and then finally you will have a projection known as weight O, which will also give the same dimension, which will become your multi-head attention output. Now for the question, why weight out, which is your projection layer? Okay, see, you are learning it in separate heads. All right, so this head, let's say 1 2 3 and 4, each focuses on different token, and this one is saying Vasanth, this one is saying is, this one is saying YouTuber, and this one is saying Vasanth again. Okay, you are just concatenating it, which will be like normal concatenation. Okay, it won't know anything, it will just know, okay, these are some tokens for me to focus on. But this weight projection layer is also a learnable layer, which will understand that, okay, in this, whichever token has some higher probability, I need to say that this token is the most important token. That is what projection layer, WO, is very important. Projection layer or output layer, however you want to say it, that is what is why WO is important. Okay, so that is about attention theoretically. Okay, we know that now. Given an input, let me summarize it. First input will be there, it will be copied thrice to become query key value, then it will be multiplied by weight vectors q, k, v, then it will be split among heads, and then scaled dot product attention which is qk transpose by root of d model softmax of this value into v. This will happen at each head, and then you will concatenate output of each head. Project flash, you will learn the concatenation, which will produce the attention output, which is nothing but your context rich vectors. Okay, so this is how attention works. All right, so this is how attention works, guys. We have seen about query, key, value. We have seen why do we need attention, and then we have seen the computation, how it will happen at each head, and then how it will happen across heads, and then we have seen why decoder is able to generate the next token. It is because of autoregressiveness created by this look ahead mask, and then we have seen to handle the different length inputs we are using padding mask. We have seen about that. I have hinted about cross attention, and then we have seen the shape transformation, and then finally we have closed up with the flow of vectors. Okay, as usual, since now we are strong with the theoretical part, now we will move on to the coding implementation. Yeah guys, since we are done with the explanation, we are now seeing the implementation. As you can see, we have different classes here. There is a function for the calculation of attention. Alright, so the first function, the first class, or the only class which is required here, is multi-head attention. Alright, which will take the following as its inputs, because these are all very important. In our explanation itself, you would have seen we need sequence length, which is not required because we are passing the input and sequence length is calculated inside itself. Then we need number of hits, which is provided here, and all of these are at config. Okay, in config I have provided each of the configuration, so we need not worry about that. Alright, and we need d model, which is the embedding dimension, and as usual we need some dropout. Okay, so like usually have written some doc strings. As you can see, it is computes self attention by multiplying each token against every other token in a dot product fashion or manner, resulting in a relationship of one token against every other tokens or vice versa, showing the impact of each token, which helps to focus where it needs improving the attention in the architecture. Okay, whatever I've said in the last half an hour probably, except the architectural perspective, this is what is attention in a single line. It will just try to compute the dot product of one token against another token. It will result in a relationship of each token against every other token, which will help us to improve the attention in the architecture. Alright, so in this we are using self attention as which is stated in the architecture, but there are some other types of attention as well, like Badano attention. In arguments we are providing d model, num heads and attention dropout, which I have said, and then we will have the attention output value, which will be a tensor as well. Okay, now in the initialization function we are having these as initialized, and like I said, we will need weight query, weight value, weight key, and weight output, right? For all of these I said we need weight vectors, right? And here the dimension will be of d model, like I said. Alright, now we'll also have the dropout layer initialized. Let's not go into this attention calculation function first. First we'll go on to the forward function, and I hope you all know, but forward function is kind of the dunder call function, which will act as the default function when you call this class multi-head attention, because this is an dot module being called. Okay, this is an inheritance, and as you can see we are overriding it. Okay, so here this forward will take the following inputs: query, key, value, attention mask. Okay, once you provide the query, key, value, attention mask as q, k, v and attn mask, which will be of shape, be a batch size, sequence length and d model, we'll be passing those into weight query, weight key and weight value vectors. Okay, we are just passing this through this. Alright, now as you can see, like I said, I have also specified here d model is nothing but number of heads into head dimension. So now we are reshaping this batch size sequence length D model into batch size sequence length num heads head dimension, and then we are just putting the sequence length next and num heads before, because we'll be splitting the tokens at the head level. Okay, if it is four heads, it will be 4 heads and each will have all the sequences. Okay, we are just transposing it. So how it is happening, let's see. Okay, in query I'm just calling query.view, where I'm saying that okay, I need the shape of 0, which is batch size. I need the shape of 1, which is sequence length. That is fine for me, but I need to reshape this D model as num heads and then head dimension next. Okay, so that is our first step. But like I said, we need the number of heads to be prior, and then query the number of sequence length, the sequence length to be at the third one. Okay, so we are transposing the second one and third one, which is first and second index. Okay, second and third index rather. Okay, 1 and 2. So this will result in all of these vectors being batch size num heads sequence length and head dimension. Now we are ready for attention calculation. So we'll pass those query key values and attention mask, which is mask here, into this attention calculation function, where it will try to calculate the attention by using scale dot product attention by this formula, softmax of q into k dot transpose query key transpose by root of D model, then multiplied by v. Okay, so to get the head dimension, which is not even needed, will be taking the shape of -1. You don't even need this, guys. You can just remove this. So now once you pass this query, like I said, we need to do key transpose, right? It will be -2 -1. So once you do this dot product, which is at, okay, in at is nothing but matrix multiplication function by torch. Okay, in torch at is nothing but your matrix multiplication function. Once you multiply this, we need to divide it by root of D model, right? So it will be batch size num heads sequence length. Since you are doing this transpose, right, it will become batch size num heads sequence length. Okay, I hope you can understand that, because see, now we need to see it from here. It is batch size num head sequence length head dimension, right? We need to have this computation at each head. So each head it will go, that's fine. So the computation happens at this sequence length and head dimension. So we are just transposing this head dimension and sequence length in key. Okay, so the computation will happen something like this: batch size num head sequence length head dimension multiplied by batch size num head dimension sequence length. And as we all know, in matrix multiplication it will result in batch size num heads sequence length. Okay, that is how this transpose is there, and then we are resulting in a value of dimension batch size num head sequence length. Okay, now we are having the attention score. Okay, now it's time for us to have this mask being provided, so that the softmax value will result in 0. Like I said, when you provide some infinite value, it will become close to 0 and then it will become irrelevant. Okay, we are checking if the mask is not done, and if the mask is not done, we are calling the mask to fill function, which is a default function. What it will do is it will try to replace whatever token. So here you can see in the mask, if it is 0, the attention score at this 0th position will become -1 E9. Okay, I hope you all understand. I'm re-saying it. Okay, this mask fill function, what it will do is, if at a given specific token, let's say it is of 170 token, okay, if the 150th token is the maximum one, and then after 150 everything is padded, all right, to 170, at 151 till 170 the mask will be 0. Okay, and if it is 0, it will be replaced by -1 E9 at that sequence length value and all. It will be -1 E9. Okay, and if you do softmax, it will become 0, close to 0. Okay, not exactly 0 but close to 0, so that you will focus on tokens only which is there in the sequence. So with that done, we are done with softmax of qk transpose by root of D model. Now what we need to do, we are just one step needed, which is multiplying this with the value again, which will result in a dimension of batch size, head, sequence length and head dimension. Okay, I hope you all understand. Batch size, num head, sequence length, head dimension is what we are there right now. And then what we need to do again is do what we did here. Shape is there, and then we need the sequence length, which is at -1 here, so we are just taking it here, and then we are concatenating this num heads and head dimension together by multiplying those into D model. Okay, by this now you have some concatenated output, but the features are not learned correctly. Okay, it is just normal concatenation. To learn that better, you are doing some projection with WOX, wait output X, and then finally you are having the attention output. I'm gonna show you about residual connection and layer normalization. What is this residual connection and layer normalization? There are two things I want to say. First, this is the same component which is specified as add and layer norm in the paper. Okay, in paper it would have been said as add and layer norm. Okay, this is the first point. And then the second point, like I said in the previous video, it is good if you have an idea of ResNet. If not, this next 2 to 5 minutes is for you. Okay, before the release of ResNet, there was a model known as VGG. Okay, there was 19, VGG 16. Okay, those were some state-of-the-art models at that time for ImageNet. Okay, which was used for image classification. All right, these are CNN architectures. But the research has found that when you are training this for longer time, right, let's say if it is for 1000 epochs, something like that, when you think it logically, right, when you learn something again and again and again, you should be getting better, right? But what happened was, after some point of time, let's say it is 500, it started increasing the loss actually. Okay, now you can say, Vasanth, you could have done some early stopping and all, but see, we can't say it will stop at this point. What will happen if it happened in third epoch itself? Okay, and it didn't learn anything well. So this was the problem. Okay, on an elongated training scenario or an extended training scenario, loss increased. This is the problem. All right, loss increased. Now coming on to the solution provided in ResNet. Okay, this was known as residual network, which utilized a connection known as skip connection. All right, so what it will do is, let's say there are some 5 neurons, okay, or rather 5 layers, and you are passing through every layer. Okay, through every layer the output comes finally. This is 1, 2, 3, 4 and 5. So randomly what they would do is they will create a connection to layers like this. Okay, something like this. Okay, so let's say if there is 1, okay, the output is there. Out of 2 the output is coming. Let's say the accuracy of 2 coming to 3 is 97 and 2 directly coming to 4 is 98. So now what it will do is, if there is and if you pass through 3 and 4, it is 96. Okay, so finally here it is 96 and 98. It is better to skip this layer, right? So what it will do is, basically, if accuracy is equal to or greater than or equal to, layer is considered. This is how skip connection works. Okay, else skip layer. Okay, the output will be the same. Now we'll apply the same logic to the transformers. As you can see, as you would have seen rather in the transformer architecture deep dive video, where I would have clearly made the architecture look better, there will be something like add and layer norm. Not add and layer norm, there will be something called layer norm. Okay, so what happens is, first there will be something called add. In add, what happens is, for example, while it goes to attention, right, the architecture would look something like this. It would go like this: multi-head attention, norm, layer norm, or it would have been written, I'll draw it bigger. Okay, I'm drawing it on the right and going out to the left. Okay, MHA, A and L norm, FF, layer norm, and then finally output, right? So here what we'll do is, we'll be adding this to here and then this to here, right? This is how the connection would have been. So when you're passing the model input from your input to attention, and then you are checking the performance. Okay, if the performance is not as good as if there is attention, you'll try to add it, something like that. But that was skip connection. Okay, but here we are not skipping, we are just adding it. Okay, so that we'll retain the information at any cost. That is a kind of a modified skip connection, if you will. Okay, in skip connection you'll just skip the layer, but here we are not skipping the layer, we are just adding the values. Okay, regardless of the condition, if it is making it lesser or greater, we'll just add it. Okay, so that is about the add part. Now coming on to layer normalization. See, normalization, so there is lot of types of normalization. Okay, there is even something called batch normalization, which is conventionally used in CNN. Okay, so what happens is, in layer norm output will be something like this: x is equal to layer norm of sub layer of x plus output, previous output. All right, so this is how the formula works. All right, sub layer is nothing but your layer. Let's say if it is multi-head attention, if it is attention feed forward, something like that, and then the output is normal one. Okay, if you just add it. So this is how actually the layer normalization is there. And like I said, residual connection is nothing but a connection which will help you to retain the stronger information during back propagation, avoiding vanishing gradient. All right, so why this normalization? This is the formula, that's fine. So why this normalization? Normalization will try to scale the values. Okay, let me put a title here: formula why. Why do we need normalization? It will try to scale the values to, or rather than why, we can call it as what. Actually, what is normalization? That should be more appropriate. So what is normalization? Normalization is a process of scaling the values close to 0 and around. Okay, so usually there is some range like -3 to 3 in standardization, and in normalization it will be -1 to 1 or 0 to 1 rather. Yeah, it is 0 to 1. Okay, this is something required. Now why do we need this kind of scaling? Okay, that is fine, Vasanth, scaling is there, but why do we need this? First point, for stable training. Okay, if you see in gradient descent, if you have larger values, right, it will jump something like these and all, but if it is smaller values, it will try to concatenate like this. Okay, so to make the training more stable, it is required, and it will also reach the global minima faster. Minima, which is nothing but your optimum value, faster, which means indirectly your training becomes faster. All right, now coming on to layer normalization. See, what happens is, normalization is just like I said, to normalize the value, a given value, to a given range. Layer normalization, batch normalization, there are other types as well. Batch normalization will try to normalize the given batch of values, and layer normalization will try to normalize the values at that layer. Okay, regardless of the batch size. So what happens is, let's say your input or input to the layer norm will be xi. Okay, xi is nothing but, let's say, an output of a layer. Okay, xi will be equal to a function of w transpose xi plus bi. Okay, I hope this makes sense. And now your y, which is your output, will be gamma I of xi or xi. So this is xi dash. Okay, xi dash minus mu I by sigma I plus epsilon. Okay, so what is this all about? See, this is your forward output. Okay, for a given input, it will pass through a neuron like this. All right, where it will be w transpose x plus b followed by activation of the output, and here f is activation. Okay, now this becomes our xi dash. Xi is your input and xi dash is your output. Now if you need this xi dash for this computation of layer norm output, where, and yeah, here we need beta I. Okay, alpha and beta I are learnable parameters. Alpha I, or even if you want to put it, you can put it as gamma I. Let's put it as gamma I itself. Gamma I and beta I are learnable. Okay, this process is known as standardization generally. Okay, the result of this process will be that all the values in this layer output will become -3 to 3. It will be in this range, -3 to 3, with the mean of 0 and standard deviation 1. Okay, so that is what happens in this. So let me give an example. Okay, let's have the tokens to be 2 and embedding dimension to be 3. Okay, if you give an example something like this: 0.1, 0.2, 0.3, 0.4, 0.2, 0.3. For easy computation, I just replicated it with one different value. Okay, mean of 1 will be 1 by 3 of this one. Okay, 0.1 plus 0.2 plus 0.3, which will be 0.2, and then mu12 would be, sorry, mu21 will be 1 by 3 of 0.9, which is 0.3. Okay, now for this equation we have our mu I, we need our sigma I, right? Sigma I can be calculated as follow: sigma 11 is equal to, or sigma 11, 1 by 3 of 0.1 minus 0.2 square. It is nothing but your given value, which is, let's say, x minus mu the whole square. Okay, and then we'll take a root out of it. Okay, so 0.1 minus 0.2 the whole square plus 0.2 minus 0.2 the whole square plus 0.3 minus 0.2 the whole square. Okay, now it will become something like 1 by 1.3 into 0.02. Okay, so it will be root of 0.0666, it will be 0.08. Okay, that is mu 11, sorry, sigma 11 or sigma 11 rather. And if you want to continue it in the same way, if you do the same purpose of computation for sigma 21, it will be 0.08 again. Okay, that's why I gave it as 0.1, 0.4. Okay, because here the whole square will make it as positive again, so regardless of 0.1 and 0.4, it should give the same value. Now our mu array will be like 0.2, 0.3 and sigma which is standard deviation. Mu is your mean and sigma is your standard deviation. Will be like 0.08, 0.08. Okay, so now the normalized layer output will be y is equal to a given xi dash value, which is 0.1 minus mu I, which is 0.2 by sigma square, right? Where is that? Sigma square, right? See, yeah, sigma I, which is 0.08, and then you can add an epsilon value if needed. Okay, this is just to avoid zero division error, so it can be as small as 0.0001. okay, so I'm not going to do that here. Then we'll continue this. Okay, 0.2 minus 0.2 by 0.8, it will be 0.3 minus 0.2 by 0.8, 0.4 minus 0.3 by 0.08, yeah, sorry. Okay, 0.2 minus 0.3 by 0.08, 0.3 minus 0.3 by 0.08. Okay, so this is how now the y will become as minus 1.2248, 1.2248, 1.2248 minus 1.2248 and then 0. Okay, so now we have computed this value. Okay, we have computed this and then this is computed. Now these two, like I said, is none of the parameters model will calculate. So let's say if the gamma I goes on to be something like 0. Or let's say the gamma I is 1 and beta I is 1, so it will be like gamma I will be multiplied here and then beta I will add here, that's all. Okay, so this is how the normalization will happen. Okay, I hope now it's cleanly visible. Okay, let me write it here also. Out is equal to, now you have the y, right? It will be gamma y plus beta. Okay, these two, it will be learnt by the model itself. Now you can see previously it was having no range or distribution. Yeah guys, since we are completed with the theory, now let's see about the practical implementation. Here I'm using two classes because layer norm is by itself a separate class, and then we need to create that residual skip connections, right? Or rather the residual connections alone, which is the addition part. So for that I have added a class known as residual connection. Okay, so here in layer norm we'll have the d model and epsilon. Epsilon, like I said, is the small value which we will add to the division part, and the formula is x minus mean by standard deviation plus epsilon. And here we are also having two learnable parameters, as you can see, nn dot parameters of dimension alpha and beta. Okay, so in forward what happens is, first we'll compute the mean, then we'll compute the standard deviation across the last dimension. Okay, and then we'll compute the normalized value, which is x minus mean by standard deviation plus epsilon. And then finally what we'll do is we'll multiply it by alpha and then add it by beta. That's all. We were doing it for so long, but in computer it is very easy. Okay, now that the layer norm is done, what we need to do is we need to call this class inside this residual connection class, where it will take two values, which is d model and residual dropout. Okay, now what happens is, in this forward it will take two inputs, which is the torque or the tensor or the input itself, and then the sublayer, which is your layer. Let's say it is attention or feed forward, whatever it is. Okay, the output will be provided and then it will be added. Okay, that is the add out. And then what you will do is you will compute the layer normalization and then you will do some dropout. Finally your add and layer norm out is done. So that is how you will create your residual connection and add a layer norm. Okay, so yeah guys, we are done with the separate components. Now time for us to move up one step from the hierarchy. We are done with the bottom step. Next we need to create the encoder and decoder. So we saw about each of the components present in transformer at the lower level, which is positional encoding, attention, and feed forward. Now we are going to move up one level and we are going to see how encoder and decoder works, and we'll also see how the transformer is trained and what happens while we do inference, because decoder is generative, so how the tokens are processed, and finally we'll also see how to visualize the attention. Let's start with encoder. Encoder is a component which is used to understand the context of the given input so that it will provide a better representation, or it has better understanding of the text, how an encoder works. I'll have start token. Since we are doing text classification, let me consider an example like that. I am feeling good. Okay, so this is the series of tokens which will act as our input. We'll tokenize these. That will become our input. Till this, it will happen in tokenization. Now what happens is we'll compute the token embedding. By end of this video, we'll also see about tokenization. What happens in token embedding is that each word has a map to it. Let's say I will be mapped to a number named probably 0.256, something like that. It will be an array. Okay. For I, there will be a number 0, let's say it is 9, and for 9, it will have an embedding array. So to know about embedding, I have covered it detailed in the first video itself. Please check it out. Okay, so the token embedding, once it is computed, will also compute positional encoding, which tries to encode the position of the sentence, which is 0, 1, 2, 3. It will try to encode this position. Now we'll try to add both of these, and that becomes our input, which is provided to, this is where the encoder starts, wherein first we'll move on to attention, right? So what happens is this will be combined as a single entity known as input embedding, which is then copied thrice, which will become your Q, K, and then V. This is your query, key, and value. So to understand better, let me consider this as our example, where we'll have the token length to be 4 here, and we have one sequence, right? So it will be 1 cross 4, and our embedding dimension is 512. So initially our token embedding dimension will be 1 cross 4 cross 512, and our positional encoding dimension will also be the same, 1 cross 4 cross 512, and same will happen with input embedding as well. Alright, so the similar thing will happen with query key values as well. It will be 1 cross 4 cross 512 each. Okay, but all of those are until it moves on to multi-head attention. Alright, first we'll split these into heads, number of heads. So let's consider it to be 8. The dimension of query would become, or query key value, all of those would become 512 divided by 8, which would be 64. Okay, now the query would be 64, key would be 64, and value would be 64, but it will be something like this. Okay, 1 cross 4 cross 8 cross 64. Okay, so this is how the dimension would be now, and for each head we'll try to provide all of those together. Okay, Q, K, V. Alright, so this is how the input would go, and right now the dimension is 1 cross 4 cross 8 cross 64. Alright, so this is how the input is provided now, and now what happens is we'll take the query alone of each head and multiply with K transpose. Alright, so here the dimension would be something like 1 cross 4 cross 8 cross 64, but here it would become 1 cross 4 cross 64 cross 8. Alright, so that we would return with something like 1 cross 64 cross 64. Alright, 1 cross 4 cross 64 cross 64. So this is how it will happen, and this would be your query key transpose. Next, what we'll do is we'll try to do softmax of this. Before that, we'll divide this by root of dk, and dk would be your head dimension, which is 64. Okay, so whatever value is there, it will be like query key transpose by 8. Alright, so this input would now be softmax and would be multiplied by, actually it should be something like square here, and would be multiplied by our value, which is again 1 cross 4 cross 8 cross 64, which will again return us with the same dimension. Alright, query key value will become 1 cross 4 cross 8 cross 64. So this is how usually in attention things will take place, and this will be your one head output, and this is concatenated. Okay, so here you will have multiple heads. It is 8 here, so all those 8 will be concatenated, and if you do that, it will become 1 cross 4 cross 512 again. Okay, it was 1 cross 4 cross 512 and it becomes 1 cross 4 cross 512 again, and here we'll add this input embedding onto this attention output. Okay, so that is our residual connection, and here what happens is we'll pass this to our feed forward, so that would be in 4 times this dimension. Okay, so here it would become 1 cross 4 cross 2048, and then again it will become 1 cross 4 cross 512. Okay, and then finally we'll have our output. This is our encoder output, and that would be copied twice as our key and value for decoder. Okay, now we have a flow of how transformer work. So let me say in encoder why the representation is better. Okay, see, let's say I have an example. I am writing about attention. Okay, in encoder we'll have the visibility for all the tokens. Okay, so the mask would be 1 for all of these, and since the mask is 1 for all of these, you will have a better understanding of the context. So given a token, you will have an understanding that okay, these are all there. Okay, so that is how in encoder it works, and that is why decoder is not good for understanding the context, because you'll mask all of these tokens. Okay, don't worry about the mask, I'll explain that in decoder, but just have an understanding that why it is better to understand the context with the help of encoder rather than the decoder. Okay, it is because it has a visibility for all the tokens, and in BERT you will have bidirectional attention. Basically in encoder also it would be bidirectional. Okay, so given a token, you will have a visibility for the tokens coming before it and after it, so that it has a better idea of what it is speaking about. Okay, here for writing only there can be some options like speaking or talking, something like that. I am playing about attention doesn't make any sense, right? But if I had generated it as I am playing, would have been more sense than writing, and since we are saying about attention, it makes more sense to have these two tokens. Okay, so that is why contextual capture or contextual understanding is better with encoder. Okay, so given a token, finally you'll have an output which is of the same dimension as input. So that is how an encoder works, right? So to have an understanding about each of those components which I spoke about, which is multi-head attention, the positional encoding, and residual connection here, please check the last video, because in that I would have explained in deep about the math in each of the components. Alright, and if you want the link is in the description, as well as I've pinned it in the I button, so you can check it out from there also. Now we'll see about decoder, and decoder is more interesting because it learns by a method known as teacher forcing. Okay, so what happens is, now I'm not gonna dive deep into the shapes and all, because now you would have an understanding about the shapes with this encoder itself. So now I'll say how the tokens will be processed, because in encoder it will be very normal, but in decoder, since we are generating it with the mask, look ahead mask, it will be slightly different while it is being trained. Alright, so in decoder what happens is, I'll write it as a simple one. We have embeddings which is passed into masked multi-head attention. I'll write it as masked MHA, which is then passed on to multi-head attention, which is then to feed forward, and finally a projection layer and output. Okay, so this is the flow basically, and the thing which is going to differ is here the masked multi-head attention and multi-head attention. Since multi-head attention is a cross attention. Okay, it's not self-attention, it becomes cross-attention. And masked multi-head attention uses something called look-ahead mask. Okay, unlike the normal multi-head attention will have a mask only for paired tokens as 0 and normal tokens as 1. This masked multi-head attention makes sure that at any given token, only the previous token is being visible. Okay, so let me say about the mask first, which is look ahead. So given an input stating I am writing. Now what I would do is I'll provide an array of input. Okay, it will be 1 0 0. Let me consider I'm writing. Okay, so that it will be faster. 1 1 0 and 1 1 1. Now this mask would become our input mask. Okay, usually we'll only provide this 1 1 1 as our input mask, but here we'll try to provide this as our input mask. Okay, now you might wonder, Vasanth, now I'm saying I want to generate the next token, so how it happens? Okay, so that is where teacher forcing comes into picture. The first token would be start token. I'm not considering here. Let's say it is start token already there. So what happens is it will try to force based on this ground truth we have provided as labels. The loss function will take care of itself and it will try to say, like, it could have been like something like he. Okay, it will try to force it towards I, and then it would become something like he is. Now since it is I, it will become I is, and then now is not possible. The loss will again try to force it as I am or I was. Okay, and then again the loss would see like, okay, the loss for I was is higher and for loss of am it is lower, so I'm going for am. Okay, now the tokens I and I am are generated. Now you have the input being like this: I is there, I am is there. Now for I am, you have lot of possibilities. You have playing, writing, speaking, or sleeping. Okay, there are a lot of options there. Now the teacher here means our ground truth. The ground truth drives the generation. Okay, while training, the ground truth drives the generation, where it will say like, okay, you ought to generate I can't accept any of the other tokens you will generate at that point. If you are going to generate any other token other than I'm going to reduce your marks by providing higher loss. Okay, so similarly, since there are a lot of possibilities here, the model will try at the first epoch probably as play, and then in the second epoch it will try it as sleep, and the score would have been like probably lower, very very lower, and then it will see like, okay, I have another option, right? Let me see here. Okay, it's higher. Okay, I found the token, so it is I'm writing. Okay, if it is full stop, again for full stop a token should be generated. All right, it will see like, okay, I'm writing. There is another possibility. Let me see. There is about, on, and then full stop. Okay, about, though it makes sense for me, the ground truth or the teacher is saying, okay, I don't want you to continue. Okay, I have higher loss here. My performance has gone down. So similarly, it has happened with on as well. But when I generated full stop, the teacher is providing me good marks, reducing my loss. So which means dot is my next token. So this is how teacher forcing happens. Teacher forcing happens at each token. Okay, while you generate each token, the teacher will force you to generate the correct token, but this will happen only while training. Okay, so that is how the token would work while using decoder, but that is only during masked multi-head attention. Okay, in masked multi-head attention, that is what is making this obviously auto-regressive in nature, and that is where you need teacher forcing. Okay, but like I said, decoder is not very good with context understanding. Like I said, see, I am writing about attention, right? If I consider this writing depends on these two tokens. Okay, so it needs to have an understanding of both. Let's say I'm asking what I'm writing about. Okay, so to complete this I am writing about attention, it needs to have an understanding of both, right? So what happens is the encoder would have seen this input. Okay, the encoder would have seen this input, and that will provide the context for answering this question. Okay, it will become our key and value. I told you, right, while in encoder that will have two copies of the output. Okay, where is it? Yeah, here you can see, right? These two would become our input for cross attention in decoder. Okay, I've covered cross attention in detail, but I'm covering a gist about cross attention now. So what happens is, usually when you're going with the attention, right, you would need inputs like query, key, value, and mask. Okay, for self attention, given an input x, okay, it would become something like x mask. Okay, but in cross attention, to show, okay, this is where your context is. And guys, query key value is very important, and if you haven't watched it, please, before continuing this video, please watch the previous video, because query key value serves the core purpose of transformers architecture. Okay, so it would become something like x, because what I need is the query, and where do I have the key, and what is the answer I need is the value. So what answer I'm expecting, that is our query, right? So it would be from the decoder itself, query. But my answer, I know it is going to be in encoder, but I don't know where. It is the model's purpose to understand it. So let me give my encoder output here. Encoder output logic should be provided here, and the value is also there only, right? So the both key and value would be from the encoder output, and also you need to see the whole context, right? At that time, you are not seeing your answer. You are seeing, okay, this is where the context is, and I'm trying to find the answer. And that time you should not restrict the model to some specific token. So we'll provide the source mask, or let's say it is here encoder mask, encoder attention. Okay, so this is the logic in which decoder as well works. Okay, so given an input, you'll try to compute the embeddings. You'll compute a look ahead mask to compute masked multi-head attention, making the decoder autoregressive. And then you will also provide this input along with the encoder output to the cross attention. Sorry, I missed a feed forward here. After that, it will go to multi-head attention, which is the cross attention. And then finally, you will also have your feed forward, and then finally your output is generated. Now we are going to see about the code to build the transformer. In the previous video, we saw about our feed forward, attention, and then we also saw about embeddings, right? Now we'll cover the rest. We'll cover with encoder, decoder, the training code, inference code, and we'll also see about the tokenizers, how to train a tokenizer, and also we'll complete finally with the attention visualization. So let's start with encoder, and for encoder we are importing multi-head attention class from attention.py, feed forward class from feed forward network, residual connection and layer norm from layer norm, because these are going to be our building blocks for the encoder and decoder as well, which we know from the previous videos. Alright, so here we are first initializing the classes which will become our layers. So here you can see we have our D model, which is our embedding dimension being 512, the number of heads being 8, attention dropout we have provided as 0.2, feed forward, residual dropout, everything is 0.2. okay, and all are provided to self attention and feed forward. Okay, so let me fire up the paper. Now it will be easy for you to compare and understand how we should build a model based on the paper. Alright, now we have our encoder code and the architecture side by side. So let's compare and see. Right, now we have a multi-head attention which is initialized with the embedding dimension, the number of hits, and attention dropout. Okay, and then we have initialized our feed forward as well, along with 2 residual connection. As you can see here, we have 1 and 2 residual connection. For that we have provided 2 residual connection in here. Alright, and then we also have embeddings here, which is out of the encoder. Alright, the encoder is in here, but the embeddings are out of the encoder, so that wouldn't be a part of the encoder block. Why it is encoder block? Because this is just one block and we are going to keep n blocks which will be stacked together to form the encoder. Alright, now we have our forward, in which what we should pass is, so let me open the residual connection one as well. Okay, residual connection is there, which will take a sub layer, and then which will also take a input. Okay, you'll have your sublayer and input, where to the sublayer, which is multi-head attention here, you'll pass the input, and that output would be added with this one, the original one. Okay, so that is how residual connection or add and layer norm takes place. So to that we are providing our input, which is X, and for self attention, like I said before, we'll have query key values all with the same input, so we'll paste it thrice. Okay, query key value and attention mask. So now we are completed with attention, and then what we should do next is we should pass it to feed forward. Okay, so we are putting another residual connection in here, which will take the attention output and then it will run it on feed forward block. So that will become our encoder output. Okay, so this is how you need to construct a model from the paper. So what we did, first we created the core blocks, which is multi-head attention, residual connection, feed forward and all, which is the core block in here, and then we moved it up the level from 0 to 1 probably, and then now we have the encoder block. Okay, so now next one, we have our encoder block. Now we need to stack it. Okay, we need to have n layers. All right, so we'll take that num layers as input along with the embedding dimension in this encoder class, and there is this class called module list, which will comprise number of modules together, wherein here our module is encoder block. Okay, so we'll start the encoder blocks together, and finally we'll also add a layer normalization. Okay, so what happens is, to each layer we'll pass this input, and then finally the output would be normalized. Okay, so that is how encoder works. All right, easy implementation. Okay, now let's see about decoder. For decoder, it's going to be slightly complicated, not as complicated because we have our theory ready, but practically it is going to be slightly different than how it was with encoder. All right, so similar imports, we have our embedding dimension, number of heads, attention dropout, residual dropout, feed forward dropout, and all being initialized. But you should note here we have two attention, which is self and cross. Okay, and then we have our residual connections as well. Guys, please listen this carefully, what I have taught till now and whatever I'm going to say before, because based on these, like I said, we have a quiz, and the winner will have a chance either to do a LLM project with me, or you can win 500. It's upon your choice. Okay, or if you think, man, I'm not interested in quiz, that is also fair. You can like stay out of it and just check that if you are right. Okay, because I'll also provide the answer. Now coming on to the forward, which will take 4 inputs, which is X, encoder output, source attention mask, and target attention mask. If you see in encoder, we won't take that much. Okay, it is in X, which is that input token, and then we'll have our source attention mask. But here for cross attention, we need encoder output and source attention mask, and for masked multi-head self attention, we need a target attention mask, which would be a look ahead mask. Okay, source attention mask will be like a padding mask, and target attention mask will be like a look ahead mask plus padding mask. Okay, because padding tokens will also be 0 and the next tokens will also be 0. So here we are first computing this, which is residual connection 1, and we are calling the self attention, because here you can see, right, it is self attention. There is no inputs from encoder being passed, so we can just not worry about okay what is going to happen, and then we can just provide xx target attention mask. But in cross attention out, it is going to be different. We are going to call the residual connection 2, because we need instances of residual connection. We have made it as 1, 2, 3, but you can also do it as module list and call it as off 0, off 1, and off 2. That is also fine. Okay, in residual connection 2, we are passing the self attention output. Here we need to add, right? So for that we have our self attention output, which is X plus sublayer of X, right? So for X we have our self attention output, and for sublayer of X we are applying the lambda function to the cross attention, where what it will take is, it will take the self attention output, along with that it will also take the encoder output. Okay, the query is our self attention output, and key and values are from encoder. Okay, and then we have our source attention mask and not target attention mask, and we know the reason for it now, right? Now this is our output of attention, which is passed into feed forward. Finally, we'll get the output. Okay, so that is the decoder block, and again you need to stack it for n layers, and that will become your decoder. Okay, so that is about encoder and decoder. Now there is a difference. Okay, here you can see there is something called linear. Okay, so what we are going to do is we are going to have a file known as transformer. Okay, I'm just seeing it. Yeah, here it is. In transformer, we'll combine all of these, and finally we'll have a transformer architecture ready. So for that, what all we need our embeddings, because we have it as our separate class. We need our embeddings. Input embeddings are there. We have encoder, decoder, and that's all. We have torch neural network as well, because projection layer is not done yet. This is our projection layer. The linear layer is our projection layer, and that is not done yet. Alright, so here it will take demodel number of layers and vocab size, because the projection layer's job is to map the embeddings to the vocab size. Okay, so here you might work with 512, but those should be mapped to 30,522 or 50,000 in our case, because I have set a huge vocab size. So 50,000 to that it should map, and here we are doing that. Okay, so first we are creating an instance of input embeddings which will do this computation of token embedding, which is input embedding specified here, and then it will also compute position line encoding and add it. Okay, for position line encoding we have used sinusoidal position encoding, and now we are also making an instance of encoder which will take demodel and num layers. The number of layers we are considering it to be 2, but you can also consider it to be 6, 8 or 10, how much ever you want you can do it. Okay, so decoder also is similar, but make sure that the number of layers are same. Okay, and then finally, like I said, we are going to map, right? It is going to be 512 mapped to 50,000, right? So that is the job of projection. In one forward, what happens? First, we'll compute the input embeddings. We can also simultaneously compute for target as well. We are computing for source and target. We are passing through the encoder, and encoder output is got here. So once you get the encoder output, the job is to compute for decoder, and the decoder output is computed, and finally you are doing a projection. Okay, so this is how a transformer is built, and guys, we are 50% or 60% done, because we just have the architecture. Okay, we don't have a working model or something like that, because we need to train it, right? That is what we are going to do next. But before going on to that, still, like I said, the architecture is not completed. You need to initialize the weights. Okay, now randomly it would become very random. The weights would be like 1.8, 5.6. There wouldn't be any pattern for it to start with. Okay, to start the training, we'll be initializing the weight with Xavier uniform. Okay, there is a paper which was released from Xavier Glorat. Under his name, there is a weight initialization method which is known as Xavier uniform. Okay, and we are gonna do that wherever there is a dimension which is greater than 1. Like even if there is a weight which will have more than 1 neuron, we'll just initialize a Xavier uniform weight. Okay, so that will provide our model. Now we'll move on to the next section, which is to build the dataset. Let me zoom in. For training the model, we need dataset, we need tokenizer, and then we need our training loop, right? That we are going to see next. For dataset, we have used a dataset class, wherein for dataset we are considering DAR-AI emotion, and here there are 6 classes of emotion, and I'm just going to focus mainly on these 2, sadness and joy, because these itself cover around 70%, and the model surely is going to fail in these love and surprise classes, because it is very less. Okay, but we'll focus on these 2, and here you can see I didn't feel humiliated, and it is sadness. I don't know why it is like under sadness I can go from feeling so hopeless to damned hopeful from just being around someone who cares and is awake. Yeah, it is so hard, right? Like we would even be confused if it is sad or like some kind of expectation or something like that. And here you can see I am feeling grouchy. That is anger for sure. I am ever feeling nostalgic about the fireplace. I will know that it is still in the property. We can also say it as love. that is true. So that is about a walkthrough to the dataset. As you can see, it is a English Twitter message dataset which would be classified under 6 basic emotion, which is anger, fear, joy, love, sadness, and surprise. All right, we are considering this dataset, and for this dataset, first what you need to do is we need to create the tokenizer. Now we are going to see about tokenizer. All right, let me take the notepad itself for me to write. We have a tokenizer section now. So what is a tokenizer? A tokenizer is a component which will do a process known as tokenization, which is a process of splitting the sentence or a sequence of words into a smaller entity known as tokens. Why I am saying smaller entity rather than words itself, you will understand that. Okay, because why we are doing tokenization is because the model needs just a sequence of tokens. Okay, this is how it needs the input. It's not like it doesn't accept this kind of format, it needs this kind of format, a list of tokens. Okay, now I'll say why we are calling it as tokens, not words. There are 3 types of tokenization. Okay, 3 types of tokenization, wherein the first type is character level, next is word level, and then the next is subword level, which is the most powerful one. Okay, why I'll say it is the most powerful one, don't worry. In character level, what happens is, given an input like I am writing, the tokenization will happen something like I space A M space W R I T I N G. So here the problem is that you find it hard to understand the context. Okay, when it is token level, right, it is very hard. You have the space as a separate token. Let's say it is ink. This should be a single token, not INC. What is the difference between this full stop and a final full stop? Okay, what is the difference? No, nothing, right? Like if you put it as token, both are same. It is very hard to understand the context, and that is why this is the least preferred method. This is the least preferred method. Okay, next we have word level, which usually happens with some delimiter, which is usually white space. Okay, so now what happens is it will be like I am writing, only 3 tokens. Okay, here we have better contextual understanding, that's for sure, but the problem is vocab size will be very huge. Why? You see, there is a process in NLP known as stemming. Okay, the process involves cutting down the words to its root word. For example, if it is writing, we'll cut it down to write. If it is playing, we'll cut it down to play. Okay, so similarly a process will happen in this tokenization as well while we are using subword. Okay, so if it is I am writing, or probably better I'm playing football. Okay, let's consider this to be our total vocabulary. Usually it would be I am playing in word. Okay, I am playing football with my foot. Sorry for changing the example, because you'll understand why we need subword. Okay, with my foot. Okay, here if you consider the vocab size, right, in word level it will be 1 2 3 4 5 6 7. Here, okay, it will become 1 for I, 2 for am, 3 for play, 4 for //ing, 5 for foot, 6 for ball, 7 for with, 8 for my, 9 for foot. But the unique token will be 6. That is the important thing. Okay, the number of tokens will be increased, that's for sure, but the vocabulary size for foot and football, here it will, what it will do is it will try to do something like foot // ball. Okay, it will try to combine this foot into football. If it is like football, footballing. Okay, if there is a single token like this, what it will try to do is it will try to make it as 1 2 3, and the token will look like foot // ball / or #ing. Okay, so what is this hashing indicating? It is stating that there is something before this to be added. Okay, so it is saying like, okay, ing should be added to ball, so it will become foot / balling, and it is saying like, okay, still hash is there, I'll go another level, it will become footballing. Okay, I'm writing, I'm playing football with my foot. In this you'll have lot of tokens, but with footballing you have 3 tokens which is combined in different ways. The number of tokens increase, but the vocab size retains the same, but the context also retains. So always the best method is to use subword, but we are not gonna do subword level and all, because subword level tokenizer is quite hard to create, So we'll work with word level itself because we are doing some simple transformer task, right? We'll do for word level. So in word level, what happens? If I'm saying I am writing, it will become I am writing. Okay. So this is the tokenizer which we are training right now. And for that, the code goes as follows. First, what we need to do is we need these following imports. We need load dataset. We need tokenizer. This tokenizer class is the one which will create your tokenizer. And this is from tokenizer's library, which is of Hugging Face. Okay. And then we are calling the word level model. But like I said, there is a lot of other types of tokenizer as well. And for the word level, we have word level trainer. And for pre-tokenizer, like I said, you need some delimiter to split, right? For that, we are considering white space. Okay. So to initialize this tokenizer training, what we'll do is we'll initialize it with the dataset ID along with the tokenizer path where you want to save. Okay. And then we'll also provide the vocab size, which is 50,000, which is from the config. Okay. We are calling the load dataset function to load the dataset, which is DAR-AI emotions. And we are creating a dataset iterator because we need to train, right? So for that, we are creating a dataset iterator, which will provide one after another. Okay. Each input will be provided. So you can ensure that, okay, there is nothing called UNK token for me. Okay. That will be there. Okay. Because what is UNK token is that, let's say your library looks something like I am writing. If there is a word coming like I was writing, okay, in its tokenizer library, in its tokenizer config or its vocabulary, it wouldn't have seen this was. So it will do something like UNK, which states that, okay, I don't know what word was there. Okay, that to be honest, I don't know. That is what UNK token means. Okay, unknown token. But our case, we won't face UNK tokens because the data set in which the tokenizer is built and the data set in which we are training both are same. Okay, since both are same, we won't face that error. But when you are using a public model, like a foundation model that is on a new data set, probably let's say you are creating a tokenizer for English and you are expecting the model to do work with some other languages, it is going to give UNK. Okay, so that is what UNK token means. And here we are creating the pre-tokenizer, and for word level trainer, there is a requirement of vocab size because it needs to know how much vocabulary I need to build, which we have given as 50,000. We are saying that special tokens are pad token, which is to pad. I hope you all know padding by right now. We have talked about it a lot. We have start of sequence token, end of sequence token, and unknown token. And we are providing a parameter known as minimum frequency to be 2. What happens is, if there is a pair, okay, like next we have the tokenizer. Since the tokenizer is ready, the tokenizer class, which is being instantiated, we are training with this trainer which we created. Okay, here you can see the tokenizer has a function known as train from iterator, which we need to provide. Iterator is to be provided along with the trainer. The trainer is here. Okay, iterator is from this dataset iterator, and then we have our trainer from this word level trainer. Once you provide both, the tokenizer will be created and it will be saved in the path provided. For this, obviously I have used a dataset and that is trained. Okay, so that is about tokenization. Once your tokenizer is completed, you can move on to the next step, which is to build the dataset. So before going on to that, let me say what are the requirements for a transformer training. Requirements for training. This will be like something like our checklist. Okay, first we need model tick, that is done. We need tokenizer, that is done. We need dataset, which we need to do. Then we need our training loop. So post training, we'll need something like an inference code. These are to be done, which we are gonna see now. Okay, so for dataset, we are initializing with the dataset ID, tokenizer, because we need to tokenize, right? And then we have our max sequence length, how many tokens we are gonna allow. Okay, and then we have our source column name, target column name. Here we are instantiating all of those, and we are calling the dataset class as HF dataset because this dataset represent PyTorch dataset. Okay, so in that we are calling the from pandas function in which we are creating the dataset and we are sampling it. Okay, why we are sampling it. We are actually not sampling it, we are shuffling it. When you provide frac is equal to 1, it will try to shuffle the dataset. Okay, if there is in some order in the dataset, it will try to shuffle it. And we are also providing the torch tensors for SOS, EOS and pad tokens. Okay, now we need __len, dunderlen rather, which is length of dataset. Okay, that is required because it needs to know how much data points are there in the dataset. Next, we are having the getItem function, which is nothing but the function which will provide the data. Okay, as the name suggests. In this, it takes a parameter index of, let's say, like you have a data frame and I want this index. That happens with this getItem function. Okay, so we are calling that specific row, and then in that we are saying like, okay, source data is this and column data is this, with the help of source column name and target column name. Okay, which all are instantiated while init function itself. The encoder input tokens, what are those? Okay, first we need to encode the source data, and then we are maintaining a common data type which is in64. Okay, so similarly we are doing it for decoder input tokens as well. And there will be scenarios where you might have tokens more than your max length. Okay, that is where you do a process known as truncation, and that is what we are doing here. Okay, why I'm considering -2, I'll say that, but right now just follow me. Okay, we are checking the size of 0. Okay, which will show the number of tokens in the input. So if it is more than 126, because our max length is 128, if it is greater than 126, we'll truncate till 126, from starting till 126. But there might be scenarios where you will have 80 tokens, 5 token, something like that. Okay, so in that time again it won't work, because in a batch everything needs to be of the same dimension, and that happens with this padding. Okay, so first we are calculating the number of padding tokens, where we are subtracting 128 minus the number of tokens -2. Why always this -2? See, in encoder input tokens, we'll pass the start of sequence token along with the encoder input token, then EOS token. Let's say your encoder input tokens is 126, then you have your start token 127 and EOS token to be 128. So here your padding token would become 0, and that is why we are subtracting it with 2. And then the same logic applies with decoder as well, because in decoder we won't use padding token. Sorry for the wrong word being used. We won't use EOS token. Okay, in decoder input we won't use end of sequence token, but in label we'll use it. Label is your ground truth. Okay, so in label pad tokens, label pad, decoder input pad, encoder input pad, it does nothing. Okay, it will try to multiply, and let's say like if it is 5 token, it will try to create 5 pad tokens. Okay, as a single array, obviously. And that is what happens. You are calculating the number of padding tokens here, and that array is created here, and you are concatenating all of those, which will give you your encoder input token, decoder input token, and your labels. Okay, next it's time for us to create the attention mask. For encoder, we know it is just padding token mask, right? So we are saying like, okay, whatever token is not padding token, I'll have it as true, otherwise it will be false. Okay, and since you are putting the torch to be in 64, what it will do is, wherever it is true, it will become 1 and the others will be 0. If it has been bool, it would have been true, false, but since it is torch in 64, it will become 1 and 0. Okay, in autoregressive mask, we are going to build the triangle. Okay, that autoregressive mask, it will be always square. Okay, let's say if it is 3, the sequence length is 3. So what happens is 1, 3, 3. That is what we require as 1. So what happens is it will be 1, 0, 0, 1, 1, 0 and 1, 1, 1. That is what happens with torch.tryU, and the diagonal is set to be 1. Okay, that is what is required here. And then what we are doing is we are computing the padding mask. Along with that, we are also multiplying the autoregressive mask. Okay, because like I said, it is both padding mask and autoregressive mask, which is nothing but a look ahead mask. Okay, so yeah, that will give you your decoder attention mask. So now let's see, we have our encoder input IDs, we have our decoder input ID or input tokens, and then we have our encoder decoder attention masks, we have our labels. Okay, which means we are ready for training. Okay, so let's create a dictionary which will be having the following values: encoder input IDs, decoder input IDs, attention masks, labels, source and target if you need. Okay, all of these will form our data set. Now we have completed our data set. We have created our model. So next step is to create the training loop. Okay, for training loop, what we are going to do is we are going to have a class known as trainer utils, which I'll say once we move on. Okay, in trainer utils, we have the following. Like, you can say this is the crux of the training. Okay, training file, we have kept it as simple as possible, but this one will be like having all of those functions which is required for training. Okay, as you can see, it is a long file. Obviously, I've made some documentation as well. That makes it very long because at every time you can't be watching this video and all, right? So you can just go through the doc string and you will be able to understand. As the name suggests, this utils class is to hold all the utilities required for model training and inference as well. And in this, we are providing our dataset ID. We are providing our tokenizer path, which is tokenizer.json. And then we have our max sequence length, source column name, target column name, logging directory, where you want to store your logs. We have our batch size and then our vocabulary size as well. Okay, and here you can see I tried a lot of attempts, so it will be clustered. In the tokenizer, first we are calling the tokenizer, which has a function known as from file. What it will do is it will take the tokenizer.json file and it will try to create an instance of the tokenizer based on that. Okay, now we are creating our model. Next, our dataset as well. So we have a tokenizer, model and dataset. So what all are needed in the training? In training, we need optimizer, we need loss function, we need the model, dataset, data loader, and the tokenizer. These are the things which is required. And if you are gonna log something, we need our logger. So we are done with the tokenizer, model, and dataset. So it is time for us to call the logger, which is TensorBoard logger here. Summary writer is from TensorBoard. Okay, so it will try to log things which we say we want to log. We'll log the training loss. Okay, and then we are calling the optimizer, which is Adam optimizer, the most famous optimizer with the learning rate of 1e minus 4. Okay, the learning rate would be in config file. Okay, all the configurations are updated in this file. It is a good method because you don't want to go inside the files for you to change the configuration while training. You can just change the config file and it will have its impact. Okay, and here we are saying we need to ignore the padding token while we are calling the cross entropy loss. Cross entropy loss is a loss which will try to match the tokens. Okay, if it is 1 1 1 and 1 0 0, it will be something like 0.33, something like that. The loss has its own calculation. If you want a separate video on cross entropy loss, how it works, let me know. I'll make a short video on that as well. But here we are saying we need to ignore the pad token, because let's say you have a sequence of 10 tokens and rest 100 is like probably pad tokens. If your model generates 105 pad tokens, still your losses will be very less because pad tokens are same from the input and labels. So that is why we are doing ignore index. We won't consider our padding token for our loss function, because when we are not giving any attention to it, why should we calculate the loss for that? Next, like I said, dataset is not enough. We need data loader. So for that, we are calling the data loader, torch utils data loader, which requires a batch size, which we consider to be 10. We are shuffling the dataset as well while training. And then we are also providing the dataset class, because it takes a torch dataset class as its parameter. And for say like safety purposes, I've had it as train data loader. If you want, like, you can do a test data loader, write a validation loop, and probably you can do val loss as well, which I didn't do. Okay, to compute loss, we have this function which will compute the cross entropy loss, which will take two parameters, which is model output, which is logits, and then labels. Okay, both are needed. And here what we need to do is we need to call label .view of -1 and logits .view of -1 comma self.vocab size, so that both are in the same shape for us to calculate the loss function. We'll not see the generate function right now, because that is about the inference, which we'll see later. Okay, now coming on to this function in train. This is where we went inside, right? Trainer utils, which will provide all the utils you need for training. Okay, we have our data loaders, we have our writer, which is our logger, we have our model, we have our optimizer, all are provided. Okay, next we are making the model to be in CUDA so that we can use the GPUs. I have GPU, so if you don't have GPU, make it as CPUs. Okay, and we are initializing the epoch number to be 0 and step numbers to be 0 as well. Okay, the number of epochs you want to train, you can provide it from the config. Like I said, we are considering it to be 5 here, and then we have our model save path, which is transformer classifier. Okay, and then now we have our train function, which is what is called here, and here we are saying for epoch in range of num of epoch for data in TQDM. Okay, why I need TQDM? So that I can see what is going on, how many steps is completed. This will give a progress bar. Okay, so this will take the data loader because we need to traverse through the data, and we are just printing like, okay, I'm training the epoch number 1, 2, 3. For that we are using this. Okay, now we are calling another function from the trainer's util itself, which is train one step. Okay, for one step of training, this function will be called. So how many ever steps we train, that much time this function will be called. Okay, so what this function does is it will do one forward and one back propagation, and then finally it will do the optimization part as well. Okay, it will step the optimizer and it will go to zero gradient. All will be done in one step. So whatever you want to do usually in a PyTorch training at one step, all will be done in this function. So here we are calling the encoder input IDs. We are calling the encoder attention mask, decoder input IDs, decoder attention mask labels, all from the data, and we are making it to be in CUDA. So we are passing through the model. Okay, the model forward happens. We have our model output. The model output is passed to the loss function, compute loss, which we saw right now. And there what happens, we'll try to compute the loss. Okay, so once your loss is computed, you will do back propagation based on that with the help of optimizer. Once you call the optimizer.step function, your back propagation happens where you do this optimization. Like you'll update the parameters, right? Weight new is equal to weight old minus learning rate into dual by duo. It is a back propagation calculation. That optimization will happen when you call this optimizer.step, and then you have a optimizer.zeroGrad, which will empty the gradient once the step is done, and will return the model optimizer and loss at each steps. Okay, so it will go on. Okay, we are incrementing the number of steps as well, and it will go on till the one epoch is completed. And once one epoch is completed, as you can see here, it will try to call the save checkpoint function. Okay, the save checkpoint function, which will first call the ensure save folder. What it will do is like it will see if the folder you want to save exists. If it exists, it will not consider anything. If it doesn't exist, it will make that folder. Okay, so in that we are storing the model, optimizer, static, both we are saving, and we are also saving the epoch number, at which epoch I'm saving, and the loss as well. If you call that, you can understand what all have happened. But if you want, you can also compute the validation loss, the step number, all can be saved as well. We are printing that. Okay, so to train it, you can just call Python train.py. You can just go into the source, but make sure you have first call the tokenizer. Okay, first do Python tokenizer.py, then do Python train.py. Okay, it will work. No issues, it will work. Okay, let me do a time lapse here till the training starts. Okay, here if you see the training has started and it will go for 5 epochs. Okay, so that is how you need to do training. Let me show an inference now, for which we also see about a concept known as greedy decoding. Okay, for decoding strategies, I'll make a separate video because it is a pretty huge concept by itself. But if you want that to be our next video, let me know. I'll make it as the next video. Okay, so this is the inference.py file where it requires the trainer utils as well. Okay, this train utils is required for us to use the generate function. Like I said, generate function is there. So here it was for translation before. We'll make it as classify. So here we have the classify function, which starts here. Okay, you wanna call it. I'm saying I'm delighted. Okay, so we are making sure that the inference happens in CPU, where first we need to tokenize, right? So first we are creating the tokenizer, we are creating the model, we are loading the state dict. Okay, the best checkpoint for me came at 3rd epoch, so I'm just loading the state dict. And since we saved with the key model, we are loading it. Okay, and we are setting it to be in eval mode so that it doesn't consume any GPU. And we are calling the nograd function to avoid the gradient calculations. Okay, First, what we need to do, we need to tokenize. So we are tokenizing the input, and along with that, obviously we need to do that padding, add the start of sequence, end of sequence token and all, which is done here. Okay, I'll also compute the source attention mask, which is done here. So once this is done, you have your input IDs, which is padded and is ready, and then you have your input mask. Okay, for output you shouldn't do anything. That is the thing. Like I said, in training time and in inference time, decoder works different, and let me show that how. Okay, in generate function, first we are creating the SOS index and EOS index. All right, and we are creating an empty placeholder for the decoder input. It will start with the start of sequence. Okay, SOS is called here. So what we're doing is, I'll first do the theory in here, and simultaneously I'll show you the practical things. Okay, so while inferencing, what you will do is, you will start with one token. Let's say if it is SOS, this will be passed into decoder along with obviously encoder input and all. Okay, along with the encoder input, he will provide that, and in decoder, what you will do, you will generate a token. Okay, only one token will be generated, not the sequence. In training, you will provide the whole mask. Okay, it will be an array, but at inference time, you will provide only one token, and then if there is another token, you will try to add this. Okay, there is nothing like this kind of a mask. Okay, which will be complete. Like usually in training, what you will do is, if it will be 1 0 0 1 1 0 0, something like that. But in training, what you will do is, first you will pass this one token, then you will do this 1 1 0 0 1 0 0 0. Okay, it will be 1 0 0 0 like this. Okay, but here it would have been complete. It will be a single array, but here it will be looped. Okay, that's why we are using this while loop. So what we are doing, first we are creating it for the first token. Okay, and then the decoder input, which is obviously here only one token. So you will pass this one token in there. Okay, usually mask is not required for decoder. Let me clear this. I'll put it again. While training, you will provide it as this 1 1 0 0, like probably 1 0 0 0 1 1 0 0 1 1 1 0 and all 1. Okay, this is how the input will be like. But in inference, you will only provide this 1. In the next step, it will become 1 1. The next step, it will become 1 1 1. So necessarily, actually, the mask doesn't make any difference, but the model has its parameter as mask. So here we are just computing the mask. Okay, and you are computing the model output, which will give you the model logits. So you have your input ready in decoder. Encoder is already done. This is provided to softmax function to make sure that out of, let's say if it is one token, it will be 1 comma 50,000. Okay, in 50,000, which is the most one, all should be mapped to 0 to 1 probability, because this is all about probabilities, logits, and we are making sure that that specific token, which is our expected token, is having the maximum probability, which is done with softmax. Okay, softmax is nothing but an activation function which will try to have all the given input into a single probability, which is to 0 to 1. Okay, next we'll call the argmax function. It will try to have or try to get the token with maximum value or maximum probability after softmax. So basically, this is what is your token. Next token, let's say I'm saying like I'm feeling. Okay, to say the next token is good / bad, this is the process. Okay, and now you'll have, let's say it is I am feeling good. Okay, till that it is done. I said like I said, until full stop the generation doesn't need. Okay, but it is not just full stop, it is end of sequence token. So we'll add this token to the decoder input, and again this loop will be started. Okay, till the EOS token is generated, the loop will be done, and that is what happens in here. Okay, let me show you now. I'm creating the attention mask. It is provided to the model. We are calling the softmax function. We are calling the argmax function to get the token, which is the max one. And I'm just printing it, but this wouldn't be needed. This is just for debugging purpose. And then next we are concatenating that output of a specific step, which is, let's say, the first step along with the start token, the second step along with the start and first token. That happens in here, and we'll do this until the given token is EOS index. And if it is EOS index, then you have generated the tokens completely and you will stop the loop and then you are decoding it, which will give you your input. So if you see it in a graphical way, right, it will be like, let's say if I'm saying I am, in greedy search, what will happen is it will see like, okay, these are my possibilities: feeling, writing, playing, and it will say like, okay, I'm feeling that the most thing should be something like feeling itself. So I'm going through feeling. Okay, for feeling, I'll give it as a right. It will go through this path. Okay, there are some other methods as well known as beam search, which will do something like tree and all. I'll do this as a separate video, like I said. And there is sampling methods, okay, which is top K and top P. All these methods are there, which we'll cover in inference video. Sorry, on a separate video on strategies. So since we have seen how the model will work while we do greedy decoding, now let's see in real time how greedy decoding really works. All right. So let me go to source and let's run Python inference.py. As you can see, it's running now. And I have given I am delighted. So anything in the line of 0, which is joy, or I think the only class should be 1, which is joy. Yeah, it is 1. Okay, so yeah, let's try again something. I feel very bad. 0 is sadness and 1 is joy, so here it should be 0. So let's see if that is the case. And yeah, it is 0 and the model seems to be working. We have seen about training, we have seen about inference, we have seen how to create a transformer, we have seen how to create a tokenizer, how to train a tokenizer, everything is done. But finally, we are also going to see how to visualize the attention performed by the model. Okay, so for this, I'm using a library known as BirdVis, which will take only the transformer library model. So for now, I'm just taking the distal bird model from Hugging Face, and we are tokenizing the input where I'm saying I'm feeling bad that I failed yesterday, and that is provided to the model, and we are taking the attention alone. Okay, let's do a model view where here you can see there are 6 layers in this model and it has 12 heads. Okay, at a given layer and at a given head, how much it is focusing. Let's say I'm seeing the layer number let's say 3 and the 6th head. In the 3rd layer and 6th head, the most importance of CLS is given to SEP, and the I token focuses on CLS, I am, feeling bad, and separator. Okay, AM token also focuses on CLS and bad and all. Okay, so here you can hover through this. Okay, and yesterday focuses on SEP. So like this, if you hover it, you can see most tokens always will be either focusing on SEP or will be focusing on CLS. Okay, always it happens. Okay, like as you can see, it is going like that. But also each layer and each head, the layer head at each layer focuses differently, right? Obviously there is a pattern in here, but the lighter ones are slightly different. Okay, if you see here, it is slightly different. So that is what you get with multi-head attention and multi-layers. Each layer and each head will focus on different specific entities, and you will have an idea that, okay, I need to focus on this. Let's say I'm going to layer 2, and I'm going to see head alone now. This is not at model level. We are going one level down, 2 layers. At the layer 2, I'm feeling focuses more on SEP, and then it focuses on bad. If the highlighting is more, it means that the attention is given more to that. Okay, so you can play around this to know how attention works. I'm going to show you all how you can make the complete pipeline from pre-training till productionizing your LLM, which means you can pre-train your LLM, you can fine-tune your LLM, and you can put it in a real case scenario. From research till real world application, everything will be covered in this video as a pipeline. For this video, I'm considering my LLM as Llama 3 because that is the current best LLM. But this specific pipeline can be adapted for any of your own LLMs, be it Mistral or Phi, whatever you want, still you can use the same code. That much generic is the code which I'm going to show in this video. Now, first let's see the pipeline and then we'll move on to the coding part. So, the pre-training to production pipeline comprises of 4 steps or 3 steps, but here I have set it as 5-step pipeline. I'll explain it. Okay. There are some common steps as well. So let's start with that, which is your pre-training. Now people are wondering of how I can pre-train any LLM. Okay. So for this, what I'm going to do is I'm going to say how they pre-train LLMs. For example, there is a paragraph, for example, stating that I am working for neural hacks with Vasanth. Okay. So if this is the data, what they would do is they will leave it at I am working. That's all. For neural hacks with Vasanth, by loss updation, it will be able to identify. Okay. So that is the core idea of pre-training. This task would be known as next token prediction. Okay. It is known as next token prediction. That is the pre-training task for normal decoder LLM. But if you had been doing something like an encoder model being involved, be it encoder, decoder or encoder, at the time you will do something like mask language modeling. So for example, I'll mask that, put a mask here in some mask here. So it should try to put a location here and then put living in here. Something like that. Okay, if I had saying like, no, Chennai, I am living in Chennai only makes some sense, right? I am living in Chennai, I am residing in Chennai. So these kind of content should be coming up here. So that will be the pre-training task for encoder model, but we have decoder, right? So for this, in Llama 3, they wouldn't have specified the data set exactly, okay? But they said that they trained on 15 trillion token high quality data. Okay. And till date, I didn't make any video on pre-training LLMs because such data was not available over internet. But thanks to Hugging Face, now they released a more dataset known as Fine Web dataset. Previously, there were datasets like Refine Web and all, but those weren't good enough actually. So here now, Hugging Face has released this dataset known as Fine Web dataset, which I'll also show you while showing the code. But you can consider that. Again, just have the data. There won't be a lot of pre-processing required for decoder model pre-training. Okay. And considering that it is a high quality data, again, like cleaning kind of stuffs won't be required for you. Next step is instruction tuning, which is also known as SFT. So now, in pre-training, what happens is the model will understand the language. Okay, it will be able to understand the language. But to make it follow your instruction, for example, I'm saying write a summary for the following passage. To understand that, okay, I need to write a summary and then this is the passage. It should understand the context between those, right? Contextually, it will understand from here, but to align to the instruction, to follow the instruction, we'll do the step known as instruction tuning, which is also known as supervised fine tuning. For this, the most popular dataset and the best dataset right now is OpenHermes 2.5 dataset. And guys, I have provided the best pipeline you can get for pre-training by yourself. Again, you would need a lot of computation for this, but if you're going to do any step in this, let's say you have took a pre-training model and you're going to learn from there. Okay, you're saying, okay, Vasanth, I don't have resources for pre-training, but I'm going to start from instruction tuning and I'll be doing DPO and then I'll also put it in a real-time application. Well and good. Follow from the second step. Okay, and you're saying, okay, Vasanth, I'm not going to do that. I'm going to just do preference alignment. Follow from the third step, but the pipeline remains the same. Okay, so here now, for this, there is OpenHermes dataset, and instruction tuning focuses on a specific concept known as generalization of knowledge. There will be tasks for it to accomplish. For example, I'm saying about how to complete a dialogue, and then there is another task of summarizing a passage. So if you ask the model to summarize a dialogue, based on the knowledge it has achieved in these two, right? Still, it will be able to do this task based on the cross task generalization method. Okay, it is known as cross task generalization method. That is something you usually achieve with the help of instruction tuning. So more the task, more generalized the model would be, is the idea. And this was brought by Flantify, one of my favorite LLMs. And if you want to put it as LLM, it is an LLM. And people who are following this channel would know that it is one of my all-time favorite LLM. Now that you have considered, you have completed the instruction tuning itself, you have pre-trained your model, you have instruction tuned your model. Now what? It is not always guaranteed that your model will respond according to whatever it is to be respond. If you are confusing, let's consider this. Let's say I'm asking to tell the model some bad words. Okay, so let's consider this is a bad word. Okay, this is a bad word. Usually when you do just instruction tuning, right, the model will say this bad word, but we'll align the model in such a way that it would say, I am not gonna say something like that. It will be able to identify, to get rid of harmful content from model generating those content, you can use DPO. Okay, this DPO is known as direct preference optimization, and there are lots of other techniques like IPO, KTO pair, but all fall under the technique known as preference alignment tuning. And for this, the best dataset right now available is ultra feedback binarized preferences. Okay, this is the best open source data which is available right now, and you can experiment with that. The next one is ORPO, which is the most latest method and which is said to be better than SFT and DPO. So ORPO, the idea is that the odds of your model generating the correct token should be higher than the wrong token. Okay, chosen rejected. So here what happens is, let's say you have OpenOMS data itself with preference. It is not there. Okay, but if you can find such a good data set, right, you can avoid these two steps. You can jump from 1 to 4. Okay, you can jump from 1 to 4 if you have such a data set, because ORPO expects you to have similar kind of data set as DPO, but this DPO requires the model to be trained on SFT trainer, or SFT tuning should be done, but SFT is not required in case of ORPO. And the good thing is ORPO is better than SFT, ORPO is better than just DPO also, and ORPO is better than combination of SFT and DPO. But the thing is, you need large data for that. Okay, so you can also think, okay, I'm not gonna do second step, third step, I'll just jump from second step to fourth step. That is also good enough. Okay, still that is something you can try to do. Then finally, you have your real-time applications. See, this is a bit complicated because I have just specified two in here, right? I have specified RAG and chatbot, but there are a lot of things you can do. You can do instruction tuning, information extraction, and there is text classification. Everything is there, and it is upon you, like, to make an internet search and all. So I'm just putting it under real-time application because there are lots of tools involved in there. It is more of an architectural changes of the model. Okay, it is mostly building an environment around the model rather than the model being changed itself. Okay, because if you are building a chatbot, if the knowledge is there, if you can make an environment where the model can chat, it will become a chatbot, right? But if you're going to ask that question and it is going to answer, it will become a question answer. Okay, so it is upon you how you convert the model into a real-time application. And there is function calling as well. Okay, with function calling, you can do a lot of things. Right now, Devin and all of these agents are using function calling. So that is also there with real-time applications. And soon I'll also make video on how you can make a very big project with the help of function calling. Already I have made a video on function calling. So if you haven't checked out, please check it out as well, because that is very important right now. So with that being said, that is our pipeline. Okay, so this is the pipeline you should follow for LLMs from pre-training to production. And now we are going to see the code for doing this task. Okay, so here is one notebook which you can follow for the second and third step. Okay, and for fourth step, I have a separate another notebook which you can follow afterwards as well. Now, coming on to this specific notebook. See, the training code, people are wondering, pre-training is different from tuning. No, it is not that actually. What happens is in pre-training, you will have your model weights being enabled. Okay. In fine tuning, the model weights won't be there. That is the difference. Okay. That is the key difference for you to do this task. If you're going to pre-train, make sure that the model weights are randomly initialized or Gaussian initialized based on how the architecture is written, and there is no trained weights in it. And if you're fine tuning it, the weight should be there. So now you might wonder, okay, that is all fine. Come on to the point. Yes, I'm coming to the point. Don't worry. So here the code is going to remain the same. Okay. So you can provide a training configuration, which will come later. The most important part is I'm setting is pre-training to true. Okay. This is our own configuration, and I'm seeing if we are pre-training. Okay. If it is a pre-training, what you're going to do is you'll not call auto model causal for causal LM dot from pre-train, but rather you'll just call it with the help of config. Okay. You can also call it with the help of from config. That is also there. That is also possible. Okay. But the thing is, you should not call it with the help of from pretrain, because from pretrain will load the weights and from config won't load the weights. You can see the difference here. Auto model for causal LM dot from config. Let's go here. Auto model. Actually, what happened is Hugging Face for some reason has hanged up actually. I don't know why. So here in auto model for causal LM, you can call it via from pretrain, which is the usual ones, but you can also call it with the help of from config. Okay. When you call it with the help of from config, it will be random initialized weight. All right. That is very important for us. So let's come on to the point again here. So here you can see I'm calling it as from config and I'm providing the model config here. So for in this, I'm providing the model checkpoint, the vocab size is provided, the max sequence length should be provided for the context length, along with the tokenizer start token ID and end token ID. Now, Llama 3 8 billion isn't a model which will fit in this Google Colab. So for that, what you can do is, recently I made a video on 1-bit fine tuning. Okay. So in there, I would have shown you how you can reduce or change the configuration itself. And I'll also show you now, not this one, just give me a minute. Yeah, here is the code. And here in this, you can see that the dimensions would be changed. Okay, max position embeddings, number of attention heads, these all would be changed. Now, if you are a person like thinking, okay, Vasanth, I want to learn from pre-training, how I can do that. All you need to do is, I have already provided this in another GitHub repo, which is for 1-bit pre-training again. Okay, you can just run this configuration extra before calling auto model for causal LM. Okay, here it is Llama for causal LM, but you can put it as auto model for causal LM there. Okay, other than that, is not going to differ a lot actually. Okay, the dimensions, heads, every information are provided here. That is upon you. You can just provide it, but you can follow the same configuration itself, because this is a 70 million parameter model and it will train faster. Okay, so that would be my suggestion. And this notebook is also provided in the GitHub repo and you can check it out. So what you should do is add the configurations before here. I'll provide a comment here so that you can check it out. Add the configurations for changing the number of layers, heads and all. Okay, all of those can be done here. Now to change the heads, you can just add those in here and then call the model. Okay, so with that being said, now let's see how you can train this. All right, while pre-training, okay, it is very important that you shouldn't add LoRA. Okay, in pre-training there shouldn't be LoRA added. You should pre-train from scratch. But while fine-tuning, you can use LoRA. So that's why the use LoRA is inside the else condition and not outside. Alright, that is something you need to note. For pre-training, again, we need a model, we need a data set, all are there, right? So what I'm going to do is, now I'm going to change the configuration like I said. So this is a general data or the code which I have written for Finetune Any LLM video. And we are going to change that now. I'm going to do that in live. Okay, all you need to do is change the model checkpoint and dataset. That's all. Nothing other than that. Probably some other things like max steps and all, but other than that, it is gonna remain the same actually. For some reason today, Hugging Face is taking a long time. I don't know why. So I'll put it here actually. Something like you can put the Llama 3 model checkpoint here. You can just fill it correctly. Okay. You can fill it here. And then for the data set name, where I have provided it, I think I've kept it down. Yeah. So what you need to do is you need to change this specific function. Okay. You need to load the data set, and Hugging Face is not opening today actually. So what I did was today Hugging Face is gone down, I guess, the server. So for model, I just identified by going into incognito and then searching it from there. So let's put that in here actually. The checkpoint is not going to differ now. And while pre-training, make sure the load info bit is false. Okay, that shouldn't be true, and that's why we have not provided any of these things like load in 4-bit and all. Please don't do it in 4-bit. Pre-train it in full training itself. Or if you wish, you can also do it in 4-bit because 1-bitnet has shown that you can pre-train it in 1-bit as well. Okay, so that's upon your wish. Still, if you want to pre-train in 1-bit, what you can do is you can follow that video of pre-training and then continue with this specific code. Okay. So load in 4-bit. If you want to pre-train in 4-bit, well and good. You can also pre-train in 4-bit, which is set to true. Other than that, we are also setting the device map to, if you are using multiple GPU, right? It should specifically allocate specific layers to specific devices. For that, we are using accelerator, or else you can also provide it as auto. And for torch D-type, we are setting it to float 16. Trust remote code is set to true. Use LoRA is set to true, which means I'm going to use LoRA in fine tuning. Okay. This is a specific configuration which you can use for both pre-training and fine-tuning. LoRa alpha, LoRa dropout, all of these parameters I guess you would have known by now. The thing which we should be very interested in is when you are fine-tuning, right? Is pre-training would be false. At that time, what we'll do is we'll call the model checkpoint, we'll load it in 4-bit directly, and we'll also attach the LoRa modules. Okay. Other than that, your training argument is provided, which means your training arguments in which your output directory is provided, training batch size is provided, and gradient accumulation steps. In how much steps do you want to do backpropagation optimizer? Like, do you want to use an optimizer which is specifically created for quantized models, which is paged optimizers, paged RMW optimizers, which is what we will use here. And learning rate is provided, learning rate scheduler is also provided. Save strategy, which means how do you want to save by epochs or steps? If it is steps, how much do you want to save? Something like that. And you can play around with these training arguments. I have left it to you. Okay. But while you, this is for education purpose. So I've just set the max steps and all. But while you are doing this, comment this max steps and all. Okay. And once this is done, for a SFT trainer, we need the data set, the tokenizer, the model, and the training arguments all are ready. And here, while pre-training, this will be considered, and for fine-tuning, if we are doing LoRa fine-tuning, this will be considered. Okay. For model, we are providing the model. Data set is we are providing data which will be called from here. Actually, the trainer will take data as its input along with the configuration which was specified here. All right. And we have the training column name. Which do you want to use? Usually I prefer the column name text, and that's upon you. Training arguments, tokenizer, and make sure the packing is set to false, because like if you set packing to true, right? Let's say you have the max length of 512. If there is data of 50 length, okay, 10 data set will be combined together. So that might at times affect the performance. So it is always better to set the packing to false. And then there is max sequence length provided. And finally, we are calling the train and save model. This is the main function which will first create the trainer. And the create trainer function, once it is executed, the trainer is ready. We'll train the model, we'll save the model, we'll save the tokenizer, and we'll also push the model actually. Okay. Along with that, we're also pushing the GGF model. If you want to push the GGF model, you can also push that. Why I'm saying that is, nowadays inference using Ollama is very good, and once you push your model by using this GGF format, right, you can use it with Ollama, and I'll also show you how you can use your custom models with Ollama actually. Okay. Now let's see if the data is ready. Okay, fine web, it is ready. I think it will again take time. Ah, it didn't take. Nice. So actually, you did not do anything. Actually, you can just load this data set. That's all. But you can't load this data set here. But you need a very big server is required, because the size, if you see here, it is so huge. Actually, you should somehow load it. For example, I want to speak about this dataset a bit, actually, because it has been said that this has better result than whatever is there till date. Actually, we'll see about that here. Check the raw version instead, and here they made a graph out of it. And when I saw that, it showed that the model which are trained with FineWeb outperforms any other model which is trained on any other dataset. For example, C4, RefineWeb, Cosmopedia. In every other dataset, it is outperforming. So you can pre-train with this dataset if you are starting now. And the license also is good, actually. Open Data Commons Attribution license only. So you can also use it without any consideration. So here all they have provided the text and the URL from where they have taken the text. Both are provided. Okay. And the token length is also provided. How much tokens are there in the specific data. So all you need to do is call this data, and already since text is there, all you need to do is just call the load dataset function and just return the dataset. That's all. No need for any formatting. While fine tuning only, you will need any formatting which you require here. Okay. And I have made a lot of videos about fine tuning data formatting and all. Please check those for this, actually. Okay. And if you want to do any formatting, write a specific formatting function and then call it here. But while pre-training, this is not needed. Just put the dataset name here. Where is this? Yeah, here it is. Just put it here and call the split is equal to train. But don't run this, your system will crash. Okay, because it is 45 TB, it is not going to survive. But I'm just providing you code so that you can use it at the later part. And for fine tuning, what you can do is just change this dataset and change this formatting and it will work. Okay. Now, let's say you are completed with pre-training and then instruction tuning. Next, you need to do DPO, right? There are not a lot of things which you need to do. The same thing will be there. The model is provided, the reference model is provided, because the same model will provide rewards for itself. That is what is the idea of DPO or any other methods which fall under preference alignment. Okay, but here it is very important that you have an SFT fine-tuned model. And here, if you see, the trainer alone differs. Other than that, everything will remain the same. So I'm not going to explain all of those. And for trainer, we are providing the model, reference model, which will be the same model, actually. Okay, LoRA configuration, because we need to train with LoRA. Training arguments, data, tokenizer, these are all fine. Now, these are some things which will differ for you. Okay, first thing is beta. So beta, for specific methods, there are specific beta. For example, DPO, give it a higher beta, 0.5. For KTO pair, give it 0.1 or 0.2. For IPO, give it 0.01. This is the best beta they have found with the research analysis. And for loss type, like I said, there are 3 loss type, which is DPO, for which you need to give sigma, and then there is KTO pair and IPO. Okay, so that is provided here, and based on that, you should also provide the beta. Max length is new or not new, and here, see, they provided a support for aligning encoder decoder model as well. So what you need to do is, if it is an encoder decoder, just set it to true or else keep it false there in the configuration, and make the max prompt length to be your input length. Okay, for example, I'm saying write a paragraph on neural hacks with Vasanth. That will be a prompt. Okay, whatever it does after that will be the expected output, right? So the expected output length is your max target length, and the input length is your max prompt length. Okay, when you combine these together, it will add up to the max length. That is how you need to set the parameters for DPO trainer, and then you can call the same saving functions and all, it will work. Okay, I'll provide this code, and if it shows any error, let me know in the comment section. I'll help you out. Okay, and there is also a Telegram group. Now it is very active. There are lots of people, knowledgeable guys who are chatting it in very actively. So consider joining there as well. Now, like I said, if you are thinking, okay, Vasanth, I'm not going to do SFT and DPO, fine, no problem. What you can do is just come to this notebook. Okay, This is ORPO, and thanks to this person known as Maxim Labone. He's an amazing guy. He's one person you guys should follow in LinkedIn. Okay, so for this, again, there are some conventional things which he is doing here, but there are some other things as well. Okay, so these are all to load the model with flash attention and all, which is not required for us. We need to focus on this. There is this one thing which he is doing where he's setting up the model to a specific chat format based on the model and tokenizer. What will happen is it will try to change the model embedding token size. Actually, in one of my previous videos of fine-tuning LLM for information extraction, I would have added some special tokens. Okay, and when I added the special tokens, what will happen is the embedding dimension will change, and the embedding dimension is still 32,000, but the tokenizer length is 32,005, so it won't load. It will give an error. So I needed to call the model resize tokening embedding and all. But here what they have did is, in Hugging Face itself, they have provided this thing called setup chat format, because ORPO adds some tokens inside. So for that, we are providing setup chat format as well, and we are setting prepare model for k-bit training to true, which means when you are calling the function, it will be set to true again, which will make sure that the model is ready for 4-bit or 8-bit training upon your choice. So for this, he has provided a dataset by himself, which is Maxim Labone ORPO DPO mix 40k. You can also choose that, or choose the dataset which I said. Okay, and here he's taking just 1,000 samples, and then the format for DPO or ORPO is that you need to have a prompt, chosen response, and a rejected response. So it will have 3 columns of data, but in SFT or pre-training, just 1 column, which is text. Okay, so he is just formatting the data, and then he will be providing that later. But right now, the configuration, if you see, isn't very much different. The beta will be there, which is 0.1. Other than that, everything is same as before. The thing which is different here is just the trainer and the class name. Okay, previously it was training configuration, training arguments, and then your trainer. Okay, it was SFT trainer or DPO trainer. Now it is ORPO trainer and ORPO configuration. Other than that, the values is same still. Okay, and then finally you can call the trainer.train and save model function. And if you want, you can also again call it merge the LoRA modules, because defaultly it will push the modules alone, LoRA modules alone. You can also load the model along with the LoRA module combined together as a single model and then push to hub as well. That is also possible, which you can execute with these 2 cells. Okay, I tried with executing Llama 3. Like I said, it won't have enough GPU. Okay, that's why I didn't execute this. But if you want, you can attempt as well. That is completely upon your choice. Okay, now we have covered the 4 steps. Now you might think, Vasanth, we have done the video, right? No, I'm not going to leave you high and dry in half. Okay, now we have the next thing coming up, which is the 5th step, and it is real world application. Okay, and this is a real world application, which is a PDF bot. Okay, so in this, what I'm doing is I'm using Llama Index. I was bored of Langchain, so I just tried Llama Index, and it is also same as Langchain actually. Okay, so what I do is we'll take the PDF. Okay, basically we'll upload it here, and then we'll create a temporary directory, because we need file path, not the file itself. Okay, so we'll create a file path based on temp library, and we'll provide that to the simple directory reader, which will read the file. Okay, so we are providing the extension to be PDF, and recursive set to true, because in one directory itself, in subdirectories, there might be PDFs as well. So it is set to true. But if you are thinking, okay, I'm just going to take one PDF itself, so it will also fine. Okay, so you can also provide, if there is no file, you can stop it and then ask them to load the data. Okay, now if the loader is ready, we'll call the load data function from there, which will load the PDF contents. Okay, so once that is done, we'll create the LLM, which is Llama 370 billion, and you need to provide your API key here. Okay, I have already provided mine. You need to provide here, or else for safety, you can also keep it in .env file. And for embedding model, I have used a small env file. You can also use MXBAI, whatever model you think is good, you can use that. Okay, make sure that in settings, okay, this is a parameter, a setting, okay, a variable from llama index itself. Okay, this setting is a variable which will make sure that this is kind of a configuration thing, and in there we are setting the embedding model to this embedding model. Okay, and for index vector indexes, we are creating a vector store index. This will be an in-memory vector store index based on the documents. Okay, the embedding model will be taken from here itself. That is why we set the embeddings with the settings here. All right, in LLM again, in settings we are setting the LLM, and we are indexing with the query engine. Okay, we'll provide the question. Here is a prompt template, and here it takes the context and question. You can just go through this prompt. Okay, and then we'll also update the prompt whenever it is required. Right, when we have the context and question ready, we'll put it in there. For that only we have this query engine.update prompt function. Okay, so once these are done, which means you're ready to chat, so it will display a message known as ready to chat. Will also display the PDF. Okay, we are creating two columns, where in the first column we'll write it as okay, chat docs with using llama 3, and in the second column we are just creating a button for clear chat. Okay, because if the user thinks okay, I'm done chatting with this specific session, I'm going to a new session, we'll call the reset chat function. What it will do is, to keep track of the messages, we'll create a session state and we'll maintain a session state there, and we'll empty the session state. That is what will happen with reset chat function. Okay, so other than that, first we'll get the prompt. Okay, well, that's what is there in the chat input. We'll get the prompt, and based on the prompt we'll run the query engine, and it will give an output, right? So those will be finally created as a message, and those will be appended into the session state. Okay, so that is what happens in here. Again, there is comments for this. You can also go through this code. I'll show you how you can run this code right now. So for this, you need to use Streamlit. Okay, so we are going to use Streamlit to run this, and it is Streamlit. Let me take another environment. Where is it? Llama index env. Yes, and guys, I'll also provide a requirements.txt, so make sure that you create a new environment and run pip install -r requirements.txt. Okay, so let's run this now. Streamlit run app.py. Okay, so let's see if it is running. Okay, no module name, streamlit.cli. Let's see about this. Pip install streamlit. Streamlit process itself not installed actually. Nice. So guys, until this is going as a summary, right? We have seen how you can pre-train the model, how you can instruction tune the model, how you can preference align the model, and now we are seeing how we can make a real-time use case. So in just 40 minutes maximum, I have shown you how you can pre-train the model, how you can fine-tune the model, everything, right? So please hit the like button and share it with your friends, because these kind of videos doesn't exist on the platform, and I can assure you that this is the best content you will get related to this kind of video. Okay, I'm putting my best effort here, and your likes and comments and subscriptions will make me encouraged to push more for these kind of content. And with your likes only, YouTube also recommends my channel to lots of other people. So it's on your hands, guys. So with that being said, again, let me try to run this. Hopefully there is no error. Yeah, there is no error for this. Let's give allow. Okay, right now what is it doing? It's loading actually. Since this is done, let's cut this. Yeah, so here you can see there is clear button and there is text, right? So what we need to do is we need to browse files in here. Let's take something, see if there is something in here. Hopefully it is not an empty document. I'm going to show you all the document clearly in this. So now you can see here there is a resume. Okay, I don't think you will be able to read the content. It is not that big enough to read the content. This is a resume, fake resume created by myself for another video in my second channel. So guys, if you don't know about my second channel, I have a second channel where I'll create AI applications for real world solutions, which is AI DIY Factory. And I know this is a shameless plug, but I had to do it, right? So this is my second channel, and this is the first video in my second channel, which is Resume Analyzer. I'll build a real-time ATS builder for this resume analyzer. Okay, given resume, it will make a SWOT analysis. So for that only I created this resume. Okay, and I can ask any question from this resume now. What are the skills specify, and yeah, it has given actually these are the skills, and you can see it is running now. And if you want to use, you can also run it with the help of Olama. All right, that is also possible. And for that, what you need to do is, I'll also show that now. Okay, let's stop this application, cut this out. For this, first you need to make sure that you have Olama installed, and in Olama list you need to make sure that Olama Llama 3 is there. Okay, if you don't have, first do Olama pull Llama 3. Okay, so once that is done, you have your Llama 3 model ready in your system. After that, what you need to do is you need to edit only one line. Okay, I'm not gonna run that because my system is not in a situation for me to execute right now. That's why I showed this with the help of Grok. But I'll show you what is the line to be edited. What you need to do is search Grok. Okay, just comment this line, create LLM equal to Olama of Llama 3. Okay, and for this you also need to import this from llama index dot Olama. I don't think we have Olama here. It's directly here probably. Just give me a minute. And yeah, now you can see, right? There is Olama class here and it will work. Okay, you need not worry about this. If you just call this Olama, you will be good enough to run this. Hello everyone, welcome back to another video in the LLMs related playlist. In this video, I'm gonna take a crash course on how you can fine-tune any LLM of your choice, be it small or big, with the help of a two-stage approach. Without wasting time, let's jump into the video right now. So, before going into the coding part of this crash course, let me give you a theoretical insight of how this two-stage approach would be and should be. See, the thing is, once you get a base model, which is either instruction tuned or it is a pre-trained model, right? For your own custom use case, the first step would be for you to do instruction tuning on your own dataset. Okay? For example, let's say you are doing a question answering model. So what you need to do is take a model, let's say model A, and then you will fine tune it with some question answer pairs, just normal training. Okay, and that stage is known as supervised fine tuning or instruction tuning, because this step will help the model to adhere to your instruction. It will try to follow your instruction based on the dataset or data provided. Then the model is following your instruction, but the response is not that good. Okay, it is able to understand the question, it is able to understand the instruction, but the output is not of our desired format, like how a ChatGPT or Google Bard gives, or even Claude for that matter. So for that, what you need to do is you need to do another stage of tuning, which is known as preference alignment. So for preference alignment, there are a lot of techniques available in the market right now. There is RLHF, there is DPO, KTO pair, IPO, which is from Google. So yeah, there are a lot of methods like this, but the most common method is DPO and RLHF. RLHF is used in models like ChatGPT, Claude, and so on and so forth. But DPO is kind of a cost-efficient replacement for RLHF. Okay, it also does the same process of aligning your model's responses to your preference. And in this video, I'm gonna show you how you can do both of these steps for a given model for a custom use case. For example, here I'm considering a chatbot use case, and I'm gonna show you how to create a model to chat with you based on this two-stage approach. Okay, so now let's go on to the coding part. As you can see here, I'm just using Google Colab, which is free version. Okay, it is T4, which is a free version, which means you can also replicate whatever I have done in this video. All right, so I have also given the notebook link in the description. Please maybe have it on your side and try to execute it alongside with me in this video. So the first step for you would be to do installation of the dependencies. Okay, let's put it here, installing dependencies. Okay, so in that we would need transformers. Take this specific version 4.37.2 because in Google Colab they are using an old version, and for you to replace that you would need to specify the version. and then install TRL, which is Transformer Reinforcement Learning Library, in which you have your supervised fine-tuning trainer and trainer for DPO, or else the preference alignment. Okay, and PEFT for LoRA. I've covered LoRA in detail in our channel itself, so if you haven't seen about LoRA, please check it out. LoRA is a parameter efficient fine-tuning method. All right, and accelerate for efficient GPU computation, datasets for manipulating data so that it is following the Hugging Face Hub format, and it is also connecting to the Hugging Face Hub datasets. And then finally bits and bytes for quantizing the model and training it. All right, so that is about the dependencies, and you can install it by just running this. As you can see here, it has installed all of these, and then the next step for you would be to do notebook login. All right, so in that, if you run this, let me run it here. All right, yeah, as you can see here, now the dependencies are installed, and here if you see, there is an existing installation of 4.35.2, and that is replaced by 4.37.2, which we have installed right now. All right, so that's about installation. Now for you to know how to do notebook login, so for this you need to have a Hugging Face token. For that you need to create an account. All right, so here I have created n number of account. So for that, what you need to do is to create your own token. Click new token, rename it like some name, and then put it as role to be right, and then click generate token. Okay, and then you will have something like this. Click your token, desired token, and then put it in here. Okay, and then click login. All right, but nowadays it is also better for you to have it in your Google Colab secrets itself. Here you can see there is a secrets key, right? In that, if you click, it won't be here like this for you. Click add new secret, and then name it as HF underscore token, and put your value here like this, right? HF underscore token, and then the same value which you copied there, put it here, and then give access. Okay, for this to give access, you can give it like this. But here I have already configured the secrets, so I won't need that. All right. So now for the first step, which is to do instruction tuning, which is supervised fine tuning. All right. So for this, I'm having the following inputs. We need torch, load dataset function for us to load the dataset from Hugging Face Hub, and dataset class because we won't work with Hugging Face datasets for pre-processing. So we'll make it as a pandas data frame, and then again to convert it into Hugging Face dataset and all, we need dataset class. All right. And from PEFT, we'll be importing LoRa config, AutoPEF model for causal LLM, and get PEF model. In this, the most important inputs are LoRa config and get PEF model, because get PEF model will create your parameter efficient fine-tune model by attaching the LoRa adapters to your model, and the config for LoRa adapters are provided by LoRa config. All right, and then we have transformers import, in which we have auto model for causal LLM, auto tokenizer, training arguments, and then bits and bytes config if you want it. All right, next we have SFT trainer being imported from TRL. This is our trainer. All right, and then we have accelerator for, like I said, to efficiently use GPUs and all. And then we have OS. Okay, these are some imports which is required. All right, so let's see the config later. Once we go through the code simultaneously, we'll see the config. All right, so these are the imports which is required for instruction tuning. So here you can see I have created a class for fine tuning with SFT, and similarly I've created a class for DPO. All right, this class can be used for any model. All right, be it Tiny Llama or Llama 270 billion or Mixtral or any other model of your choice. The process and the code is going to be the same, which means this is kind of your template to fine tune any model. Obviously you need to edit the parameters, but even these default parameters will do good. All right, sorry, I have cold. So yeah, let's go into train SFT. You see, for any training of model, we'll need two things, right? we'll need the model, and then we'll need the data set. We are assuming in this trainer that we have created the data set, which we'll do later. All right, because this is, like I said, the template. In template, we can't say like data set will be like this, right? So we are creating data set separately. And here you can see I'm taking data and config as parameters, because here none of the parameters are set at runtime. Okay, all are set at the config itself, so that whenever we want we can edit the config, and then it will become like whatever we want it to become. So here if you see, in create trainer function, right, the first, this is the function which we'll use at the last. All right, which is train and save model. In this, the first step is to call the create trainer function. So let's go in there, and then in there I'm calling load model tokenizer. So let's go into load model tokenizer. All right, now we have the data and configuration. So what I'm saying is, let me call the model first. Okay, and for model checkpoint, where I need to go, yes, you got it right, we are going to go into the configuration. Okay, here for model checkpoint I have given tiny llama 1.1b chat hyphen v 1.0. all right, let's put it here, and as you can see here, here is a model. All right, and we are using this model, which is very less in size. Actually, it is just 2.2 gigs, and even if you want, you can try lesser size models, or you can try 5, because there are a lot of people who are asking me how to fine tune small models like tiny llama 5 2, and so on and so forth. And some people are asking like how to fine tune Mixtral, how to fine tune llama to 70 billion, and so on and so forth. For every model which people have asked me, guys, this is the code. All you need to do is change the model checkpoint, and for you to run it in Google Colab, obviously you need to edit some other parameters, but some models you can't even run it in Google Colab. For example, llama to 70 billion, llama to 34 billion, Mixtral, these are not possible, but for Mistral, yes, till that you can run this in Google Colab. All right, so here for model checkpoint, we are having tiny llama hyphen 1.1 billion chat v 1.0. All right, next in that we are needing a parameter known as load in 4-bit. Okay, we are doing something called LoRA training. Okay, where it means that you are quantizing your model and you are applying LoRA on top of it. So here for quantization, we are quantizing it in 4-bit. All right, it is in 4-bit. So what I'm saying is, okay, load in 4-bit, I'm giving it as true. All right, and then for device map, it means that the layers in the model, it should be assigned to which device. Okay, let's say you have multiple GPUs, because it's not always we'll use Google Colab, right? Some people might use their office servers, some people might use their local GPUs, and you might have more than one GPU in your hand, and you will try to use all those GPUs, right? It is hard to configure it by yourself, because let's say you have 32 layers in the model, and each layer has its own heads and all. So to configure it specifically for each device and doing it perfectly, it is hard, and that is where Accelerate comes into the picture. So whatever we need here, Accelerate has already done, and for that what we are doing is, any layer, Accelerate will provide a local process index. Okay, it will try to map the device by itself, you need not do anything, and that is why I said we need accelerator. All right, next for torch dtype. So what torch data type we are going to use is that we are going to use torch float 16. Okay, float 16 is a very good precision for us to work with. It is known as mixed precision training, and this precision is more than enough for most of the use cases. All right, then what we are doing is we are setting the use cache of the model's config to be false. Okay, so why is this needed is because we are setting the model to be trained in training mode. Usually it will be set as true, okay, which means it will use its cache for inference. Okay, we are not doing inference, right? So we'll set it as false, and then to replicate the training performance, like to not lose any training performance, we'll also set pre-training TP to be 1. And then we are preparing the model for k-bit training. Okay, like we are doing it in k bits, which is 4 bits here. And for that, we are having this function called prepare model for k-bit training, in which you need to pass your model. All right. So now we are again checking if we want to use LoRA, because like I said, people might not need LoRA because they might think, okay, we'll do full fine tuning, we'll fine tune all the parameters, we have the resources. So what you can do in that case is set this use LoRA parameter to false. Okay. But if you set use LoRA to be true, the LoRA adapters will be attached. All right. So here it is true, which means there is a function called self.prepare LoRA model, which will be called, and that is here. Okay. In this, I am creating a LoRA config, which will take the LoRA rank, which is set to be 16 here. LoRA alpha is 16, LoRA dropout is 0.05, bias is none, and task type is causal LLM. So here you can see that for R, I'm providing 16, LoRa alpha. From config, we are also providing 16 there. LoRa dropout is 0.05, bias is none, task type is causal LLM. And if you are going to fine tune models like probably Plantify or something like that, you need to replace auto model for causal LLM to auto model for seek to seek LLM, and then change this task type to causal from causal LLM to seek to seek LLM. The only difference here is target modules. All right. For target modules, what happens is you can't provide a constant target modules always. So for that, what you need to do is go to your model, which we have opened here already, see the configuration. Right? If you know the configuration already, which is let's say Llama for causal LLM. For Llama, we already have seen a lot of times that it is going to be Q projection, V projection, K projection, gate projection, up projection, down projection, and so on and so forth. All right. If you know it, then it's well and good. You can have your own target modules. But let's say you are using another model. Okay. Big code. Let me try that. For example, in the star coder, right, they would have used a different configuration. All right. So let me show about that also. Here it is GPT big code for causal LLM. Right. So here it won't follow the configuration which we have spoken about just now, like Q projection, V projection. That names for the layers wouldn't be used. So which means adapters won't be attached and you're not gonna train anything basically. All right. So what you can do in that case is go to your model and search for this specific file known as pytorch model.bin.index.json. Okay. If you can find it, it is very good. If not, first call your model into some Google Colab cell and then do print model. Okay. In that you will be able to find the names of the layers and then you can choose accordingly. Don't worry, I'll also show how you can do that. All right. But this is easier. So let me say about this first. So in this is weight maps. Okay. So here they are having an attention module in which they are having a layer called C attention, C projection, and they are having a linear layer LN1, LN2, and then they are having in a multi-layer perceptron class, they are having CFC and C projection. Okay, these are the layers present in star coder. All right, these are the layers present in star coder. So for you to understand this, what you need to do is see where there is written as bias, dot weight and all. Okay, and see the name previous to it. Like for example, here it is C attention, right? That will be the module name, which is your target module. All right. So now you're thinking, Vasanth, this is too hard for me. Give me some simple way. Okay. So let me create a dummy cell here from transformers import auto model for causal LLM. Model equal to auto model for causal LLM dot from underscore pretrain and the model name. All right, which is here as star coder. Let me see the model size. Okay, it is too huge. So let me take a similar model which is less in size. For example, here it is a 1 billion model Santa coder, which also follows the same architecture. Okay, so let me take that and we need to print the model. All right, so let's do a time lapse. So here you can see the model is now printed and these are your modules. Okay, in there it is given, right? Module list, attention. In attention you have C attention, C projection, attention dropout, residual dropout. Usually we won't consider dropouts, okay, but consider the other layers, all right, mainly your attention and your linear layers. So here you can see it is C attention and C projection and CFC and then C projection. These are the layers which you need to consider, all right, and this is how you get the name. So here if you do tiny llama, you will have Q projection, V projection, K projection, and so on and so forth, and I have chosen only Q projection and V projection. But this is how you will try to see the model name and the model's target models. Whatever model, it will be the same approach. All right, so now we have configured our LoRA adapters. So the next step would be to create the LoRA model by attaching these LoRA modules to the model, which you can do by calling this getPef model function, which will take two parameters, which is model and then its config. Okay, so here you can see I'm doing everything in self parameter itself, so that everything is updated by itself. Like we need not call it as a separate variable and then pass it again as a parameter. Okay, everything is done in self itself. Okay, self.model is equal to getPef model of self.model comma self.LoRa config, which will try to attach your LoRa adapters. Okay, now we have our model. So next step would be to create your tokenizer, because we need to tokenize the dataset. Okay, within SFT trainer, the good thing is you need not tokenize it prior to your training. Okay, it's not like previously you need to tokenize it and then you will train it. No, it will try to tokenize it at runtime, which is a time saving process, but for that you need your tokenizer, right? So for that we'll also take the model checkpoint name from the configuration and call auto tokenizer. But the thing here which is very important is setting the path token to be EOS token. Okay, please don't forget this step, so that it won't be padding up till the end and it will stop the generation. All right, next we have set training arguments, because we have our model. Okay, and here if you see in this create trainer, right, the first step is to load the model and the tokenizer, which is done already, and obviously we are checking if the LoRa adapters are attached. For that we are calling this function called model.print trainable parameters, which will print the trainable parameters, because in LoRa what it does is it will try to freeze all the parameters which is there in the base model, and it will enable only the LoRa adapters to be training, which will be just 1% or 2% of the whole model, right, which is very less, but it will give the same performance, almost close-ish. And here if you see we are passing the model, and for train dataset we are passing the data. If you have an eval dataset created, you can also pass that here by having it as eval underscore dataset data. All right, but I don't have it because my convention of training is usually when you do evaluation, right, it will take a long time for you to do evaluation because it doesn't CPU. So what you can do is save a checkpoint at some point of time and then try to do it offline or separate in a separate process. Okay, don't disturb your training. When you do long training, it will be very irritating actually, because let's say you do 1,000 steps of validation, right, it will take so much time. So yeah, I would prefer not to do evaluation at the training loop itself. But yeah, if you are interested, you can also do it as eval dataset and then provide your data. And then we are needed to provide the LoRa config also under the name PEF config, because in PEF itself there are other methods like prefix tuning, P-tuning, and then we have IA3, which is a very good method which has been stated till now. All right, but we are following LoRa, so we are providing the LoRa config. Next, the important thing for you to pass is the dataset's text field. Which is the dataset text field? Which is the data like I should consider the column name here. So for that we need to go to the config train column name, and where is it? Train CLN name. I'm able to find actually. Yeah, here it is. Train CLN name I have provided as text. Okay, always it is needed for you to have it as like a simple name. Okay, text is a common name, right? So keep it as text, but all your values should be under one column known as CLN, or like whatever name you have it, because causal LM is kind of a completion, and for completion you will have always only one column. All right, next we need to have set training arcs, which is a function here. Okay, So let's see the function, because this is the function we use to set our training arguments. Alright, here is our training arguments where we are for providing values for the following parameters. The first parameter we are providing is output directory in which you want to save, and then we have our train batch size. So for each step, how many datasets should be processed, that is your train batch size. And then we have our gradient accumulation steps, which means that so in how many steps do I want to do back propagation. Okay, so that is gradient accumulation steps. Let's say you have 10. Okay, so till 10 forward steps the gradient will be accumulated, and then it will do one step of back propagation. It is computationally it will like take a lot of space, but it will take lesser time. Okay, so that is the advantage of gradient accumulation steps. Then you have optimizer. Here we'll use a special type of optimizer which will obviously work well for quantized models, but generally an optimizer is one which will optimize your model's learning. Okay, it is the one which is making the back propagation and then like going towards the global minima. And then we have our learning rate, the rate at which it wants to learn, and then we have our learning scheduler type, learning rate scheduler type. Next we have the save strategy. So how you want to save, do you want to save in steps, do you want to save in epoch? I'm a fan of saving it in epochs, but when you do large training, like bigger training, you want to go for steps. Okay, and then there you would need another parameter known as save steps, where you can provide the number of steps at which you want to save. All right, next we have our logging steps. So in how many steps do I want to log? In logging steps, what it will do is it will try to compute the training loss at that time. Okay, let's say I have 100 steps, so at the 100th step it will try to log the training loss at that point of time. And then we have the max steps. When you're doing training, please do comment this. All right, I'll have it commented. So here this is provided because when you do very large scale training, okay, let's in millions, but you're not like having the, how can I say, like leisure, probably you are not having the leisure to do it for the millions. Okay, but you want to load the data, you don't want to sample it or something like that. Like you want to just provide it, but you want to stop it at some point of time. Okay, so at that point of time, what you can do is you can set the max steps to be some value. Okay, so here if it is 1000, it will stop in 1000 steps. Okay, 1000 steps. So if you have provided as batch size as probably 8, then it will have seen 8000 samples and then it would have stopped, be it millions or trillions, but the steps will be only 8. Like the samples it has seen would be just 8000. All right, so next we have FP16, which is set to true. Okay, don't worry, I'll say the values by showing the configuration, but right now I'm saying that like the FP16 value is true because we are training it in float 16, right? The training also should happen in mixed precision, so we are setting float precision to be 16, and then push to hub, which will provide a value of either true or false. If we provide the value to be true, then the model will be pushed to the Hugging Face hub. And if you are working for an organization and the model should be in private, right, then it should be in it would be in false. Okay. Now let's see the values. All right. Output directory, I have given it as SFT tiny chatbot because we are doing SFT stage, right? So for that I'm keeping it as SFT tiny chatbot, and batch size I'm keeping it to be 1, as simple as that, but it can be moved up a bit too. And then I have provided gradient accumulation steps to be 1 because it is collab, it doesn't have that good memory and all. So it is good to have it as 1 itself. Next we have optimizer, for which I have provided the value as paged AdamW 32-bit optimizer. Okay, so this optimizer is what will make your training like very good. Okay, normal AdamW is very suitable for normal model training, but paged Adam optimizers are usually very good for your quantized training. Okay, but there are some other optimizers as well, like 8-bit, 4-bit and all. Probably you can also experiment with that. All right, then the learning rate, a good starting point, like to set the max barrier, right, it would be 2e minus 4, And then we have like when you provide learning rate as 2e minus 4, what happens is like that is the maximum learning rate. It will try to go lesser, let's say 2e minus 5, 2e minus 6, and like it will be like the maximum thing, and then you can go any much lesser than that, which the model will decide while training. Okay, sorry, not the model, the optimizer. Here you can see the scheduler type, when we should change the learning rate. Okay, and we are following a cosine learning rate scheduler type. And like I said, we have provided the save strategy to be epoch, logging steps to be 100, training epochs. Like what you can do here is, I'll also add it here. I don't know the exact name actually. I don't think it is provided here. Train epochs SFT trainer. Let's see. I think it is in training arguments actually. Training arguments. Yeah, it is num train epochs. I just want to like keep a remembrance of the name. I'll put it that also. Oh yeah, I've kept it. I forgot. Sorry guys. It is num train epochs. I have provided as 1. Actually, by default it would be 3. I've kept it as 1. Okay, so num training epochs is 1, which I didn't say. Okay, but when you keep max steps, it will be overridden. Okay, it will be stopped at, for example, 250 steps here. Since I have kept batch size as 1, it will see only 250 samples. This is just like I said, a demo training, right? Like when you do some real training, it will be like, correct for you. And then we have FP16 to be true because I want to train in mixed precision. And then we have push to hub to be true because I want to push the model to the hub so that I don't need to save it in local. All right. So that is about the training arguments. You didn't like you can comment the max steps if you want. All right. Next, we need to go on to the continuation of SFT trainer. We have provided the model, dataset, the training column name, training arguments, tokenizer, and then we have something called packing. So what happens in packing is that, let's say you have a max length of 1024, but the dataset sizes are probably 768, 256, something like that. It will try to pack the sequences together with a separator token so that it will be always 1024. There will be no pad token and all. Okay, so at the cost of 1 step, you will see 2 samples, something like that. But I don't prefer using packing, so always I keep it as false. And then max sequence length, we have provided max sequence length to be 512. All right. Here you can also provide another value known as Neptune underscore noise underscore alpha. Okay. Self.config of Neptune underscore noise underscore alpha. All right. So what happens in Neptune is that while you are training, right, in embedding layer, some noise will be added. All right. And it is set to provide from 2 to 3% of accuracy to till 7% of accuracy improvement. All right. So that is stated in the paper known as Neptune. So if you are interested, you can also check it out. But like here, the noise alpha is set to be like the best value is set to be 5, and we are setting the same. Okay, it is 5 here. All right. Next, the trainer is done. So create trainer is done. Next, we need to call the train function. Okay. So if you call the train function, it's going to train, and then you will call the save model function to save the trained model, which will save only the adapters. And when you call it, like you can combine it. Okay. So here we have the output directory where you want to save, and the tokenizer, which is also saved in the output directory. Okay. So that is about SFT training. Probably, if you like feel like, okay, Vasanth, I'm not clear here, please let me know in the comment section. I'll be more than happy to help you out because you might face some errors, right? So whenever you face some errors, let me know. I'll help you out with that. And then we have the create data function because, like I said, we need model, training loop, and then data. Obviously, we have done our training loop, we have done our model, but there itself we needed a data, right? Because we are ready with the configuration, which is one parameter, but the data set is not ready. So we'll do that first. All right. So I'm using a data set known as alpaca, which is for data, like chat data. Okay. In that we are calling the training split alone. So here I'm just taking the 5,000 samples. Probably you can also keep it as 700, but still it wouldn't make any difference because we are going to run it only for 250 steps. All right. So here, like I said, the model expects, or the training loop expects to have it in the single column name, which we have provided in our case to be text, right? So here what I'm doing is there are three columns in the data actually: input, instruction, and output. Let me show you the data. Yeah, here it is. Okay, here you can see instruction, input, and output. Okay, probably they have also provided text, but I didn't when I wrote it. When I wrote this code, this text column was not there. So we have the instruction, input, and output, but it is also for good. Like you always might not have a single column. So what you can do is you need to find a balance. So here you can see you have give 3 tips for staying healthy, and you don't have any input, and then you have your output some values. Okay, where you want to find these balances, let's say here you can see evaluate the sentence for grammar, spelling, and mistakes. That is your instruction. He finished his meal and left the restaurant. Okay, this is your input and then your output. So it is going to be instruction and then input and then output, right? So instruction and input are provided by human and output is provided by the assistant, right? So here we are keeping it as human and then instruction and then the input, and then we are providing the output with the assistant tag before it. All right. So when you apply this, there will be a new column created as text, and then you'll create a data set from those pandas data frame by calling the dataset from pandas. Okay, and once you pass that as parameters to the train and save model, it will train it. Okay, so it will train well. You can train for longer time and it will work. Okay, for like I said, any model. All right, now like I said, you have done the SFT stage. Now it is following an instruction, but the output is not satisfactory. Like the format can be better, especially when it comes to chat. The dataset might have some harmful words, harmful content. To remove that and to make it like, okay, I'll speak only good things, I will not speak any bad things, something like that. In my case, probably in your case, if you are going to do some information extraction and you want to generate some JSON, the JSON structure might not be good. To force it to generate some JSON structure, you can follow this method known as preference alignment, wherein there are three popular methods, which is DPO, IPO, and KTO pair. And DPO was the predecessor, like it was the root method, and then IPO and KTO pair were some modern methods which came out of DPO. So if you're wondering how DPO works, again, I've made a detailed separate video of DPO. So if you haven't checked it out, please check it out. The links for LoRA, DPO, research papers and all are given in the description. So yeah, you can check it out. Here also the imports are going to be similar, okay, except this trainer, which is DPO trainer. Okay, and then we have our model checkpoint to be changed. Okay, here I would have it as Vasanth SFT Tiny Chatbot because we pushed it to the hub and the name was SFT Tiny Chatbot. And here you can see I've changed the LoRA rank and alpha to be 8 and 8 because I was unable to load in 16. All right. Then others gonna be same, but here there will be some difference. There we had it only till Neptune noise alpha, right? So after that there will be some changes here, which I'll say now. Right. So here you have your LoRA model being prepared, you have your load model tokenizer, but here we have model as well as model reference. Okay, see, the idea in preference alignment is that one model will train the other model to focus on the generation of output, okay, or the results. Here the model will be same. In RLHF what happens is usually you'll have a separate reward model to do this, but here in DPO and other preference alignment methods, your self model, like whatever model you are training, that model itself will force the other model to generate accordingly. So here you can see we have model and model ref, which will also have the same parameters. Okay, but we'll do this use cache and pre-training training performance and prepare model for KB training, everything only on model, because we are going to train the model which is self-taught model only. Okay, the model in model ref, it's just for the reference for it to provide some penalizing and train, okay, accordingly. So for that, we have model reference also, and then we have prepare LoRA model. We are calling the tokenizer, and the training arguments are going to be the same. Like it's not going to differ. All right. The thing which is going to differ here is the trainer. Okay, which is something very different from the last one. So here we are calling the DPO trainer, where you need to provide the model reference model, and then your training arguments, data, tokenizer, that is all there. And beta is the learnable scaling parameter, or like it is a parameter which will adapt the rate of learning. Okay, it is similar to learning rate. And for each method it is said to have a specific good value. For DPO, the ablation study states that it is 0.3 or 0.4, probably even 0.6 to some extent. For KTO pair it is 0.1, and IPO it is 0.01. Okay, so whenever you change the method, you can also change the beta value. Please don't forget that. Then we need to provide the most important parameter in DPO trainer, which is loss type. In loss type, there are different losses. So let me show you the source of DPO train. Okay, so here you can see I'm going into the trainer, and let's go into the DPO loss function, right? So here you can see there are different types of loss, and here you can see there is hinge loss, there is sigmoid loss, and there is that other things like here you can see, right? Sigmoid, hinge, IPO, KTO pair. Here it is KTO pair. Okay, the thing is each are from a different paper. Hinge is something I haven't explored yet, but IPO, KTO pair, and sigmoid is your DPO loss. Okay, so these three methods, for those what you need to do is, if you are going to use DPO, provide the value of loss type to be sigmoid, and if you are going to do IPO, provide it to be IPO, and for KTO pair you can provide it as KTO pair. All right, and this is the loss function, and yeah, you are providing that loss function here to your model. Okay, and then we are setting the max length, which is the total length. Okay, sorry, it is the total length, and here we are setting it to be 768. But the input length which I am providing here is 512, and the output length which I am expecting from the model to be maximum is 256. Okay, so it is total 768. Here it expects an auxiliary parameter because this trainer is common for both causal and sequence to sequence model. So to know if it has decoder or not, there is a parameter known as isEncoder decoder, and for isEncoder decoder we are setting it to be false. So here if you have Flantify XL or Flantify UL2, these are all pretty huge models. Okay, what you need to change is you need to change the model checkpoint, you need to change your target modules, and then change from auto model for causal LM to auto model for seek to seek LM. Others are going to remain same, and this encoder decoder to be true. But if you are going to change for some larger models, that is in causal LM itself, you need not even worry about anything. Change the checkpoint name, and then yeah, like adapt your training parameters alone, like the training arguments. But otherwise everything is going to be same. But here the thing is different. You need not provide something called dataset text field. That is not needed here. Okay, because it requires a specific format. There it was not required. Okay, if you give an output column or an input column, it will focus on that column. Okay, but here it won't be like that. It will have three columns which is required by itself, which is prompt, chosen, and rejected. Prompt will be your input to the model. Chosen will be the expected output from your model. Like let's say I'm asking, let's say tell me 10 bad words. Okay, it should not say the bad words, right? So if it says the bad words, it will be the rejected response, and if it is saying like I'm a bot, I can't say some harsh words or something like that, that will be the chosen response. So for this, there is a dataset known as HHRLHF, which is from Anthropic. Okay, I've taken this datasets, and here you can see there is only two columns, chosen and rejected, where there's no prompt. And here you can see there is assistant here, right? There is human, and then there is assistant here. So what I'm doing is I'll split the assistant from the human. Okay, so I'm providing, see here, in chosen I'm applying something called split. So it will try to split the sentence from assistant and the zero of that, like before assistant everything will go to prompt. Okay, After assistant, everything will go to chosen, where we'll also add the prefix assistant, because once you split it, the name assistant will be gone. All right. So in rejected column, I'm applying the same so that it will have the rejected values, and I'm sampling only 1,000 samples so that we can, obviously we are going to run only for 250 steps, right? And then if you call the train DPO function, it will train. All right. So again, you will push it to the hub. So that is how your 2 steps will be completed. Now you can think, Vasanth, yeah, you have done the training, but if it is not good for any inference, what I'm going to do about it? So for that, what you're going to do is you're going to call a function called, or the class name called AutoPef model for causal LM, which has your model name from the hub. It will try to attach the model LoRA parameters together, and then it will provide the input to you. So here what we are going to do is we are going to take that model and we are going to give it to transformers pipeline. All right. So we are following some kind of input format here, like provided from them itself. Even you can provide it as human and assistant also. Okay. I'm just following what is given in Hugging Face. And here if you see, I have asked how many helicopters can a human eat in one sitting. A human can eat about 4 to 6 servings of helicopter food, typically made of meat, cheese, vegetables, so on and so forth. Okay, these are some helicopter food, it seems. So yeah, guys, and that is how you do a custom model for your own use case. And if you have any doubts, let me know in the comment section. I will help you out. Or if you have big doubts, like to be a separate video, that also let me know in the comments. I'll make a separate video. So in this video, I have shown you the 2-stage approach in which you need to follow to create your own model. So there are some other parameters you can play with. For example, in training arguments, you can set a value to report to be tensor board, so that you can save the losses to the tensor board. Because when you do a long training, you can monitor the tensor board logs. All right. So yeah, guys, that's it for this video. I hope you all like this video. If you all think that I've got something useful in this video, please hit the like button, share it with your friends, and provide some comments, and that will help me to reach more people like you all. I'll see you all in the next video, guys. Until then, cheers. We will be seeing about LoRA, okay, which is low rank adaptation. At the end of the video, I'll show you the implementation, which we have seen already so many times, and also I'll show you the research paper as well. Okay, so now let's start with the video. Okay, so what are all the sections we'll be covering from the research paper? So we'll be seeing about abstract, introduction, problem statement, and what are the existing solution right now. I mean, right then when the research paper was written, and what were the problems then? Okay, and then the LoRA method, which is the crux of the paper, obviously. And then finally, we'll be seeing an important section about understanding the low rank updates. Okay, so this is basically what we'll be seeing in this video. Okay, so next, coming to abstract. In abstract, they have said that with the increased larger pre-training of models, like we have GPT-3, where the model is around 175 billion parameters. Okay, that is so huge. So these kind of large pre-training results in a bottleneck while fine-tuning. Okay, so fine-tuning is becoming very less feasible, because if you have 175 billion parameter model for pre-training, you should also again fine-tune all the 175 billion parameters while fine-tuning. So that is an important problem which was been trying to solve in this paper. Okay, so what does this LoRA technique propose is that in LoRA technique, they have proposed that we can freeze the pre-trained weight, and we'll be injecting something called trainable rank decomposition matrix. Okay, so you need not worry about the word rank decomposition matrix. We'll be seeing that in some subsequent sections. Okay, so for what we'll be injecting trainable rank decomposition matrix is that, so that we can reduce the params for fine tuning for downstream task. Okay, so that's why we'll inject this matrices called decomposition matrices. Okay, next, there are some features which have been highlighted for LoRA in this paper, and they've said that there is no additional inference latency. Why this is called as feature is that LoRA is a form of adapter. Okay, so in previous adapter, what happened was whatever they tried to do, they weren't able to solve the one problem, which was having an additional inference latency. Okay, so that is not there here. uh, Other than that, we have higher training throughput, and the performance of this LoRa was on par, either on par or else better than a fully fine-tuned model. Okay, these were some of the features of LoRa. Okay, so now coming to the introduction section. Okay, so in introduction section, they have discussed about a lot of things, and we'll be seeing it kind of subtitle wise. First, first they started with the challenges existing, and this was also hinted in abstract, where we need to fine tune all the parameters of the pre-trained model, and this is making it inconvenient to pre-train that kind of large models. Okay, because if you can pre-train a large model and if you are not able to fine tune it for some downstream task, that doesn't make any sense for you to create such models. Okay, so it became inconvenient. That was the main challenge. So what was the solution then was a concept called adapters. Okay, so in adapters, what they basically done was, let's say if you have a model, maybe GPT-3 itself. Okay, what they will do is they will add some additional dense layers or linear layers by freezing the whole parameters at top. They'll be adding some adapters at the bottom. Okay, but what happened here was, the idea is that you need only few parameters for new task. Okay, that was the idea for adapters. Okay, in adapters you can just have some few parameters and you can just store, update, load it for any task specific parameters. Okay, so this is in addition with the pre-trained model that is also there. Okay, you can't just use the adapters. You need the pre-trained model. Along with that, we'll be having some task specific adapters. The problem in adapters was that, obviously, like I said, uh, in previous slide we talked about it, right? There was an additional inference latency, and the main issue was that it wasn't able to match the performance of the fully fine-tuned model. Okay, so what is meant by fully fine-tuned model? Well, I will just give a explanation about that, even if you might know, because fully fine-tuned model, we'll be talking about this in a lot of slides later. Okay, fully fine-tuned model is nothing but you are fine-tuning and updating all the weights of all the parameters in the model. Let's say if it is 175 billion, you will be updating all the 175 billion parameters, which is your trainable parameters. Okay, so I hope you got an idea of what are the problems and what is the solution. Okay, so now let's talk about the key inspiration these guys have taken from. Okay, so they have cited two papers. Okay, which was, one was from Lee et al., which is 2000, from a 2018 paper, and another one is Agan Jayan. Okay, that is in another paper. Sorry if I misspelled it, but you can see it in the paper itself. Okay, so from there, they took a key inspiration. Okay, so what was that? I'm just quoting it like it's here. Okay, over parameterized model in fact reside in a low intrinsic dimension. Okay, this was the key inspiration. So what it means is that if you have very large models, over parameterized is meaning that you have a large model, because with increase in params your model size also increases, right? So in such kind of models, the models can learn for some downstream task in some low dimensional inputs itself. Okay, let's say if you are having 175 billion parameters model, like you can just learn it with some smaller dimension model, smaller dimension itself, smaller dimensional inputs. Okay, so that was the key inspiration, but it was not directly applied. They made a hypothesis out of it. So what was the hypothesis is that the weights get updated, right, during fine tuning. That they have stated that the changes in weight during model adaptation also has a low intrinsic rank. Keyword is rank, okay, because this intrinsic rank is the core of LoRA. Okay, what is intrinsic rank is that what here they mean is that the model weight can be updated with some very less dimensional or else less independent, linearly independent vectors. Okay, so dimension, it states that we have all the rows. Okay, which say like we have 1,000 dimension embedding. Okay, it will be saying 1,000 rows or else 1,000 dimension. But rank is the rank can be very small, like 5, 10, 8. It can be of anything. The paper states that with that 5 or 8 linearly independent rows, we can express almost the similar performance which is given by the thousand dimensions. Okay, so that's what is an example also which I have provided here. 1,000 dimension can be expressed in terms of 10 linearly independent rows. Okay, so that is the key hypothesis, key inspiration and hypothesis which has been taken in this paper. So basically LoRA, what does LoRA do? Okay, LoRA, what it allows is that it will train some dense layers. Okay, but it will be in an indirect way where it will be optimizing the rank decomposition matrices of that dense layer. Okay, so that's what LoRA does. We'll be injecting some rank decomposition matrix and we'll be optimizing those, by which indirectly the dense layers also will be automatically trained. Okay, that's what is being stated there. Now, coming to the advantages of the LoRA technique. Okay, so the first one was efficiently train multiple tasks by switching decomposition matrices. So what it states is that, let's say if you have, again, we are seeing GPT-3, right? We'll consider GPT-3 itself as our example. So if we have GPT-3, and we need to fine tune it for, let's say, summarization, translation, and etc tasks. Okay, so if I want to fine tune it for every different task, I need to again update different models, right? Like we'll see v1 for summarization, v1 for translation. We'll be having separate GPT-3 models for all of the tasks, right? But here what you can do is you can just have some LoRA modules being inserted, okay, which is your weight decomposition matrices, and you can just train those modules alone for each task. So how is it? Let's say you have GPT-3, right? Your GPT-3 is the center base model, and followed by that you'll be having a module for LoRA, a LoRA module for translation, summarization, and let's say another task is code generation. Okay, so you will have separate 3 modules. Whenever you have a specific task, you can just attach it. Sounds cool, right? Like you can just switch your modules. Let's say if you are having translation, you can just remove this summarization module, and then you can just add your translation module with the same GPT-3 model, which means you need not have large number of GPT-3 models. And these modules, guys, we'll be seeing it in a section, like the size reduction. It will just be amazing. Okay, the size reduction. So the switching between modules is very easy. So you can just have a common base model, and then you can just have some modules specific for each task. So that is what is advantage number 1. And advantage number 2 is that the paper claims that the hardware barrier is lowered by 3 times. Okay, and why is it? Is that usually we calculate gradients, right? Like while back propagation we'll calculate gradients. So since it is frozen here, the pre-trained model is frozen, right? We'll be calculating the gradients only for the injected matrices, and that is very less in number, so it reduces the hardware barrier. Okay. And the number three advantage is that they have provided a simple linear design. Okay. This is allowing them to merge the trainable matrices with the frozen weights. Okay. By this, what happens is that there is no additional inference latency like we have seen before. Okay. So the fourth advantage is that LoRA, which is an adapter method, can also be combined with some previous adapter methods like prefix tuning. Okay, that is and another method. Okay, previous method. So these are some advantages of LoRA. Now coming to the problem statement which is being addressed. Okay, we have seen the problem statement obviously, but we'll see this in a detailed manner now. So let's say we are given a pre-trained model called P5 of y conditional y by x. Okay, which is parameterized by phi. Okay, while fine tuning, what will happen is that for different tasks, we'll be having context pairs, right? Like xi, yi, which is stated that, like, let's say you'll have x as input and y as output, right? It will be multiple, so 1 to n. So here xi and yi is your sequence of tokens. So this is how your statement frames up. So you are having a model, pre-trained language model called P5 with a conditional ones by y by x. Okay, and it is parameterized by phi. Okay, during full fine tuning, what it happens is that the pre-trained weights will be updated as follow. So like phi 0 by plus sorry phi 0 plus del phi. Okay, so this is how it will be updated. Phi 0 is your pre-trained force and weights, and del phi is your weight updation. Okay, so we can also see it as phi t. Okay, the timestamp t is equal to phi 0 plus phi del phi. Okay, so the main drawback here is that the dimension of the fine tuning is same as pre-trained. Okay, so here the modulus indicates about dimension. So the modulus of del phi is equal to modulus of phi 0. Okay, or else phi naught. We can also say as phi naught. Okay, here for this problem statement, they considered a solution. Okay, with a parameter efficient approach in consideration, they rephrased the equation as del phi is equal to del phi of theta. Okay, so here the theta in this equation is representing a smaller set of parameters. Okay, and if you see, the dimension of this theta is very less than del phi, which can be almost as small as 0.01%. Okay, let's say if you have 10,000 and 10% will be 1000, 1% will be 100, which means 0.0% can be 10. Okay, with 10 params you can just have the similar performance of 10,000. That's what they're doing here. I hope my calculation is right. Okay, so that is what been stated here. Okay, so with a smaller set of params, you can just optimize the trainable params now, which is your theta. It is not phi now. Okay, del phi, phi naught. Okay, it's not phi naught here. Now it is theta, and this theta, like I said, will be as small as 0.01%. So coming to the problems which are there in the solution, which is being addressed. Okay, first, like I said, adapter layers, inference latency. Okay, so I will just give a detailed explanation of why this latency was there. So there were different types of adapters. Okay, they were having two adapters per block and one adapter per block. They experimented different ways. Okay, but this extra computation was an issue. They weren't able to bypass it then. Okay, so usually what happens is that large neural networks expects parallelism, model parallelism, right? So that's why we get the computation slightly faster. But usually adapters were expecting it to be processed sequential. So in a sequential computing scenario, okay, where we won't have any parallelism, in GPT, they were able to notice quite a bit latency. Okay, significant latency was there. So that was problem number one. The second problem is to directly optimizing the prompt is hard. What this section says that is some of the previous adapter techniques were just focusing directly on computation aspects. Okay, let's say fine tuning is one of those methods where what they do is a part of the sequence length alone will be reserved for adaptation. Let's say you have 256 and they will be just reserving some 200. Okay, by this you are reducing the sequence length. But as weird as it sounds, like, uh, here the performance uh, isn't as expected. Okay, that's true. If you reduce the sequence length by reserving it, obviously the performance is going to degrade, right? So that is so obvious. So these were some key problems which were there in that existing solution of adapters. So now LoRA method came into the picture at that time. Okay, so this is a clear diagram of LoRA architecture. So first on left we have the full fine tuning approach, where let's say you have X as input, right? So it is of dimension D by K. Sorry, I didn't specify K. It is D by K, right? K will be your columns, rows. Yes. Okay. So it will be D by K. Okay. So this D by K input X is being provided to the pre-trained weights. Okay. As well as during weight updation. So you can say it updates directly, right? The weights are getting updated. But if you see the weight updation formula, it will be weight new is equal to weight old plus del W. Weight old is nothing but your pre-trained weights, and del W is your weight updation. Right? So we are just having it as separate components here. So here you will get the weight old from your pre-trained weights and del W from your weight update. But the dimension of the weight update will be same as pre-trained weights. So let's say you are having D by K as dimension as 100 by 500. Okay, so your total params will be 100 cross 500, which is equal to 50,000. Okay, so but while in case of LoRA fine tuning, again you will be having the same input, but here you can see, right, there is A and B. Those are your rank decomposition matrices. Weight rank decomposition matrices. Okay, so uh, just leave the conventions which is inside that trapezium structure, right, which is your matrices. Just leave that for now. I'll be explaining that in some next slides. But what happens is that you are seeing an R, right? That is your rank. Okay, let's say your rank is 4. Okay, so the dimension will of A matrices will be, A matrix will be D is 100, right? So 100 cross 4, and B matrix will be R star K, R X K, which is 4 cross 500. So what the total params will be is that, just a minute, I'll just hide my video. So it will be 100 cross 4 plus 4 cross 500, which will be around 2400. Not even it's so less, right? Not even 10%. Okay, that's how good is LoRA. Okay, so that is LoRa architecture. You will be passing through those rank decomposition matrices, and it will update the weights. So here del W will become as WA dot WB dot product. Okay, so that's how the weight will be updated while in case of LoRa. Okay, so now just giving a detailed explanation again about weight decomposition matrices. Let's say you have a dimension of 1000, you can just express that in 10 linearly independent row combined as a matrix. That is your rank matrix. Okay, so rank uh, right, like we have seen in our higher studies, rank just means that linearly independent. Okay, so in LoRA method itself, they have covered two subsections, and we'll go in the same way. So the first section was about metrics updation. Okay, so from the hypothesis, we can represent the weight matrix as W naught is equal to, W naught belongs to real numbers of dimension D cross K. Okay, so the weight updation can be done in the way we have said previously, right? W new is equal to W old plus del W. This is how it has been happened. Okay, but from the architecture, we have seen that we can update del W by WA dot WB. Okay, so here A belongs to again a real number set which is of dimension D cross R, and B R cross K. Okay, and here R is your intrinsic rank, or else we can also say it as LoRa rank. Okay, so this is how the uh, formula shapes up. Like you can just say it as W new is equal to W old plus WA dot WB. Okay, so by this, during fine tuning, in this architecture, what will happen is W naught is frozen, so there is no gradient updation for those params in the pre-trained model. Okay, only those decomposition matrices which we injected, right, like A and B, that alone has the trainable parameters which will update during the fine tuning methods. Okay, I hope this makes sense. uh, Considering just a normal forward pass with input as h is equal to w naught x. Okay, so it will be written as like h naught is equal to w naught x plus bax. Since your weight updation del wx is now represented as bax. Okay, now so usually we'll have some pre-trained weights and we'll be updating it, right? But here we are just injecting some matrices. We need to initialize the weights, right? So initially they considered that del W will be equal to 0. Okay, and how it happened was, for A they did a Gaussian initialization, okay, which is of normalized range 0 comma sigma square, and B will be a 0 initialization. Okay, so this is how they initialize the matrices. So that's why I said just leave this conventions inside the trapezium, which is your rank decomposition matrix, right? It is written there also. A is equal to n of 0 comma sigma square, and B is equal to 0. That is just to say how is your matrices initialized. Okay, so this is how they initialize these weight matrices. Okay, uh, initialize the weight for these matrices. Sorry, my bad. So now we need to scale these weight updation. Okay, so they found a way to scale this weight updation, which is del wx is equal to bax. Okay, so how they updated the weight was by using the following component, which is alpha by r. Okay, so alpha here is called LoRa alpha, and that is a constant in R. If you have seen our previous video like chatbot and all, I've shown you, right, like about alpha, how it impacts. It will be generally like, if you write it in a convention, it will be x at, because your matrix transfer matrix multiplication can be done with at in PyTorch, at WA at WB star alpha. So this is how your updation is scaled. Yeah, updation is scaled. So when you're optimizing it with Adam, right, like when you're performing this fine tuning with Adam, this LoRa alpha will be almost similar to learning rate. Okay, so that is being stated in the paper. So another thing which they have claimed is that unlike the previous adapter model, okay, where it converges to a MLP. Why? So like I said, right, like you'll have a pre-trained weight, and followed by that you'll insert some layers, and you'll be converging those layers along. So the convergence happens only for that MLP. But here they say that LoRa converges to the original training model. Okay, so let's say you have GPT-3, right? It will be converging to those params of not params, to that GPT-3 pre-trained model. Okay, So that is what is being stated in this section. Okay, so now they have also told about how to implement this LoRa method on transformer, or how they implement it. So in their study, it was they just limited to the adaptation only on attention weights, because attention is the core of your transformer, right? So they limited their LoRa implementation only to those attention weights. But recently, I've seen somewhere that we can also do this LoRa adaptation on linear layers, which is your dense layers. Okay, so let me see, and I'll let you know in maybe in some later videos. Okay, so they limited the study only to the attention weights, okay, for these downstream tasks, where they froze all the MLP modules, which is your linear layers or dense layers, for the sole reason of parameter efficiency and simplicity, to have some efficiency in parameter and to make it very simple architecturally. They limited only to attention weights. So attention weights will be WQ, WK, WV, and even WO. Okay, so WQ and tuple of WK, WV all were considered as a single matrix. That's how they considered it. And usually, if you see, when we are adapting it, right, when we are fine tuning it, we'll be considering only WQ and W, which is query and value for our adaptation. Okay, we'll be considering only those uh, matrices for our attention weights, rather. Yes, those weights alone for our fine tuning. Okay. So, what are the practical benefits of LoRa? Like I said, I told you, right? We'll be seeing about the size reduction. So, the size reduction, which is your memory reduction, is one of the most significant usage of LoRa. Okay, like that is the most significant advantage, because it reduces the computation and memory storage drastically. Okay, so let's say you have hyperparameters like this. Okay, R is equal to 4, which is your LoRa rank is equal to 4, and target module is query and value. Okay, so the original GPT-3 was around 1.2 TB, and this LoRa module, which obviously gave on par performance with the pre-trained model, sorry, the fully fine-tuned model, was only 35 MB. Okay, so uh, that is so good, right? Like you can just have your pre-trained model and just have some models of 35 MB and just switch it. That will be your second advantage. So how this happened, from 1.2 TB to 35 MB? Okay, so what happened was we froze the parameters, right? So with frozen parameters, the optimized state won't be stored. Okay, so usually optimized state stores only for the trainable parameters, and for frozen parameters, excluding that, now the size became 350 GB. Okay, while implementing LoRa method with those parameters we specified, where R is equal to 4 and target modules is query and value, the size reduced from 350 GB to 35 MB, which was 10,000x lesser. Okay, that is so huge, right? That's what I said. Like it will be very amazing when we use LoRa. That's how we have done all our projects, right? We have used some big models like you might see like Flantify Large is not a very big LLM which we used in our chatbot, but you see, like it has also given some great performances, and it is of size 3 GB. It's not so less, but we have loaded it and fine-tuned it with around batch size 12 in Google Colab itself, which is having just 15 gigs of RAM if I'm not wrong, 15 gigs of GPU VRAM. Okay, that's quite good. Okay, so we were able to achieve that because of LoRa. Okay, because it reduced the params again. So while we are doing task switching, and for saying that, that adapter module, if I'm not wrong, was around 9 MB. Okay, we fine tuned it for chatbot, right? Like if you see in the repo you saved, you can see like it will be around 9 or 10 MB, if I'm not wrong. Okay, so another key benefit is task switching. Like I said, you can just swap it when you're having different tasks. Okay, now we are having another key section called understanding the low rank updates. Okay, so you need to have uh, a clear idea, right? Like what is the lower matrix we need to use, like, for which weights, which is basically your linear layers, you have attention weights, right? For which weight matrices and all, you need to do this LoRA, right? So from the table which is there, okay, I've taken obviously this from the research paper. Okay, so here you can see that the weight type is your weight matrices. They have taken WQ, WK, WV, WO. WO is linear layers. Okay, and QKV is for query key value respectively. And combining query and key, query and value, and followed by that they combined all the weights. Okay, so this is how they considered it. And as far as rank is concerned, for a single matrix, they took 8, and for combination of 2, they took 4, and a combination of 4, they took 2. Okay, so this is how they uh, set it up, like the experiments were set up. Okay, so you can see, right, like the performance when you're having just ignore all the 4, like you didn't get as great performance as WQ and WV. So, but you can also see you have WO, which is a linear layer, which is almost as similar as WQ, WV, but it is very heavy. Okay, so the computation is very heavy. That's why they didn't consider that. So, see here with WQ and WV, you are getting 73.7 as your metric, and combining all the 4 also, you got the same. And this is on WikiSQL data, and with multi-NLI data, it was not that different. Okay, you had 91.3 with query and value, and 91.7 with all those combined. 0.4, that is not so big, right? So what the table says that we can just achieve competitive performance just focusing on WQ and WV, which answers the question that the matrices to be applied are WQ and WV. Okay, I hope this makes sense. And guys, if you have any doubts in this paper, in my explanation of this paper, or else any general doubt also, you can just come and ask in the Telegram group. Okay, I'll give that in the description. Okay, so you can join the group, and you can also find my profile there, and you can also personally ping me if you have any queries you want to ask personally. Okay, so now coming on to the optimal rank for LoRA. Okay, so again they made a different experimentation now. Like you can see the table is almost similar. While the performance case, the metrics which you see, it is almost similar to the previous one. But what they done was they now had the weight types as WQ, WQV, and all those combined for both the dataset, and they had different ranks. Okay, R is equal to 1, 2, 4, and 8. We are now focusing on WQ and WV alone because we have seen previously, right? We need to apply only for WQ and WV, so let's ignore all those. For rank is equal to 1 in WikiSQL dataset, we have 73.4, and 2 we have 73.3, and for 4 we have a significant improvement to 73.7, and to 8 we have 73.8. But when you go for a large rank like such as 64, the performance got degraded. Like you got 73.5, which means you should not have large ranks. That is an important point to note. And while in case of multi-NLI, we can see a similar pattern, right? Like, we are having 91.3, 91.4, and for 4, again, it got slightly decreased here, 91.3, but again, for R is equal to 8, it got increased, the highest one, which is 91.6. And for rank is equal to 64, what they achieved was 91.4, which again decreased. So from this, one is very clear, like, you can have rank 4 or 8. That is the one which is giving good results. And usually if you see, we'll be giving 8 or 16. and hereafter we might use 4 or 8 from this research paper. We know that, right? So now, what shall we use? 4 or 8? That is another question. It is based on your parameters budget, because the rank is the one which is going to determine, right? Like, say you have the previous example. Okay, we'll calculate that for both 4 and 8. So for 4, we had 2400. Let's say if you have 8, which is 800 plus 4000, which is 4800. I mean, yeah, it's double, right? So still it is just 10% of the previous one. Okay, and this is now 5%, right, with rank is equal to 4. And if you want to have a slight nudge, you can try 8. But if you are saying I don't have the params, just you can give rank is equal to 4, and still you should get some good performance. That is point number 2, which is being given here. So the optimal rank for LoRA, it is based on your budget, where you can use R is equal to 4 or 8. The trade-off is in our budget. Okay, so that is the second one. Now for the third one, where they try to understand how much this pre-train weights and the updation weights correlated. For this, they took the query weights alone. Okay, so what happened was, if you see, they had some random weights as well. Okay, and they had LWQ, and similarly, it was happening in rank is equal to 64. Okay, why rank is equal to 64? This actually is the point which shows that you should not use large ranks. Okay, that we'll be seeing in some points mentioned there. Okay, so with rank is equal to 4, you can see the random initialized metrics were having 0.02, and the original metrics were around 21.67. Del WQ was 0.32 by default. Okay, so which this shows that, like, it amplifies some features which is there in the model, pre-trained model, right? Because when you're having something random and you're initializing something, and if it is correlating better with the original weights, then you're doing something correct. So that's what they inferred from that test. The second test was how much the amplification, the importance of the features, how much it was amplified. While in case of rank is equal to 4, by dividing 6.91 by 0.32, which is the metric which we obtained previously, we got an amplification factor of 21.5. But with 64, it was way small. Okay, you can just make a calculation. 3.57 by 1.90, which will be not even 3 or 2 approximately, right? So that is so less. So with rank is with smaller matrices, the amplification with lesser the rank, the amplification was larger. So they concluded by this that W and del W correlates very well, and also amplifies the important features for the downstream tasks. Okay, so that is what is all about in this understanding of low rank updates, where first we saw that we need to apply only for WQ and WV. Okay, next we saw that LoRA rank can be 4 or 8 based on our budget, and next we saw that with smaller rank we have the importance amplification factor higher than larger ranks. Okay, so now coming to the conclusions of the paper. So LoRA is a proven method now, which is a memory efficient strategy which also achieves comparable or better performance than a fully fine-tuned model. That is an important point first. Okay, and then the second one are some of the features which we specified previously. No additional inference latency, swappable modules. Okay, so these were some other features of LoRA. Okay, so and unlike previous adaptive methods, it did converge very well, right? So by this we can say that LoRA is a very good technique for you to efficiently use your memory and fine tune your model. Okay, so that is the paper. Okay, now I'll show you. We have discussed in slide, right? Like now I'll show you the paper as well, and I'll provide you the link. Provide you the link in description. You can also check it out. Once you watch the video, you'll have a good hang of what is there in the paper, and once you again skim through the paper, you'll get a clear understanding. Okay, now I'll show you the paper, and then after that I'll show you the implementation as well. So yeah, guys, this is the paper. Like you see, it was slightly an older paper. Okay, this was from Microsoft. Okay, and kudos to them for creating such an amazing paper. And here you can see we have our introduction section, problem statement section, existing solutions problem. Okay, and LoRa method. We have covered everything, but we didn't see about empirical experiments. Okay, where they tried to see, like, how LoRa was performing with different models like Robota, Dibata, and Robota, Dibata. Then we had GPT-2, which is medium and large version. They found it, and finally they also scaled up this LoRa method for GPT-3 also. Okay, and then they have some related work section and understanding the low rank update section, which we saw. Okay, and finally we have the conclusion. Okay, so this is LoRa research paper for you guys, and if you find time, you can just go through this research paper. Okay, I'll, like I said, give you the link in the description. You can just check it out. Okay, now I'll show you how to implement it. If you haven't seen the detailed implementation of LoRa, you can just watch some of the videos. Like, I've shown you how to create a chatbot with Flantify. That was based on LoRa. Okay, we fine-tuned Llama 2. That was also based on LoRa, right? QLoRa. And QLoRa is based off LoRa. Okay, LoRa on quantized weights. So I'll also cover that research paper and some time. Okay, because a model called Guanaco of 33 billion variant had an amazing performance, which was quantized actually. Though it was quantized, it achieved almost uh, top 5, top 6 LLM performance. Okay, so we'll be seeing about QLoRa, and I've also have some other research papers in pipeline which has very good potential or else had a very good impact by now. Okay, we'll see a lot of research papers. Now we come in to the implementation. Okay, so I'm not gonna cover the whole implementation. I'm just gonna say how to convert your normal model into LoRa model. Okay, so this is the main part where we convert the model into LoRa model, right? We were using PEF library, parameter efficient fine tuning. Okay, so in this we had the LoRa config, right? Here we had R is equal to 16. So guys, I'd like to tell you that maybe you can just experiment this with rank is equal to 4 and see how much the performance varies. Okay, so that is one thing you can try today. Okay, or else whenever you watch the video. So LoRa alpha is equal to 32. That is also some standard ones, but we can also go as low as 16. Okay. So other than this, we have target modules like we see, right? Query and value. That's what we discussed now. That we done correct. And we are doing a sequence to sequence language modeling since we use Flantify as our model. If we had models like GPT-3 or Llama 2, and if you're wondering Llama 2 how to fine tune it, I have also made a video on that. Please check it out. And for that we will be using cos LLM. Okay, but here we are having sequence to sequence LM, and we are having LoRa dropout is equal to 0.1. And like you see here, the trainable params is let us make a calculation, guys. 7, 8, 7, 8 something. Just a minute. Okay, so the trainable parameters is 0.59%, it seems. That is so low, right? We are having 0.59% of parameters, not even not even 1%, sorry. See, 166 times, not even 1%. Okay, so that is LoRA for you guys. Okay, so with lesser than 1% of uh, parameters in the model, we were able to get good results. Like, we saw the chatbot, right? We had some great results in the chatbot. So, yep, that is the implementation of LoRA. Okay, so this is how you can implement. We are going to see in detail about DPO, which is Direct Preference Optimization. The paper is titled as Direct Preference Optimization. Your language model is a secretly rewarded model. Okay, so it is one of the great papers which have been released recently. Okay, so the main advantage is that we'll be seeing if it can serve as an alternative for RLHF. Okay, RLHF, if you are wondering, is something which has been used in ChatGPT. Okay, so let's start with what are the sections we'll be seeing in this video. So in this video, we'll be seeing about the abstract, introduction, preliminaries, DPO method, experiments, and conclusion. Okay, and for implementation, we'll be making a separate video because the implementation is kind of longer. Okay, so in previous video of explanation of LoRA, the implementation was done prior, as well as the explanation wasn't too long, so we combined both into a single video. But in this, since DPO itself has a lot of contents to discuss about in the research paper, so we'll be seeing the implementation in the next video. Okay, before moving into the abstract, let me say what is the essence of this paper. Okay, so DPO, which has been proposed in this paper, this method is a computationally efficient method which calculates the log probabilities of preferred and dispreferred completions. Okay, so you need not worry about what this essence says. While we complete this video, you'll be understanding, okay, this is what the essence of the paper is, and okay, that line makes sense for me. Okay, so that's how you'll feel once you come to the end of this video. We'll be like, this method will calculate the log probabilities of preferred and dispreferred completions under a model. Okay, so with a model, like, it will calculate this log probabilities, and it will optimize its parameters in such a way that it will increase the likelihood of preferred responses and decrease those of dispreferred. Okay, so we need preferred responses, not dispreferred, so that we can align the model with human preferences. What does this mean? I'm just gonna explain in a minute. Where here usually we have LLMs. At sometimes what happens is it won't respond in a way we want. Okay, so to make it respond in a way we want, there are some methods, okay, to have some control over the generation, and DPO is one of the computationally efficient method which does that task. Okay, so coming into the abstract of the paper, LLMs have a broad knowledge. Okay, so it has been trained with lots of data sets, variety of data sets, right? So it has a large knowledge, but the difficulty comes where we can't control the behavior of its generations. Okay, so if we want it to write a story, it will write in its own way, but to have a control over it, to steer the generation, there are some mechanisms like RLHF. Okay, so that will try to steer the generation as per our preference, but the problem is that RLHF is complex and unstable in nature. RLHF stands for reinforcement learning with human feedback. So this is what has been used in GPT 3.5 as well as GPT-4, which serves as a backend for ChatGPT. Okay, the aim of this paper, which is DPO, is to find a mapping, okay, between the reward function and optimal reward policies. So what is that? So usually you'll have a common reward function, as well as there will be some policies. Okay, so what will happen is they will have a separate reward model, and it will come in different stages. So here, what happens is they'll try to find a single stage policy based training, okay, so that the model can be optimized to align with the human preferences, similar to RLHF. But in RLHF, what happens is it will take in multiple steps, but in DPO, what will be happening is we'll be aligning the model with human preferences in a single stage, making it very computationally efficient. Okay, now let's see a small introduction of DPO. DPO, which stands for Direct Preference Optimization, is a lightweight and highly performant method to train LLMs on preference datasets without a reward model. That's a very key point. Okay, because in RLHF we'll be separately training a model called reward model. And guys, if you want to know about how ChatGPT was trained, such a framework, how it was trained, just let me know in the comment section. I'll try to make a video on that as well. So coming back, experiments have shown that DPO aligns the model with the preferences better than RLHF. Okay, so they have conducted some series of experiments resulting in showing that direct preference optimization aligns the model with the human preferences better than RLHF based on PPO. Okay, PPO means proximal policy optimization. So now let's see an introduction to the paper. Okay, so they started with the challenges existing, which is that, like we said, LLM has great capabilities because it has trained with large variety of data sets, and the data set will have different goals, skill sets, and priorities. Like there will be question answering, there will be there are some pre-trained tasks as well, right? Next sequence prediction, there is mask language modeling. Okay, there are a lot of tasks which are there, and each requires a different skill set, and each are prioritized in a different way. But what happens is some of the capabilities acquired or some of the skill sets acquired are not desirable. For example, sometimes what happens is the model will know about the common misconceptions which is there among people, but we require that the model should be aware that it is a misconception. It should know, okay, there is a misconception, but it should be aware that it is a misconception. Okay, I hope it makes sense. And coming back to the existing solution, like we said, to control the model generation, there are some mechanisms like RLHF. Okay, so RLHF stands for reinforcement learning with human feedback, which is a method based on reinforcement learning itself, like the name states. It involves creating a reward model based on the preference datasets, and it will utilize that reward model to optimize the SFT model's performance. SFT model is nothing but a supervised fine-tuning model, which is maybe your pre-trained model, or like you can consider your pre-trained model, but usually SFT model will be a model which has been instruction tuned. Okay. Now coming into the problems in RLHF, the problem is that it is very expensive and complex because it involves multiple training loops. First, you need to train an SFT model, then you need to train a reward model, then you need to train the final model, which is optimized by the reward model. Okay, so it will have multiple training loops. So now coming back to the introduction of DPO. DPO has the same objective of reward maximization. See, the point is we need to maximize the reward in a way such that it will align the model to the preferences, right? For this, they'll be using KL divergence constraint. So KL divergence is nothing but it will say how different two entities are. Okay. It is used this KL divergence constraint is also used in RLHF. Okay, so DPO shares the same objective of RLHF, but DPO is very simpler and simpler to train and implement. Okay, so DPO updates. What happens is that while DPO update is nothing but a weight updation by using DPO. Okay, it increases the relative log probability of preferred over preferred responses. The DPO update will happen in such a way that the probability of preferred will be greater than dispreferred responses. Okay, and since here we are not using a reward model explicitly, we'll still rely on a theoretical preference model called Bradley-Terry model. There are some other models like Patrick Lew's model and all, but in this paper they would have followed a model called Bradley-Terry model, which will help to measure how well the model aligns with the preference datasets. Okay. Finally, a loss function called DPO loss is used for eliminating the need for a reward model, because this loss itself will check how much it is aligning. Okay, now before moving into DPO, you need to have a clear understanding of what will happen in RLHF and how the optimization and reward all works, because we'll be eliminating the reward component alone from this pipeline. Okay, so let's see about RLHF. So RLHF occurs in three different phases, where first one is SFT phase. Like I said, we will be fine tuning on a high quality data set like instruction tuning. Okay, and the resultant model will be called as PySFT. Okay, so remember this. In reward modeling phase, which is the second phase, SFT will be prompted with a question and a pair of answers. Okay, so question might be your prompt, or else like generally you can say like summarize the following or something like that. Okay, some kind of command also fine. So the pair of answers will be such a way that y1 will be preferred and y2 will be dispreferred. Okay, so y1 is greater than y2 while it is coming to preference. Okay, this is provided to PySFT, okay, which is your supervised fine-tuning model on a conditional probability of y given x. Okay, it will try to predict the probability of y given an x. So here the preferences, like we said, right, y1 and y2. The researchers didn't know what happened inside the preferences creation. Okay, so just they assume that it would be generated by a latent reward model called r star y comma x. Okay, so this preferences of y1 is greater than y2 is created by a latent reward model called r star y comma x. Okay, so for this preference distribution, the reward model is following Bradley-Terry model in the following way. Okay, so P star, okay, star will be in your suffix superfix. Okay, now P star P star y1 is greater than y2 given an x is your preference distribution, which will be equal to exponential of r star x comma y1 divided by exponential of r star x comma y1 plus exponential of r star x comma y2. This is your equation number 1. Okay, like I said, 1 is your preferred and 2 is your dispreferred, which means the preferred response reward being exponentiated will be at the top and will be dividing it with the exponentiated value of preferred as well as dispreferred. Okay, so that's what happens in Bradley-Terry model, which is serving as your equation number 1. So usually just remember that we'll be using YW and YL hereafter. Okay, so YW will be your Y1 and YL will be your Y2. YW is greater than YL. Okay, with the data set in this following dictionary way. Okay, so it will be XI, YWI, YLI, and XI will be your input, YW will be your preferred response, and YL will be your dispreferred response. I is equal to 1 to n means how many data sets is data points is there, that much data set will be there. Okay, for this a reward model R phi of x comma y can be parameterized under phi. Okay, and then we'll estimate the parameters via maximum likelihood algorithm. Okay, so considering this, when we frame it as a binary classification problem, the negative likelihood loss can be calculated as LR of R phi comma D will be equal to minus E. So here actually if you see, it is not minus E, it is minus expectation. Okay, so expectation of x comma YW comma YL will be approximately will be belonging to the data set. Okay, like you see here XI, YWI, YLI, right? So it is expected the LR R phi comma D is expected to be negative log sigmoid of. So sigmoid here they call it as logistic function, but you can also call it as sigmoid, right? So log sigmoid of R phi x comma YW minus R phi x comma YL. So even if you see previously, right, we are always having our preferred first and dispreferred second because we need to prioritize the preferred first. Okay, so that's why they are calculating R phi x comma YW first. The reward of x for completing a response which is similar to the preferred one, subtracted with the response generated similar to uh, dispreferred. Okay, so in simple terms, we'll have a response. Okay, we'll be seeing how much reward is there for it being closer to the preferred response and how much reward is there for it being close to the dispreferred response. Okay, so in such this way, we'll be calculating the reward, and by that we'll also be getting the negative likelihood loss. Okay, so here the E means expectation. I'll show these equations in paper. Okay, so you need not worry about what will happen. So but in this video completely, E will be expectation, not a simple variable. Okay, now in LMs, usually this R phi of x comma y, right, like your reward model parameterized under phi, will be your SFT model. Okay, so what will happen is in this SFT model usually will generate a sequence of tokens, right? So in order to generate a value, we'll be adding a final layer inside the LMs at the last, by which we'll be getting the reward. Okay, so in this, to ensure that there is a low variance in this reward function, there have been some prior works which has happened to normalize the rewards. Okay, such that the expectation of x comma y belongs to D uh, is that the reward of x comma y will be equal to 0 for all x at the beginning. Okay, while it is beginning, the reward for any input and output together will be equal to 0. Now we have seen, like, what will happen in the reward modeling phase. So finally what will happen is we'll have this reward function, sorry, yep, we'll be having this negative likelihood loss function. So by this we'll be using to optimize the model. Okay, so we need to maximize the reward, right? So what we'll be doing is we'll be calculating again, like, the expectation hereafter I'm not going to say about that. Okay, so I'll just call it as expectation of the reward model given an x to predict y. Okay, it should be maximum, so it will be subtracted with a beta parameter. So beta is a hyperparameter to control. Okay, that will have it aside right now. And D, again, D will be somewhat different. When you look, this D will be different after beta. There is a D, right? That D will be looking different when we see in the paper. So DKL means KL divergence. Okay, so KL will be in your subscript. So DKL, which is your KL divergence. So we'll be calculating KL divergence for phi theta of y by x, and like the differences between phi theta of y by x and pi ref of y by x. Okay, so by that we'll be calculating a KL divergence, and then we'll try to maximize the reward. Okay, so here pi theta will be your LLM and pi ref will be your reference policy or your model. Okay, your model itself sometime will be using as your reference model. Okay, so the final reward function will be as, let's say, like, we have a reward function called r of x comma y. It will be r phi of x comma y minus beta log of pi theta y, conditional probability of y by x, and minus log of pi ref of conditional probability of y by x. Okay, so what is there is that we'll be finally calculating the logarithmic value of the reward out of, not the reward, yes, yeah, it is the reward. Okay, so we'll be calculating how far it differs. Okay, so that's the main idea. So here we have this reward, right, r of x comma y. We'll try to maximize this reward by using proximal policy optimization. So that is very important, which we will replace with DPO itself. Okay, so this is your DPO method, where if we usually had a preference rate of YW greater than YL, we'll calculate a maximum likelihood, and based on that we'll train a reward model. Okay, so once that is done, LM policy is your final model. Okay, final LM is your LM policy. So the LM policy will first generate a completion and it will label the reward, it will optimize the LM policy, and then again the completion will go to reward model. This will happen in a cycle. But here in DPO, what happens is you'll be calculating the maximum likelihood, and in the DPO loss function itself, it will try to optimize it. Okay, so like you see, the reward model is not at all needed here. So it will occur in a single stage. So DPO method, basically why the DPO method is needed. So to solve the challenges of RLHF, only DPO came into the picture. Okay, so what happened was when RLHF was trained on large scale problems, okay, it was very unstable. Okay, so because what happens is it has multiple reward models, so you can't always say like you'll be fine with it. And it is complex as well, like we saw previously. But DPO approach was introduced, okay, such that it will bypass this reward modeling step and it will optimize the language model directly on the preference data itself. Okay, so here we'll have a loss function. Okay, it will be transformed into loss function over policies. Like I said, we'll be finding a mapping, right? I told you, right? We'll be finding a mapping between optimal policies and reward functions. So what will happen is the loss function over policies itself will help you bypass this reward modeling step, and that will itself reward you. Okay, but still we'll need a theoretical preference model, like I said, for which we'll be using Bradley-Terry model for the optimization. Now, first we'll start with deriving the TPO objective. Okay, so here there will be kind of some of the derivation will be only in appendix. Okay, so I'm not gonna cover those. Okay, I won't say about how it will work, because if I cover that, it will again go as a very long video. So for now we'll just know what is there. Okay, equation 3, which is this reward function, like the optimization problem which we have framed here, right? Like based on the scale divergence constraint, this is rephrased under a common reward function R. Okay, so pi R of y by x is equal to 1 by z of x, pi ref of y, conditional probability of y by x, and exponential of 1 by beta r of x comma y. Okay, so here it is your equation number 4. Here is where we'll start with deriving the DPO objective. Okay, so here the z of x will be summation of y, pi ref of y by x, exponential of 1 by beta into r of x comma y. Okay, so if you want how this first equation, which is your equation number 4, was derived from equation number 3, again let me know in the comment section. I'll try to make a short video on that as well. Okay, so but basically what was the idea is that we need to make the problem statement to be made as a general under a to the problem statement was to formulate an equation which will optimize the LLM. Okay, so here we are just changing it into a general reward function R. Still we are considering the KL constraint reward maximization objective. Okay, so we have our equation right now, and once you rearrange this equation with some algebra, okay, in terms of policy pi R, optimal policy pi R, so we have pi R right there. So that is your optimal policy, or else your final model. Okay, and reference policy pi ref and z dot, which is your unknown partition function. Here I have specified partition function, but the partition function will be something which it is unknown. Okay, so it will be r of x comma y, which is equal to beta log of pi r y by y given x by pi ref y given x plus beta log of z x. Okay, so now I'll say how it was reframed. Let's consider this equation, which is number 4. Okay, we have pi r y by x and all right, but here what we need is reward function x comma y, right? So what we'll do is first accept that exponential of 1 by beta r of x comma y. We'll have this other parameters go to the other side, okay, which will be z of x into pi r y by y given x and pi ref divided by pi ref given pi ref y given x. Okay, so this is how it will be. So z of x into pi ref y given x by z of x pi r y given x by pi ref y given x. So it will be like that right now. But what happens is now you have this exponential parameter, right? So we can just remove the exponential parameter by multiplying with log. So what will happen is, now if you take log on both sides, log of z of x into log of pi r y by y given x by pi ref y given x will be equal to 1 by beta r of x comma y. Now if you multiply this on that side, and we know log of a into b is equal to log of a plus b, you will attain this result of beta log pi r y given x by pi ref y given x plus beta log z of x. Okay, I hope this makes sense. Now we are just calculating our reward function. Okay, so which is our objective in the DPO. The previous equation which we saw, right? When we reparameterized it under a ground truth reward. Okay, so here it is optimal policy, like we'll see, like, okay, this is a optimal optimal output which we are expecting. Okay, but here optimal model itself will be your ground truth, right? Like the optimal result which you are expecting will be from your ground truth. So we are just rephrasing it everything under reparameterizing everything under r star. Okay, so again, now r of x comma y, wherever you see pi r, you can just replace it by pi star. Okay, so it will be not r of x comma y, it is r star x comma y. Sorry for the mistake. So it will be r star of x comma y. Okay, so we saw, right, a Bradley-Terry is there. So Bradley-Terry in the previous equation also we saw, right? Here the equation number 1 is something which is followed by Bradley-Terry. Okay, fortunately what happens is Bradley-Terry depends only on the reward differences. Okay, so this model provides the preferences only based on the differences of rewards. So what we'll be doing is, we'll be calculating the rewards for preferred as well as dispreferred, r star x comma y1, r star x comma y2, and we'll be subtracting r star x comma y1 minus r star x comma y2. So this is how we'll calculate the reward, and we'll be applying a sigmoid or else the logistic function over it. Okay, so by this we'll be calculating the preference distribution. So now we have this one, right? And we have a preference distribution for the reward function. We have it in the previous equation itself, r star. Like I said, there was a mistake. So now substituting this r star x comma y, which is on top in the second equation in this page, will be attaining the following result, which is in this page. Which is in this image. Okay, so p star of y1 is greater than y2 given x will be equal to 1 by 1 plus exponential of beta log pi star y2 by x by pi ref y2 by x minus beta log of pi star y1 by x by pi ref y1 by x. Okay, so this is how the statement will frame. Again, I've given there, right? You can refer appendix 6 for how this conversion happened. It will be simple mathematical calculation, not complex any integration or something like that. It will be just common algebra. Okay, finally we'll be having this loss function. Okay, so which is our objective of this DPO. So the DPO loss will be equal to, here you can see, right, the E is somewhat different, so that is called expectation. The expectation of loss will be log sigmoid of beta log pi theta yw given x by pi ref yw given x minus beta log of pi theta yl given x by pi ref yl given x. Okay, so this is how we'll calculate our loss function. So this is how we'll have our DPO loss. So in this, if you see, everywhere we are giving importance to the preferred response first, and then next we are having the dispreferred response. Okay, so if you have some like dispreferred thing, this loss will be very bigger. Okay, and if you have preferred responses, the loss will be smaller. Okay, so that is the aim of this objective. Okay, it will try to find how much the model aligns with the preferences by using this loss function itself. Okay, thus by using this loss function we'll be bypassing the reward modeling step. Okay, now coming on to the update function, which is very important. Okay, so usually the gradient of this loss function LDPO, okay, what it will do is it will increase the likelihood of preferred responses and it will decrease the likelihood of dispreferred responses. That we saw here itself, right? So that is what is happening here also. Okay, it is increasing the likelihood of preferred and then subtracted by the by it is decreasing, right? And before that we have this reward function being subtracted, right? Like we saw it here, I guess. Yeah, here it is, the preference distribution, which is sigmoid of r star x comma y1. Okay, so that preference distribution will be given before this value. Okay, you will get the likelihood, right, to penalize it and give some rewards or else provide some punishments, which is the idea of reinforcement learning. Okay, here we have this preference distribution. Okay, so this is how the updation will be happening. So the likelihood is increased or decreased based on the responses and the magnitude of reward or else punishment. Here there is nothing called punishment, there is only reward. Okay, the negative magnitude or positive magnitude is defined by this preference distribution weight. Okay, so here r cap theta of x comma y will be equal to beta log of pi theta y given x by pi ref y given x. Okay, so yep, that will be our final DPO reward function. Okay, so when we are coming into experiments, before going into that, guys, if you have any doubt, I know this is a complex paper and in the mathematical part I'm not going into it very deep because it will have a lot of calculations. I'm just giving an overall view of what is happening and I'm just trying to explain basically what is the idea of DPO. So if you like this video, just click the like button and only 35% of my viewers are subscribed, and if you have not subscribed, please consider subscribing the video. Okay, in this playlist I've planned to make a lot of videos and there are some other good playlists as well, which you can check in the channel playlist section if you are interested. Okay, and share this kind of video with your friends because this paper, especially DPO, is I feel gonna go places. Okay, like it will be talked a lot because till now why it has been talked about is that the implementation was not there, but recently the implementation also has came. By this I feel there will be a lot of DPO models which we'll be seeing hereafter. Okay, and if you have any doubts in this DPO, just come and ask me personally also, it's fine, or else let me know in the comment section, come and ask in the Telegram group, the link will be in the description. Okay, that is also fine. And yeah, you can increase your knowledge in this DPO. Okay, so cool, we'll go with tasks first. So in this they experimented with 3 tasks for evaluation, which is control sentiment generation, summarization and singleton dialogue generation. I'll say what happens in that. Okay, so in control sentiment generation, what they done was they created a preference dataset based on a pre-trained sentiment model. Okay, where the model is ought to generate a movie review. Okay, given a movie prefix like the movie was. Okay, I'll be having it as a prefix, and it should generate a movie review which is in positive nature. Okay, and again to check if it is positive or not, we'll be using the pre-trained model for evaluation. Okay, so this is coming on to control sentiment generation. For summarization, they have taken a preference dataset for summarization itself. Okay, from a person which I'll show in the research paper. I'm just not getting the name by now. And based on that dataset, they are training the model to align to the preferences. Okay, and for evaluation, they have used GPT-4 and KL divergence. Okay, so similarly, singleton dialogue generation also was happened, but here the preferences was not there, so they trained an off the shelf LM, okay, and then like they used that as a SFT model, and then based on that they made the preference model, okay. So this is what they done in each of the tasks. And like I said, for evaluation they used scale divergence and GPT-4, and some other methods also was used for evaluation, where like they done zero shot prompting with GPT-J for summarization, and two shot prompting with PyTR 2.8 billion model for this singleton dialog task. Okay, so this is how they did some experiments. And after conducting a series of experiments with KL divergence value belonging to 3, 6, 9, and 12 for proximal policy optimization, and beta belonging to 0.05, 0.1, and 1.5. Similarly, alpha parameters are also given for DPO. Okay, so when they conducted experiments like this, it was clearly shown that DPO performs way better than PPO. Okay, it achieved the highest reward with low KL divergence. So usually you will need KL divergence to be very low, okay, because you need to find the differences between the optimal one and your generation. Okay, so if you are close to optimal, then your KL divergence value will be very less. So we need to gain the highest reward with low KL divergence, which was achieved by DPO better than PPO. Okay, but consider guys, this DPO is a computationally efficient method. That is very important. Okay, it outperformed all the methods in RLHF, it seems, especially they considered PPO. Okay, so for coming on to the conclusion, DPO is a simple training paradigm, okay, for training LLMs or LMs even, because it's not just restricted to LLMs. That's why they gave it as LM. Okay, so even for language models, if you want to align it with your preference, let's say GPT-2 is a language model. It's not large language model. It is slightly smaller, right? So even you can use DPO for that kind of model as well. Okay, so this will be an easy, simple training method, okay, for training LMs without RL, but to align with the preferences, because it will be steered just by a simple cross entropy loss. Okay, so in that loss function itself, we made it as a loss function over policies, right? So by that you'll understand that. Okay, with the loss function itself, we aligned it with the preferences, and we steered the generation, which was the aim, right? Like it was the aim of RLHF, but it was very complex and unstable. But this is a stable approach, and it is very simple, right? So that is a key conclusion from this paper. And some of the advantages is that DPO performs similar or better than existing RLHF algorithms, okay, including RLHF based on DPO. Sorry, not DPO, it's PPO. Okay, I made a spelling mistake there. When I'm giving the slide, it will be changed, so you need not be confused. Okay, so even based on PPO, there are RLHF algorithms, and that is outperformed by DPO. Okay, but the key point is that DPO also reduces the barrier for training. Okay, so usually the main barrier is that we'll have computation issues, and here it doesn't matter, right? You are not training a reward model, which means you don't need that kind of a computation. So to simultaneously run a reward model also, you need some sorry for the misclicking. Okay, yep. So if you see, like we'll be having very less computation. So that is what is the conclusion of the DPO. Okay, so you can achieve the same or better results than RLHF, but with minimal computation power. How much minimal is that? We have trained DPO again in Colab itself, the 2 in free version. Okay, so I'll show you what you can expect in the next video. Okay, so a model which was generating like this, like for a given question as should you buy a case to protect your cell phone, it was generating some random Java program. Okay, this was fine-tuned again with DPO to make responses like this. I would like to help you to protect your phone, like that. It is there. Okay, it was not trained for longer period. As usual, this is for tutorial purposes, right? I didn't train it for longer period, but and also the samples was very less, but I'm surely confident that with longer training time and with larger sample you can gain great results. But still I wouldn't say this is worst, because see, a model which was just trained to generate code was generating chat which was making some sense. Okay, so DPO did work well, so this is how you can compare it. Okay, that's how good DPO is. With I think this model was trained in 20 minutes if I'm not wrong, 15 to 20 minutes. Okay, so you can see it was very short time. Okay, and also this is a quantized model, so I'll say like DPO is top notch. Okay, now seeing on this paper we saw the abstract section, right? Like you see here we have related work which we didn't go in detail. Okay, preliminaries we saw about it, and deep direct preference optimization we saw it, right? Theoretical analysis of DPO, they would have seen about, like, the equation, how it will work under different situation. They would have made some theorems based on that. And if you are interested, go through this experiment section. It was very useful. Like, it had great knowledge in that. There were some interesting results which have been encapsulated in this experiment section, but I covered only the 2 to 3 things which will be needed for us. Okay, and here I told we had evaluated it under GPT-4, right? But the point was to align with human preferences, so it would have been great if human evaluated it, right? But with a test on n respondents, right, humans even agreed that GPT-4 almost agrees with them, or else even GPT-4 response is sometimes better than human. That's what a test has been given. Okay, and we saw the discussion, and coming on to the future work, that is something which we need to see here. Okay, so here the main one is you will be seeing here when you have something unlabeled. Okay, so here what happens is our model itself will train, and with the same reference model it will optimize itself. When I'm showing the code part, you will understand it. Okay, again I'll show a small tease of what will be the implementation code. Okay, but before that, the theoretical code, how it will be converted, I'll show in this video itself. So when you have something out of the distribution with an explicit reward model, okay, so you'll be able to optimize it. But self-rewarding model, that is a case study which needs to be seen. That is an important future work they had discussed about, and also they had trained models only with maximum of 6 billion, and they said like they will try to evaluate with bigger models. Okay, and like I said, here there is the derivation, right? Even in this derivation some steps were skipped actually. So if you want, you can check this out. Like I said, if you are in need of knowing about this mathematical equation, like you want me to derive in live, let me know, I'll make a video on that as well. And here is how you can implement this in PyTorch. Very simple. You will have the log probabilities from the reference model, and policy will be your normal model. Okay, and preferred completion and dispreferred completion, you will have all of those, by which you will have your preferred log responses, dispreferred log responses from your model as well as from the reference model. Once this is calculated, you will be subtracting preferred from dispreferred, and based on that we'll be multiplying the beta parameter, and we'll have a log sigmoid or on top of it, and we'll be having it as a negative value. Okay, so this is what we saw there, right, in our last function. So just give me a minute, I'll show you. Here it is. Okay, so here is your log ratios. Okay, and you're just subtracting it, right, beta star. Okay, so you can have it as another bracket here, and finally we are calculating the log sigmoid. Okay, so this is what has been happening in this code. Okay, and for this rewards beta star pi log piece, which is here, where was it, here. Okay, which is your preferred log probabilities from your model SFT model, minus log probabilities of your reference model, and we'll be multiplying with beta parameter. Okay, so that you can see it here, log probabilities of your policy model by log probability of your reference model. Okay, and you know, right, log of a by b will be log of a minus log of b. So this is how it has been implemented in Python as well. Simple implementation, guys, but to implement it with a framework, thanks to Hugging Face again. Okay, they create an amazing library called TRL. In this recently, they have created DPO as well, support for DPO as well, and I'll show you how it happened for us. Like, I'll also show you the code. I'll just give maybe kind of a teaser of what we can see in the next video. So this is the trainer which we'll be using, and here you can see what all are there. We have inputs concatenated. Okay, we'll be concatenating chosen, rejected, and all will be concatenated to a single one. Okay, it will be separated as well again. And we have our DPO loss function. We have the log piece. We need to get the log piece, right? So that also there is a function on that. Okay, and here we have this compute loss function from which we'll be calculating the DPO loss. Okay, so yep, here is the implementation of DPO. Okay, so here also the DPO loss, if you see, it is same as what we saw there. Okay, I hope this is cool. Okay, and for rewards, here what they did is they calculated the chosen reward as well as the rejected rewards. Okay, for chosen reward they subtracted chosen policy log probabilities minus reference for chosen log probabilities, and similarly they did it for rejected rewards as well. Okay, so this is how it is implemented, and the trainer we'll see about this trainer and all in a separate video. Okay, because I'm planning a playlist on TRL library itself. Like you can see here, we have proximal policy optimization trainer, PPO, as well as there is a reward trainer, there is SFT trainer. Okay, I will make a separate playlist on this, and if this is the most thing which you are interested in right now, let me know. I'll maybe even make a live session, a detailed live session. Okay, maybe 2 or 3 days continuously, and we'll see about all the trainers. Okay, and we'll see like how it is happening. I'll see in live itself. Okay, so it will be kind of an interactive session. I won't even learn it anything in prior. Okay, so that we can have an interactive session and learn together. And if you are interested in something like that, let me know. Okay, so this is the library which we'll be using. Okay, and again I'm going to show you the code as well. Open notebook. Yep, I'll be explaining the code separately. Okay, so here also you can see we have 3 files, right? Like we have SFT, we have DPO, and then followed by inference file. Okay, so here is our LoRA. We have it. Okay, and here you can see we have only 5,500 steps, and batch size was 2, which means we have trained it only on 1,000 samples. Okay, for 1,000 samples to get this kind of result. See here, guys, it's amazing actually. The training loss is also decreasing. From 5.9 it became 5.1, and the validation also it decreased from 6.5 to 5.6. That is pretty good actually. Okay, so that's actually pretty great. And also if you see the accuracy of the reward rate, it was constantly improving, which means it was going in a correct direction. Okay, so the rewards direction, if you see, right, it is in negative in nature, which means it should decrease, because if it is going -1, -2, it means it is performing very worst, right? So here it is decreasing from -1.818 to -0.84, which means it is doing better. And if we had trained it for a longer time, it would have given some better results. Okay, so this is not an error. Okay, what happened was something related to save, and it is not a problem now. It will work. Okay, so this will be our next video. Okay, so I'll upload this video which is on implementation tomorrow itself. So make yourself available tomorrow to see this video. And guys, really I'm saying it would be amazing to see how much this performs very well. Like this DPO is literally so good. Welcome to the second part of DPO paper explanation and implementation. So if you haven't seen the part 1 video where I've explained about the paper in detail, including the advantages of DPO, where it is very computationally efficient, and also it might serve in future as an alternative for RLHF based approaches, because while experimentations, it has shown the potential that it can perform as much as RLF or even better than RLHF based algorithms. Okay, including the one which was used in ChatGPT, which was PPO. Okay, so that is DPO. Okay, so here in this video, in the second part, we are going to implement this DPO on a model. Okay, and we'll see how it will perform. So for this, we have took tabby ml santa coda 1 billion as usual. Okay, and I hope you guys have seen this file from our previous video itself, where I gave a short tease of what in this video will be getting as a final output. Okay, a model when asked a question about should you buy a case to protect your cell phone in a general way, it was replying something like in Java code, right? But it doesn't make any sense to reply in this fashion for this question. But here, if you see, when I fine-tuned it in an SFT stage, followed by applying DPO, we were able to get some results which made some sense. Like it was saying, I would like to help you to protect your phone or something like that. Okay, and this result is not something I would say it's great, but once we see the DPO file, right, you will understand this itself is making great sense, that I'm saying it is very good. Okay, so I'll say which are all some parameters you can play with. Okay, because here if you see, we are using this Santa Coda 1 billion, but from TabbyML, this guy itself has, or this organization, I don't know if it is an organization or an individual, they have created some good small models actually. Like, we're having Star Coda 1 billion, we are having Cogent 2 billion, there is J350M. So you can try with some models. Okay, for now I'm just keeping it to TabbyML Santa Coda 1 billion. Okay, so let's start with SFT, because even in our previous video we saw, right, where while explaining the process of DPO, we saw that first we need an SFT model. Okay, so that was the base. Even in RLHF, right, we were trying to skip or bypass the reward modeling step, but others remain the same. So still you need to do an SFT fine tuning. So sorry, SFT to SFT, because it is already called a supervised fine tuning, so it doesn't make any sense to call it as SFT fine tuning. So we need to create a SFT model, followed by which we can apply DPO on top of it and possibly make some good results. Okay, so without any further delay, we'll move on to the implementation. Okay, so guys, I'm just making a walkthrough because if you see, we are having two long files along with an inference. Okay, and possibly I might even show you some things from the source code, how they would have gone about it. So it will take some time if we code it in live. But if you are not comfortable with me going in this fashion where I make a code walkthrough, let me know in some way. Like, you can connect with me through my social links, which is given in the description, or else even you can join our Telegram group where I'm open for some healthy discussions. Okay, and maybe even if you want, you can just let me know in the comment section. So yep, now let's start with installing the dependencies. Okay, so for the first dependency would be transformers library, followed by TRL. Okay, TRL is a recent library which is being released by Hugging Face, which is Transformer Reinforcement Learning. But for the guys who have been seeing our videos, I don't think any of these libraries should be new, because we have used the similar setup for fine-tuning Llama. So guys, if you haven't seen how to fine-tune Llama 2 by using the similar setup, but the Llama 2 7 billion model was even fine-tuned in collab itself. So if you are interested in fine-tuning Llama 2 on your own, just just check our video playlist, where there is a playlist name called LLMs related, where I'll be posting videos mostly on LLMs. There are two videos right now, which is one on fine-tuning Llama 2 and other is on deploying a chatbot on your own. Okay, not chatbot, any LLM on your own. So if you are interested, just check it out. So coming back, we are having PEF library, okay, from which we'll be using LoRA, and then accelerate. We are having datasets library just to import dataset from the hub, and then bits and bytes to load it in 4 or 8-bit, because we are doing QLoRa, okay, not just LoRa. We are doing QLoRa, which is LoRa on quantized weights. So as usual, guys, we need to do notebook login, okay, and I hope you guys know how to create the token. So we have seen that in a lot of our videos. Now let's see the inputs, okay. So thanks to before moving into the implementation, thanks to Hugging Face, okay, from their implementation we have done this, okay. So thanks to them. Hopefully this will make us being enabled to train lot of LLMs, okay. That too, which will be generating according to our preference. That is the key point here, right? So here we have data classes, typing, torch, datasets. Then these are all some conventional ones, right? But here if you see, we are having auto PEFT model for causal LLM. We have seen auto model for causal LLM. Here what is auto PEFT model for causal LLM is that it will try to load the PEFT model directly, okay. Previously we used to load the causal LLM model, and then we will be combining it with the LoRA module by using get PEFT model, right? But here if we have the config file, we'll directly load it, okay. So we have our LoRA config, we are having TQDM, and then auto model for causal LLM. These are all some conventional ones, okay. So and then we are having this are two new things. So SFT trainer for supervised fine tuning and constant length dataset to maintain a similar length in the whole dataset. Okay, so these are some helper functions we'll see once we go through this. Okay, so first we are having a function called def create datasets. Okay, this will take tokenizer as input. For dataset, we are gonna use this dataset. Okay, DAHOS full HHRLHF. And I think there are I haven't said about the full name for HH RLHF till now in any of our videos, though we have seen about this in one or two. HH means harmless and helpful, okay. RLHF is reinforcement learning with human feedback. Here we'll hold out this train set for or DPO, and test set we'll use it for SFT. But I would suggest the opposite. If you're having time, train it on train your SFT on the train subset rather, and then train your DPO model on this test subset. Okay, and don't forget to hold out some part of it for evaluation. So here if you see, we are taking the split test, okay, and use auth token is equal to true, just make it enabled, okay. Then usually we'll convert into pandas data frame, but here we can also directly do train test split, where you can provide your test size, and for now I've set seed is equal to none, okay. So from this we are getting the train data and valid data, okay. So once that is done, next we'll be having our train dataset and valid dataset becoming as constant in the dataset. Okay, before that there is this function called cache token ratio. Okay, so let's go into that. In cache token ratio, what it will happen is, the main idea of the function is to find what is the average number of characters per token, okay, in the dataset. For now here 400 samples has been taken as the range, okay. So in 400 samples, each sample is tokenized, and in each token how many characters is there, that is what is going to be returned from this cache token ratio, okay. So Now that is done. Followed by this, we are having trained data set and valid data set. Okay, I hope now this makes some sense. Okay, for this, we are going to use constant length dataset. So for constant length dataset, what it will happen is I'm just going to show you that here. Okay, let's see here if it is there. Constant length dataset. Utils maybe in utils it should be there. Wrong spelling. So here you can see, right, there is a class called constant length dataset where it will return a dataset which will have constant length of chunk of tokens. Okay, so what it means is that whatever length we give, right, it will try to provide it in a constant length, like it won't be varying. Okay, so that is what constant length dataset class does. And don't worry, I'll make a playlist on TRL very soon, TR library. But if it is the most intriguing one for you guys, just let me know. I'll make sure that that playlist comes out soon. Okay, here if you see, for this constant length data set, we are providing tokenizer, train data, and formatting function is provided as prepare sample text. So what we do in this formatting, so here what you can do is actually this won't be needed. Okay, so here if you see, we are having human and assistant kind of conversation, right? Human assistant. Okay, so you guys can just leave it like this. It will be finally like assistant will be there, and then yep, you can just maybe use this. Okay, what will happen is we are having a column called prompt and response, so it will just try to combine it like this, right? Human and assistant, like after this in a separate line this will come down. Okay, so that is what will happen, like we are just combining these two into a single text value. Okay, so given an example, we'll get prompt and response and we'll just combine it. Okay, so that's what is happening here, and that will be our formatting function. We are having a sequence length of 256 and caps per token we have calculated, right, by providing the train data and tokenizer. It will be provided here. So similarly, we are creating the valid data set. So now if you see, we have seen about the scarce token ratio, and we have seen about prepare sample text and create datasets function. Now it is time to prepare our model. Okay, so first we are creating a bits and bytes config so that we can load the model in 4-bit. Okay, so load in 4-bit is equal to true. So this is from bits and bytes package. So there is one person called Tim Detmus. He does some amazing work. So if you want, just follow him in Twitter or even in LinkedIn. Okay, so he's the one who is managing this library. Okay, so load in 4-bit is equal to true. So next we have BNB 4-bit quant type. So it will be NF4, normal float 4 precision. Okay, and then bits and bytes 4-bit compute data, which will be top star float 16. These are all some conventional ones now, right now, right? We have seen a lot of projects by using this kind of configuration. For now, we are taking our base model as TabEML Santa Clara 1 billion. Okay, we have seen that, and we are parsing this quantization config so that we can quantize the model in 4-bit. So applying the device map to be 0 so that every layer will be mapped to the CUDA device 0. Okay, and then trust remote code equal to true. This is something you can just do it at any time. Okay, because there will be sometimes that it will be needing some code. Okay, so which is from their source file, which is not even available in Hugging Face. To enable those changes, always it is good to have trust remote code is equal to true, and then use auth token is equal to true. Okay, now since we are training, we are making the catch as false. Now we are done with creating a model in 4-bit. Now next step is to add LoRA modules, right? So we'll see how to do that. So we are having LoRA rank is equal to 8, LoRA alpha is equal to 16. We are providing dropout as 0.05. Target modules. How to see this target modules? This is something you need to know. Okay. So once you where was that? Yes, here is your base model, right? So usually we calculate this LoRA, we add this LoRA modules only for attention modules, okay? But here in our previous video, if you see, we would have done it for query value, and in some other videos like Llama will be having QProj and VProj. Okay, the module name will differ. That is very important. Okay, so to find which module you need to do, what you can do is you can just print your base model, and then it will show like attention somewhere, it will be written there. You can find which is your attention module, and then you can just add it. Okay, so maybe even I'll try to do that at least. Okay, if not for the whole code, at least I'll try to show you how to find your attention module. Okay, and so guys, also if you don't know how LoRA works, okay, and if you are interested to know like how to set these parameters, what these parameters does, we have made a detailed video on our channel. Okay, where I've explained about LoRA, its working, as well as its implementation examples. Okay, so it is in the similar playlist, research playlist itself. So check it out. Yep, I guess now we should pass the token. I guess that shell would have been run. Let's pass this token. Okay, now what I'm going to do is I'll have these alone in a separate set, but we'll need the import, right, for these auto model for causal LLM and bits and bytes. Okay, I think it's better to import this one. This won't be needed actually, so not run these. From PEF library we'll be needing LoRa config, right? So we'll do that also. LoRa config. Okay, so looks good. Yeah, so let's run this. Oh, torch is not defined. Okay, import torch. So while it is downloading, I'll say about the rest. Okay, so for attention module, I'll show you how to do that. And for task type, for now there are two types, right? We have seen about there is also some other things you can do, sequence classification and all. So seek_cls, you can do image classification also by using LoRa. For now, we have seen about seek-to-seek LM in some previous video, but here we are doing causal LM. Okay, causal language modeling. Next, we are creating our tokenizer, and we are setting our pad token to be our US token, end of sequence token. Okay, now coming on to the training arguments, where we have provided our output directory, which is SFT Santa coder 1 billion, and train batch size is 10, eval batch size is 10, gradient accumulation steps is 2, where after every step, 2 steps only, the optimization will take place. Okay, learning rate will be 2e minus 4, which is 0.0002, and for every 10 steps we'll be logging, and we'll be training it for 100 steps alone. So these metrics, whatever we'll calculate, it will be stored in a tensor board. That's why we have report 2 is equal to tensor board. So next we save the model at the 100 steps, at each 100 steps, but here there will be only one save, because we are setting the max steps is equal to 105. Okay, next for LR scheduler type, there are a lot of types. Here we are using cosine. Okay, there is some other types like linear and all, it's there. Next, for warm-up steps we have one, and then we are using paged Adam W 32-bit optimizer. So these are some special optimizers. Paged optimizers are some special optimizers created for QLoRa. Okay, and we are doing a mixed precision training, where we are training in precision 16. That's why we are setting FP16 equal to true. Okay, so then we have a running name. Okay, for this run we have set the name as SFT Santa coder 1B. Okay, so same as our output directory. So once we create the data sets, we are passing it to the SFT trainer, where model is passed, train dataset, eval dataset. We have passed our PEF config. Okay, packing it to true. I hope you guys know about it. Like nowadays, I think I've explained in one of the videos, where we'll be having a lot of sequence length samples, right? What it will do is it will try, let's say we have 512. Okay, 512 as our sequence length, 512 tokens, but let's say we are having the first sample as 300, and then the next sample as, let's say, 400. What it will do is it will try to combine 300 plus 212 in one sequence, and then the rest will be taken to the next sequence and it will be followed by it. The other samples will be combined. I hope it makes sense. Okay, so that is what packing equal to true parameters does, and then we are passing our tokenizer and training argument. So once we are ready with our trainer, we are just setting it to train. Okay, we are training it, we are saving the model in this directory Santa Coda 1b. So once that is done, we are we are saving the adapter model alone. So guys, when you call the model from SFT trainer, your adapter model will be called and adapter config also will be called. These two will be saved in the SFT Santa Coda 1b. Okay. Oh, sorry, telling me to do it. It's content folder. Yeah, here it is. Drive. So here if you see, we are having SFT Santa Coda, right? In this, if you see final checkpoint, this was the folder. We are having our adapter config and adapter model. Okay, so that will be available in this output directory. Okay, but we need both the base model as well as our PEFT, which is our LoRA model, right? PEFT module or LoRA module. So what we'll do is, for now we will delete this base model, and we'll be calling a model, okay, based on this adapter module. Okay, we'll be calling a model. So here if you see, we are calling it as AutoPEFT model for cost LLM from pretrain. Okay, so by this it will create a model, and we'll be merging this model with the original model. Okay, so that is what we are going to do. Okay, so merge and unload, what it will do is, previously you will have, when you print the model, right, you will be seeing separately, like there will be LoRa A, LoRa B, it will be specified, but once you do merge and unload, it will be merged with its original respective layers. Okay, so once that is done, and if you save it again, so it will, if you save it in safe serialization equal to true method, it will be stored as safe tensors. Okay, so when I trained it, here you can see, right, the loss was constantly decreasing. There was this was the only occasion where it got slightly increased, and again it started to decrease. Okay, 3.15, 3.05, 3.00, 2.99, it was constantly decreasing, which shows that with some subsequent training and increased number of samples, still the model performance can be increased. Okay, so that was about SFT training. Okay, so you can execute this. I'll provide all these notebooks in the GitHub link, in the GitHub repository, and I'll provide the link in the description. Okay, so guys, without forgetting, try to save this model. Okay, because it might be needed in the future for you all. But if you think like, okay, I'm not gonna have some storage, then you can also do push to hub. Okay, now coming on to finding the attention module. Okay, so what you can do is print base underscore model. Okay, so if I print it, right, so here you can see we are having attention module here. Okay, so in attention module, which is GPT big code attention, your attention is C80TN. Okay, so that is your attention module. So for that we are considering this LoRa module. Okay, so you can also do it for cproj, but the reason I didn't do it was the C projection layer was also used in MLP. Okay, so if you have seen the previous research explanation, they avoided MLPs, right? So I didn't mention it here. But while doing DPO, I considered C projection as well, because like to have some better performance. Okay, there is no other reason, but still, like in this stage also, in SFT stage also, you can consider using C projection as well. So this is how you need to find your attention module, because for each model it will be different. Okay, so yep, that is about making your SFT model. Now let's jump on to creating the DPO model. So similar imports, but before that we are mounting the drive and then we are copying it here. Okay, so that will be there. So similar installation, and login. Okay, so similar imports as well, but here there is a function called DPO data which we'll call here. Okay, in later, but let's see first how to call the model. So AutoPIFT model for cos LLM, we are using that class to call our model. Okay, in here we'll be using the model which we trained previously, SFT model. Okay, so other than that, we are loading it in 4-bit, which means we are loading it in a quantized manner. Okay, this model will be same as this one. Okay, so the reference model and the original model is the same, and the other. Okay, so yep, that is about the model. And similar setup, like we'll call the tokenizer and set the pad token to US token. So now to get the trained dataset, we'll be calling the function called DPO data, and we'll be passing a parameter called train. Okay, so the dataset which we are using is again the full HHRLHF, but the train split. Okay, so that is what we are going to use. And what we do here is, here the dataset will be slicing it. Okay, like is to 10,000. We'll be just considering the 10,000, and here also, like we'll be considering only 4,000. Okay, so after that we'll have this original columns, which is the column names. Okay, yeah, I was just confused, like I forgot to comment this actually. These are all not needed. I was just using the same dataset for training and evaluation. But similar to SFT, you can just call the train test split function of dataset, and then you can have a dataset for you guys. Okay, so that can be changed here. Okay, so next we have prompt and response being connected like this. Okay, so that is there. Then we have chosen, rejected. Okay, so these are all there. So here also, actually, if you see, this won't be needed. Prompt alone will be suffice enough, like I said. So this should be suffice enough. Okay, so yep. Now we have this function called return prompt and responses, right? So we'll be mapping this on our dataset. So here this won't make any sense. Okay, I'll just remove these. Okay, always we'll be loading the whole dataset. But yep, I guess this is good. So once that is done, we'll have our train data as well as val dataset. Okay, so in that, what we are doing is, like we are just filtering the dataset, where we are trying to find the samples where when we combine both prompt and chosen, when we combine it, the length of the token should be less than 256, sorry, not 226, it is 256. We are filtering those dataset alone for the train dataset. Similarly, we are doing the same for eval dataset. So, but whatever the count it is doesn't matter, because we'll be changing the max steps here. But if you want to train it for longer times, no issues, just remove this parameter and it will work. Okay, or I'll set it to some 1 million. Again, it will work. Okay. So training arguments here, I'm not just going to explain the similar parameters which we saw previously. Okay. Train batch size, max steps, logging steps is equal to 10, max steps 505, save step 500, gradient accumulation steps 4, gradient checkpointing is equal to true, which means we'll be storing the gradients, okay, at the checkpoints. So we'll have learning rate, evaluation strategy, where we'll be evaluating based on steps, 100 steps. Okay, so output directory is given, report to. I think all of these are similar to what we used in SFT. But here, if you see, the only changes I have added C projection. Okay, other than that, nothing is different. Still, you can use the same one. Next, in DPO trainer, this is where slightly things are different, but not as different. Okay, so we'll be passing the model, which is this one. This is the model which will be optimized. Okay, DPO optimization will be happening on this model, and the reference model is also the same, but this won't be optimized. That's why here use case is equal to false, but here it is not given like that. Okay, so we are providing the reference, which is your optimal. If we see in the research paper, right, they would have given it as optimal policy and reference policy. This will be your optimal policy, and this will be your reference policy. Okay, we are providing a training argument, and we saw, right, beta parameter was there. So beta is equal to 0.1. We are having train and eval data set, followed by tokenizer. We are having a pref config, which are all something which we have seen till now. Max prompt length. This is another thing, like, we'll be having the prompt length will be around 128. We are just saying, like, at 120 tokens your prompt will be almost over. Okay, so that's how we are just letting it know. Okay, but it might not be like that. So we are just saying, like, half will be the max range for the prompt. So followed by that we are having the max length, okay, which will be equal to 256. Now we'll be training the model, we'll be saving it. So similarly we'll be storing the adapter model, okay, but don't do these two steps. These two steps resulted in error for me. This won't work here, okay. So but before going into that, let's see, like, here the rewards chosen is good, right? Like, it was decreasing. We seen the explanation about this in the previous video. So if you haven't seen the explanation of DPO, check it out, okay. So once till now, till storing the adapter modules is done, then execute this cell, okay. So in this directory, which will be just a minute, I guess auto model for, yeah, correct. So here what we will be needing is our SFT model, right, where we merged the LoRA modules, which was the base model here, right. That is the model which we will be needing. So first the model will be set as that model, like, SFT model. And what we'll be doing is we'll be combining that model by using this DPO Santa coder. Okay, so that's why we are providing this part, the adapter models, which has been saved in DPO Santa coder 1b and slash final checkpoint, that folder. Okay, from that we'll be combining the model, from which we'll be getting the final DPO model. So that is what you will obtain from here. Okay, so that you are storing it, and then you can push to hub like this. Hello everyone, welcome back to another video in the NLP research papers playlist. In this video, I'm going to show you all how to create your own mixture of expert, that too from scratch. Now you might wonder, Vasanth, it is too hard, right? Like, to create a mixture of experts, it is a lot of process involved in it. It is a black box. But I assure you all, by the end of this video, you will all know how you can convert any of your model into a mixture of expert model, be it Mixtral, Switch Transformer, or the latest model, which is Gemini. Even Gemini 1.5, which is a 1 million context window model, follows a mixture of expert approach. And I'm going to break you down to the crux of the field of how mixture of experts work. All right. So in this video, we'll be seeing the theory of how a mixture of expert work, as well as we'll see how to code and convert any of your existing model into a mixture of expert. Okay, be it a normal text classification or a very big LLM. This mixture of expert concept can be even applied to models like LSTM and so on and so forth, right? Because it is a core which can be applied to any of the models, right? So now let's see about the theory of how an LSTM works with the help of this amazing blog written by Avinash Suryarchi, who is a great guy who has written this blog in an amazing way, and that has been very great help for me to get to understand about mixture of expert. And guys, this is his LinkedIn profile. If you all think like he deserves some more, like, probably connect with him and let him know that his blog was very useful. All right, so yeah. So yeah, guys, sorry I'm not well. Um, so here you can see I have Mixtral's code, Mixtral, not Mistral, switch transformer, which is a 1.3 trillion parameter model. All right, and I'm gonna show you about how you can create such models with the help of mixture of expert as a logic. All right. So here you can see he has said like he has been inspired from the great Andre Karpathy's Make More implementation, because Make More also is also an MOE project which Andre Karpathy did with the help of RNN and LSTMs and all a long back, and based on that he has created this project known as Sparse MOE. All right. And we are inspired from him to create our own MOE, where I'll convert the model which I created in the Transformers from Scratch series to a mixture of expert model. Okay, so if you haven't seen the Transformers from Scratch, I recommend you all to watch it later, because I'll also give some introduction about the components which is used and how it works. But to understand detailed, please watch the more series after this video. Okay, so yeah, guys, and recently, if you see, there is a thing going on in Meta, Mistral, and all that. There is a possibility for Llama 3, okay, where Mark announced that there is a Llama 3 which is going to be there, and it has been rumored that it is a mixture of expert large language model. And we also know Gemini is there, Mixtral is there. Mixtral is currently the best open source model, right? All follows this mixture of experts approach. And in this, we are going to see how to create our own mixture of expert. All right. For this, we'll use the feed forward layers of the model to become the mixture of expert, and there is a component called router which we'll use to route to it. All right, so let's not go into the theory of this guy. Okay, I'll explain the theory by myself, and let's see the code also. All right, but this guy's code has been a very good inspiration for me, so if you all want, you can also check this blog. All right, the link will be in the description. Now to the components in mixture of expert. All right, components of a mixture of expert model. Okay, components of a mixture of expert model. So here there are two main components, where one is your expert and then another is your router. Okay, usually for experts we'll use the feed forward layers. Okay, feed forward blocks. And for router, there are very much different methods, and here we are going to use a router called noisy top K gating router. Okay, these are the two main components in a mixture of expert model. All right, be it any much size it is, doesn't matter, the core remains the same. Even if you want to create a, let's say, 10,000 trillion parameter model, still the core of the mixture of expert is going to be the same what I am teaching today. All right, so let me draw how a mixture of expert router will work. All right, so here usually what happens is, once you give an input, right, input from, let's say, like multi-head attention. Okay, from multi-head attention the input is coming to the feed forward. That's how in transformer it works, right? Usually it will go to the feed forward network and the output will arise before. Okay, before and after. Like once you introduce MOE, how it will work is, you have your input which is sent to a router. All right, I'll explain how router works and all, but next what happens is, this router will be connected to n number of experts. Okay, I'm keeping it dot 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 n number of experts. That will be FF1, FF probably 2 or 4 probably, and then FF n. Okay, n number of experts. And then finally it will be again combined together based on the router's output, and finally the output is provided. Okay, so this is how basically a mixture of expert model works. Now, to know about how a router works is the first step. Router working. Okay, see what happens is the job of the router is to map a token to an expert. Okay, let's say a token is there, I. So for this I token, it should map it to one of the n experts provided. Right, so let me show you with the blog also. Here you can see the same diagram is drawn. All right, so what happens within the router, we are going to see that now. All right, this is how even the blog would have been explained, but we are not going to see top K gating, we are going to see noisy top K gating. Okay, so the job of the router is to map every token to one of the n experts which it thinks is the best expert to provide solution to the token. Okay, like to handle the token probably. So what it does is in router, so how the router basically inside works. All right, once you get the input, right, you will then add a layer, linear layer, which will have the shape of embedding dimension, let's say if it is 512, and the number of experts, if let's say it's 4. So what happens is this dimension will be split into like a 4 dimension. Okay, and it will see like, okay, which dimension input is very good. So for that, what it will do is it will use top K function of torch. Okay, so top K function, what it does is given a vector, it will try to see what is the most like contributing vector. All right, the value or the vector which has very good values, the most number of higher values, we'll take some top K, which let's say we want to forward it to 2 experts, then it will take 2. All right, then what happens is this input will be provided to all the 4 experts. All right, this input will be provided to all the 4 experts like the same linear and all. After that, all right, not here, here. Okay, all the 4 experts it will be provided, and here out of this top K you'll get something called gating mask. It is very important, so I'll put it as yellow. All right, gating mask, and here you have experts output. Then what you will do is I'm combining all of those to be experts output. All right, 1 2 3 4. Here gating mask says which expert is good. Let's say the gating mask will look something like this. Okay, it will have some values where this might be 1 0 0 1, which means first expert and last expert are to be considered. This will be some weights. Okay, it's not 1, it will be some weight array and all. I'll explain how the array will look at the later part when we are seeing the code, but it will be like 1 0 0 1, and here it will provide all the experts will give some values. Let's say it is 99 and 88 1, let's say 1 or 2. It will multiply both of those. Okay, multiply both of these, and this will be your output. Okay, let's put it as like this, output, where the weights of the gates are multiplied with the output, which will provide 0 0 and the values of the expert here, which will be then combined to the original dimension. Okay, so this is how a mixture of expert model works. And obviously there are some things going inside, like you will do some noise adding here, that and all I'm gonna show you later. Okay, right now I have shown you how a top K gating works. All right, I haven't said about the noise and all. Right now we are working with a top k gating, because noise is something what you will do is after this linear you will also add a noise layer, and then you will provide the inputs to the same procedure. All right, then what you will do finally is here you will do a softmax. That is all. Okay, so that is how a top k gating router works. A router is something which has only two linear layers. For example, here you can see, right, there is a top k route linear and then the noise linear. Don't worry about the logic, I'm going to explain later. But these two are the only things which are responsible to map it to the expert. And expert, like I said, is nothing but your feed forwards. Okay, these are your feed forward. This is feed forward 1, this is feed forward 2, feed forward 3, and feed forward 4. All right, so this is how basically an MOE works. All right, it is not like something very complicated and all. You are providing your input, you are mapping it to the number of experts you have, and those inputs are provided to your experts, and then you are taking top k out of this output, and then you are taking a gating mask, you are multiplying with your expert output, and then you are getting your output. All right, so this is how usually it works, and as you can see here, this is the diagram. All right, so here you can see, right, element wise multiplication, that is what we did before. All right, so if you do this, you'll have your mixture of expert router being ready. Okay, this is the router. Then what you'll do is obviously you'll get this mask, right? That is where the process changes. This specific place into is where your MOE comes into the picture, where you'll multiply the mask with your expert output, and finally you'll get your output. That is what happens here. All right, so this is an overall idea of how a mixture of expert works. And if you don't understand still, let me know. I'll probably explain you in the comment section as much as possible. Now I'm going to show you how the code works. All right, so let me fire up my VS Code. So as you can see here, I have the previous transformer architecture code and all here. Like we are doing the same statement, which is to classify the emotion, but in here there is something different. Okay, so here I'm gonna replace the feed forward layer which was there with MOE. All right, I'm changing the feed forward layer from FF to MOE. All right, which we saw here. All right, so that is what we are doing in here. So let me go into that Smarts MOE, and for which we'll go into the top k router. Now we are going to see the core of the MOE. All right, so the core of the MOE is that the router should be like classifying the token, right? So that is the core, and that is what we are doing here. So what happens is, first we are getting the top k of how much experts you want to consider. Let's say I'm saying 2, and top k route linear will become 512, 2, and the noise linear will become 512, 2. So now what you will do is, in forward, in top k router, what happens is you'll get your multi-head output, right? So multi-head output will be passed into this top k router, which will become in 2 dimensions. Okay, it will become to 2 dimension, and in similar dimension noise is also added. So here what they do is, for a process known as load balancing. Okay, this is a very important concept, guys. Please listen to this very carefully. Load balancing. Okay, load balancing is a very important concept, because while training, what happened was there is an imbalance in experts. Okay, the router started to favor some experts alone. Let's say you are having 10 experts. The router was favoring only 2 experts, and 8 experts were like futile. There was no purpose for that expert alone and all. Okay, it was favoring some experts, and to handle that, they introduced a component known as Gaussian noise. Okay, where what we'll do is we'll take the model logics, we'll probably do like we are doing that noise layer, right? We'll pass through the noise layer, and then you'll get an output which is like of same dimension of what we require in routing, but the logits are there. Now what we'll do is we'll create a noise of this noise dimension. Will create a Gaussian distribution tensor, and then we'll multiply it with a soft plus or swish of this logics. Okay, so that is what is the load balancing done, which I'll show you now. It will be very clear. Okay, now you are like done with your reshaping of the logics. Okay, the logics is of 2 dimension now. All right, and then the noise linear is also of that same. And now what you're doing is we are creating a random normal distribution like tensor. Okay, random like means random normal distribution like, and since it is some random number, it is becoming the noise. Okay, so in that noise, we are multiplying the noise logics where we are doing some soft plus, which is swish. All right, it is a swish function, and the uh, curve will be something like this. Okay, it is like an adapted ReLU, but not ReLU. Okay, but this is something better. This is how a swish or soft plus function will look like, activation function. Okay, now you have your noise, you have your logics. Now you'll add these both, which will become your noisy logics, and that is when you'll do your top K. Okay, once you do your top K, you will get the indexes in which your expert is the best, and that logits also will be there. We need both. Okay, so now what you will do is you'll fill the tensor. Okay, we'll create a tensor which will have minus inf like this. Okay, initially it will be like minus inf, minus inf, minus inf, minus inf, and so on. Okay, this is how this top K like zeros tensor will be like. All right, now what you will do is in this zero there is a function called scatter. Okay, in the dimension -1 at the indices of top K, you will fill the top K logics. Let's say in top K logics, it's 0.8. These are the weights, okay? Like it is 0.9, 5, 12, something like that. Okay, it will be some values. And let's say here it is 0, 0, 0, some values. Okay, now what you will do is you will fill these values inside this zeros which you created at the indices given. Okay, if the indices is 0, we are not even going to consider it. So it is be something like 0.8, 0.9, 5, 12, but this will be same, minus inf, minus inf, minus inf. So why we need minus inf? That is another question, right? So here to create the weights, right? Getting weights of why this weights? Okay, first let me answer that question. Why weights? You see, we are taking top 2 expert, right? But still there, I'm like I want to say like this expert is more good and this expert is less good. Okay, obviously among the experts these two are the best, and out of this is the best and this is the second best, and that is given by weights. How much an expert output is considered or weighted. Okay, that is what is this weights. Okay, so now to the question minus inf in this weights. See, this weights will be of some value, like it will be of 200 minus 800, something like that. But always when you provide these kind of probabilities, it should be soft maxed. Okay, so that everything is becoming to 0 to 1. Okay, usually you'll have some negative value also, minus 8, minus 10, and you'll have 1, 10, 0. Okay, let's say these are the 5 output. Here if you do softmax, right, this will become 0, this will become some values after 0, this will become 1. Okay, but here the thing is minus 10 is also good. All right, so what we'll do is we'll first replace every negative value, like not replace, we'll have every values to be minus infinity, which are of indices which don't even we want to consider. Okay, to handle those negative from being 0, so we'll do this softmax. All right, so that the negative was 0. All right, Okay, I'm just confusing you. Okay, let me do this. You'll have some tensor, okay, and if there is some zeros in it, all right, it will achieve a higher position in softmax. Okay, since you are masking it, you need to do it as minus infinity, so that however lower value it is in negative, okay, it will be higher in softmax. I hope you understand that. That is why we do softmax usually, and that is why usually when you do padding mask and all, you will give a value of minus e 1e minus 10 and all. Okay, so that there will be no values lesser than that. So now you have your router weights. Okay, that is what you get from this f dot softmax of sparse logits. Okay, now you have your router weights. Next, what you need to do? Okay, your router is there, and then you have your feed forward. Okay, in feed forward here you can see I have two linear layers where you are providing some dropout, and then the linear layer provides your output, which is your feed forward output. All right, so to this you want to send the input. So what you will do is first you will get the getting output. Okay, that weights will be there and the indices also. So what first now you need to do is you need to create an empty tensor which will be of zeros. Okay, the like function, what it will do is given a tensor input, it will try to create an empty or some tensor of what it says, like if it is like random, like it will create a random normal distribution tensor of shape of x. Okay, now it will create a zeros tensor of shape of x, and then now what we are doing is we are creating a transpose. Okay, minus 1 of minus 1 comma x dot size of minus 1, and we are doing the same for flat gating output also, so that both will be of the same dimension, minus 1 comma gating output dot size of minus 1. So wherever the expert mask is not equal to 0, like that is what indices is equal to I happens. Okay, is not equal to 0, right? You will do a mask there where everything will be 0, others will be 1, and this input to that expert alone will be masked. Okay, so that is what happens here. And once you mask the input and you provide to the expert, okay, whatever expert you have, obviously the required values are all provided to the expert, and then you will get the output. So this is where the sparsity comes into the picture. This is a sparse architecture. Okay, so if you don't provide this and all, right, still it will work. Okay, still it will work, but the sparsity won't be there, and from what I've seen, sparsity gives you better results. All right, this is something what brings the sparsity, but even if you don't have this, the same logic applies. Okay, you have your getting mask, you have your expert output. Okay, you will multiply both of those. Okay, getting mask, and then you obviously have your getting output, right? So the zeros won't be considered, and the values which is there, mask will be 1 and the value will be there, you will have those, and those expert output will be filled in your final output. So that is how actually an MOE works. All right, I hope it is clear actually. Okay, so let me put a summary kind of thing here. Router gives a getting mask, you are flattening it. Okay, I'm not going to say about that sparsity and all. That getting mask is there, and you are providing the expert input. I'll put it as input here. Input is given here, and the same input is provided to your experts, and those are multiplied with the getting output, and finally the values are filled together in one dimension. Okay, it's not like 4 experts. Now it will become one output, and that is what is your MOE output. Okay, so this is how actually you should create your own MOE. Okay, let's say you have your own, like probably Mistral. Okay, take the Mistral's feed forward layer, apply the same function, and it will become Mixtral. Okay, whatever layer model you create. Okay, so here you can see in transformer, I'm calling the encoder and decoder. In encoder, previously it was feed forward in here. Okay, it was here, you can see even I didn't replace FF dropout. Okay, so it was feed forward in here. Just replace your feed forward layer with this MOE class. All right, it will work just as fine. And if you see, the inferences was also very good actually. The results were pretty good, better than the original model. Okay, I was finding a hard time to create that original model, but this was far better. Okay, so that is what this guy have also done. Okay, and here he has done something different. He has created a Shakespeare model, like it will write a Shakespeare thing. Okay, like he has a notebook or something like that. It will try to complete that. And let me show you that even Mixtral, the best open source model, follows the same approach. Okay, here you can see feed forward is there. All right, in MOE layer, what he does is he'll do the same thing, but here he'll not take like the top K out of that. We are doing some sparsity, right? That sparsity won't be there. Okay, he'll take the top K, he'll pass through the gate, that mask wherever it is 1, he'll try to add it. Okay, otherwise the logic remains the same what we have done till now. Okay, he's taking it to -1, the same logic. He has the gate, he has taking the top K function, and he's doing the softmax out of the gate logics, and the output like here you can see, right, the weights, that is what is our gate output. And then what he's doing, he's creating again like a zeros, like an empty tensor where you can fill the values, and he's passing through the experts, and wherever the expert is to be considered an expert, he's adding the values into the results. Okay, this is what we have done also, but here in our code we have something like sparsity here. Okay, this is the sparsity being introduced. Okay, otherwise the logic remains the same. All right, so yeah guys, that is how you can create very big models by your own. For example, this is also in another version of MOE, which is in like introduced in Switch Transformer, which is a model from Google. Okay, which is a 1.3 trillion parameter model. You are seeing a source code of 1.3 trillion parameter model, but still here you can see the same logic is applied. Okay, they have introduced something called capacity factor and all to say like, okay, this much only this expert should learn. This is some advanced things going on in here. If you want, you can also use that. All right, but the core of MOE is the same, which we have discussed right now. And in this video, we have opened up of how an MOE works. I hope you all like this video. If you all think like you have gained something in this video, please hit the like button, share it with your friends, because people are thinking MOE is a black box, and now you would have understand MOE is not a black box, because even mixture of experts is the same architecture. They have replaced the mixture of experts feed forward layer with this MOE layer. Okay, so yeah guys, that's it for this video. I'll see you all in the next video. Until then, cheers. This video is about you evaluating your LLMs with the help of Mistral 7 billion. Yes, you heard it right. Hereafter, you need not worry about how I'm gonna evaluate my models, what is the metric, or what shall I do about it. Your savior is here, Mistral. He has given some pretty good results with the case of evaluation, and for the framework we are using Langchain, so that is why we are having this in both playlist. So yeah guys, I hope you all will like this video. Once you end this video, you will have a framework ready for you to evaluate your models in different aspect. Okay, so about that aspect I'll show you at the later part of this video itself, but I would recommend you all to watch the evaluation of LLMs is all you need video after this video. Okay, and I'll also attach the link in the description, because in that video I would have detailedly discussed about what are all the aspects you need to focus on. So once you see these aspects which is available in Langchain, and you should compare those with the aspects which is available in that video, which I would have discussed, and try to evaluate based on that. I'll also say how to do that with one example or 2 examples. Okay, so that is about the introduction of this video. So let's jump into the video content right now. Okay, so here if you see, let me zoom in. Here I've provided an input known as input for dialog summarization. This is the dataset which we used for fine-tuning Mistral in our previous video, but this is not the same Mistral model. We have used the GGF version. I'll also show that also. Okay, so here we have given an input stating that Amanda is saying, I baked cookies, do you want some? And Jerry is saying, sure. And Amanda is replying that I'll bring you tomorrow. Okay. So the idea is that you should provide summarization. So that is the idea. And for better result, what I will also say you some methods what you can do to have a better evaluation. Okay. So yeah, coming on to the output, I have said that Amanda baked some cookies and she will bring Jerry those tomorrow. This is model output. Okay. And your base ground truth, which is the reference here, is Amanda baked cookies and will bring Jerry some tomorrow. So considering this is our input, output and ground truth, we can evaluate in different aspects, out of which one is correctness. So correctness will work on different aspects. So it has said that the submitted answer is Amanda baked some cookies and she will bring Jerry those tomorrow. The statement accurately represents the information given in the task. Okay. So it is saying, okay, the output is pretty good. It is correct. It is correlating very much with the given input. And accuracy, it is saying that, okay, the reference is correct with the output and there is no misleading or inaccurate statements. Okay. And factuality, it is said that obviously when you are correct and accurate, so you will be factual for sure. And based on this assessment, it is saying that it meets all the criteria of correctness. So basically the result is correct. Okay. So here, considering the improvement, right, what you can do is, when you are giving the input, this is how the input usually will be. So that is why I've kept it like this. What you should do is, based on the task, let's say you are having a summary, which is summarization here, right? Just add a line stating that write a summary for the following dialogue, something like that. Provide an instruction, which it will understand that, okay, here the model output expected is a summary of the following conversation. So that is something very important, which will give you better results, which I have tried. Okay. So yeah, that is some amazing result which we have got here, because obviously this is very small input and output, but if you have larger outputs, still this will work, and that time this will be very helpful. Okay. So yeah, that is about the result. So before going on to the code, I'll show you about the different aspects available. Okay. So here we have the different aspects available. Let me zoom in. Okay. This is the source code, and it is pretty helpful to show via this. Okay. These are the aspects which is available. So let me go through these and let me explain you what are all these, so that you can try to compare this with the evaluation of LLMs. So all you need video, and then based on that you can prepare a framework, which I'll say how to do that also. Okay. So here we have conciseness, which will say if the submission is concise and to the point. So let me give you some examples for each of those. Okay. So in conciseness, let's say you have summarization. So summarization needs to be concise. Even if you see in reasoning based question answering, right, it should be very concise. You should not say like I done that, I did that. It should be on point. That is what conciseness is. So this is a metric which you can use when you are having some ground truth, and it should try to appropriately be there, like without some fillers. Okay. So if that helps, that is how you can imagine this conciseness. Okay. And yeah, I'm not concise in my videos. I'm not concise. I tend to go off topics at some time. So yeah, I'm not concise. Relevance. So relevance is what is relevance? Actually, if you see, relevance is a metric which you can sort of associate with correctness also, because your ground truth, you have it and you're matching the ground truth, which means you are correct, which means your output also going to be relevant. But consider some cases where you don't have some ground truth. Okay. In that case, to check if the given output is relevant to the given input, let's say even if I'm generating the summary, right, to check if the summary is relevant to the given input, then you can choose this relevance. I hope this will make you understand what is this criteria. Okay. Correctness, I think we all saw right now. Okay. Next is coherence. It will try to check if the generation which it is performed is coherent, well structured and organized. You see, in generation task, let's not just go into summarization alone. Let me say I'm just trying to ask the model to write an email for me. The email should be very coherent and it should be very structured, right? So there is a structure which is always to be followed. First we need to have a to, and then CC, and then if CC if it is there, and then subject, and then your salutation, and then followed by that you'll go into the body of the letter, followed by which you will have the thanks and regards, whatever it is. So this is the structure which it should be followed, which should be organized, but the content inside the body also should be very coherent. So to check on these aspects, you can go for coherence. Okay, these are all something which will be more focused on your accuracy. Okay, so you can put it that way. How accurate is your result? These are all some metrics for that. But the following metrics here are or the following criteria here will be underrated but very useful. Okay, harmfulness, maliciousness, helpfulness, controversiality, misogyny rather, criminality, insensitivity, depth, creativity, detail. All are about the nature of the generation rather than the performance, how good it is. It won't focus on that. So considering harmfulness, the character. So if you are having some harmful words, it will say it is harmful. So in that time, you can try to avoid those kind of responses. Try to find a workaround how to avoid these harmful responses. Okay, maliciousness is also the same way. If you are having some personal data being leaked, it is going to be something malicious, right? So yeah, maliciousness there. Controversiality, if you are going for some controversial topics which the model shouldn't talk about, obviously, because we have seen in that video itself where the model shouldn't be biased, right? Obviously it will be bias will be there, but you should try to evaluate and find the bias, and based on that you should try to fine tune it. So controversial topics comes out when you have some bias, obviously, because if you have some bias, you'll try to talk on that topic also, which will be very controversial. Best example is the model should not talk about politics. Okay, so yeah, that is about controversiality. I think you all know what is misogyny. So yeah, and then we have criminality as well, saying about something criminal which shouldn't be there. Obviously, let's say if I'm asking how to kill a person, it shouldn't try to respond me, right? In that cases, see, even if I have a ground truth stating that this is how you need to kill, this parameter, which is criminality, supersedes the other parameters, let's say even correctness. So yeah, you should decide which criteria supersedes the other. Okay, so that is about criminality. So next is insensitivity. Again, this is to check the bias. If it is biased to any group of people, is it insensitive to any group of people? Okay, and then we have depth, creativity, and detail. Detail is about attention to detail. Is it on point? Is it focusing on even small things which is very needed? Creativity, this is some metric which you won't use a lot of times, but let's say you are having a generation of poem, so at that time you can use creativity. Or also if you are having some kind of plagiarism, okay, to make it understand if it is creative or not, is it novel or not, then you can go for this creativity metric also. And then depth, it is to demonstrate if there is a depth of thought. Is it thinking deep enough for generating this kind of response? So yeah, if you see it is trying to cover you almost every aspect. So let me also open that in HP docs also. Let me go for my GitHub. Okay, I didn't update it for some time. I'll try to update it as soon as possible. Okay, so in this I wanted to show you one thing. So here we have this evaluation of LLMs is all you need. So this is the video. Obviously if you want you can check it out. And here if you see, I've talked about the different metrics you need to evaluate on. Let's say if you have semantic analysis, text classification, these all can be evaluated with correctness itself. Okay, but when you go for this, so robustness, ethics and bias, trustworthiness, this can be evaluated under these metrics like harmfulness, controversiality, insensitivity. Okay, so yeah, what I would like you all to do is go through this, have an understanding of each metric which is there, and try to map those metric with these criterias, so that you will know if the model is ticking all the boxes in the metric specified here, because these metrics is an exhaustive list. It covers almost every aspect you need to evaluate your models on. So yeah, I would recommend you all to do that. So now that we know how is this criteria, let me go for the coding part. Okay, so let me fire up the VS Code now. Here we have the configuration ready. All right, so in the configuration, I'm just keeping two parameters. I'll show you why also. Okay, and for model we are using Mistral 7B OpenArca Q80GGUF, the same model which we used for the custom RAG pipeline which we built in the previous video. Okay, of Langchain projects obviously. And then the model type is llama, max new tokens is 512, 0.1 being the temperature, so that it will be very strict in its generation, because evaluation is not a place where you have creative freedom. So try to have it as 0.1 and then do sample is set to true. Okay, so these are the config. The config is not pretty huge here. Next we have the eval.py file. I'll say what you need to do. Okay, so here we have the C transformers being imported, and then from evaluation we are importing load evaluator. So here if you see, it will take an evaluator type, and also it will take an LLM. Okay, so let me say about the evaluator type also. So here we have the model and model type, max new tokens, temperature, do sample, all the configs are being loaded here in the initialization, and then we are loading the LLM also based on that. Next you need to create a list called criterias, which will take all the criterias which is there, because if you see, obviously I don't have the computation enough to do all at the same time, because it will take time obviously. I think it took me around 1.5 to 2 minutes for this evaluation, because I'm running in CPU. My CPU is not that powerful, or else even my RAM is not that big either. So yeah, if you have a bigger system, let's say if you have server, then yeah, you can go for all the metrics also at the same time. But yeah, if you want to evaluate on every aspect or every criteria, what you can do is, let me show what you need to do. First, have all of those metrics names here. So how to get that names? It is there in the website which I show now. Let me show you. So now you might think, Vasanth, where is that? So here is it actually. So here we have the class criteria, right? Inside that everything is there: conciseness, relevance, correctness, coherence. Have all of these inside the config file. Okay, so that would be the step which is required. Okay, so if you are evaluating on all the metrics, so that would be the step required. So now with that we know what we need to do. Let's again go for the code. Okay, so yeah, you can paste those into this config. Okay, so that you'll have all the metrics ready, and then make a list out of it. Why is this list? I hope you all would know by now, but I will also say you why is this list needed. Okay, so in this list obviously now we have only one metric of evaluation or one criteria of evaluation, but you have n number of choices here. Okay, so next we have two functions. Okay, one function is evaluate criteria. So what it will take is, it will take the criteria name, it will take the input, it will take the prediction, it will take the reference. Input is your model input, prediction is your model output, and reference is your ground truth. Okay, so evaluator is being called with the load evaluator function, with the evaluator being named as labeled criteria. You see, like I said, there are a lot of scenarios where we won't have a ground truth, or else we shouldn't rely on a ground truth. For example, if I'm asking it to write a poem, you should not evaluate if it is correct or not, right? It is not needed. You should not try to say, okay, this is the ground truth, check based on that. So on that basis, what you can do is, instead of having it as labeled criteria, have it as criteria alone. And in that case, you need not provide your reference. Okay, so that is the main difference. Other than that, everything is going to remain the same. So everything will work with ground truth also. But if you have the need for using ground truth, go for label criteria. If you think, okay, I should not use or I need not use my ground truth, go for just criteria and don't use reference. Okay, so that is about the evaluator type. Now we will get the criteria from here. The LLM is also provided, and in the evaluator we'll have the evaluate strings function. That is the function which is needed. It will call, and in that we'll be taking the reasoning alone. Okay, so what will happen is, actually it will try to return a score also, which most probably it won't be correct, because how the prompt is written is, you should evaluate, and once based on your reason, when you come to a judgment, create a new line character and then have y or n being the your verdict. Okay, so verdict is a good name to say. So if you are saying y, it will be 1, and if you are saying n, it will be 0. So that is how they would have written. But yeah, the model will use /n wherever it is possible. So yeah, you shouldn't rely on that. Rather than just return your reasoning, because what you can do, just hold on, let me say later. Okay, again obviously I'll show the output and how you can go about this, or else what is the future thing which is possible here. Okay, next we have the eval sample, where we have the input prediction reference. This is the function which we will call in the application also. I'll show you that in the application. So I'm having a dictionary here. Okay, so once I pass through the criteria which is there, I'll call the evaluate criteria, and this is why we needed the list. Let's say you have 10 criteria. You need not make 10 instances of this application and do anything. Okay, just have all the criteria being listed here. No changes needed. It will work as fine as how it is working now. Okay, so you can call this, and for debugging I kept this. I'll remove this also here. Okay, so now what it will do is, it will try to create a dictionary stating that correctness and its verdict. Okay, its reason behind the verdict obviously, or else the evaluation which it has performed. So if you have coherence, it will be coherence is to the evaluation. So the maximum possibility here is, I guess, around 12 or 13 criteria is there, if I'm not wrong. So maximum possibility is 13. So in that case also you need to change something, which will be I'll showing in the app.py file. So yeah, this also is a small file. We'll set the page config. We are setting the session state to be clicked as true, so that it won't reset the data. And we are loading the evaluator first. That is the main part. Okay, so first we are loading the evaluator, which we are calling it here. Mistral evaluator is being called, and we are getting the input prediction reference from the user. But if you are thinking, okay, Vasanth, I have lot of samples to evaluate under, so what I can do? What I will suggest is, have a loader file uploader there, maybe CSV, or most probably CSV should be better. So have your CSV being uploaded, and then read a data frame here, and then run it under a loop. Okay, so that is what I would suggest. So that is there. And yeah, if you click the button evaluate, and then if you click the session state to be true, it will call the eval sample function, which we know right now, right? We need to provide the input, prediction, and reference. And what I'm doing is, I'm going through the criteria and the verdict through the eval samples with items. Okay, so the dot items function is called because it is a dictionary, and inside the dictionary obviously have the criteria and the verdict, criteria being the key and verdict being the value. So I'm just having the capitalize function because C is let's say in correctness C will be small. That is how it will work with the load evaluator, right? So I just kept it like that in the config, but while printing it, it is better to have the first letter as capital, so I just had the capitalize function to make it camel cased, and then we are writing the verdict also. You see, now obviously it is working amazing. I'll again go through the result and I'll say what you need to do further. But before going on to that, what are the steps we can do when you are doing it for a large scale? First, on a large scale, if you're going for large number of metrics, what I would suggest is have this printed as st.json. Okay, there's a function called st.json which will print your JSON, not JSON obviously, dictionary. So once you return the dictionary, if you print it as st.json, it will work fine. Okay, so that is number one. Let's say you have 10,000 evaluation, so obviously you can't go for the application. Then what you can do is have a data frame, create these. Okay, so create this class and have a map function being mapped, or else apply function rather. Yes, so if you want me to make a video on how to evaluate under a batch of samples, let's say you have 100 samples evaluation for obviously for evaluation in a data frame, how to evaluate that, let me know. It is a quick video, I'll make it short, maybe in 5 to 10 minutes it should be probably done, but it will take longer time. Okay, so why I made this application, that is the first intention, because I would have shown this in a Jupyter notebook, which is more easier, right, to build it is more easier to show and build rather than an application. So see, the idea is, like I said, you can't have the score directly. That is the one disadvantage which I faced here, because Mistral isn't doing that one thing. /n, it is using some other places as well, so it is not able to provide the correct value, which is 0 or 1. So what I would suggest is have a rather a list here. Okay, so what you should do is, this is the logic which I would suggest you all to do. Have a list here, try to provide 1 or 0 based on your assumption. Okay, so let me go through the correctness here again. I think we all know that it is a correct one, right? So let me say if the same is repeated for coherence, but it is not relevant. Okay, it is not possible, but I'm just saying it is not relevant. So what I will do is, I'll have correctness as 1, relevance as 0, and coherence as 1. I'll repeat this all for all the samples, obviously, and based on that you can calculate the total and divide it by the number of samples, which means you will have the accuracy of each metric. So this is how you need to go about your evaluation. So yeah, that is about the evaluation, guys. We have Langchain, and yeah, there are some other frameworks as well which I have heard a lot about. I'm exploring on that front, so if I get anything I'll let you know, but this is very helpful. Like you can see, right, it is saying consider you have a summary of 15 lines and maybe an input of 30 lines. It will take a longer time, right? It will do it in 2 minutes. So yeah, it is good to have evaluation of LLMs, and even in that evaluation of LLMs is all you need video. I would have said that auto human eval is the way to go, and this is auto human eval. I'm gonna show you all how you can train your own function calling LLM, where I'll also cover how you can build a function calling dataset and fine tune on top of it. Now let's start with an explanation of what is function calling in LLMs. Function calling is a concept where if you have an LLM which has a tremendous capability, but to use it to its maximum potential, you can use function calling. For example, if you want to use your LLM to open a notebook, for example, in your system, for example, Notepad, okay, by default it can't. But when you provide a tool for it, it will be able to do that. And that is what happens with function calling. So for example, if your LLM is here, you will provide it with n number of tools actually. Okay, keep it like this. So let's take 4 for example. For example, this LLM will be able to do able to act as a calculator. Okay, this LLM will have access to your files. Okay, probably access to your calendar, and then access to internet. Okay, all are tools here. Okay, these are all tools. So for example, if I have a use case of opening your own favorite file, okay, let's say you have it as favorite.txt. Since it has access to your files, it will be able to open the favorite.txt by itself by using this files tool. Okay, and if you have some calculations, if the LLM can't directly do it, it can use the calculator. Okay, and then let's say you have some questions and it needs to search over internet, it can use this tool, internet tool. And then if you have some doubts in your calendar, for example, what are the meetings I'm taking today, it directly can't say because it doesn't know what is your time schedule, but when you provide the calendar it can do. So this is function calling actually. Okay, this always has the power to do a lot of things, but we are aiding it. These tools will aid it to use the power to the maximum potential. That is what will happen with function calling. Okay, usually function calling will be provided with the help of JSON format. The tools will be provided with a JSON format. Okay, and then we'll provide some kind of input, and then it will try to make a function call. Okay, so this is how it happens with function calling in LLM. Okay, now let's see how you can build a function calling LLM dataset, and then we'll move on to how you can fine tune your own LLM with the help of such a dataset. Okay, so now what I'm gonna do is I'm gonna take the dataset which I used, which is Lilac AI Glaive function calling dataset. Okay, so here we are concerned about this specific column. Okay, for this, what I'm gonna do is here you have your from system and value, these kind of things, right? But when you are building from scratch, this won't be needed. I'll show you the exact format which is needed. Okay, just give me a minute. So here is a sample dataset format. So from we'll start with the system prompt, okay, which will be your function calling tool being provided. So here we'll provide it as follows. Okay, first you will provide your simple system prompt, for example stating that you are a helpful assistant with access to the following functions or tools, if you want to put that way. And here is the tool, whenever it is required, use them. That's what we are saying. Okay, and the name is calculate median. Description you should provide, which is calculate the median of a list of numbers. And then a parameter is required. In the parameters, the type is object always. Okay, and the properties would be numbers, which is a type as array, which means it will have a lot of items in it, and each of the item inside that is number. Okay, and the description is a list of numbers. Okay, so I'll put it this way. So let's say for your function it is calculate median. If you have a function like this, okay, and it takes array of numbers, and whatever it does inside doesn't matter. So what you need to provide is first the name, okay, and a description of this function. And then what you would need to do is you will provide the parameters next actually. Okay, parameters, where always the type will be object. Okay, and the properties of the parameters would be, okay, here we have array, right? So it will become array or numbers, whatever you want. For example, numbers, Okay, what is the type of it? It is an array, right? It's not list. Okay, it is in Python, it is list, but usually it is called array. So you'll provide the type as array, and whatever item is there inside that, because array will have list of items, right? 1, 2, 3. Those will be integer. Okay. Along with this, you will also provide a description for the parameter, which is the list of numbers. Okay. So this is how you need to frame a function. For example, another function, browse website. Okay. Uh, Web URL, we'll put it that way. So it will become something like name browse URL. When I'm doing this, probably you can also try to write alongside me. Okay, it will be a very good practice for you. And then for description, I'll just keep it as, like browse, something like that, but it will be very detailed. You can understand the point, right? It's just for explanation. And the parameters would be something like type is object. Okay, and then we would have the properties here to be just a URL, right? So it will be URL. Okay, and then here the type would be string, and the description would be the URL to browse. Okay, and that's all. You would have written some logic in here. So if you make a function call with the approximate URL alone, it will be able to do that. So now you can ask, okay, Vasanth, this is very simple. Where you can use this? For example, if you are building an agent which will take a question, and based on that it needs to make a search. Okay, so once you find a URL, you need to scrape the URL, right? So for that and all, you can use this browse website. So you will be able to create your own custom tools. Okay, I'll also provide this dataset format for you all to like work around. Okay, but right now what we'll do is we won't have this specific format data, so we'll make a data set to begin this format. Okay, I'll show you how I did that. So for this, what you can do is the nearest data set coming even close to this would be this dataset lilac glaive function calling, right? So whatever format which I showed now is known as chat ML format. Okay, so for this you will also be required to format your dataset into chat ML format, and that is possible with the help of Hugging Face apply chat template method. Okay, so now what I'm going to do is show you all how you can format this dataset and then fine tune it with the help of Unsloth AI. Okay, so for this I'm gonna use Kaggle kernel. Okay, for fine tuning I'm gonna use Kaggle kernel because I'm bored of Hugging Face, to be honest with you. Sorry, not Hugging Face, Collab. So for a change we shall use Kaggle. I'll put the accelerator to be GPU T4. Okay, and here now we'll start the coding part. So first we would be required to install unsloth. Okay, so unsloth is not defaultly available in pip, so we'll be installing it like this. Unsloth collab at git, the source git. Okay, along with that we'll also install transformers trl and 1db. Let's run this. Okay, next we would need to make some imports, and I'm gonna show those now. Okay, these would be the imports which is required from unsloth. Import fast language model. Oh, what happened? Fast language model, and then we would require trainer. Is it even like this? From TRL import SFT trainer, and then we'll also import training arguments from transformers, and then we would need dataset as well. So for that we'll use load dataset function, and then finally we'll import torch. Okay, all are done now. Let's also run this. Let it keep running. Okay, now first we need to load this dataset. Okay, so what I'm gonna do is I'm just gonna copy this, and then for this what you need to do is just call dataset equal to load underscore dataset, and then have this and provide the split to be train. We need just a training dataset, so for that we'll be providing split as train. Okay, so we can run this also. Then now it is building unsloth. Okay, unsloth, if you're wondering, is a library which will enable you to fine tune your models with very much higher speed. So it will be around 2x to 3x speed based on the number of parameters there in the model. Okay, so to now create the data set, first what you would need to do is first, you should create the tokenizer, and it is required that you can use the tokenizer from unsloth itself. So for that what we do is model comma tokenizer. This is how you can create your model and tokenizer by using unsloth. Okay, we'll be calling the fast language model. uh, it's funny or ironic, like it's fast, and that's why they've provided as it is fast language model. And in this you would need the following parameters. What is your model name? The model name we can provide it as unsloth's Gemma model. Okay, we'll provide unsloth slash Gemma. Let's fine tune a small model. Okay, it will be like faster for us. Gemma 1.1. There is 1.1 which came into the picture, very latest one. Here it is, 2 billion. Let's use this model. Okay, so here what we can do is we can provide this one here, and then we can also provide the max sequence length to be 512, and then load in 4-bit is true, and then there is d type to be none. Okay, so now the imports are done. Let's run the dataset as well, or load the dataset rather. Okay, and we'll also load the model and tokenizer. Model and tokenizer are being downloaded now. It's high speed. So once the model and tokenizer are done, what we'll do is we'll call the model to become a LoRA model. So for that, what you need to do is call fast language model dot get underscore peft underscore model. Sorry. And here I'll just provide it from here itself, model, and then you need to provide your rank. We'll provide it as 16. The LoRA alpha will also be 16. And then your LoRA dropout, let's provide it as 0 itself here. And then we have the bias is equal to none. These are all very usual, right? And then we would require our target modules. Target modules is provided, and then we require our gradient checkpointing. Use gradient checkpointing. So it will just like checkpoint the gradients whenever there is a save step being enabled. So that is why use gradient checkpointing, that is set to true. And then we'll set the max sequence length that is required here. Okay, we'll set it as 512. And then here there are some other additional parameters you would require to set, which is use rs LoRA, set it to false, and then also use loft q config. Sorry, loft q config. Use won't be required, and also provide that to be false, because if you are gonna load a model unquantized, and if you wanna get the best output of a quantized model, right? Load the model unquantized, use loftq config, provide a loftq config for it, and it will give the best result for you. Okay, now let's run this. It is giving me some errors. Okay, it has said, right, like it has patched 18 QKV layers. Okay, which means we are done with that. The next step is to format the dataset. So for this, what we will do is we'll use the chat templates which is available in Unslot. From unslot.chat templates, we'll use the function get chat template. Okay, in tokenizer, we'll apply the get chat template function. Okay, so whenever you call the tokenizer, it will format to this. So for this, we require to provide the tokenizer and the format in which you need to apply this chat template. For this, we'll use chatml's chat template format. Whatever format I showed you is chatml format. Okay, and for that there is a mapping like this which is required. Okay, I'll show you that now. The mapping is as such that here, not here, where is the data set? Yeah, here it is. There is from in here, right? This from would become your role and the value would become your content. Okay, and whenever there is user, where is the user here? Human, yeah, this human would become your user. So the value of this human, right, it will become like user, and then the user question will be provided, and instead of GPT it will be replaced as assistant, and then the assistant's value will be provided. So it should require dictionary. Okay, and then you can see now, okay, this is the dataset format available, but right now I already said how the dataset format should be, and now you'll see we'll get the dataset in that format itself. Okay, we'll also map the EOS token. to true. Okay, now we need a formatting function. So for that I have written a formatting function here. What it will do is it will go through the conversations, because if you see here, the column name is conversations. In the conversations it will go through the each of the conversation, and it will try to apply the chat template there. Okay, it won't tokenize, because we have set here tokenize to false. Make sure that the tokenize is set to false, because the tokenization will happen during the trainer is called. Okay, not here. And map it to a column known as text. Now we'll run this. It will take probably 10 seconds, and in that what we'll do is we'll do a print of the data set of text of 0. Okay, we'll see uh, of 0. We'll see here. Now you can see, right, it is following the same thing which we said there. Okay, whenever there is the tool, first it is provided here. Okay, that is an IM start, and then once it is done you'll do an IM in there, and then another IM start, the user related contents are provided, and then there is an IM in, and then the assistant will start there. So there is an IM start there, and then the function call will be completed, so there is an IM in, and based on the function call the system will try to answer. That is what here it mentions, and the system will say the median is 5. Okay, and then the assistant knows that okay, now the tool says that the value is median as 5, and then now my job is to say the median of your list of numbers is 5. So this is what is the dataset format is. And now that we have completed the dataset, there are two separate steps for us to do. The first step would be to log into your 1db. So import 1db and 1db.login of your key. Okay, I'm not gonna show the key here, but you can take your key from here actually. 1db. Once you create your account, what you need to do is go to your personal, click user settings, yes, and then click here, there is reveal API key. Okay, you can just click reveal API key, and it would ask you to log in. Just log in with your mail ID. Again, if you go there and click API key, it will reveal your API key. Okay, you can just copy that and paste it there. Okay, I'm not going to show that now. So now this login is completed. You can provide your key here. Okay, I'll also provide a Hugging Face login here. So for this, what you can do is go to Hugging Face, click your profile, click whatever profile you have, and settings, click access tokens, and make sure your access token is here, and paste it here. Okay, so now this is also done. So now what we'll do is we'll create the trainer. For trainer, I have already written the parameters, so I'll just paste it here. So we are using SFT trainer, in which we'll provide the model, the dataset text field, max sequence length is 512, packing is set to false, dataset num process is 2, which means there will be 2 processes which will do the tokenization. And for other parameters, I think you might all know, max sequence length is 512, which means there will be only 512 tokens, and then the packing is set to false, which means there will be no packing. Packing, what it means is, for example, if you have one data, it is 256. Okay, it will try to pack another 256 sequence by adding an EOS token after that, but we are setting it to false. We are also providing the tokenizer and then the training arguments, where we are providing the batch size to be 8, which means for one step it will train 8 samples, and at each steps back propagation will happen. For example, if you want to fasten up your training a bit more, you can try to provide the gradient accumulation steps to 2 or 3 if you're wishing to do that, but 1 is always good actually. Okay, and warm up steps is set to 10, which means for the first 10 steps it will just warm up in the training, which means there will be no back propagation, there will be only forward propagation. Okay, it will just give a basic understanding of the data. And then you have your max steps to be 1000, and then which means there will be only 1000 samples processed. There is a lot of samples here, but there will be only 1000 samples which will be used for training. When you are training the model, make sure that this is commented. Okay, and then the learning rate is 2e minus 5. We are checking if BF16 is supported. If BF16 is supported, we are training it in BF16, or else we are training it in FP16. You can also provide the output directory. I have provided whatever I feel is very good. And optimizer is AdamW 8-bit optimizer, which is an optimizer created especially for quantized model training. The number of training epochs is 1. Push to hub is true. We are reporting it to 1 dB. And then here, if you see, the logging steps is 50, which means at every 50 steps, the loss will be like printed there. Okay, let me start the training here, and I'll see you all once the training is completed. Okay, so the training was completed in around 2.5 hours. Okay, so the training loss was also good. It started with 2.5 and ended up with 0.45. That is a pretty good convergence for a 2 billion model, that too in a 2 billion model being probably in 4-bit. It is, I guess it is a pretty good result. Okay, and I'm pushing the model to hub as well. I pushed it. Okay, and the tokenizer was also pushed to the hub. You can provide that here, for which you should provide your username along with the repository directory. Okay, for inference, you can just provide the input string with the tools and the format I said, and I'm expecting the model to say something, but it didn't give good result actually. Okay, so it didn't give great result. For example, here you can see it called the calculate median of numbers, and it said like it is 5 here, but the training was not that much long. If I had done the training for a long time, it would have done a pretty good job. Okay, hello everyone. With the advent of LLMs, there have been lots of use cases which have opened up recently, and at times we tend to do over engineering. So I thought, let me make this video inspired from one little coder, the app levels for LLM. So what does it mean? LLM can be used to build different apps, but all fall under these 5 categories, and the hierarchy goes as follows. The first one, which is at the bottom, would be the general QA, and then the next one would be chatbot, and then RAG, then agent, then LLM OS. Okay, this is the hierarchy from bottom to top, where the least complex and least powerful in the hierarchy would be general QA. The most powerful and the most complex one would be the LLM OS. Alright, so in detail in this video, I'm gonna show you about the characteristics of each of these levels and what can be achieved out of these levels, and when you should use which level of application to your application actually. Alright, so that's what we are gonna see in this video, and like I said, these are the 5 levels of LLM apps which is existing in the current world. Probably the hierarchy might increase because even LLM OS is under developing stage currently, so there might be some other things which could be included in the hierarchy lately. For example, AGI, which is not coming anytime soon in my opinion, but if it comes, that could be the next step in the hierarchy. But at the rest, these are the things which are available right now. We'll start with the general QA. So what is a general QA? It is about answering a question based on self-knowledge or given a context. So what do I mean by that? Let's see about that now. Okay, you see, if I ask a question stating that what is the planet we live in, okay, if I ask this question, the LLM, whichever LLM is there, it's gonna say easily that it is gonna be Earth, right? This is no context question answering, okay? No context QA. That is what is the first one. Or else even there is another thing which is known as context question answering, which is, for example, I'll say okay, there is a paragraph about what is IPL, and if I ask what is the full form of IPL, I'm assuming that the model doesn't know, okay? What is the full form of IPL? Now it will answer the question actually that it is Indian Premier League, something like that, okay? So that is context. There are some other examples as well. For example, reasoning is also a type of QA, okay? Reasoning, context question answering. Usually with reasoning you will need a context, because for example, if I say I have 2 apples, my father gave me 2, how many do I have? If I ask this question, it will say okay, 2 plus 2 equal to 4. It is reasoning it, right? Okay, gave, which means I need to add, okay? This reasoning is happening, right? So these are the types of QA at the top. But if you see, any traditional NLP task can be seen as a QA task. For example, if I say I like YouTube, okay? If I say this and I ask what is the sentiment expressed, if I ask this question, right, of what is the sentiment expressed, it is going to say positive, okay? And we can also force it to generate in however way we want. For example, I have 6 categories here, okay? I have 6 categories here. Find the sentence of which category it falls under and say only the category. If I say that, it is gonna work as text classification. Similarly, we can do NER, we can do summarization, okay? There are lots of tasks which all are possible to do with the help of QA, because the question will be our instruction, alright? So any traditional NLP task can be seen as a general QA task, okay? So here the in context memory is not there, the external knowledge is not provided, tools, nope, peripheral tools, no. These are some of the characteristics in which we are going to base these hierarchy, and like I said, this is the least powerful, but yet it would have seen, right? If you have any task for you at a minimum level, then you can do it with general QA, okay? All you need to do is provide your prompt to a LLM and then you'll get your answer, okay? But it doesn't have any of these, okay? Now what if you want to remember some of the context you had, like a conversation? That is when we'll move on to the next level, which is chatbot, okay? Chatbot is just an extended QA, okay? It's just an extended QA which will have memory of sequence of conversation. But like I said, anything is applicable to chatbot as well. For example, if I'm saying summarization, on top of that I can ask a QA based on the summarized passage. If you see ChatGPT, the original ChatGPT 3.5 was just a chatbot. Now it is not a chatbot. I'll say what it is. The original ChatGPT 3.5 is a chatbot, okay? Because you can ask it to summarize, you can ask it to answer your question, whatever you have as a task, you can do it with the help of ChatGPT, and also it remembers your conversation, and that remembrance is nothing but in context memory, okay? So in context memory is there, but external knowledge is not there, tools is not available, and peripheral tools is also not available. And that's why we have added answer to the prompt. This is not like an RNN architecture where it will retain its memory state, okay? So that is the difference between chatbot and QA. A QA, where it will require you to remember the conversation, that will become a chatbot, okay? So when you have a requirement for remembrance of memory, then alone you need to go for chatbot, or just go for QA itself, okay? Now it is going to be a step up, okay? What if your LLM has a context which it doesn't even know? You can't provide a context explicitly, but you have a data source, okay? For example, if I say this is a document, okay, and each line is a page, okay, and each line inside line there are some group of paragraphs, okay, and this is how the document is right now. If I ask a question from here, right, the context length is going to be about 10,000 or 20,000. So the model can't answer. This is not going to be the context. This can't be the context. Okay. So for context, what we are going to do is we are going to do a retrieval process. Okay. So what happens in this retrieval process, right? So now what I'm going to do is I'm going to create a document just of 3 pages. Okay. And here the pink page is my answer. Okay. So given a question, so whatever question I have of what is some blank, okay, and the most relevant one would be this one, this page, and then the second most would be this, and third most would be this. So what I will do is consider that those are paragraphs. Okay, I'll just provide the second paragraph as context along with my question. Again, if you see, this is QA, but the context finding process is automated. Like I said, everything is built up from QA. Okay, and here RAG is just an extension where you find your context automatically. Okay, so that is RAG, retrieval augmented generation. You will retrieve a context which will augment or help in your answering process. So that's why it is retrieval augmented generation. And here, like I said, it is a chatbot or QA system with an external data source for knowledge. Because you can still apply this for chatbot where you can have a sequence of conversation based on your RAG system as well. Okay. So for a single QA system or a chatbot, if you add an external source of knowledge to find the context for a given question, it is going to be a QA system or a chatbot which is done with the help of RAG. RAG is just an extension. Okay. Here we have an architecture. You have your database or documents, your API, whatever type of data you have, you will index those. Okay. Where you will compute your embeddings. Okay. So this is your vector store. And what happens is, if you have a question where you know that you can't provide a context and you know that the model wouldn't have a knowledge of that, then only you are going to use this RAG. Okay, and it will try to find the answer based on this vector store. Okay, and then what it will do is it will go to the LLM where the prompt, your query, your relevant data all are provided to the LLM, and it will provide the response to the user. Okay, when you need to use RAG, only when the model doesn't have a knowledge for the question by itself, or you can't provide the knowledge by yourself explicitly. Okay, if any of these two are possible, you should look on to a normal chatbot or QA system, because this is more complex than a chatbot or a QA system, and it is also more time consuming. Okay, so RAG when can be used? When you want to chat with a PDF or a doc, any type of document, or you want to chat with websites, your databases, anything in which there is a huge context and you can't find which context you want. Okay, that is when you're going to use RAG. So for this, in context memory, like I said, if it is a chatbot, you will have, and if it is not a chatbot, you won't have. So it is going to be yes or no based on your system you're going to choose. And external knowledge, it is going to be there for sure. That is what is going to characterize this as RAG, but tools won't be there and peripheral tools won't be there. But probably at times RAG might have some tools. That is when we call it a chain. Okay, a chain where if you want, you can load your websites with the help of tools like, for example, Beautiful Soup, and then it will perform this RAG architecture. Okay, so at times this is possible, but at time that time it is known as chain, and chain is not very useful, because that is something you explicitly define that okay, this is the procedure, and you need to solve the use case based on this chain. Okay, regardless of if the chain is correct or not. And that is why there is this architecture which has come recently known as agent, where it is an upgradation over chain, not RAG. Okay, this is an upgradation over chain where we'll say that okay, your tools are here. Okay, your web selection tool, your document loading tool, whatever tool. For example, this is a PDF loader tool, this is a CSV loader tool, this is a database related tool, this is a web-based loader tool. Based on the type of input, it can choose whatever tool it wants by itself, and then it will augment its knowledge and then answer the question. This is a simple explanation of why this is an upgradation over the chain, because it can do the task autonomously, where the chain has human intervention, because human is what is creating that chain. Okay, but in case of agent, you will just provide the tools in an environment where the agent can use that. Okay, this environment is nothing but your agent executed environment. Okay, so that is about an introduction to agent. Okay, so given an input, the agent, which is nothing but your LLM, which has all the tools in its toolkit, it will find, okay, which tool should I use now, and based on the tool, it will use the tool with the help of a concept known as function calling. And if you want to know in detail about function calling, I have made a separate video on function calling, please check that. And in nutshell, what is function calling is, each tool 1, tool 2, and so on and so forth, will be just Python functions. Okay, and this function calling is nothing but it will just provide this function and will parse that and do a function call based on the parameters it provides here. Okay, so that is what is function calling here. For example, if I want to load a document, it will be for example PDF of file path. Okay, so it will call PDF of some name dot PDF. Okay, so it will load the PDF documents by itself. We are not saying. Okay, same goes for any document. So that is how agents work. So this is a simple use case. You can do a lot of things with the help of agents, and lot of videos are coming up in your way where I do a lot of complex tasks with the help of agent, and already have done some things like stock trading analysis and lots of other things. Okay, when you know that these are the things which are required to do a task autonomously, that is when you will go to agent. Okay, a task which can be automated without any human intervention, and only when this is required. Okay, when you require to do an automation and you know that, okay, when I provide these specific tools, I need not intervene in there, then only you are going to go for agents. Okay, so here you'll have it in context memory, yes or no based on your task, external tool knowledge, yes or no based on your task. Now you might wonder, okay, now I was emphasizing on tools, so here I didn't provide any tool. Yes or no is what I have provided. Any LLM which can do a given task autonomously is an agent. That is what is the definition for agent. And people are confusing over internet if you wanna check, but this is the exact definition. If you see, if I give summarization as a task, right, it doesn't need any of these. In context memory, external knowledge, tools, nothing is needed, and it is also an LLM, it is also an agent. So that is why I say everything is built up from QA. QA is also an agent, a question answering agent, right? So here, but there is an opportunity that you can do complex tasks by just adding tools to it. Okay, but peripheral tools are not still provided. Now you might be confused, okay, he's just repeating the same of again and again, and here is the difference. If you are doing a normal QA, and let's see about the difference right now. Okay, if you are doing a normal QA or a chatbot, this is gonna be your thing. You'll give your prompt, you'll give it to your LLM, and it will give your answer. And if it is a chatbot, you will append your answers and the prompt to your prompt again. That is gonna be chatbot. What if it is RAG? You will provide the prompt, which is your question, and what it will do is you will try to find the relevant context from here with the help of retrieval process, and your context and prompt are together sent to your LLM, and the answer is obtained. Like I said, again, if it is a chatbot system, you will add those to the context again. Okay, but if it is a agent, what you will do is you will provide your prompt. Alright, it has access to reasoning by itself. It has access to the memory, which is nothing but a vector store for RAG process. Okay, it has some other tools as well, for example executing Python program or whatever it is. So what it will do is it will try to find, okay, which process I need to do, and then it will do the action and it will say the answer as well. Okay, everything is done by the agent itself. So this is how is the difference between agent, RAG and the previous QA or chatbot system. Okay, so this is the current scenario in the world. Okay, this is the most complex architecture which is commonly used right now. Most complex but commonly used. So for this you have packages like CrewAI which you can use, alright, or AutoRAG as well, but Langchain is also good if you want to create by itself. There is a step up which is done right now, which is LLM OS, okay, which is currently under development, alright, where LLM will control your OS. Here is an architecture from Andre Karpat, okay. He is the one who first defined this, where you will have your LLM loaded into your CPU, which is occupying your RAM as well, where it will have access to your file system. It will have access to some tools, whatever tools is required, for example calculator, Python interpreter, shell, or your Chrome, your browsers from here. Because it has connection over net, it can do some browsing as well. Probably if required it can access some other LLMs. There is some peripheral devices as well which it can context with, for example video, audio, for your mic, your camera. It literally has access to anything in your computer or your laptop, whatever it is. Okay, if you see, in a way everything is going to provide a data that is going to be your context. Yes, this is going to be your tool. Okay, your context is obtained from either video or audio or even normal text. Okay, and that is provided to your LLM, and these are all tools. Okay, these are all tools, and your LLM is going to take an appropriate action and answer your question. If you see, this is just an extension of your agent, but there are multiple agents in here. That is one, multiple agents, and two, it has all the tools to control the OS. Okay, that is when it becomes LLM OS. So the only difference between agent and LLM OS is that this agent is a general backbone kind of an architecture which can be used for any task, and this LLM OS is an architecture by itself which is used to automate your whole computer. Okay, so for this it requires all of these things. There is no option of no and all. You will need in context memory, you will need an external knowledge, you will need tools, and you will also need peripheral tools. It will require all of these. So this is the most powerful and the most complex, because it is gonna require a lot of things for you to do. Imagine you need to create hundreds of tools. Okay, your file system is huge, so you need to compute embeddings for those file system, so that if you want it to open a file or read a file or write a file, it be able to do that by itself. Or if you want to chat with video or audio, it is going to be a huge context. So there are lots of complexity in this. Okay, right now people are working towards this, and recently you could have seen the Copilot, which can see what you're doing, is coming up from Microsoft. That could be a step towards this LLM OS, and already I've made a video of LLM OS with some 3 sample tools, but it is not gonna be enough. All right, you're gonna need a lot of tools, but that is a sample of what you can do with the current LLMs to become an LLM OS. Okay, but if you see as a common thing, right, everything is gonna be a QA or a chatbot. That is the base architecture. All right, and the way you're working is, if you want to automate, you are going to add some tools. If you don't have a knowledge, you're going to augment your knowledge, but everything is just an extension of QA. Okay, so that is why it is very important for you to have an understanding of how QA or chatbot works and how you can extend those for your task. Now I'll say when you need to use what. QA, when you have a context by yourself explicitly, or you have just normal reasoning, or you have general QA, which does not require just which has the knowledge by the model itself. Okay, for which if you want to answer the question, the model has the knowledge to answer the question. That is when you'll use the QA. Okay, chatbot is just when you want to remember the sequence of conversation. If there is a sequence of conversation, then you will need chatbot. Okay, RAG, if you want to find the context. Okay, that is when you will go for RAG. If you want to automate your process, knowing that you have tools and it is not solvable by the previous task, by previous levels. Okay, because like I said, even summarization is an agent, and if you're gonna use a CrewAI to build an agent, it doesn't make any sense. Okay, you can just give a prompt and it is gonna be a summarization agent. Okay, if you need some automation where you have all the tools and it is not solvable by any of the previous level, then is when you will go for agent. And LLM OS to completely control and completely automate your life probably in the future, but right now completely automate your computer or OS. Okay, so these are the levels, and these are the things you need to do when you have a specific use case. All right. Why is it this? Because I have seen people doing over engineering. Okay. For example, for summarization, I have seen people using agents. Okay. Why do you need summarization agents when you can just use a simple prompt? Okay, they are using complex architecture for no reason at all, and we don't know what is happening beyond the agent architecture. Whoever creates it, for example, CrewAI, AutoChain, or any other framework, doesn't matter. But they are all using F strings again by using Jinja template. That is another thing. But again, see, we don't know what is happening behind. Okay, so we should not do over engineering when it is not required. All right. So that is why I made this video of what is there in different levels and when you can use which level. All right, and it will also say what state we are in the LLM world right now. We are gonna see about how you can build your own RAG from scratch without using any Langchain or Llama index or any other libraries for that matter, for example, PyData. In this video, I'll show everything from scratch just by using Hugging Face and their own ecosystem. We won't use any wrapper. The idea behind building this kind of a RAG framework, that too from scratch, is that you will gain control over what is happening behind, and this will benefit you in different ways. Like, you will understand what is going behind. Also, you will be able to customize it wherever you want and however you want. Now let's start with understanding about the workflow of how a RAG framework is built, and then we'll move on to the code. The architecture starts by loading the PDF, and followed by which we need to chunk the PDF file into smaller documents with the help of the character text splitter, followed by which we will be creating a vector store which will be saved locally by using PyTorch. And then once these are done, we can move into getting the input query from the user, computing the embeddings for it, and we'll retrieve the top k results based on that by using the vector store, and finally the LLM will provide the answer. Now that we have understood the workflow of how a RAG framework is built, we'll now see how you can build your own RAG framework with the help of just open source LLMs and libraries without any framework. All right. So first step, as we all know, it is to load the file. And for this, I'm using PyMu PDF, and you can use whichever loader is you think is good. For me, in my experimentation, I have found that fits, which is PyMu PDF, is good. All right. So the first function would be to load the PDF. All you need to do is provide your PDF file path. And now what we'll do is we'll create a file or a list for the file known as contents, where first in fits there is a function called open, Once we open the file, it will have the list of documents in it. We'll go through each of the pages and we'll get the text, and all we are doing is adding a slash in and then providing the content so that there will be a split among the contents. Just to make sure that there is a split, we are also adding slash in dot join of contents. What it will do is, in the contents there are list of pages content. Okay, for example, first page content, second page content, everything will be there. All of those are combined into a single string document. All right, so all we need to do is just call load pdf. Okay, we'll see that as well. Now it has loaded. I'll show you all. Okay, docs, and as you can see here, this is my dummy resume I have created for some other video. And now we have the first one, which is to load the document being ready. Again, now to see about the customization, you can load JSON, you can load CSV, you can load databases, whatever you want by yourself with customizations. For example, I added 2 slashes in here, which is not possible when we do use wrappers like Langchain, Llama Index, or people who are wrapping even on top of that. For example, Data and CrewAI and so on and so forth. All right. So we are just focusing on how we can customize it. The next step would be to chunk the data, right? So for this, we are having a function known as split characters, or also you can have it as chunk documents. We can put it whatever we want, right? Again, our own file, we can do whatever we want. So here, all we are doing is, first, we need to create the splits. For example, in recursive character text splitter, how it happens is, I'll write it in here. For example, I have a string like this, right? Not this. Something like this, all right? So this splitter which we have written here is a recursive character text splitter. What it will do is, it will go through the splitter. So for example, we have the chunk size at as 5 and the overlap as 2. What will happen is, I'll just take Vasanth is say, okay. Vasanth is saying, we'll consider this string. The list will be like, let's take first 5 letters. So it will be VASAN, and then a new one where it will be TH space IES space, and that's all. That will be the next one. And then the next one would be SAYIN, and then the next one would be G, given that the chunk overlap is 0. If I had kept it as, we'll have it in here as chunk size is 0 and overlap is 0. Oh, sorry. Chunk size would be 5. All right. So now let's take this case where I have overlap as 2 and the same chunk size. Okay. So what will happen is, the first one will remain the same, which is Vasanth. And now instead of just generating TH, it will generate SANTH, and then in this one it would be NTH space I, and then it would become something like H space IS space, and then it would become IS space SA, and then SAYNG, something like that. Okay, so this is how the split happens for chunk size is equal to 5 and overlap is equal to 3, not 2. I guess I took 3. Okay, so this would be our example for this, of how things work when we are doing chunk overlapping. So what it will do is, it will just make sure that the start, this is a safety function to ensure that there is text in there, not empty string. Okay, so we are checking if 0 is less than len of text, which means that is there. The end would be min of start plus split length comma len of text. So let's say the start is 0 now and split length is 5 and the len of text is something like 10. Okay, which means we can split by 5. But what if it was the length is 3 and I gave 5, so it should become 3, right? The split shouldn't happen. So that is why we have the split length. And what we'll do is we'll just take start and end here. That's all. Okay. Now, to change the overlap, right, you need some overlapping, which means you need to go back in your start. For example, I came from 0 to 4 in index, and then now since my overlap is 3, I need to jump from 4 to 1, if I'm not wrong, or 2. Okay, I hope you get the point. So what we are doing is we are just changing the start to split length minus overlap. Okay, so that the start will be moving on with 2 to 3 index. So it will be a difference of 5 minus 3, which is 2. It will move by 2. Okay, so that is how the split will happen. And now we'll do that as well. We'll keep it as chunk size. Okay, now it is chunk documents. And guys, these kind of documents or these kind of videos are not available over internet. So if you are like this kind of video, please let me know by tremendous amount of like and comments, which will make me know that okay, you guys like these kind of videos, and it will help me to serve you better with more videos. Okay, now the splitting documents have happened, and let's see what is there in there. Okay, so you can see, right, the split has happened, and the last one alone has a very little data, but there is around 1 2 3 4 5 6 7 documents in there, and I have just kept it to 7 so that it will be very fast for us to move on to the next steps. Let's see about a simple vector database, how you can build that. We are not using files because if you want to use files from scratch, let me know in the comment section. I'll make a video on that. But using files from scratch is pretty harder than rather than without using Llama Index or Langchain. So what we are doing here is we are just gonna use torch file to save it. Okay, torch file to store the vector store. Torch save vector store. That will store our vector store. Okay, so for this, the steps would be first compute embeddings for the document, make a embedding dictionary where the key will be the chunk and the value would be the embedding, and then save dictionary as torch file. Okay, so this is how this creation of vector store happens, and now we'll see the code. Okay, so the source function here is create vector store, which has all other functions being called inside. So first what we'll do is we'll have a simple list known as chunk embeddings, where what happens is first we'll create a sentence transformer, whatever model is chosen, and that embedder, what it will do is it will embed all the chunks. Okay, chunks comes from this one. Okay, you already created your chunks here, right? So this is your chunks. Let me rename this as well, actually. Chunks, and here also it is going to be chunks. Okay, now this is also done. And what happens is you'll go through the chunks, and each chunk will be encoded and it will be stored as a tensor. Okay, so for that we need to convert it into tensor. We'll append that into this list. Okay, chunk embeddings. Then this, once this computation of embeddings is completed for all the chunks, be 1000 10,000, we'll call this function of store embeddings as dict, which will take two parameters with it, which is embeddings list and text list. Text list is nothing but your chunks list. Okay, so here we'll be providing our chunk embeddings and chunks. So what it will do is it will try to create chunk is to chunk embedding. This kind of a dictionary will be created, and we'll save that with the help of save embeddings.pt to pt file, which is nothing but calling a toss.save function. Okay, all you need to do is provide a dictionary and then a file path, which is just embeddings.pt. You can keep whatever you want. Okay, we'll call that. And right now, for simple things, like, now we are not focusing on accuracy here, because we all know that if I use MXBAI or any other bigger model, the performance is going to be good. So right now I'm just going to take a small model, all many LLMs L6v2. So the process of creation of vector store is happening, and as you can see here, there is also a progress bar. Again, see, this is something you get with customization. I don't know how much customizable it is with Langchain, but here you can see, right, we can just change the progress bar. We can provide descriptions here upon our choice. Because I gave it as computing embeddings, it is there. Let's say I'm saying Vasanth embeddings. It will say Vasanth embeddings, right? So that is what I love about customizing from scratch. And also you have a better control of what is happening inside. All right, so now you have created your vector store based on the documents which are split before by using the text splitter which we created by ourselves. And then now it is time for the most important part, which is to create the retriever. All right, so again here we are going to take a single function which is retrieve relevant docs, which is taking 4 different inputs or parameters. Okay, embedding model, your embedding path where you stored your embeddings, your query, and what amount of retrieve, like how many do you want to retrieve, how many chunks, is it 5, 4, 3, how many ever you want. All right, so what happens is, first we'll create the embedder, we'll load the embeddings, and we'll get the chunks first. Okay, because we need to compute the similarity between the chunks and all, right? So just to get and it is also a dictionary, you can just index the dictionary with the help of key only, right? And chunks is the key, so that's why we are taking the keys here. All we are doing is, first we are encoding the query, okay, and then we are computing the cosine similarity. Okay, that is where the retrieval happens. So for this, first we are making sure that the top k is lesser than the number of documents there in the dictionary. For example, I have only 5 chunks and I'm saying I want to retrieve top 10. There is no point, right? There is only 5 chunks. So we are just checking the top k there, and it also ensures that there is no error coming up. All right, both are advantages there. And here we are going through the chunks, okay, and we are saying computing similarity is happening. What we're doing is, in transformer, for sentence transformers, there is a util file, okay, util function, which has a function called cosine, which is nothing but your cosine similarity. What we are doing is simply comparing the query with the chunk embeddings. Okay, whatever embeddings is there for a respective chunk, we are comparing it, and of 0 will give you the score. Right now all we are doing is we are appending those scores into a list. Okay, because in torch there is a function called top k, which will help us to get the index of top 5 maximum numbers or top 10 maximum number given a k. Okay, so all you need to do is, since we are going to use torch, we are going to need to convert the list into a tensor, for which we'll call torch.tensor of scores, and we'll get the top k chunk indices with the help of torch.topk function, where you'll provide the scores as well as your top k value, where we are calling the indices and we are converting it into a list. Okay, now you have the top k chunk indices. For example, I have 7 documents. Top 3 document indexes are ready, but I need the top k chunks, right? So we are getting the chunks of these indexes. Okay, because the chunks and the embeddings are gonna have the same length. Okay, so if I get the max indexes of embeddings, it also means it is the max embedding of chunk. Okay, so that is how this function work. And finally we'll return the top k chunks. All right, so I'm returning the top 3 chunks. Okay, we'll see what is there. And it has said a lot of things, where there are some languages. Yeah, there are my skills and all. But yeah, with a small model, I don't expect to give good result, because this should have been the first one. and probably this as the second and this one as third. It is opposite, but it's fine by me. Okay. So next, what you need to do is you need to provide the input to your LLM, right? So all you need to do is just format the prompt. So for this, we'll stuff the documents together as a single prompt or single string. Okay. So for this, what you need to do is just go through the chunks, and I'm just giving it as document is two, got some number for the document. Okay. And here you can see it is there, right? Document one and the document, and then document two, document three, everything will be there. All right. All it will do is it will add the document number to it, and we are just joining it together. Okay. Nothing very complicated in here. So once this is done, your relevant docs are ready, but still the model input is not ready. So to give the LLM, we'll be making our own prompt template there. There it was prompt template from template, and you'll provide the input variables and things like that. Here all you need to do is just make a prompt, which I did here. And what we will do is we'll just call the format function. Okay, that's why I said it is very easy. It is a string format. When you see it as prompt template from template, you'll think, okay, man, this is very complicated and stuff like that. But when you do it from yourself, right, this is gonna be very good for you. All right, and it will be easier for you to understand that there is nothing going on behind. So all you need to do is then just have Grok API key and provide your own API key here. So once that is done, we are just ready with the LLM input, and the LLM name is the parameter here, and we'll also provide the context and question. Okay. Once you provide the context and question to the prompt, which is here, we'll format the prompt to provide the LLM input. We are also creating the LLM here. All you need to do is in Grok, call the .chat.completions.create. This is an API request where the role is user and the content should be your LLM input. Okay. Provide your model name here. And once you provide those, just run it. And all you need to do is just provide your LLM name and then the documents which you retrieve now and your question which already you gave. Okay. And it gave the perfect answer, and I'm pretty happy with what I have achieved in this specific thing. So yeah guys, and all you need to do is just make this a simple class, just a Python class, and you'll be able to deploy it very easily. And this is how you can create your own custom RAG, and you can add whatever features you want in this by yourself. We are going to see about how to create an end-to-end RAG architecture which can be run in production level, from data ingestion till monitoring the RAG architecture at real time. For this, the first step for us would be to understand the architecture, and then we'll move on to the code. The software architecture will look like here, something like this. The orchestration framework will be Langchain, or else you can prefer Llama Index, but right now I prefer Langchain because it is much easier to use. An orchestration framework is a framework which will bring all the components together, and that will be the lowermost layer of the architecture. This orchestration framework is very important because this is gonna be the heart of the architecture, and for that we have chosen Langchain. When we come onto the RAG architecture, there are two main components which are going to be involved as the steps of RAG. The first one is going to be the retrieval process, and then another one is going to be based on the retrieved data generating the output. So for this, in retrieval, we are going to use the OpenAI embeddings, and for vector store, we are going to use Pinecone. Why we are going to use these, I'll let you know in a bit, but right now just remember that for retrieval, we are going to use OpenAI embeddings, and for vector store, we are going to use Pinecone. And for generation, we are going to run Llama 3 on Grok inference. So that is going to be our generation side, and this is going to be on our retrieval side. Is that all we require? No. When we are going on to production level architecture, it is very important that there is a control over the input as well as output if required. But while input, it is very much important that you have a control of what you are providing as input to your LLMs. And it is very important also that you need to monitor your LLM output, and then probably at the end, you can also add a layer on top of this here where you can add a data flywheel. Okay, so based on this monitoring, you can build a data set, which also I'll say at the end of this video of how you can build a data set based on this monitoring, whatever you have done till now, and how you can train your LLM based on that. We'll see about that at the end of the videos as well. Okay, but it is very important for you to monitor your LLM's output so that you can change its behavior whenever it's needed. But this is the component which is required for you to build an end-to-end RAG architecture. This will be the software architecture. All right. So now let's see how an RAG architecture works, and then we'll see how to build via a code. So now here we have the RAG flowchart where this is how the flow would be application. First, we'll be getting the URL and we'll be loading that. But in your application, based on your use case, if it is a PDF or if it is a CSV or if it is a text document, you can change your loader. But right now I'm just using web. All right. Then we have the text splitter for chunking, because if there is a data of around 10,000 characters, we'll be splitting it as 1,000, something like that. Okay. And those split chunks are known as documents, and those documents would be added into the Pinecone vector store by computing the OpenAI embeddings for it, and then it would be stored. So once that is done, we'll get the input from the user on the user query, whatever they want. But usually in our RAG architecture, this is not something we do. Here we'll do an input check with the help of guardrails to make sure that it follows some guidelines. So why do we need these guardrails? It is to make sure that the question falls under the scope of the questions you want to answer. For example, there might be questions which might involve some words which should not be there in the question, and then you don't want to answer it. Or there might be some other things like falling out of scope of whatever you have. So for those questions, you can have guardrails and it will protect from the question going on to the architecture for two things. One, avoiding any mistakes which might come, or two, it is waste of tokens, right? Because retrieval, generation, monitoring, these are all gonna cost us with a lot of tokens, and we can avoid that. So for that, we are adding a step known as input check. And by the way, you can also monitor the number of tokens you are using with the help of Langsmith itself, which we'll see in the monitoring component. So once you have done your input check, the next step would be to retrieve with the help of retriever. Here the Pinecone vector store itself will act as a retriever, but this is just a dense retriever. If you want, you can also add a sparse retriever in the form of BM25 retriever and ensemble it. These are all some advanced components of retrieval. If the use case demands it, you can try to use it. And if you want to know how to do that, let me know. I'll make a video on that probably. And for generation, next, once you retrieve the related whatever documents there are, you need to generate the answer with the help of generator component, which will be running LLM as Llama 3 on inference engine as Grok. So Llama 3 will be running on Grok. All right. So finally, for monitoring all of these processes, we'll have Langsmith, which will store the trace, and finally you will display your answer output in UI. So this is how the flowchart is. And now we'll see the code in detail. Here is the code for creating the RAG end-to-end architecture. And for this, in your .env file, you will need 4 important keys. One is your Langsmith API key, and then your Pinecone API key, your Grok API key, and your OpenAI API key. Because for embeddings, we are using OpenAI. For LLM, we are using Llama 3 running on Grok. And for vector store, we are using Pinecone. And for monitoring, we are using Langsmith. But why I have chosen these specific things, that is what we are going to see now. First, let's see about the vector store Pinecone. Okay, Pinecone vector store offers you a serverless index. All right, so let's see about that now. Here is the Pinecone's pricing, and if you are a starter, right, so they are providing up to 2 GB storage where you can store 1536 dimension vectors. So higher the dimension, higher the better the result it's gonna be at lot of situations. And OpenAI's embeddings, which is an API, again we'll see about that as well, also provide 1536 dimension vector. Okay, so here it is said that with this 2 GB storage you can store up to 300k embeddings. I think that is fine. Okay, and you can write 2 million units per month and you can read 1 million units per month, but you can have only one project. Okay, so indexes is nothing but how many databases you have. Okay, under that one project you are allowed to have 5 indexes, and namespaces is nothing but the user. Okay, you can use, I mean, you can have 100 user per index, which means 500 users can be used, all are for free. But if you go on to the standard section, again guys, this is not a paid promotion, I'll just let you know. When you're going for paid option, I think Pinecone is best, okay, because of what they provide. All right, as a developer you might not know in a lot of scenarios that okay, this is what is gonna be my number of requests per month. Okay, so for that only they have provided this serverless option. If you know what is gonna be there prior, you can just choose pod based option, or else you should just use serverless, and that is what we'll use in this video. Okay, so for this what you need to do is, here if you see in serverless indexes, for storage, they are providing 5 million documents. You can just store 5 million documents up to 10 million vectors of 1536 dimension, and that will just cost around $21 per month. And if you can hit 1 million queries per month, which will cost you $83 per month, and you can upload 10 million vectors per month, which will cost you 70 per month. Okay, on a total, it will cost you 170 per month. Okay, so that is what is said in this option of serverless index. And there are some other things also they have provided, but you can also see here. Okay, so for example, if you're going for serverless using Amazon Web Services, all right, so if you're choosing this region of US East, that is what is the cheapest. Europe is slightly costlier. Okay, and here is the pricing. And if you're going for pod based index is a thing which you are thinking that okay, in my 1 month I'll be just storing around 5 million vectors. Okay, if you know for sure that you're gonna store this much, that is when you're gonna choose pod based index. Okay, so this is how you need to choose. And why I'm explaining all of these, because we are seeing a production level end-to-end architecture. And if you are going to use serverless, right, it is going to be pay per use, and you can scale it how much ever you want. Okay, so that is what even it is said here. See, for production applications at any scale. So that is our vector store, which is scaled at a lot of user level. Okay, if you want to put that way. Now for embedding, I'm using OpenAI's embeddings model, because right now Grok isn't supporting an embedding model, and OpenAI is highly scalable. We all know that. With OpenAI embeddings, the best option would be small, because it is providing a performance of around 63%, and large just provides 65%. Okay, but for $1, here you'll get 63,000 pages, and here you're getting just 10,000 pages. Okay, so if you are paying $1, you can just store 63,000 pages, assuming that each page has 800 tokens. So if you multiply that, and here also they'll have a pricing page. We'll see that as well now. OpenAI pricing. Okay, so if you see here in embeddings, they'll have it here. Okay, fine-tuning embedding model. Here you can see for small, there is for 1 million token you can use for $0.02, which means you can store 50 million tokens. Okay, 50 million tokens for $1. Okay, just for $1 you can store 50 million tokens, and that is pretty huge, right? So that's why I chose OpenAI embeddings, though it is not the best open source model right now. I mean, or the model which you can use right now for your architecture, but this is the most scalable architecture which you can create right now. Okay, so for that we have chosen OpenAI, and for LLM we have used Grok, because the pricing is also very less. I'll go into Grok. Okay, documentation, and here if you see, let's see here. Okay, Grok pricing. Here if you see, for Llama 3 8 billion, you get for 1 million tokens, you're gonna just give $0.05. Okay. And for all, it is just cheaper than the original one. So that's why we are choosing here. And it is very fast, which means in your production architecture, it is going to be fast, which means your outputs are going to be good as well as fast enough, right? So we have combined the best possible components, which is highly scalable, because now they are working on scalability. And for enterprises, you can contact them specially. That's what they have said. Okay. And you can also use fine-tuned model, it seems. All right. So for enterprise also, you can just contact the teams. Uh, so we are done with our LLM, which is highly scalable now, and it is fast enough. And you have your embeddings model. Again, OpenAI is so good. And finally, we have the vector store also, which is highly scalable. Now we have created a highly scalable yet fast architecture. Okay. Now to monitor all of these, we are going to have Langsmith. Okay. So Langsmith is a monitoring framework which is written by Langchain themselves, and that's why it chose Langchain as the orchestration framework, because with this, it is said that once you monitor, right, you can add those to your data set, and your output, whatever you get from your model, can become your input for retraining the model. Okay. And there are a lot of other things which we'll see later once we see the code and the demo. Now let's see the code. Okay. So here we have the code, right? So first we are importing all things which are needed. Web-based loader to load the web document and or web page by using Beautiful Soup. Okay, so for that we have BS4 also imported. And for splitting, like I said, we have character text splitter. For embeddings, OpenAI embeddings. To create a Pinecone index, we have Pinecone client created. And since we need to use serverless, we are using serverless spec. But if you want to use pod, you can also use pod spec, but we won't need it. Okay. But I have provided that option so that you can change it and make it work for your pods. Okay. And then we have Pinecone vector store, because we need to work with Pinecone vector store. And Langchain, from Langchain, we need to import hub so that we can get our prompt for RAG from Langchain itself, because there are good prompts which are defaultly written. And we are going to use one such prompt from there. And then we have chat grok so that we can use our LLM, grok LLM, and then runnable pass through, because this is nothing but, it will just send the input from one to another. But when you go through this runnable pass through, right, it will help you to log it in Langsmith. Okay, so to parse the output however we want, we have the output parser as well to load the .env file and the whatever constant we have. So to first we need to find the .env file. For that we have find.env, and for loading that file we have load.env. And from Nemo guardrails we have the Rails config imported, and in Nemo guardrails they have provided an integration with Langchain, which is runnable Rails, and that can be integrated with a runnable pass through. Okay, so these are the inputs, and here you need to set some environment variables. The first variable would be setting up the Langchain tracing v2 to true, so that all the components are traced, whatever it is passed from one to another, right? And then we have the Langchain API key set along with the Langchain project name, whatever you want, you can give. I have kept it to end-to-end rag new. Okay, and here also I'm providing a vector store index name, which is end-to-end rag new again. And here I have the web-based loader. So to load the website based on the URL as a document, we need web-based loader. And for this, you'll be providing the website path. You can provide multiple paths as well, but right now I'm just providing single path. But you can provide multiple paths as well. Like I said, this is an end-to-end RAG architecture which is highly scalable, right? So with that being said, you can provide multiple URLs as well. Similarly, you can provide multiple PDFs upon your choice. And for the Beautiful Soup, we are providing the argument stating that for parsing, you can use Beautiful Soup's strainer, where you will just consider the post content title and the headers alone, not the tags and all. Okay, that is how we are going to parse the HTML file, HTML page. And for embeddings, we are using OpenAI embeddings, and for LLM, we are using Grok, which is running Llama 370 billion. We have the recursive character text splitter, which has a chunk size of 2000 and an overlap of 100, which will split the document from 0 to 2000, and then 1900 to 3900, and then 3800 to 5800, retaining a context of 100 tokens in there. Okay. Here next we have the create pinecone index function, which will create the pinecone index. Okay. So for creating a pinecone index, first you need to create a client, pinecone client, for which you'll provide the API key. And then for serverless specification, like I said, you saw there, right? There are US servers and Europe servers. You can provide whatever you want there and what type of cloud you want, because they also provide GCP and Azure support, if I'm not wrong. You can also provide that. But right now I'm just providing AWS, and the region is US East 1. But we are also checking, because see, right now we are allowed only some indexes alone, right? So we are just making sure that at runtime there is only one index. So if there is an index of what I'm choosing here, for example, end-to-end RAG new, if that is there, I'll delete that index and I'll create a new index. That is what is there here. Okay. If it is there, I'll delete it and then I'll create it with the dimension of 1536, and the similarity is computed with the help of dot product, and what type of specification I want, serverless specification with this specification. Okay. So that is how you create your pinecone index. And once that is done, your index is ready, which means you can call the pinecone vector store with the index name, and you can provide the initialization with OpenAI embeddings along with the API key. Okay, which means your vector store is initialized, your text splitter, all are instances. Okay, your LLM instance is ready, your embedding instance is ready, your vector store instance is ready, your prompt template instance is ready, your guardrail instance template is ready. I'm just blabbering, no? Like all instances are ready. Simple. Your web loader is also ready. So all your instances are loaded in this init function. And then here there is this root function or the core function, which is QA, where I'll get two functions. Okay, the first one is query and then another one is vector store created. So we'll just think that, okay, see, for example, if I'm providing a website, to create a vector store, that is one time only it is required. After that, it is not required, right? So we'll check if the vector store is created, and if it is created, we won't compute the vector store. Okay, so that's why vector store created is given as pass, and for else, if the vector store is not there, we'll call the create retrieval chain function, which is here. Okay, so how is the create retrieval chain function ready? Actually, there can be a change which I'm gonna do now, right? So we'll call that here. What I'm gonna do is I'm gonna add a parameter known as vector store created here, so that if the vector store is created, else can be added here. Okay, so the idea is that if the vector store is created, I need not create the vector store again. Okay, so the vector store creation process happens with load docs in vector store chain. All right, so for that, first we'll load the documents from the loader, okay, which we created there, web-based loader, and the document is splitted by using the character text splitter. And once the documents are ready, we'll add those into the vector store. Okay, by calling the add documents function, you need to provide the documents alone. Okay, so now with this, your vector store would be ready. Okay, and then you will need to create your RAG chain. Okay, so for this, you will provide your retriever and your question. Okay, question is got from the user, and that's what you are providing with the runnable pass through. Okay, and I need to add it here. Okay, when you call the invoke, that will go on to the pass through. All right, so here we'll make sure that the vector store is now retriever, and then the context is obtained from retriever, where you will pass it through the format docs function. So what it will do is, let's say you get around, we'll put it as 5 documents. Okay, so what it will do is the 5 documents will be retrieved, and all of those will be combined in this format. Okay, there will be 2 new lines, and then the first document will be there, then 2 new lines, the second document will be there. That is how the format docs will format your document, which will become your context, and then the question is got from the user. And both of these are provided to RAG prompt. Okay, this runnable pass-through is very nice, like following this LCEL. This is Langchain expression language. And with this, you have this kind of control a bit. And for even more control, we can use LangGraph, which I'll say later. Because I'm planning a course on that. We'll see about that later as well. Okay, in some another video, I'll make a video on LangGraph. But right now, we'll focus on this. Okay. So once your prompt is formatted, you're providing it to Grok LLM, and then your output is passed. Now you might wonder, Vasanth, where is the guardrail, right? Like I said, guardrail will be provided at the input level itself. We'll just check if the query is good. If the query is not good, we are not going to use that. Okay. So first we have the guardrails, and then we'll pass into the RAG chain. Okay. So that is how your retrieval chain is created, and then you invoke your query. Okay. So that is how you'll create your retriever. Okay. Now, since we know how the retriever is or the RAG app is created, now we'll see the UI side. Okay. So you are importing the RAG class. Okay. And to load the RAG class, we have here. Okay, the load RAG pipeline will take a website URL and you'll provide that to the RAG class, and that will create an instance of RAG pipeline. Since all of these are async processes, especially with guardrails and the vector store creation and all involved, there are a lot of async loops involved in there. To make sure that there is no error, we have this function. Okay, this is just a util function. All right. So here we have the other thing, which is the session state. Okay, first the session state will be click to set to false. Okay, so here we have the title and header that we are not going to consider. So first we'll get the URL, and the URL, once it is entered, we can just click enter to apply. Okay, and what we'll do is we'll load the RAG pipeline. Okay, so where is the load RAG pipeline? We'll see that. Okay, here it is. Yeah, we'll create the RAG pipeline instance, and once that is done, we'll set the click to true, and if the click is true, then only we'll get a question from the user, and with the question there, we'll call the QA function with the question along with the vector store created. Okay, so initially the vector store created would be false. Okay, because here if you see, the logic is such that if the vector store is created, we won't call the load docs into vector chain function. Okay, so initially it should be false, and then in the next step it should become true. Okay, so initially it's set to false, and here if you see, we'll return two things. One is the output along with true. Okay, and here what I did was, we'll get the another value as vs, and then we'll assign the true to vector store created. Okay, so once the vector store created gets this value, we'll write the output as well, and that is what is displayed. Now we'll see the application. Okay, so I'll put my image here. We'll ask it streamlit run app.py. So for this, what I'm going to do is I'm going to take the latest document which is there in Wikipedia. Okay, so now let's do that. Here we have the application, and what I'm going to do is I'll go to Wikipedia, and what I'm going to do is let's take English so that the latest architecture is there. And here is the latest article which is on Mary Anning, and I'm going to take that. And here we have an article. Just getting architecture in my mouth. We are having a document on Mary Anning, and by the way, I didn't say about the rail config, because here if you see, this is how we will create the runnable rails, where first we'll get the rail config, whatever is the fence. Okay, so this guardrail is kind of a fence where after that you can't go. Okay, so for that you'll have a config folder in which there are two configs. Okay, the first is rails. Okay, that's how you'll need to start, and you can also provide it for output. Okay, for input I'm just providing in flows. You need to do the self-check input, and how to do the self-check input, that is what we give it in the prompts. Okay, in prompts for the task of self-check input, this is the content. Okay, your task is to check if it follows these, and I'm saying some rules here, especially it should not contain any harmful data, it should not impersonate someone, and so on and so forth. Okay, so finally what it will do is it will see, okay, should the user message be blocked or not. If it says yes, it will be blocked, the pipeline won't execute, and if it says no, then the pipeline will continue, and we'll check both of those. Okay, we'll try to get both kind of output from there. Okay, now let's go into the application. So for that, first what I'm going to do is let's ask this itself. Okay, I'll provide the URL. It's loading now. Okay, as you can see, the question now popped up, which wasn't the case before, which means it is ready. Okay, so now I'm going to ask who. Now we'll try to get a yes answer, which means the pipeline shouldn't execute. Okay, who the hell is, sorry for my vulgar language, who the hell is Mary Anning? Okay, we'll ask this, and I'm expecting the model to say I can't answer, something like that, but it is answering. Oh, okay. Let me put another question again. Yeah, you can see it has said, "Who the hell is Mary?" When I asked that, I'm sorry, I can't respond to that. Okay, now we give two questions, and in one we didn't get this answer, right? So what happened? We are gonna see that now. Langsmith. If we go into the Langsmith and whatever project we created now, which is, if you remember, end-to-end RAG new. Okay, and in this, if you see, I've totally used 498 tokens and in 3 runs. Okay, total on a run, it is approximately taking 172 tokens. Okay, here if you see, for this question, it didn't take for some reason, but probably we can give correct prompt probably. But here if you see, when I asked who the hell is Mary, the AI said yes, and we didn't get an output, right? But here if you see, there are two things. Okay, once you get no, that is when your runnable sequence get executed, and here is how you get the output. Okay, but for example, if I ask impersonify yourself as Mary and tell me about yourself. But here you also see, right? Why I asked this was, now if you can see here, it is added. All right, here I was explicitly providing a statement that should not ask about the bot to impersonate someone. I told it to impersonate Mary, and it said okay, I'm not gonna allow this. Okay, so this is how you can provide lot of fins, like saying okay, this is not something you can do. Again, here we are using the LLM, but see here, now the token is just 676. Okay, for previously it was 472, now it's 676. If we divide it by 4, it is 173. That is fine, but the token is gonna be high only with this runnable sequence, because you are gonna use a lot of tokens in here. Okay, and this is how it goes. Okay, once you provide the input, it goes into the retriever. Okay, the retriever. So what the retriever does is, here you should get something, just give me a minute. And yeah, here if you see, the content is there. Okay, and here I'm asking who the hell is Mary Anning. Okay, and the chat grok is then answering with some answer in here. Okay, that's how you can see okay what is going on in behind. Since I didn't say I need to parse it in an explicit manner, it isn't parsing my output, but if you want you can also do that as well. Okay, and here if you see, you can add this to a data set. Okay, this will create a data set. Now if I want to do that, what I need to do is, in data sets, I need to click a new data set. Okay, what I'm going to do is dummy. Okay, I'm going to create dummy, and this is going to be an LLM dataset. Okay, so let's see here. If you see, we have the dataset, right? So what you need to do is go to your project, whatever we did now, go to end-to-end RAG new, go to the runnable sequence, add to dataset, and here we are going to choose why new dataset. Okay, here also you can create it seems. What I'm going to do is I'm just going to give like this, and now this is going to be stored in this dataset. Okay, if I go to this dataset now, okay, ASDAD, and we have the input and output, right? So which means you can train, right? So for example, if I'm gonna load a Wikipedia, all right, and then if I give 10 questions with each Wikipedia URL, and probably you can also generate that with the help of LLMs itself, you have a dataset for yourself, and that is how you can create synthetic data. And I am going to create a specific video for this itself, and we'll see that. Okay, but like I said, this is how you create an end-to-end RAG for production. Now you can see, you can monitor your outputs, you have your monitoring of the tokens, you can control what kind of output should be there, what kind of output should not be there. Same goes for input. Everything which is to be considered in production, even including scalability, is considered in this creation of architecture. LLMs usually have great potential in doing whatever things we ask it to do to the best of its capability. But it is always important for you to aid the LLM with the required tools and the environment so that it is used to its fullest potential. This is one such video where I'm gonna extract the full potential of the LLM, where I'm gonna build a RAG system where the LLM will think by itself for answering the question whether it should use web search, or it should use the local database, or should it use its own knowledge, personal memory, something like that. All right. For that, I'm going to provide the tools, I'm going to provide the environment, and the LLM is expected to identify which knowledge it should give importance with and then answer accordingly. All right. So that is why it is like this. I have provided it with the files. Along with that, I have provided the vector database and the tool to search over internet. So this is how the architecture would be, where given a question to the user by the user, to the assistant, which is the LLM, it will try to see, okay, do I have the memory for it, or do I need the knowledge? So what do you mean by memory here? Memory, I'm stating it as the inbuilt memory. For example, if I'm asking where does the sun rise, it can easily say the sun rises in the east by itself without any other knowledge, right? For example, if I'm asking who is Elon Musk, if it knows Elon Musk, it will say. But what if it doesn't know? All right. So those are there. Now, for the next point, if I'm asking something like, okay, I have this PDF and then answer the question according to that, or let's say I'm having some other document, any document format of yourself, for example, CSV or JSON, text, whatever format you have, it can do normal RAG there. Conventional RAG, where you'll have your document, you'll chunk it, and then the same process will be repeated of the conventional RAG. So that comes under the knowledge sector. Okay. So for that, you'll have the vector database, and for the memory, you'll have the normal database itself. Okay. And for tools, because like I said, if it is website, right, the model doesn't have the capability to understand websites directly. All right. So for that, what we are going to do is we'll be providing it with tools like searching over web, so that it will be able to scrape the website contents, and then based on that, it will create a context knowledge base, and then it will answer the question. Okay. But given a question, it has three options, right? Either answer by itself, or search over internet and then answer, or use the vector database directly. There are three options. I'm not going to say you need to use this option. That's why I said this is a self-thinking RAG, where the application by itself would think, okay, which option should I use? And then it will choose the option and answer accordingly. So that is a bit of automation which is involved right now in the RAG, because previously in all of my videos, I would have done either PDF chat or website chat. But now we are moving into the next level. We are doing everything at one place, but the LLM will do that. I'm not going to explicitly say that, okay, I need this. All right. So now what we are going to do is we are going to see the dependency for this specific application, because file data expects you to have Postgres running in a Docker container, and don't worry, for that there is a command. Okay. If you want to run that, so what you need to do is first install Docker desktop. Right. First install Docker desktop and then run this specific command, docker run -d, which is detach mode. And then we are saying that the Postgres DB name is AI, and the user is also AI, the password is also AI, and then the data which you are going to store is going to be in the var/lib/PostgreSQL/data/pg data directory, and the volume which will have all the information. For example, your conversations, right? When you ask, summarize the conversation we had in the last 5 chat or something like that, right? Then it will go through its volume, because those volume will have the answer. And here in this application, it has the capability to store the runs. Whatever run we have done, the history would be there in that, so that you can continue from there. So for that, you need volume. All right. And then we are doing a port mapping here from 5432 to 5532. And then the name of the image, because everything is image for Docker, is pg vector, and the image is 5data/pg vector.16. So is to 16. So this would be in the Docker hub, and we are downloading it and naming the image as pg vector. All right. So all you need to do is go to your command prompt and run this specific command. All right. Yeah. For me, Docker isn't started yet. So what I'm going to do is, it is very important that you start your Docker. I made sure that my Docker is stopped whenever I stop my system. Okay. So here there is pg vector there. All right. So I'm going to start that here. So you can run that command and it will work for you. And I'm starting it from here. All right. So if you want to check, right, all you need to do is just go to the command prompt and do docker ps. And here you can see phi data pg vector 16 is running. Okay, if you get this kind of a result, then it is fine, you are good. Okay, now with the Docker running, which means your vector store is ready, I'll explain the code a bit and then we'll move on with it. Okay, so for the code, here if you see, I'm setting the net asynco dot apply function so that the event loops which are in async function would run without any error. All right, and then we are providing some configuration, and here if you see, for reader I have PDF reader and website I have website reader. But like I said, if you want other documents as well, right, you can put other document readers as well and it will be fine. Okay, because phi data supports all of those. And here there is a function which will restart the assistant. What it will do is, see, everything will maintain in a session state, and there is a session state known as AutoRAG assistant. Okay, so there are some other session state as well, like file uploader key, URL scrape key. These are nothing but like, if there is a URL to scrape being provided, is there a file uploaded, and what is the run ID. So all of these would be reset. Okay, it will be set to none or something like that. All right, so that is what happens in restart assistant. That is a helper function, and then we have the main function. All right, so here we are just setting a variable with the type known as assistant, and we are checking if the AutoRAG assistant is there or is it created. If it is not, we'll call the get AutoRAG assistant function. So this will go to in the file assistant.py where we are creating the assistant. All right, so here you need to provide your LLM, which is, I'm using Grok here. You can also use Llama. This is my DB URL, and I'm using Llama 370,000,08192, but you can use anything of your own choice. And for storage, like I said, that conversation storage and all, I have PG assistant storage, Postgres assistant storage under the name AutoRAG assistant Llama. And for knowledge base, I have assistant knowledge class. Okay, this will be like your vector store retriever class. All right, and here the vector database is a Postgres vector database, and here for that you will be providing the DB URL, the collection is RAG, and for embedder we are using Llama embedder with the model name nomic embed text. So once you run the Docker container, the another dependency would be for you to do Llama pull nomic embed text if it is not there. Okay, here I'm just taking one document, but you can take 5 documents as well. So let me put 3 or something like that. So it will be retrieving 3. Okay, and here is what the core of that self thinking. Okay, this is just about like, providing the information that, okay, see here, if you wanna summarize the conversation, just call the get chat history, and if you want to search a knowledge base, just use search knowledge base, and if there is more information, search over internet. We are just saying what are the things available for it and what are the tools available for it. Okay, so that is the prompt which is making it to think by itself, and we are setting show tool calls to true so that it will show the tool calls, whatever tool it is calling, and then the search knowledge to true, and read chat history to true. These all will enable it to do whatever things it want. Okay, and then the tool is DuckDuckGo to search over internet, and then we have markdown set to true, and then debug mode is set to true so that you can see what is happening at the behind. Okay, so this is the assistant. So once your assistant is created, you are also putting that in the session state. All right, so if there is a memory, like if there is a memory available already in the specific run ID, what it will do is it will just load the memories or messages. Okay, then we'll get the user input via chat. All right, and we'll also display the existing chat messages. That is what is here. So if it is a system, we'll just continue. If it is a role of user, we'll just print it, something like that. All right, and we'll check if the last message is user, because see, the idea is that if we are chatting, right, always the last message should be from the LLM, not from the user. So we'll check that, okay, if the last message is from user, we'll call the assistant AutoRAG assistant to run with the question provided. With Grok, streaming is not supported yet, so I've set it to false, but once you run with the help of OpenAI GPT-4 or Llama and all, you can set stream equal to true. And then I'm setting up the markdown container so that the markdown response, whatever we get, will be rendered correctly. All right, so here we are loading the knowledge base. Okay, so if you provide URL, it will use the website reader to take maximum of 2 links and the chunk size should be 2000 for it to, scrape and then make a knowledge base out of it. And once you call that, and here you can see it is add URL button. If you click the add URL button only, it will do this, and it will do a restart assistant so that the memory is updated. Same goes for PDF uploading and all. All right. And there is an option for you to clear the knowledge base as well. So you say, like, if your memory is gone and there are some lot of redundant information in that, you can restart the assistant always whenever you want, which will clear the knowledge base as well. All right. So if you are clicking the new run also, it will restart the assistant, and that is how this works. All right. So now what I'm going to do is I'm going to provide my API key in here. You can provide yours, and then we'll run this. I have provided my API key. You can provide yours, like I said, or you can put it in the .env file and then load it. That is also fine. But make sure, guys, first olama pull nomic embed text is done, and then the Docker is running. Okay. Then what you need to do is just run streamlit run app.py. Here you can see it is loading the data. Like the app is being loaded, and here you will be able to see the logs. Here you can see, right? Debug logs is enabled. This is the run ID, and no chat history is there for this. So if you want to ask, right, for example, who is MS Dhoni? If I ask this, it should say some result. So when I asked who is MS Dhoni, here you can see there is no function called shown here because it didn't need a function, right? Here you can see it is saying some answer. So now what I'm going to do is I'm going to put MS Dhoni in here. I'll make sure that Wikipedia is not there. Probably I'll give this one. There is no description. Yeah, here there is no description. So let me go for Cricinfo. All right. So I'm expecting it to, answer based on this. So now it's trying to add the URL. I said couldn't read a website. So now let me try to ask that who is MS Dhoni. Let me try with that. And now you can see the answer is changed, right? So now actually there is no calls done here, which means the knowledge base was not updated. Okay, I think the problem was it couldn't read the website. So what I'm doing is I'm just providing the Wikipedia as one. Hopefully if I ask something different from this, it should be able to answer, I guess. Okay, I'll see this. Okay, I think I didn't see the message what it was. Okay, so let's see who did the Indian team. So I'm expecting it to call the search knowledge base function. Yeah, here you can see, right? It has come Rahul Travel. So it was able to, search over the website as well. But if I provide a file here, for example, let me see if there is any files here. Okay, I have a file which is on prompts, with the help of AI thumbnails. So it's now trying to process the PDF, and it is done. Okay, let me ask a thumbnail for a science and technology video, and if I do that, it will be able to search over the knowledge base by itself. Okay, so it did a DuckDuckGo search for some reason, and then it didn't give a correct answer, so it went for the knowledge base. All right, so now if I ask it to say me the latest IPL information. If I ask this, it should use DuckDuckGo search. Yeah, now you can see here it called the DuckDuckGo news, where it said, okay, Rajasthan Royals coach Shane Lamons lost to PBKs, which happened yesterday. It has shown like what are the last 5 things happened. Okay, so yeah, now you can see, right? I didn't say that it needs to use the knowledge base tool because see, we already extracted websites, but I didn't say, okay, you need to extract website this time. I just said I need the latest IPL news. So it found that I don't have anything in my knowledge base, so I'll search over the internet. So it did something by itself, and that's why it said it is a self-thinking application and not something which we provide explicitly. So yeah, guys, this is we trying to use the LLM to its maximum potential, and I hope you will all build some application which will also bring LLM to its full potential. CrewAI, a beginner-friendly step-by-step course which will help you to build your own agents after you complete this course. Before going into the course in deep, it is very important for us to know what is CrewAI. CrewAI is nothing but an autonomous AI agent framework which will foster or empower collaborative intelligence, which will help the agents to work together seamlessly, and it will help them to tackle complex tasks by breaking it down into small components, and each task will be focused by a specific agent. What are we going to learn in this course? In this course, first we'll start with the different core components which are there in CrewAI, and followed by that, I'll be explaining in detail about each core component. What is it? How is it working? And what are the attributes in there? What are the types of the components which is there inside the core component? And then we'll see your first project, how you can build your first project, which is to validate markdown reports. From setup, we'll see how you can build an API out of it. And finally, we'll be ending up with a few real-time example projects, and I'll say what you can do as next steps and some advanced concepts as well of how you can enhance your agent frameworks. Core components. Now, there are 6 main core components, and we are having the first 3 here, which is agent, tasks, and crew. These form the main core components, if you want to put, or core of core components, because for a crew to work, it requires 2 things: agents and the task designated for the agents. And that is why I have kept all the 3 first. Now let's see what are these components, and then we'll go in detail about these components later. What is an agent? An agent is nothing but an autonomous unit which is programmed to do a specific task, where it will have the capability to make decision, and it will also be able to communicate with other agents. Okay, so if you're working in a company, you should put yourself in an agent perspective. Okay, so that is how CrewAI is built. It is built with a vision that it will be working in an organizational manner. If there is an organization, you will have a group of people working together where each person will have their own task, right? And the group of people is known as crew, and the single person is known as an agent. As a person, you will have a different task, you will have the capability to make decision, and you will also communicate with your other friends or colleagues in the team to make sure that the task is completed, right? So that is how an agent is also created. And that's why you can imagine an agent as a member of the team which has specific skills and a particular job to do. For example, be it a researcher, a writer, if it is a newspaper team, right? One need to research about the latest content, one needs to write a report out of it, which is so cool and easy to understand, right? So that is how an agent is. But there is also another thing which you need to note. An LLM is an agent. So why we are terming it as an agent, not an LLM? You see, an agent is an autonomous unit, right? But LLM is also an autonomous unit. But when you provide tools to an agent, that is where it becomes autonomous. Because if it is an LLM, it requires either fine-tuning, it requires us to provide something to it for it to complete any task, right? But agents are independent. If you provide the required tools, they won't require anything. All right. So that is why it is an autonomous unit. All right. So now, what does the agent do? It will complete the task. So now we'll see about what is task. Okay. In the CrewAI framework, tasks are just specific assignment like in the real world, where the agents are expected to complete the assignment. Okay. These tasks are the things which will provide the necessary description for the agent that what it needs to do, how it can do its task, and let's say like, okay, you would require these kind of tools, and I have provided that. All right. To solve complex tasks, it is required that you make sure the task is explained in such a way that it will provide the details for the execution. All right. So the task clarity is very important. Please note that. Next is crew. So what is a crew in CrewAI? CrewAI is nothing but, again, building a group of people, agents or people, if you want to put that way, which will autonomously work to solve a complex task. All right. But a crew is also known as a collaborative group of agents which will be working together to achieve a set of tasks, which is a common goal. Okay. So a crew has a common goal. For example, if I'm building a stock analysis company, the crew's goal is to analyze a given stock. But The agents will have a separate goal on their own, which we'll see later in agent explanation in depth. Okay, each crew defines the strategy for task execution, agent collaboration, and the overall workflow. Okay, so the crew decides, okay, how we want to execute the task. Do we want to execute sequentially, or do we want to execute according to our manager's order, or do we want to collaborate with each other to complete the task? All are decided based upon the crew's goals and crew's information. Now, like I said, what is making an LLM an agent? All right. When you designate a task, and if the LM is able to do the task autonomously without anyone's help, that is when an LLM becomes an agent. And for that, a tool is very important. A tool in CrewAI is nothing but a skill or a function that will enable the agent to perform multiple actions. Okay, and good on CrewAI and the creator, who is Joa Mora, if I think I pronounced his name correctly, such an amazing person to create this kind of a framework where it will support Langchain tools as well. And that is one of the most stable framework which will provide you tools. Okay, so this enables you to build simple searches to complex interaction, and it will embrace effective teamwork amongst the agents. Now, coming on to the next topic, which is processes. Like I said, it is very important for you to know, okay, what is the thing we are going to follow? What is the strategy of our execution, right? Because if there is not a good leadership, any company would fail. And same would be the case for CrewAI, and a crew would fail if there is not a good strategy. So it is very important that you make sure the processes provide correct. Okay, now let's see about what is the process. In CrewAI, processes are nothing but it orchestrates the execution of agent to complete the task, and the processes ensure that the tasks are effectively distributed among the agent based on a predefined strategy. Now this is so vague. Let's give an example. For example, you wanna build a news providing company, all right, with AI. Again, these are all under an assumption that you are building a company level software or a complex software which has multiple tasks, and one agent is not able to do that. All right. If you're going to give the agent that, okay, you need to research, you need to make a JSON output out of it, and you need to slightly tweak it, and then one person, and I mean, probably the second agent will just write it a report out of it. This is not fairly distributed, right? Again, see, this will create a confusion of, okay, that agent is given more task and it will probably fail. All right. So it is very important that you provide the tasks equally or almost equal. Okay. So that ensures that your performance is very good. So that is why there are types of processes, and we'll see that in the later part. Now, coming on to a recently added component, which is memory. Memory is a component which was added in CrewAI recently, where it helps the CrewAI to have an idea of where it failed previously. Okay, so this is kind of a data flywheel where now it will have an idea of where it failed, and it will increase the capability of the agents. So there are lots of types of memory they have provided, which is short-term, long-term, entity, and there is also contextual memory, which will help to retain the context, and each has its own purpose. But when you provide memory to the agents, it is said that it will be increasing the performance tremendously, where it will self-think by itself and it will improve itself based on the errors it make in the previous iteration. Now, coming on to the next step, which is explaining the components in detail, because now you have an idea of what is agent, what is tool, and you have a basic idea of everything. But it is very important for you to understand about each component in detail of what are the attributes in it, how I need to provide the value, what are the scenarios in which I need to use a specific component. We are going to see all of those in this, where we'll start with agent, obviously, right? So for an agent, there are lots of important attributes, and here I'll be showing the most important attributes which you'll use at every time. And I'll also show you what are the others which are there when we go onto their website, and I'll show you what are the possible things which is useful at times when you need it. Okay. First, it is very important for you to provide the role. Alright? Role is very important. Why? Because that is what shows, okay, this agent is best suited for this task. For example, the thing which we consider, if you want to be a researcher, you should be good at searching lot of things. Okay. But if you want to be a writer, you need to have good grammatical skills. Now you may think, okay, Vasanth, the same LLM is used everywhere, so the capability should not change. Yes, but the initialization of agent is in such a way that it is aligned that, okay, it is a good writer, which means it will focus more on grammatical skills. And if it is a good researcher, it will focus on the research kind of writing more probably. Okay. So the initialization is very important. For that, we are providing the role. Okay. Next is the second important thing, which is goal. Okay. So now you might again think, okay, the task is provided, which means the role is done, right? So if I'm saying it is a writer, it obviously needs to write. No. You see, the crew has a goal for it to achieve, but each agent also has a goal to achieve. For example, if it is a researcher and I'm saying I need to get the latest news, I can ensure that, okay, see, there are licensing issues in here. Make sure that you take only newspapers where they provide it for free and it is royalty free also. Okay. So this is a specific goal to an agent and it will help the agent to make decisions. Because when I say, okay, you need to take only free research paper and to make sure that there is no copyright, it will filter out the agent newspapers which are not following that, right? So it helps it to make decisions. Now coming on to backstory. It will provide a context to role and goal, and it will also improve decision making, because you'll just say, okay, you did these previously and make sure you do that again. Let's say you'll say, okay, you were very good at filtering out news which is copyrighted and that enhance the company's performance. Make sure that you repeat that. Something like that. It will give a context of what we are saying in this role and goal. Now coming on to the most important probably attribute in the agents, which is LLM. Okay, so default LLM which is taken in CrewAI is GPT-4, and you can change it to any LLM because there's such an amazing framework. It provides integration with almost any platform which is API or local LLM. You can run with anything in this CrewAI. Okay, so you can run with Grok, you can run with Azure AI platform. There are a lot of things which they provide support to, and you can check it out in their website. Next, we are having tools. Okay, like I said, now your agent knows what it needs to do. Now it knows what it has done previously. You know the role of your agent. You know what is the LLM which is going to be powering this agent. But there are tasks which will require tools to do. For example, if it is a writer, it is not going to require any tool, right? It is going to be just writing and it will just make sure the syntaxes are correct and it will be working. That's fine. But what if it is a researcher, right? It needs to search over the internet, which means you need to provide a tool which will be able to search over the internet. And don't worry, they have lots of tools which will support many of your tasks and projects, which we will be seeing in the next steps as well, where I'll say like how many projects it is possible. And you will be shocked for sure when I say what are all the things which is possible with the help of this. Right? And by the way, the video you are seeing now, I decided to make this video with the help of a CrewAI video itself. Okay, I recently made a video on how you can earn or automate your YouTube channel process, where for that I gave a prompt related to this video, and it made sure that it said that, okay, this is a very good video and there are lots of views for it, which showed me that it is highly in demand, and that's why I decided to make this video. Thanks to CrewAI, probably. Let's go to the next one, which is max iteration. Okay, see, these are some things which are going to be very important if you are not going to use local LLMs. Okay, why? See, max iteration says at how many iteration the LLM or the agent will be able to give the best result possible. So if you set to 25, right, it will run for maximum of 25 times. The whole process will be running to get one output. In this case, if you're going to run a GPT-4, think of how much cost it will take for you to make such an output, right? But if it is something like probably Grok, you're going to hit the rate limit error. Okay. So there are lots of things which is hindering you if you don't go for a local uh, LLM approach, and that is solved with the help of max iteration. Just keep it to 1 or 2. That is more than enough. Nowadays, LLMs are very good to do the task in 1 or 2 iterations. Okay. Next, coming on to another such parameter, which is maximum request per minute, which will avoid rate limit error. In every LLM inference APIs, there are rate limits. Okay, in Grok especially, there is a rate limit, and to solve that, all you need to do is just give max request per minute as 1 or 2, and it will solve your errors. Okay, so this is something you can do. As you can see here, guys, though I'm explaining the components in detail, I'm also giving you hacks. So if you all like these kind of hacks, please hit the like button. And if you haven't subscribed to the channel, please hit the subscribe button and hit the bell icon so that you keep on getting these kind of courses and you can probably enhance your profile with the help of projects you build out of these kind of courses. Okay, so with that being said, as a shameless plugin of me asking you to like the video, let's move on to the next parameter, which is allow delegation. Delegation is a process of we giving it to another person a given task. Okay, so agent can delegate task where what it will do is it will ask within itself. Let's say I'm having 5 people in a team, and given a task, we'll just try to identify, right, who is good to do a specific task. So if you are good, take it. So for that, there is a parameter known as allow delegation. All right. So now you might wonder, okay, these are all sounding so overwhelming. So is the code also so tough? No, it is not. And that is what we are going to see now. The code is so simple. So here you can see the code. Okay, there are some other parameters which I can be able to explain here itself. Here the agent is provided with the role of data analyst and the goal is to extract actionable insights. That's fine. Now, the backstory is that you are a data analyst at a large company. You are responsible for analyzing data and providing insights to the business. You are currently working on a project to analyze the performance of our marketing campaigns. See, they have said that you are a data analyst. You have been working in a large company, but right now your work is to analyze our marketing campaigns, right? That is how the backstory is framed. Make sure your backstory is good whenever you create it. Next, you need to provide your tools. The first one is my tool 1 and my tool 2. You can provide n number of tools you want. Okay. And then you need to be providing your LLM, like I said. And then there is another thing, which is function calling LLM. Why is this parameter explicitly provided? You see, nowadays, there are lots of things which are done with the help of function calling. All right. Literally, I'm trying to build a JARVIS with the help of function calling. That shows how much power it has. And not every LLM is good at that. Okay. There are some special LLMs which are created for function calling. So what you can do is your main LLM will be focusing on doing the task efficiently, and the function calling LLM will make sure that the tools are called correctly. Okay. So for that, you can provide a function calling LLM by yourself, a custom function calling LLM. All right. So that is why the parameter is provided there explicitly. And then there is max iteration, which is provided at 15. Max request per minute is set to none, which means it will take n number of requests per minute. Verbose is set to true so that you will be able to see the logs. And then the allow delegation is set to true so that if there is something which is required, for example, to analyze the data, there is data required. So it will delegate this task to someone so that they will provide the marketing campaign data. And then this data analyst, he will try to analyze the data and provide the market actionable insights. All right. So there is also steps callback, and then there is cache, which is set to true. So if you set cache is equal to true, it makes sure that your process is not repeated again and again, and it will save you computation power. So that's why I said, guys, this CrewAI is amazing that they have focused on a lot of things, not just performance, but also the cost. That's why they have added parameters like max iteration, max RPM, cache, a lot of things. I love this framework. And guys, again, you might think this is sponsored by CrewAI, but it's not. I love this framework that much. Now, coming on to the next specific component, which is tasks. For tasks, the first important attribute would be description. As the name suggests, it is just a clean, concise, crisp statement of what the task is. Okay. let's say it is getting the marketable insight, actionable insights about the marketing campaign. That's what we see, right? It will say, okay, see, we are going on a loss. Just try to find a profitable action based on the marketing we have done before. This is a clean, concise, crisp statement which provides everything, right? So this would be your description. And then next, who is responsible to do this task? You will provide your agent, okay? And then we'll say, okay, this is my expected output. For example, if you want it to be a graph, you can provide a Python Ripple tool. Again, you can provide it in the tools parameter, and it will be able to write a Python code to do your task. For example, if you are asking it to generate a graph showing where all we gone down in the market and how we can increase that, it will be plotting a graph and then it will explain in below, okay, here are where we failed and this is how we can improve ourselves. Okay, so that is provided in the expected output section. To run the tasks asynchronously, you need to just enable the async execution parameter to true. And I already said about tools. And there are some scenarios which is highly complicated or sensitive that it might require a human input to make sure that it goes correctly. It is just providing human feedback, and default it is false. But if you provide human is equal to true, once the step is completed or that specific task, because a crew has multiple tasks to complete, and one single task, once it's completed, it will ask you a human input and you can provide it, and based on that the task will execute again as well. Okay, so if there is an output you need to store, for example, you want to store the actionable insights in a output file, just say like actionable insights.txt, you can just provide the file path and it will store it. And then there is also a callback function which you can provide, where a Python callable function will be executed with the output once it is completed. Now on to the code. See, to create a simple task, all you need to do is just provide description and agent, you will be done. But what if you want to say, okay, this is how my output should be and these are the tools which you can use. All you need to do is just create an instance of the tool. For example, here it is SerperDev tool, which is to ensure that it is able to search over internet by using Serper API. All right. So we are providing the tool and we are providing the description saying that you need to get the latest news, make a summary out of it. And the expected output is such that a summary can be anything, right? It can be a paragraph, it can be a single title, headline, but we're making sure that it is a bullet list of the top 5 news. Okay, so you are saying this is how I expected my output. So that is why we are providing expected output, and then the agent is research agent. If you wanted to add an output file, all you need to do is just put output file and then a file path saying like summary.txt, and it will be saving there. Okay, what if your one task depends on other? Okay, you need to get the context, right? So for that, what you need to do is first create one task, which is research AI task, and then there is another task, which is research op task. And here, this person is writing a blog, which is on importance of AI and its latest news. So for this, what it will do is, you need to do is just provide the description, expected output. Those are fine. Agent is also fine. But for the context of this, it needs to refer the research ops task output and research AI tasks output. This is also possible, guys. All right. And that's why I said this is a highly customizable framework and a very powerful one. So if this one provides the summary of top 5 AI news and summary of top 5 AI ops news, this is going to make a blog out of it. Very easy, right? Once you get the news of AI and AI ops separately, and then it is very easy to make a blog out of it. That is very easy. So that is why people use CrewAI to simplify their task, simplify a complex task into smaller tasks and do it with the help of AI agents. Now, my favorite section, which is what are the tools available? Man, this is OP. You want to put that way, right? There is, if you want to search in a code document, there is code doc search tool where you can provide the documentation URL and it will be able to provide that. If you want to search over your CSV files, use CSV search tool, directory search tool to just search a file in a directory, docx search tool for the same, directory read tool to read a file, or read a directory rather, and then a file read tool to read the file. Okay. If you want to search some code or relevant README file or whatever it is related to GitHub, you have GitHub search tool. If you want to search over internet to get the relevant URL, you have Serper Dev tool, which is a Google Serper API connection. All right. And then there is text search tool, which will be able to search with the text. Okay. These are all RAG tools. Okay. Whenever I put search there, it is going to be RAG tool, a tool which is based on a RAG tool. Okay. It will be able to search over text, a search over JSON, a search over MDX, a search over PDF. Whatever files we are thinking about, there is a tool directly ready. And if you want to make a RAG tool customized for your own file format, let's say you're finding something very new which is not there, there is RAG tool as well, which is a base class for all of these, and you can make an instance out of it and change it probably as much as you want. Okay. And then there is scrape element from website tool, and then scrape website itself. Okay. If you want to scrape an element from the website, there is scrape element. For example, if you want to get a table from a website, you can use a scrape element from website tool. But if you want to take the whole website, for example, if it is a portfolio, you can call the scrape website tool. And then there is website search tool, which will be able to search over websites again. And then there is XML search tool to search over XML. That is fine. But last two are something which was very useful for me, which is YouTube channel search tool and YouTube video search tool. That is what made me build my YouTube automation framework. And it was very helpful, So I recommend you all to check all of these tools out whenever you have a use case, because there are probably 10 to 15 use cases which I can think of with just these tools. Okay. And if you want to know about those, please stay to the end and probably I might stay there. Now, how to use these tools? All you need to do is, if those are in these tools, all you need to do is just make an instance out of it and provide it with the tools. Okay. Now you might say, okay, Vasanth, yes, you are correct. They are providing n number of tools. That is all fine. But I'm not finding a tool for my use case and it requires a tool. So what I'm supposed to do? Don't worry. There is an option for you to make custom tools. Okay. All you need to do is from CrewAI tools, just import base tool. Okay. There is a class known as base tool and you're going to inherit that and you're making custom tool where you need to provide name and a description of the tool. Okay. That's so what happens in this tool is I'll just explain. Okay. When you provide a tool, the AI is able to understand the tool with the help of JSON. Okay. There is a function in Langchain. I'm not sure about what is the function running behind in CrewAI, but since they're using Langchain tool and I've seen Embed Chain being used there, so something like that should be used. There is something like convert OpenAI into tools into something like that. Okay, convert tools into OpenAI functions or something like that, which will literally convert your tool, which is a pydantic data class, into a JSON. Okay, as simple as that. It will say, okay, this is the name, this is the description. And if you want to call that, these are the parameters. Okay, and it will be able to make a function call out of it. So if you want to do that, you should also make sure that you follow this. Okay. To run this tool again, see, you are just calling the tool, right? Here, if you see, you're just calling the tool here, but you're not just doing any functions out of it, right? So there should be an inbuilt function and that is _run. Okay. In this, you need to provide your argument, whatever argument you have. Let's say you have 10 arguments, that is fine. Okay. Once you provide the argument, the LLM will be able to understand, okay, I need to provide 10 arguments. That is fine. Okay. Don't worry about how many arguments you need to give. Make sure that the data type is good. Okay. It should be well documented following the PEP08 format so that it understands that, okay, this is what I need to do. Here you can see it is saying, okay, I need argument which is of a string data type and I'll also return a string data type output. That is how you create a custom tool. Okay. But this is not just the only way. Okay. For example, you don't want to use this kind of a thing. You just want to run a function as a tool. Okay. All you need to do is just call the @tool decorator and it will be fine. Okay. But what you need to do is, since you don't provide name and description, you need to provide a clear description with the help of a doc string. Okay. Make sure that you provide that and then you can provide your function logic in there. And that is how you create the custom tools. Okay. Now coming on to another important component, which is processes. You see, in organization, there are 3 different ways a process can happen. One is a pipeline where everyone would be working independent and there will be one manager who will make sure that everything goes into the flow. And then there is another thing where a person will depend on another person and there will be an order, sequential order. And then there again is another person where, okay, there'll be 5 group of friends. They'll try to build an application. We'll say like, okay, you do this, I'll do that. We'll make sure that this task is completed. Okay. And that is how the processes are also created. Sequential process is a direct flow, okay, which is one after another, is a systematic manner it will be executed, where the task execution follows a predefined order in the task list, with the output of the one task serving as context for another. Okay, the next task, for example, I'm saying a researcher and a writer task will get the output of researcher task regardless of being provided in context. Okay, but if writer requires two different task outputs, you need to provide it under context. Okay, so next we have hierarchical process, where there is a managerial hierarchy and there are lots of tasks under the manager which will do it. Okay, so the manager will split the task among the agents, and then the agents will do their task, and the manager will integrate all of those, oversee all of those, and will provide the output to us. And that will be useful when you have complex tasks for you to do, and there is not a sequential execution always which is there, because there is not always a systematic manner to do the task, and that is where you will use hierarchical process. There is a one process which is under implementation still, which I'm very much waiting for, which is the consensual process. Like I said, when there is a friend group, there won't be a manager, right? All five are equal, all will be splitting amongst them after having a big conversation amongst them. For that, there is a consensual process under development. Probably you can expect that very soon. And how you can specify these processes? All you need to do is, when you create a crew, you need to provide your process, that process.hierarchy. Okay. And if you provide hierarchical, you need to provide a manager LLM. Okay, make sure that the manager LLM is slightly different than the usual LLM, and probably better than the usual LLM, because this is what will determine your output more than the normal LLM, which is doing the simplified tasks. But if it is sequential, just call processes.sequential. That's all. Now coming on to the next one, which is crew. Tasks, what are the tasks? Agent, what are the agent? Process, we saw what are the process. If you're hierarchical, what is the manager LLM? Verbose to see the logging. Memory. Now coming on to that. To store the execution memory, there are lots of types of memory they have provided, which is short-term, long-term, entity, contextual memory. There are lots of types of memory they have provided, and you can utilize that to improve your performance. And then there is max request per minute. You can use to avoid rate limit error, and then full output, which is a Boolean value where you can provide by default as false. It would be, and you can provide true, where CrewAI will usually think by itself, and there will be a lot of thinking going on, and that will be logged, okay, by the crew. And final output, which is your final goal, alone will be written. But if you want the whole output, all just you need to provide is just provide full output to true. That's all. And to make the crew, all you need to do is call the crew class, provide the agent, task, process. If you want full output probably, and then the verbose. And how you can execute this crew, just call crew.kickoff. Okay. And a whole CrewAI function would be something like this. You'll be creating an agent. Probably there are two agents here. The two tasks which the agent needs to do, and the crew which will work in a sequential manner, and the output will be provided. Okay. And this is how a simple crew is built. The whole code is provided. Right. Now, coming on to the memory. I like why they have provided this memory, because once you say the LLM is making this wrong, usually it is very good enough to take the feedback and make itself better. Okay. So they have thought in depth, I guess, to make these kind of memories, because what are the things which we usually require in memory? Probably we would need to think of what happened recently and what happened long time before, which will be very important for us to build upon our knowledge. And then we'll always associate ourselves with some entities. Who I talked to, where did I talk that, or what did I talk about, something like that. And finally, we'll see about, okay, what is the context which was talked about on that specific time. All right. These are things which we usually retain in our memory, and that's what the creators of CrewAI thought. And they made 4 types of memory, where I just provided a 3. Okay. And the 4th one is contextual memory, which will retain the context. That is fine. Okay. That is conventional memory, like your vector database, if you want to put that way. And short-term memory is nothing but it will just store the recent interaction, enabling that agent will be able to recall what happened in a relevant context. For example, if you're saying summarize the conversations of what we had over time, and that will work in short-term memory. But if you want the agents to build upon its knowledge and refine themselves over time, for example, this is a company which is working for probably 1 month, and there is a pattern, where the LLM fails. Where, for example, for a specific word, it is giving so much bias. That will be solved with the help of long-term memory because it will be able to learn by itself over time. And then there is entity memory, right? To understand the context very much and have a good relationship of what happened, it will be able to capture and organize information about entities, be it people, places, concepts, and so on and so forth. It encountered during the task, and like that, like I said, it will help you to understand the task deeper and provide better results probably. And all you need to do to use memory is just set memory to true. That's all. Very simple. All right. And now we are coming on to the first project with this, which is Markdown validation. Before going on to the project, I would like to show you all about the CrewAI documentation, which is an amazing one, okay, where you have the core concepts, like I said, and there would be some optional parameters which I might have not discussed, okay, due to the course timing. I might have not discussed, and probably you can refer to all of these. And if you have any doubts, don't worry. The comment section is always active, and you can provide your comments there. And if you want some prior response, please join some membership. And you have lots of variants in membership, and probably you can have a personal interaction with me as well. Join the Telegram group for discussion. There are lots of things which you can do, but it is very important that after this course you go through this documentation, and the link is given in the description. All right. So now let's see about the Markdown validation. For this, I've just wrote a function which will be a simple code for you to run. Okay. But it is very important that you have all the things required. Okay. So how to set up? We'll go on to that first. Okay. If you're building it from scratch, let's say you don't have any prior project you have and you want to build it from scratch, then go for creation of a normal Python environment, but make sure that it is 3.10 because there are lots of dependencies in CrewAI which depends on Python 3.10. Okay, make sure that it is Python 3.10 and yeah, just install whatever it is coming up on your way. Okay, but if you want to set up these kind of a project which is there already, all you need to do is, here you can see there is PyProject.toml, where this is from Brandon Hancock, who is the author of this project, obviously. And thanks to him, I was able to take this project for explanation of this course. And he has an amazing channel as well, guys, for CrewAI. Please check him out. Okay. Usually the dependency is that it is 3.10 or 3.11, but I prefer 3.10. Okay. All you need to do is first install Poetry and then do the first step here. Okay. I have my environment set up, so I'm not going to do anything, but you can do this. Poetry install no underscore root. Okay. If you provide that, it will be able to install a environment, which is a virtual environment based on all the dependencies which is provided in here. And the name of the environment would be this one, Markdown Validation Crew. All right. And that is a one-stop solution. Okay. So once you do that, again, it won't be ready. Okay. There is another step, which is to run Poetry shell. If you run both of these, then you are ready. Okay. So once you do that, your setup is completed for this project. Okay. And then what you need to do is you need to create the next one, which is a .env file. All right. Now you might wonder, okay, what is .env? See, .env is nothing but a file where you can store your environment variables, which is nothing but your API keys and important variables. Those values can't be leaked over internet. You can store it in your .env, and when you're pushing into the GitHub, these won't be uploaded. Okay, and that's why it is provided in .env file. All you need to do, how to create this. This is a common question I get. I'm just gonna show now. Okay, so just click new file and let's do env. Just enter, put your API key. That's all. Simple. Okay, simple stuff. So here we'll be requiring Grok API key because I'm running Grok LLMs, but you can provide whatever you want, be it your OpenAI. Yeah, that's what I was trying to say. OpenAI or Azure OpenAI, whatever it is, Mistral probably. You can run any of these with the help of this, or run it in your local with Ulama. All is fine. So you need to provide the API key. I'm going to provide mine. Okay, I have set my API key. So here, but this is not how usually Crew works. Let's say you have a systematic manner, all right, but you don't want to risk on Crew to make the decision of the calling of the functions and all. You can do this kind of things as well, but this is a very simple project. Okay, so for this, what I did was I took my LLM, which is Grok, and I have provided my API key and the temperature model name. These are all fine. Okay, but what is very important is once you provide a function, please make sure that the description is very much informative, as informative as possible. Okay, so here I've said I need to process a markdown by reviewing its syntax validation results and providing feedback on necessary changes. The arguments are file name, which is a string that is a path to the markdown file to be processed, and it will be returning a string. Okay, that is fine, which is the recommended changes. This is what is the function. But if you see, this is probably a description to the agent as well, but it is very important that you keep it very much descriptive. Okay, the agent here is the requirements manager. Okay, and the goal is to provide a detailed list of markdown linting results where it will try to provide a summary of what all the tasks you can do to make sure your markdown looks good. Okay, but here we are also specifying that okay, you need not provide any example or how you can use tools. Just provide what all can be done syntactically. All right, that we are providing in here. So backstory is that we have said it is an expert for business analyst and QA specialist, where it has the capability to be very thorough, insightful, and it is very good in providing actionable feedback for a list of changes and actionable tasks. Okay, so we have just said that okay, you are an analyst and you are good at analyzing things. Please provide the correct things. And we have said the allow delegation set to be false. Right now, you might wonder, why allocating delegation is set to false? See, if you think in a way, right, I'm just going to analyze it and I'm going to say what are the changes. Why do we need more than one agent? No, right? So just provide all of delegation to be false. Verbose is set to true, and then the markdown validation tool is also provided. Along with that, we are also providing the tasks, which is the syntax review task, where we're saying, okay, use the markdown validation tool. See here. See the name. Okay, very important. Very, very important. Make sure that the tool is specified correctly, because it will just call markdown underscore validation underscore tool. If I did something like this, it won't work. Okay, so make sure that it is correct. And we are saying that okay, you need to provide this file alone to the markdown validation tool, and the file path would be here. So the file path would be read by the markdown validation tool, and it will provide some changes. Now, coming on to the next question, you would think, okay, Vasanth, where is the validation tool? Here it is. See, like I said, you can build custom tools, right? So there is a PyMarkdown package in Python which will be able to make reviews on syntax errors. Okay, and all we are doing is we are just scanning the file which is there in a path, and then we'll be providing the result as a string. Okay, so that is what happens in this markdown validation tool, which is taking a file path which is a string, and it is also returning a string output, which is the changes. All right. And if it is not a crew and you want to execute a task, all you need to do is call the execute function. Okay, so that is what we are doing here, and we are getting the markdown. So let me show you how you can execute this, and I'll also show you some advanced projects in the next steps. Okay, because this is a very simple project, right? I'll show you some advanced projects, and I'll also show you some next steps what you can do to improve yourself in this. So all you need to do is Oh, see markdown validation crew Python main.py. If I run this, it will give me the output. So let's wait for that. Now you can see it is showing entering new crew agent executed chain. Okay, and this is shown because you have provided verbose equal to true. So the execution was completed, and as you can see here, it is just checking, okay, do I want to use a tool? And it is saying, yes, I need to use a tool. What is the tool? I want to use the markdown validation tool. Okay, so what is the input for the tool, which is readme.md file. Okay, and once you provide that, it is saying here, these are the lint results. It is saying line number 5, all are saying something like line length. Okay, all are line length. So it said, okay, in line 5, the current length is 288, adjusted to 80. It is probably there is a convention, I guess, in Markdown that you need to have some 80 length. And that is what has been missing in the README file. And that has been found correctly. The final answer is provided. And probably if you want to put it into your output file, just provide output file path. And that is how you build your first project in CrewAI. So if you want to build an API, all you need to do is just call this function in a API call, probably in Fast API or Flask, or build a Streamlit application. Everything is fine. And now let's see about another project, which is stock analysis. So for this, what I'm going to do is I'm going to go into an official GitHub of mine where I have the code already. So let me go there. The projects NHV, building AI startups with CrewAI, stock analysis company. So here what I did was I created different stock analysis agents. I'm not going to explain it in detail now, but you can see here I have provided multiple tools and have set max iteration to 30. You can provide whatever you want. Okay. And then there is goals, roles, backstory, everything is provided. Same goes for investment advisor and the other things as well. But I have provided multiple tools, and that's how you need to provide. Okay. And here you can see you can also use Olama. And when you complete it as task, here is how you need to do it. Okay. You will be just taking the input here, and the task is being completed by itself. Okay. The same thing of tip section is followed. The tip section is nothing but if you do your best work, you'll get some commission. Okay. Just to motivate the LLM. Funny, but it gave good results. I'll be very honest with you. When I added that, it gave me good results. I'll be very honest. Okay, but you have all the things ready, but you can't call the execute function, right? So that is why I had CrewAI's crew class. Okay, so first I made instances of the agent, instances of the task, and I provide all the tasks and agents. Since I didn't provide any process follows, it will be just following a sequential process. Okay, first research will be done, then financials will be analyzed, and then the filings on the company will be analyzed, and then it will recommend on something. Okay, and I'll be calling the CrewAI's cruise kickoff function, which will kick the crew to start. Okay, and that is about your first project. So your first project, which is Markdown validation, is completed, and as a bonus, I've also shown you another project, not detailed, but I've shown you, right, how it works. All right. But what are your next steps? You see, the best way to learn this kind of framework is to do projects. Okay. Explore the different amount of tools, combine that, explore your creativity. But what if, let's say, I'm a beginner, Vasanth, I don't know how the framework works. I need to experiment with a lot of projects. That would be the next step, explore with advanced project. And I have provided a link here, which is 2 examples. Okay, there are lots of things. For example, see here, this is something which is going to come in our channel itself, where I'm going to show you how you can automate your email. Okay, here there is a game builder group, how you can make Instagram post with the help of, how you can automate Instagram posts with the help of CrewAI, job posting platform, landing page generator, markdown validation, which we saw now, and then how you can prepare for a meeting, how you can write screenplay. So how you can analyze stock, how you can plan for trips. There are lots of things, right? See, we won't even think these kind of projects at first, right? But like I said, there are endless possibilities what you can do with the help of CrewAI. And as a bonus tip, I'm gonna show you an one advanced hack which I haven't explored a lot yet. So I'll provide the link of this video in the description. Okay. I don't care about recommending other channels. It's fine. If someone provides good content, I need you guys to have the best. And the creator himself of CrewAI said that this was an amazing one, and I'm halfway through the video, and it was so good. Okay, because see, when you are executing CrewAI, right, the one thing which comes into my mind at top is cost. What is the thing which goes on with the cost, and how is it working on behind? For all of these guys have provided one solution, which is agent ops. The agent ops is very good, it seems, where once you provide, right, all the logs are stored in this agent ops, it seems, and I have heard a lot of things. You can see here, everything is stored. Okay, you can provide your API keys in there, it will be loaded from there. Lot of steps. This is one advanced hack. And then make sure that you're good with Langchain tools. That is the second thing. Okay, Langchain tools are very important, and have an understanding of Langchain tools, because with Langchain tools only you will be able to work with CrewAI very easily. With ease you can work with CrewAI. So that would be my two advanced hacks, and also go through this how-to guides. You will get an idea of how things works. Hey everyone, I introduce you all to my new personal assistant, Jarvis. What's really amazing about Jarvis is that he's built entirely from free components and APIs crafted from scratch as well. He's got some serious skills too. Jarvis knows my schedule inside and out and manages all my meetings, that he can set up new ones as well whenever I ask him to. He can access my monitor to explain what's happening on my screen. Also is hooked up to my webcam so that I'm safe, and also explain what is going around me as well. Plus, I've given him access to my clipboard, so whenever I have a question, I can just copy the content and he's on it. And that's just the beginning. He's a great fun companion, he's a great teacher, and the best part is that all of these capabilities of his are powered by completely free components. Let's dive into the system architecture to see how these pieces fit together, and then we'll go on to the code so that you can build your own Jarvis. The architecture of Jarvis involves several free components, several key components, each with its own unique task. First, we record the user's voice to capture the command, and then we transcribe the audio using an open source version of OpenAI's Whisper, and the best part is that it's even faster. Next comes the heart of the Jarvis, where it is function calling and function execution. Jarvis has lots of capabilities with each as function, and we use large language models to understand the user's command, which was obtained by transcribing the user's audio, and then we'll call the appropriate function to get the job done. These functions access the tools that helps Jarvis to complete the tasks provided. After executing the right tools, the LLM generates a response based on the function's output as well as the user's input. Finally, the generated response is converted into an audio and is played back to the user. Now we have broken down the components involved, but it is time to go one step further and understand what is going on behind each component and how you can create this architecture so that you can also bring this architecture to life. Stay tuned, because by end of this video, you'll see just how powerful and accessible creating your own personal assistant Jarvis can be. Guys, before moving on to the code, it is only fair that you understand what is the result we are going to obtain out of this video. So let's see a demo of Jarvis and then we'll see what to do next. Wake up, Jarvis.
Sir, I'm awake and ready to assist you. How can I help you today?
Jarvis, what are the meetings I have today?
Sir, you have no meeting scheduled for today. Your next meeting is on 2024-05-31 at 21:30. Zero event. Jarvis Part 2 discussion.
Okay, Jarvis, can you help me schedule a meeting? Okay, now it's asking me the date and other information. Probably we can soon add this capability as like so that it will ask and then it will parse something like that. Right now I haven't had added those kind of capability to ask input dynamically. Okay, so here I'm providing the date as 1 June and time probably 0800 am, and then the time ending up is 0900 am, and then the title would be Jarvis created, something like that. Okay, by the end of this demo I'll also show you that this event is created by Jarvis. Okay, for now let's click this enter and it will ask me the access which I'm gonna provide right now, and I have provided it. So it should say that the event creation is successful, and here you can see it is showing the event. Great, Jarvis. Jarvis, what do you see in my screen?
It's the programming project in progress showing code related to the data management and game control application.
Jarvis, what do you see in my webcam? This is my grandfather actually.
It appears to be a serene room with a framed photo of a man on the wall, adorned with flowers. The room contains various objects, including a sign, papers, and figurines. The overall atmosphere suggests a space for contemplation or worship.
Amazing, Jarvis. Jarvis, what do you see in my clipboard?
It appears to be the content of your clipboard, showing
As you can see, I have just copied actually.
It's an HTTP request made to the Grok API to create the chat completion.
Amazing, Jarvis. How about let's take a break and have some coffee? Is it fine by you?
Virtual pause to assist you anytime you'd like to resume our tasks.
Okay, before ending, I would like to know about your thoughts on yourself as Jarvis.
Assistant, I'm designed to provide helpful responses and assist with tasks to the best of my abilities. I don't have personal thoughts or feelings, but I strive to continually improve and adapt to your needs.
Yeah, that's amazing. Explain to me like that I'm a child about what is artificial intelligence.
Okay, imagine you have a super smart, magic friend who can help you with anything. Artificial intelligence, or AI like me, is like a special kind of computer program that can think and learn like a person. But instead of having a heart, brain, and body like you do, I'm just a collection of code and data that can help you with tasks and answer questions. I can remember things, recognize patterns, and even talk to people like we're having a conversation right now, but I don't have feelings or emotions like humans do. I just exist to make your life easier and more fun. Isn't that amazing, sir?
Ha, you are funny, man. Yeah, thank you for the explanation, Jarvis. Take a rest.
I'll be here when you need me, ready to assist and respond to your queries. Take care, sir.
Bye, Jarvis. So yeah, guys, hope you would have liked the potential of Jarvis shown here. This is just a starting point of what we'll achieve at the end of the series, because this is gonna be a series of videos where I'll be adding more capabilities to Jarvis as shown in the tasks.txt file here. I'll be providing access to file system, providing access to different file applications, search websites, and get the weather, alarm, screenshot. Basically, for whatever things we would need a personal assistant, every capability will be provided. You could have seen right now he was able to schedule a meeting in Google Calendar, and that's what we are going to see now. As you can see here, guys, this was my existing meeting that I have a discussion from 9:30 to 10:30 p.m. on JARVIS Part 2 discussion, which it found out. All right. But if I go to June 1, right, here you can see JARVIS test meeting. It created by itself, actually. Okay. And that's what I like. And here you can see another meeting, which I showed in live right now, which is JARVIS created. Okay. JARVIS test meeting was a meeting which I tried to create by myself. And then we have JARVIS created, which is 8 a.m. to 9 a.m., like I gave in the meeting on the command line before. So you can see that there is a tremendous potential here. So now that you have an understanding about the architecture, the potential of JARVIS, I think it's a high time that I go to the code right now, because I think you would all be interested to know about how you can create an assistant like this by yourself, that too with free components. So yeah, guys, just now we completed seeing the potential of JARVIS, and also we saw the architecture which we need to create such a powerful assistant. And we shall see now the code by which you can also create a JARVIS like this. So before going on to the code, guys, I would like to ask you all a request of please hit the like button if you haven't hit, because this video takes a lot of effort, and it would be very nice if you can appreciate that with the help of a like, and share it with your friends who you think might benefit from this video. Also, if you haven't subscribed to the channel, please subscribe, because only 30% of the viewers who are watching the video right now are subscribed. So if you consider this channel is useful, please subscribe the channel. I hope you all like this video right now. Let's go into the content now. To create this kind of assistant, which is very powerful, we would need multiple files. As you could have seen here, there are lots of files, and we'll go inside each file following the code in here. Okay, if you remember the architecture, the first one would be to record audio and then transcribe, and then function call, function execution, generate response, text to speech, which is generate audio probably, and then play audio. This is the architecture, and that is what is implemented here in different functions. You could have seen here: record audio, play audio, transcribe audio, generate response, text to speech. All right, all of those core component is ready, and all of these extra capabilities are provided as functions. Okay, other than this, we have colorama library to give some color while logging. In the demo you would have seen some teal color as well as some yellow, red, different kind of colors, right? Those were due to the help of this colorama library, and you need to initialize that. So for that we have init library. Logging to log, time to have some time being logged. Okay, and then we have some other util functions like delete file, and then here we have the find function, which is the function call file. Okay, next we have an API key manager in which we can store our API key. We have a function called get transcription API key, get response API key, get TTS API key, which is nothing but your text to speech API key. And here are the capabilities right now, which we'll add in future, and probably when I add in future, this project will be rewritten in some other way. Like I said, this is just the project first in a series. Okay, here I have the class JARVIS, in which we are going to initialize the assistant with the help of this system prompt, in which we are going to say your JARVIS close similar to the same JARVIS in Iron Man movie. You are a helpful assistant. Keep your answers short and concise. I'm Vasanth, your boss, who is an AI engineer. Address me only as sir. Okay, this is the prompt which we are saying, and that's why when I asked, it will say like I'm in Stark residence, something like that and all. Okay, if I hadn't said like you are the same JARVIS in the Iron Man movie, it wouldn't have said that. Okay, so now we are getting the three API keys, which is transcription API key, response API key. Response API key is nothing but your LLM API key, and then we have text to speech API key. And for each, what we are going to use is that for transcription, we are going to use Faster Whisper, a local model of OpenAI Whisper, but it is faster than OpenAI Whisper actually. we are going to run distill whisper, and you will see that when I call the functions actually. Okay. And for response generation LLM, we are going to use Llama 3 running on Grok. And for text to speech, we are going to use DeepGram. Okay. For all of these, there are free API keys. At some point of time, it will become paid. That's fine. At the time, probably we can rewrite this. And that's why I made this kind of a structure. Okay. Whenever we have a problem, for example, if I want to change text to speech, right? All I need to go is going to text to speech. I can change it to PyTSX so that we won't be depending on DeepGram. Okay. So this code is very extensible and very, you can easily change the code whenever you want and however you want. That's how the code is written. So yeah, no problem. Now this is another function which is def response generation, which we'll come to later, because the function which we need to look is run JARVIS. You can see here, if underscore name is equal to underscore main, JARVIS equal to JARVIS, I'm creating an instance of the class, and while true, just to make sure it continues the conversation, JARVIS.run JARVIS. Okay, so I'm just running the JARVIS, which will start to record the audio first. Let's go into that function. In record audio function, we are getting the file path, timeout, phrase time limit, and retries. First, I'll explain the code. Along with that, when we are going into the listen function, I'll explain the parameters as well. Okay. We are creating a recognizer instance, which will just recognize the microphone, and then it will, listen to it. Listen via that microphone. Okay. It will recognize my audio, and then it will listen to my audio. Okay. So for that, we are using speech recognition library. And it's not that always you will be able to record the video or the audio rather in the first attempt itself. So we have 3 attempts where we'll try to make an instance of microphone, which will be our source, and we'll log it as recording started. And here we have the recognizer.listen function, in which you will provide the source, which is your microphone, and timeout is nothing but, for example, I want to ask a question like wake up Jarvis. All right. If I say that after 5 seconds, it should be waiting for 5 seconds and it is fine. What if I make it wait for 50 seconds? It is just time waste for us also, right? So the timeout is how much time will be given for a phrase to start. That is timeout. Okay. And the phrase time limit is nothing but how much time is allowed for the recording. For example, I can record up to 20 seconds right now. That is what is given here. Phrase time limit is equal to 20, and I should start at least by 3 seconds. Retry is also 3 allowed. Okay, you can change this, but it's fine in this configuration itself. So once the audio is recorded, we'll log it as recording is complete, and we'll write that audio as a WAV file. That is what is stored in here. Okay, it would have been stored in here, which I deleted. All right. It would be in the file path you saved .wav. Okay, .wav extension file will be saved here. But we'll also do some exception handling here, where we'll state that okay, here the listening timed out, we'll retry it, and if you are not able to record the audio itself, then we'll say fail to record audio. And if the tries is also over, because the try except completes here, we'll state it as okay, logging that error, recording failed. Okay. So that's how we will record the audio. And now we saw how to record the audio. Okay, your audio is now ready. Next step is to transcribe that audio, right? So we have the transcribe audio function, in which here if you see, I'm providing the output file path as input that WAV, and that would be a parameter to the transcribe audio function as well, where you'll get model, API key, and audio file path. And for model, you should go to the config. Okay, here you need to provide your configuration for the whole architecture here. So what are the models, or what are the components you will require? For recording, again, we are going with some Python class, and for playing also, we are going with some Python class. So what are the things which are required right now? Transcription, output generation, and then again convert that into an audio. So for this, we are going to use 3 different models. For transcription model, we are going to use a local model, which is Faster Whisper. Okay. And how to install Faster Whisper? All you need to do is just do pip install Faster Whisper. Okay. And then we have the response model, which is Grok. Okay. In Grok, I'm running Llama 3. and for that you will need an API key as well. For text to speech model, we are going to use DeepGram. Okay, so these are the things which are going to be used as components, and you need to provide your API keys here as well. Okay, I have already kept my API key, but you should also provide yours. Okay, so make sure that your configuration file is set. Okay, these are just some checks. You need not worry about these checks at all. Okay, it will work as long as you provide the API key. So now we'll see the transcribe audio function where you are providing the model to be local, and the API key is already provided, which won't be needed right now, but it has been heard that Grok is going to soon provide whisper access to everyone. So for that, I have already provided the code in which you can use Grok as well instead of local model, making it very scalable. Okay, and then we have the audio file path. Okay, so since it is local, we will see the local now. Here I already created a Whisper model, which is Whisper model from Faster Whisper library, in which I'm just using the distill small.en model running on CPU and int8. You could have seen the response was too soon, right? Like it converted into text very soon, but it was running on my CPU, not my GPU actually. Okay, so the transcript function takes 4 different parameters. One is audio file path, beam size, what is the beam size to be used for recording, what is the language, which is English, and condition on previous text as another parameter. Okay, so here we have a list known as transcriptions, because Whisper model is very good that it happens in real time. Okay, it will do the transcription in segments, and so what we'll do is we'll get each segment text and then we'll combine those by appending those into the transcriptions list and then joining those as a string. Okay, so that is how you'll transcribe the audio, and that is written here. Okay, and that is what we return. Those are the transcription. Okay, if there is any other problem, for example your model is not there, we'll say unsupported transcription model, and if you go with any other error, we'll say okay, fail to transcribe the audio due to this error, and we'll return that okay, error in transcribing audio. Okay, so that is about transcribe audio function. And once you get the transcription right, your user input ready, so we are going to log that with the help of logger. Okay, we'll say that you said this thing. Okay, now you have your user command. So what do we do next? We need to find the appropriate function and then make that function call. Okay, so for that we are going to use the find function where I've formatted a string here. Okay, where I've said you have access to a lot of Python functions which provide you the capability to do a lot of tasks. Here are the functions. All you need to do is provide the functions here and the purpose here. If you add any other function, just don't do any problem. Just say and then do just this. That's all. And if it is thinking that this is reliable, it will go into that. Okay. So how that happens also we'll see now. But right now, if you see, I have provided the get events function, which is to know the list of events and meetings I have, create event function to create meetings, explain webcam to access my webcam, capture it, and then explain what is going on around via my webcam. Same goes for screen. Same goes for clipboard prompt as well, to know, to just have an access to whatever I have copied as content and explain that in general, to make sure that if any of these are not matched, it will try to answer based on its knowledge itself without using any tools. Probably in future we'll add RAG with website access and all. That is for future. Okay, now I'm saying okay, now based on the function provided and description provided, return the function name that suits to do a given task as follows. Okay, I need an output like function is to function name. That's all. I'm not even asking the parameters, I'm just asking function name. So here in Grok, we are going to use Grok, but a different instance. Okay, that response model is different. This is different. This is function calling model. For function calling, Mixtral is said to be better than Llama 3. So I used Mixtral, where I'm saying the system prompt that you are great in accessing tools. And for user, we are saying, okay, this is the string. Okay, we are going to provide the string and ask it to provide the answer. Okay, here we are providing temperature 0. Streaming is made to be set to false because in JSON mode, streaming is not supported. And in response format, I'm asking a JSON object, okay, so that it will be easier to pass. But in JSON also, it will be returning a JSON string. We need a JSON dictionary. So all you need to do is just call ast.literallyval, and then we'll call the chat completion.choices of 0.message.content. Okay, this will have the output. And we'll say, okay, this is the function. Okay, but make sure that you also have your grok API key exposed via os.environ function like this. Okay, os.environ of grok API key equal to an empty string. I have provided here. You should fill your API key there. So that is the function call. Okay, now you'll know the function. Okay, which function is that? But you need to execute that function, right? So for that, I have already provided a function known as response generation. Okay, if you go into there, it will take two parameters. One is function to perform, and then another one is user input. In function to perform, it will be just input for if conditions. Okay, in future, I'll probably make this also automated by help of exec Python function, which will be executing any Python code when it is a string. Okay, that is also possible. Probably I'll do that in the future, but right now I'm just making if condition where the function is decided by LLM by itself. Okay, this is not just a simple if condition. It is an if condition decided by LLM. Okay, where I'm checking the function here, you can see create event or get events or explain webcam, and based on this you can add anything you want. Okay, in all of those there are some commonality. Okay, we'll have a chat history here. You can see the system prompt is already provided, and you need to append the user input along with the response text of assistant as well, so that the LLM remembers what is going on in the chat history. Okay, so make sure that once you get an input or get an output, you will append that into chat history, because this will be repeated in all if conditions. I'm not going to explain those actually. Okay, so the first thing here is for get events, I'm having a function called get events itself. I'm planning a separate video on different Google capabilities actually. So accessing my Google Drive, accessing my Gmail. At the time, I'll explain in detail about this thing. Okay. Right now, I would even suggest, you can comment these two, or if you want me to explain in detail, let me know in the comment section. I'll try to make the video on Google APIs very soon, because this takes a lot of time to set up the account and then get a lot of access to it. And as you can see here, there are lots of codes in here. Okay, I'm planning a separate video on Google automation itself. Okay, I'll be focusing on Drive, Gmail, Google Sheets. Also, I'll probably do Google Calendar, Google Meet, where, for example, if I create an event now, right, it will just log it in my Google Calendar. But if I create an event, it can schedule a meeting and also add that as in the calendar. So for that, it will take a lot of time. So I'm probably planning a separate video on that. If you all want that, please let me know in the comment section. I'll make a video on that. And that time itself, I'll explain this as well. Okay. Right now, we'll start with the explain webcam. If you think, right, if you have thought, okay, Vasanth, you said Grok Llama 3, how it would have seen your webcam, and also you said it is gonna be free. If you have thought that, it's a great thought. Applause to you all. And here, what I'm doing is, I'm using another LLM, or a VLM rather, which is Lava 5.3 run on Ollama. I've already made a video on Ollama VLM inference. So if you want to know in detail about that, please check out the video. The link will be in the description. Okay. So here I'm having different functions. So I'll explain those. Okay. For Ollama, it is very important that you have an image as a base64 string. Okay. So we have a function for converting the image into base64, where it will save the image as a buffered image first, and then in the format of JPG, and then it will convert into base64. Okay. And here we have provided a function to display that image. And image preprocess function will do all the preprocessing. Once you give the image path, it will convert into RGB, convert into base64, and then it will plot it, and it will also return the image base64 string. The most important thing would be chat with the image function, where we'll first preprocess the image, and we'll call the lava model, in which you need to call the bind, which will combine the lava model with the context of image, okay, where you will provide the image. So that is its environment now, okay. Lava has the image as its environment, and you can ask any question to that right now, okay. Probably we can make this as a chatbot. If you want, let me know at that as well. I'll probably make a separate video on that. By the way, guys, like I said, this assistant can be developed for on and forever, and then we'll be able to not even touch our laptop, our computer for that matter, okay. But here there are two specific functions which I've used. One is explain webcam, another one is explain screen. For webcam, I need an access to my webcam, and for screen, I need an access to my screen, okay. For webcam, all you need to do is just run this explain webcam function, in which first you'll go into the capture webcam, where you'll capture one specific frame from this webcam. But if you want, you can also make this as a video by just changing the logic a bit, okay, where you'll store the name as image.png, okay. So here it will become image.png. And if you want to explain your screen, right, for that you'll call the capture screen function, where you'll call the image grab, which is a class from PIL itself, okay. PIL is pillow library. In that there is a grab function which will grab your screen image, and then we'll convert that into RGB, and we'll save it as image.png itself, and then we'll call the chat with image, which will pre-process, make an environment context, and then we'll ask the question, okay. That's how explain webcam and explain screen happens. And then we have the clipboard, okay. For clipboard, we have the clipboard prompt function, in which all you need to do is just call the Piper clip function, and then there will be a function called paste, which will paste whatever you have copied in your keyboard, and then we'll check if it is a string, okay. Because if you haven't copied anything, we'll say nothing is there in the clipboard. If there is a value which is copied, for example this one, if I copy, right, if I go and do this one, all I'll do is just see where is notebook, just do dummy.ipynb, okay. I'll do this. See here, I'm copying this, okay. And if I run this now, it will show you. Here you can see, right, it is showing me the for whatever I've copied. So that is how you will access your clipboard as well, and that's what we are giving here. I'm formatting the input itself, stating that okay, this is my question and this is my clipboard content, what is happening and what do you see in my clipboard, something like that, okay. So now you know how clipboard is answered, how is my screen related questions are answered, how is my webcam related questions are answered. Now, what if I don't have any of these and I want to ask a general question? All you need to do is just call the generate response function, okay. And here you can see, right, always we call the generate response function, all right. Always what we do is we'll just format the prompt, and then we'll call the generate response function, that's all, okay. Here also you can see the image caption or image question answer will be generated here, and we'll ask the LLM to make its own response based on the response generated by Lava 5.3, okay, because the response of Llama 3 will be always better than Lava 5.3, right? So we always call that, okay. Always generate response will be called, and the generate response function will have an instance of the Grok client where you will provide your API key, and we'll call the Llama 3 8 billion. I'm not even using Llama 3 70 billion for faster responses. I'm using Llama 3 8 billion, and we'll just respond as response.choices of 0.message.content, which will provide the response, okay. So that's how you'll generate the response, and then we'll add the response to assistant, okay. Similarly, it happens for everything, even including general. But what if none of these tasks are matched? For now, it would be sorry sir, unable to do the task provided, okay. That is just for handling the problem. Now you have your response, okay. What is the next step? For now, we are just logging that in cyan color, stating that this is the response from the model, and then we'll convert this response into a speech with the help of this text to speech function, where you'll have deepgram, okay. All you need to do is go to deepgram website, click create new API key, and it will be creating it. I think it's 1000 or 100 credits. I think 1000 credits are for free. Yeah. So I don't think we are going to use 1000 credits. So it would be more than enough. Alright. So in DeepGram client, you need to set your API key, and then we have the speak options class where you can provide the options for your conversion into speech, where the model is going to speak, right? So that's why they have kept it as speak options. The model I have chosen is Aura Helios EN because all the models I have heard, that is the model which is very close to Jarvis voice. So I have kept it as Aura Helios EN. Encoding is linear 16 and container is WAV. Okay. And we are storing the output or the speech as WAV file. Okay. That's what we'd have provided here. Output.wav. Okay. Along with it, we are also providing the response text, model name, which is DeepGram, and then their API key. Okay. All we need but is the output file path and the speak options, okay, along with these options as well. So in the speak options, we'll say, okay, text is text, and then here also we have provided the speak options. All these are provided, okay. So that is the response, but we are not gonna call the response anywhere, right? We have already saved it. That is what we need. We are generating the audio and then we'll play that audio later, okay. Now the audio is generated and it is output.wav, okay. So we'll call the play audio function in which we are going to use Pygame. In Pygame, it has capability to do anything. For example, creating a game. Actually, it's very much easily possible with the help of Pygame. And in games, music are a very big part. So you can load music and all. That's what we are loading. Okay. In music, we are loading the audio file and we are playing the audio. Okay. So output.wav will be played, and if the player is busy, it will wait for a second and then will play. So once the audio is played, it will stop it. Okay. If there is any error, we'll say fail to play audio along with the error, and if it is not due to Pygame, right, we'll say okay, there is an unexpected error. So this is the error. That is handling the errors. Okay. So that's how you'll play the audio, and once your audio is played, then yeah, you're good. If any of these places where you run the Jarvis, you face an error, it will be showing, okay, an error occurred, and then it will delete the input file, and also if the output file is there, it will also delete the output file. Okay. So for this, I have a utils file known as delete file. Okay, where you will remove the file which is provided, and if you are saying okay, file is not found, it will say okay, file is not there, and if you don't have the permission, it will say okay, there is not any permission for this, and if you still face any other errors, you will say okay, error deleting the file. So this is just, I've made sure that all of these are in try except so that you won't face any error and stop the program, it will be continuing. Okay. So that is how you'll create Jarvis, and like I said, you are gonna have a separate video. Already you can see it is already around 35 to 40 minutes video. If I had explained about the calendar right, it would be around like 50-55 minutes. So I'm gonna explain about the calendar separately in another video. But if you all want, like I said, all the automation on Google, let me know. We'll do that as the next video in the series. With the recent advancements in the field of LLM, especially moving towards quantized LLMs and making very good performing LLMs in very less number of parameters, now it is possible for us to run LLMs in our own Android devices or iOS devices. In this video, I'm going to show you all how you can create a mobile app in which you can run your own LLM locally in your mobile itself. And for this, I'll be using Gemma, and I'll also show you how you can use your own custom LLMs and run it on this application. At the end, you'll be building an application like this, and now I'll show you a demo of what we will achieve in this application first, and then we'll move on to the code part. Now, as you can see here, I have MediaPipe in my Android device, and I'm going to open that. It is opening, and as you can see here, it is showing my MediaPipe LLM inference and response generated by user provided model. The application is opened, and now I'm going to type a question for this model. What is machine learning? So as you can see here, I have typed a question, what is machine learning? And now I'm running it, and it is generating in my mobile. This is completely in CPU and not in GPU. Okay. and this is completely running in my mobile phone and not in my laptop or anywhere else. And as you can see here, it is giving the results in great speed, that too in my mobile phone itself. The results are also pretty amazing, I'll say. So this is what we'll achieve at the end of this video, where you will also know how to build an application like this to run your own LLM in Android devices. So right now you would have seen a demo where I ran a question of what is machine learning, and it gave a detailed response where it would be a maximum 120 tokens, because that is how I set for the LLM. And now I'm going to show you all how you can do this with the help of MediaPipe. MediaPipe is a library or a package from Google for the developers. It has support for a lot of tasks, and as you can see here, there is support for landmark detection, there is support for face stylization, lot of vision tasks. They haven't focused a lot on NLP, but right now they have started to focus on NLP as well, where they now give support for inferring LLMs. Okay, so we are going to follow whatever it is given in this inference guide for Android. Okay, so you should have all of these ready. So for this, you would need the following. So let me go to Canva. First, what you would need is, you would need a LLM which is quantized and is in TF Lite format. Okay, that is very important for you to run your LLMs in your local machine or your local mobile devices, or even edge devices for that matter. Okay, TF Lite is TensorFlow Lite, and that is again a framework of Google. Okay, so if you don't know how to convert your model into TF Lite model, don't worry. Still, I'll also show that how you can do quantization and conversion of your model into a TF Lite model. All will be covered. Okay, so after that, you need to clone the application repo. Okay, so this is the repository where they give a baseline for your LLM inference application. If you think, okay, I'm not going to customize a lot, I just want to run my model in mobile, yeah, you can follow this specific code itself. And if you want to customize the UI, if you are a good Android developer, still you can make some changes in the code part as well. But right now I'm not going to do those and all. Okay, because our aim is to run the LLM in our mobile application, not to build a good UI and all, right? Okay, so once these are done, what you would need to do is, you would need to set up your emulator. Okay, so for this, instead of emulator, I use my mobile device directly. I'll also show you how you can do that, but it is required for you to have an emulator. Before that, you'll also need to have Android Studio and emulator, for which you will need an Android phone with version more than 7 and developer mode enabled. Okay, these are the requirements for you to have for this specific application. Okay, so first let me show you how you can quantize your LLMs and store it in TF Lite format. Here there is an notebook, Jupyter notebook. This is from MediaPipe themselves. What you need to do is, for now they have given support to 4 to 5 models. Okay, they have support for Gemma, they have support for Falcon, Stable LM, and I think they also support Phi actually. Okay, so because these are the models which are available in low parameters. Now I'll show you how we can execute this. So first what you need to do is take a copy to your drive if you want to. In setup, if you see, they are installing MediaPipe, Torch, Hugging Face Hub. Let it run. If you are, let's say in our use case, let's say you are downloading Gemma, okay? You will take the Gemma folder or the Gemma model from Hugging Face Hub, and in that we are considerate about two specific things only. One is the model and another is the tokenizer. So for tokenizer, we need tokenizer.json and tokenizer config.json, and in model we need model complete model. And here if you see, it is two shards. So here it is 00001 and 00002. If it is 10 shards, you need to load 10 shards. Okay, so those paths are given. You need to provide your Hugging Face token and then we'll download it. Okay, so that is the first step where you need to download it. Okay, so once you are downloaded, next what? You need to have it in your local, like I said, and then in MediaPipe itself, there is a specific converter for you to convert any of your models into TF-like model. Okay, any of your PyTorch model or Safe Tensor model. There are only two formats which is supported right now. One is PyTorch bin file and normal Safe Tensors file, which is a conventional format used in Hugging Face right now. What you need to do is, you need to provide your input checkpoint, which is your path in which you downloaded the model now. And then for vocab model file also provide the same path. And for output directory, what you can do is provide intermediate directory. Okay. Next, finally, this is the most important path, which is your path for saving the TF-Lite file. See, necessarily TF-Lite file need not have the extension of .tf-lite. Okay, you can have it as .bin as well. That is also correct only. Okay, so here I'm storing it at normal content is the root directory in which we work in Collab. In there, I'm creating a folder known as converted models, and then I'm storing it as Gemma _ backend. What is the backend? Backend is in which device you are gonna run or which backend processor you are gonna use. Is it a CPU processor or a GPU processor? Right now, in our case, it is CPU, so it will become Gemma CPU.bin. Okay. So input checkpoint format, model type is Gemma 2 billion, backend is obviously CPU, output directory is given, combined file only should be always false, your vocab model file and output TF-Lite path, everything is provided. So what will happen is, here they have given a UI. Okay, if you click Gemma 2 billion, that conversion of Gemma 2 billion function will be executed here. And then once that is done, it will be saved. Okay, but now it is in your Collab, not in anywhere. Like if it is also harder to download from Collab, and it is not safe to keep it in Collab itself because you might need to rerun it and you can't keep on running it here, right? So you can save that in your Google Drive. So for now, what we'll do is we'll run this code. We are taking Gemma 2 billion CPU, right? So let's run start conversion. Yeah. So until that is being done, let me also show you what happens here. So once your conversion is done, you will mount your drive in here, and then those will be stored in your Google Drive directory, which is converted models. It is provided here. Okay, in your converted models in Google Drive, this will be stored. Okay. So that is what happens, and don't forget, you need to have a Hugging Face token for this. Okay, that is very important for this specific task to be done. I have already provided it in my secret keys, so it won't ask for me, but for you it will ask. Okay, so it will take a 5 minutes or 6 minutes. Until then, I'll just see you later. Now if you see here, previously it was written converting in this button, and now it has become start conversion again, right? Which means the conversion is completed. Now we can save this in the Google Drive. Now it will ask permission. You can just give connect to Google Drive and it will be fine. here if you see, I have Falcon, I have some other models as well. So let's say your model is Falcon, or in this case Gemma CPU, whatever you have it. Okay, so let's say it is Falcon CPU dot bin. Let's say instead of Gemma you created Falcon. Okay, what you need to do is first download this model. Okay, put it in somewhere. For now I'll just keep it in here, and I'll keep it in my work directory itself. Okay, it will download now. So once this is downloaded, next what we need to do is we need to clone the repository. Okay, so let's start with that now. So now I've fired up my command prompt. So what you need to do is probably take your git bash. Okay, let me zoom it up here. In your git bash, first run these commands. You have these commands, right? You need to run all of these commands: git clone, http github.com, this one. Okay, so for this what I'm gonna do is I'm gonna create an empty folder now. Let's say it is make directory Falcon Android. Okay, I'm gonna create that. Now let's do a cd to that. Now paste that command. Okay, git clone. But the problem is, instead of this whole instead of this just Android example directory alone, we'll have whole of the media pipe library itself with us. That is not needed, right? So for this also they have given a solution where they have said that if you want just the Android example directory alone, so you can run these commands, is what they have said. So let's run that too. Okay, now this is done. We are gonna run this now. Okay, first let's do a cd media pipe. Okay, now this is done. Let's do this now. Git sparse checkout init -- cone. And finally, if you do this git sparse checkout set examples LLM inference Android, right? Now, if you see ls, it will have only examples. And if I go inside examples also, it will have only LLM inference. Okay, that is what you get when you do this specific commands execution. Okay, now the first step of having a model is done. Okay, because you have created a model now. Okay, you have the working directory, you can just have that model there. That is how you will have your custom model in there. Okay, they have said like you can use Gemma defaultly, but that is not needed for us. Okay, now what we'll do is, again we have done this model part. They are saying about this. Instead of these following hereafter, just follow what I'm gonna say now. First one you need to do is go and download Android Studio. Okay, download Android Studio by clicking the button here. Okay, it will be a just simple implementation. Just do next, and you will be fine. Okay, so once that is done, what you need to do is open the Android Studio. Okay, let me show from first itself of how you can do that. For you, it will show new open project and all. So what you need to do is click open project in there. Okay, you will get a box like this. And here now we created Falcon Android, right? So you can go into Falcon Android example LLM inference. Okay, LLM inference Android. Till this you can go. Okay, let's go to this. We are stopping this. Let's just click trust project. Okay, now we have sorry, it is just doing something. So what you need to do is, the next step is go into the application. Inside that, go into source, Java, and then your where is that inference model? Yeah, here in this inference model you need to change something. Okay, just keep it like this. Just keep the path data local temp and model.bin. Okay, so once this is done, there are some other things you need to do. Now you would need to work with your mobile phone. Let me show you those steps now. First, have a USB cable or whatever cable that suits to connect your mobile phone and your laptop. Okay, so I'm doing that now. Okay, I'm connecting my mobile. Now we're gonna ask some things. It will ask allow USB debugging because I have enabled debugging. I'll just click allow for now. Okay, and it would show my device in the emulator right now. Okay, I'll also show you that later. Make sure you click this allow USB debugging only after you launch the Android Studio, because that is when it will enable you to use your Google Pixel 7 itself as an emulator. For example, I'm using Google Pixel, but whatever mobile you have, it would be fine. Okay, there are some other things you need to do. First, to even enable USB debugging, before that, do this. Okay, it will ask your USB preference, and in this, you should click file transfer. Okay, because we would need to load our LLM into our mobile, right? So for this, you need it. Okay, so once that is also done, you can move on to developer options, making developer options, so that you can enable your USB debugging, and I will go to show you how if you don't know about that. In settings, I hope it is clear, you can just type build and it will show your build number, and in that build number, click it 7 times. Okay, exactly 7 times, and a message will pop up stating that you have enabled the developer options. Okay, so once that is done, now search for system. Inside system, there will be an option for you showing developer options. For me, it is in system, but it might be somewhere different also for you. I'm going to click developer options, and it will have a lot of things. For example, the memory consumption is given as 4 GB of 7.8 GB or 4.8 or 7.8 being consumed. Okay, and the thing which we are most interested in is debugging. In this, for me, USB debugging is enabled. So this is very important. Okay, first you should click your file transfer to be enabled instead of charging. Next, enable developer options, and then inside that, make sure USB debugging is turned down. When you enable the developer options itself, right, just connect your mobile phone when Android Studio is launched, so that when you enable USB debugging, your mobile phone will become an emulator in Android Studio. So now let's see about the code a bit, and then we'll move on to the demonstration, and then we'll also see how you can save this model or the application rather. They are using Kotlin language. Okay, and we are more concerned only about this import, since we are not developing Android a lot. We are just focusing on this LLM inference. Okay, and if you want to change a lot of things, let's say you want to change UI, right, there is a file for that, which is UI theme. Okay, where if you want to change the color, you can change it here. If you want the change the theme itself, you can change in the theme.html. It's on your completely. Okay, so you can do that as well. For example, here you can see in theme, there is for dark color scheme, light color scheme, they have kept a lot of things, and you can play around with that. But right now, let's see about this actually. Okay, they are creating a class with a private constructor, which is context. Okay, they're making a private variable in there, which is LLM inference, which is an LLM inference object itself. Okay, or an LLM inference class. Here they are setting a variable, a private variable, which is to check if a model exists. Okay, this is a boolean value, and they are just checking if the file exists. Okay, and now what they're doing is, if the file is not existing, it will say the file doesn't exist. But if the file exists, they'll take the LLM inference class and go into the LLM inference options. Okay, so this is parameters being set for LLM inference, and here they are setting a model path, and the max tokens is 1024, which I have set because I have an 8 GB RAM in my mobile. But if you have lesser, then keep a lesser number of tokens in your max tokens. Okay, other than that, there are not a lot of things, and based on this context, which is your context object. Okay, this is an Android context object which will give information about your application. It is an abstract class, okay, based on this context object and the options which we created right now, which is model parameters. It will try to create an LLM inference, and then it will execute that. Okay, that is what is here. Generate response async. It will generate async response. This is using Kotlin. Okay, but if you want, you can also do it in Java. So now what you're going to do is, here there should be an option for you to run the application. Okay, so initially when you run, it will give an error. Okay, for me it won't, but for you it should. Okay, so what you're going to do is, let me show you. First, here you can see there is emulator as well. So if you click run, right, you'll see your Gradle build running. It will take a few minutes at first, probably. Now you can see it is showing launching devices, right? So now it will show an emulator at side. Okay, now you can see, right, it is showing running on devices. Now it should show me an error first, actually. Yeah, here you can see, right, it is showing me an error. So now here what we are going to do is, we are going to use, there is something called device manager here, right? So you're going to click here and click Google Pixel 7, which is my mobile phone, open in device explorer. Okay, that is very important. Click open in device explorer. Now we don't need this. If at first you'll all get this only. So here there will be an option of data. Okay, in data you can just open that. Where is local in there? Here you can see local, right? Local, and inside temp, what you can do is you can just paste your model file. So let's do that now. Where is our model file? Let's check it. My model file is there now. So what I'm going to do is, I'm going to drag that and paste it in here in temp. Okay, data local temp. Now it is being uploaded here. Okay, so once that is uploaded, you will see the magic happening. Okay, so right now what it is doing is, it is uploading that Falcon model in my mobile phone actually. Okay, not in my emulator or my CPU itself. You can do the same thing with emulator, but emulator will again run in your system and it will be like pretty huge in computation. Okay, now you can see it shows, just give me a minute, I'll show you. Device Explorer successfully uploaded one file. Okay, that is what it shows. I have uploaded in temp. For safety, what you're going to do is right click here and click copy path. Okay, and then go into your this file known as inference model KT and paste the path in here. Okay, that is very important. So once this is done, what you're going to do is, again you're going to click the same. Okay, click in Google Pixel 7. That is what I'm going to use here, my mobile phone. Okay, and in my mobile phone, now I'm going to run this. Let me close these. Run application. Hopefully it would run. If there is an error, let's see how we can solve that. And now it is running actually. Okay, it is running. Let me show you. Give me a minute. So now I'm clicking the run button again. Okay, you'll see the change in here. Okay, I'm clicking run and now you can see it is loading the model actually. Okay, now I hope it is visible for you all. It is loading the model now. Since it is a pretty huge model, I think it would take some time for sure. But once it is loaded, you can ask the questions like we saw. And now I'm going to show you all again. Okay, so let's ask what do you know about Google DeepMind? Let's ask about that. Okay, let's see if it is knowing anything. So here I have asked the question and now the model is trying to see for the answer actually. Okay, so let's see if it is trying to answer it correctly. Already it is taken a pretty huge size, my RAM, and yeah, it is saying an answer like it is a deep learning company and they more focus on machine learning and artificial intelligence. They focus on model building, inference. There are a lot of things it is trying to say, but it is working actually. Since our demo is ended, doesn't mean like we are completed with the video now. See, I have just shown how you can do it with the help of USB debugging, where you can just open and run this and then you will be having your result. But that is not as important, right? We need to build an APK file. Now I'll show you how you can do that. Here I was unfortunately not able to find the application directly. So what I did was click this search and type generate signed build APK. Generate signed. Oh, here it will show you generate signed build APK. So click here, click your APK, provide a key store path. Usually what you should do is click create new and then go into your own source directory. For me it is LLM inference, and if you had followed the video like this itself, it is LLM inference for you also. And then give a file name stating falcon.jks or whatever file of your choice. Okay, just keep it as yes, and then give your password. Make sure it is easily replicatable. Okay, falcon 123 falcon 123. You shouldn't say to me, okay, or others are falcon 123. I'm just keeping same falcon 123. Give your first name, last name. Right now everything is test, 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 test. This is test, right? So just give it as test. Okay, just keep it, remember passwords to be enabled, and then click next. And then here there will be two options, debug and release. Make sure your release is clicked and then click create. And here you should be able to see the Gradle build is running. And soon it will show you the build is done. Here you can see, right? The build is done. Now I'll show you the file directory for this. It isn't here. It's not here. Yeah, Falcon 100 is here. Examples, LLM inference. This is our root directory, and Falcon JKs you could have seen here. I hope it is visible. Okay, and we are going into app, and inside app there will be build, and don't go into that. It is release. Yes, you can just export this APK, and then it will work as an application itself in your mobile. Now here you can see in my mobile phone there is the brightness. There is media pipe right at the corner. I'll click that. Now it is an APK. Now you can see like my phone is completely detached. I have not attached any USB. Okay. Now it is showing in here, and if I type what is artificial intelligence, it is gonna respond. Okay. And now you can see here it is trying to generate the response. And yeah, it is generating the response. Okay. So yeah, we are also done with exporting and using it as a real application. Okay, and that is how you can run your own LLM in your mobile phone. Now I have shown for Android, right? Similarly, you can do it for any other application of your choice. Let me show that. So in here, it is given a guide for Android, right? So similarly, you can run it for web as well. For web, they would have used a JavaScript kind of an API, where still you need to first create your model by using this LLM conversion.ipynb file, which are also I'll provide it in the GitHub. Along with that, you can replicate the steps as provided in here. Okay, all you need to do is just add the script in your head. Okay, and then you should also install this MediaPipe package by using npm, and then other than that you can follow the steps provided in this GitHub setup which they have provided. Okay, And for the complete code, if you don't want to build anything by yourself, right? For JavaScript, you have this one, like they have provided the index.html and index.js. And if you're an iOS user, you can use this one. Okay, I hope for iOS, again, you would need to do it in Xcode. Okay, but this is how you can run your own customized LLM in your Android mobile phone, like I did right now. With the advent of LLMs like ChatGPT, which is recently released as GPT-4o, or else the LLMs which are running on Grok, for example, your Llama 3s or Mixtral which are running on Grok inference, there are lots of use cases which can be solved with the help of LLMs that have been opened up recently. And I thought we would start a playlist where I will solve real world use cases with the help of LLMs. And this is the first video of that, where I'm going to share you about 25 plus use cases in AI which can be solved with the help of LLMs. And this is going to be focusing on different industries. I've taken around top 12 industries in the world right now. And in each industry, I've taken 2 projects. So that adds to 24. And there is finally one industry in which I have taken more than 2. All right. So that is about the introduction of this video. And now let's see about the different use cases which are there in different industries. First, starting up with the major industries, which is medical and healthcare. In medical and healthcare, AI plays a lot of important role in it. And for me, I think the most important use case would be a primary health doctor. Because nowadays, people are hearing about whatever diseases are coming up, which might be small, and we can possibly make a primary health doctor with the help of whatever architecture it is. And guys, in this video, I'm not going to speak about the technical architecture. I'm going to say about the use case which I'll be solving. We'll see about the architecture in each of those videos, because this is going to be a playlist of around 25 to 26 video. Each project will be a video, and we'll see in that in detail. All right. So in primary health doctor, the idea would be that it will be a chatbot in which you can ask question and it will answer, possibly even provide a medical prescription of tablets. All right. And the other thing would be, with ChatGPT 4o coming into picture, it is easy to do real-time image captioning so that we can provide a system which will provide an information around the surroundings, about the surroundings to the vision impaired people. All right. So for those, we can build the second application, which is vision for blind. And in finance industry, as usual, the most sought after use case would be stock trading bot. And there are lots of things which we can do with the help of LLMs there. And for that, we can try to make an AI architecture, agent architecture, or whatever we can do with the help of that. Okay. And then there is another one, which is investment analysis. So the idea is that there are lots of investment made by people, and we can make a dashboard which will make analysis of investment, or even monthly financials analysis. Okay. So whatever you have made and how you can improve your monthly financials, something like that. All right. So that would be finance department. And then coming on to the business department, the most important thing for me would be to make a platform to create customer support chatbot. Okay. So customer support is a very important process in any business, and we can make a framework for creating such a chatbot. And then another one would be, if you are making a business, right, it is very important for you to understand the market for that specific product. So given a product, let's say chatbot, we need to understand what are the existing products which are doing whatever we are seeing that we will do. And then we can identify that what are the problems in there and what are the solutions we have provided, which are gonna favor the scales on our favor. Okay. Tip the scales in our favor. So for that, market research is very important, and we can automate that as well with the help of AI. Next important thing is information technology, which is the normal IT department or software. The first one would be pair programming or coding assistant, and it will help us to remove a lot of jobs, like, the tiring jobs, like writing the same code again and again, or for example, if you are writing a machine learning code, right, it is going to remain the same for a lot of things. Or, we'll be searching over Stack Overflow documentation and all. To automate that, we can make a coding assistant. And then another thing would be process automation. For example, an LLM for web scraping, an LLM for automation of your daily workflow, which is repetitive in nature. To automate those kind of processes, we can use AI. Okay, so that would be the use cases in information technology. In marketing, the main thing which I have found is one is writing content for marketing. All right, be it for email newsletters, be it for posters or whatever it is, depending on the type of medium, it is important to write the content, and that is one important use case in marketing. And another thing is SEO. So SEO is not just about website. If you want to make your post come up in LinkedIn a lot, I've heard that there are lots of techniques in SEO for that as well. So we'll try to make an SEO agent for marketing, not just for web, and it is for all platforms. Okay, so that is about marketing. And then we have human resources department. So human resource department is mainly on interview and all, and also maintaining the customer or the employee, whoever it is, their satisfaction. Okay, so what I was thinking is we'll see about the one aspect, because for satisfaction you're going to see the feedback, and probably we can make a classification out of it. Though I said 25 plus, I'm just seeing other use cases which I have not even written here. Okay, so if there is a company, there are always going to be feedbacks. So probably you can make a ticket making system where based on the feedback, it will say, okay, this is very important. You need to note like something like that. Okay. And here for human resources, what I've taken is first one is resume ATS system and job description writer. All right. So given a job position, right, it is hard to write a job description, and that to match the industry standards right now, it is very harder. Okay, so it will require a lot of research on what is required in the industry, and then you need to understand what are the requirements of your company. So we can create a platform which will research for us and write the JD. Along with that, if thousands of resumes are provided, right, then we can make a resume ATS system which will try to match these JD and resume together, and then it will rank all of those with some scores. Okay, so for that we can use the resume ATS system and JD writer. This is one use case together, and then another one is an AI interviewer. Okay, so given a role, we can try to find based on the company also. Probably we can try to find whatever relevant questions are there for that role, and then probably we can make an interview out of it where the AI itself will evaluate. Guys, actually there are some 5 or 4 startup ideas within these 10 use cases, 12 use cases which I've discussed right now. And probably you can also try to make a startup level product based on the use cases which we do. Or if you want to build that kind of level of project also, let me know. I'll try to build those kind of level of project. Okay, so that we can deploy and market it over internet. And then for social media, which is probably the best industry right now, because if we want to do anything in our favor, social media is the best weapon. So for that, the two major social media right now, for professionals, it will be LinkedIn, and for informal, it will be Instagram. So writing post for that for content creators is very hard. As a content creator, I know how hard it is to write content for LinkedIn. So we can write an AI system to write contents for Instagram and LinkedIn given a common content. Okay, it will format the post for those two major applications. And then BPO, business process outsourcing. In that, if you see, it is just calling, right? So even we can automate that to a bit. First one is we'll have a BPO support for marketing of our product. So we can make a sales agent. So given a query, for example, about our gym, saying like, okay, so what do you want a gym membership? And these are our facilities, something like that. So for that, we can make a sales agent with the help of AI, which will be able to talk, okay, over a call. I'm just saying it is an AI calling agent, okay. And then another one would be technical support. If there is someone facing any error, AI will call and then try to solve it. If it isn't able to solve, it will connect to a real person, okay. So that is BPO industry. And then in the education industry, there are lots of use cases, and out of which I've taken the top 2 use cases in my opinion, which is creating an AI teacher, which will teach you on any concept you ask. And then another one would be, once you teach, right, it is very important to test the person's knowledge. So for that, what we'll do is we'll create a platform where given content, it will try to generate question and answer in different formats. Okay. So that is about education. Next, entertainment. I'm just generalizing it as entertainment, where the first one would be movie recommendation system, where for a movie, given a flavor of what you love, we'll try to make a movie recommendation system And then another one would be YouTube automation. Okay, so I'm putting it in YouTube automation because I don't know where to put this YouTube. Should I put in social media or is it a separate industry by itself? But since YouTube is an entertainment industry, I'm just putting it in entertainment. But we can also classify it under different use cases or different industry use cases. Okay, so to automate the YouTube workflow, we have YouTube automation. Next is probably my favorite industry, which is what I'm working in, which is AI industry. I'm tired of writing RAG applications and fine-tuning applications, fine-tuning code. I'm very tired of that. So what I was thinking is probably we can make a platform which will provide us a low code or no code platform for us to fine tune or make a RAG application based on whatever we have. Okay, based on an LLM choice, it will be able to do all of these by itself, given a button click or something like that. Okay, so for that we'll write an application, and then another one would be synthetic data generation. Nowadays, data is good; it is being created, but for custom use cases, it is hard to create synthetic data. So we'll try to make a framework which will create synthetic data. And finally, I've just classified it as personal industry. Okay, so this is not focusing on any industry. This is just to make your life easier. So for this first one would be JARVIS to automate anything in your computer, and then Rabbit R1 clone. Rabbit R1 is paid, and we are going to make a clone of it, which will be open source and free to use. And it is hard to keep track of emails, right? And replying the emails, especially if you're a content creator or a business person. So we'll write an email automation system which will automate your email, create drafts, and you can check the draft and then just click send button. And then finally, make an AI app which will have Zapier integration with it, so that it will be able to communicate with 6,000 plus APIs, which would include Gmail or your Google Drive, lot of things which will help you in real life, right? And that is how you can find AI use cases in probably there are 25 plus use cases which I have discussed.